Welcome everyone. We are here to kick off our AWS Advanced Networking Bootcamp. I am beyond excited to see you all here today, and we are going to have a very fun, strong educational experience. This is our training for the ANS-C01, and this is a full AWS Networking Specialty Course. I'm going to tell you the way we're going to do this. We're going to make sure we are going to begin at the beginning. And that way, if you've been in tech or you've never been in tech, it doesn't matter. We're going to make sure you have all the skills by the time you are done. I want to tell you about the staff that's going to teach this, give you some information about the housekeeping, and then we get into what I consider fun, which is talking about networking, learning about networking, and doing networking things. I want to let you know that we have a lot of free things. We have an incredibly ambitious agenda. And we're going to do some labs live, and we'll do many more on Sunday if we have time, but we have a lot of labs for you. We have labs for AWS that'll teach you how to configure things on AWS. We have labs that will actually explain networking things to you, because you could configure things on AWS all day long, and because the underlying technology is hidden for you from you, you might not see it. So Mark Milovanovic, you can see him on the screen. He's a Cisco certified internet expert, and together with Mo and Benedict, we have almost 2 full days worth of labs for you. So sign up for your free labs, and you can get them. The link is in the chat box in the description below. The other instructors that are going to be here with me, if you don't know me, my name's Mike Gibbs. I'm the founder and CEO of Go Cloud Careers, and I've been a network architect now since about the year 2000, a little bit before that. My CCIE number is 7417. I was a lead architect at Cisco. I was a principal architect at Comcast. I was a principal architect at Riverstone Networks. And I've worked on Wall Street design systems for banks and internet service providers. With me, we have Benedict. Benedict is a network architect with about 10 years experience. He is a rock star. When Benedict talks, everybody learns something. So I'm super excited that Benedict is going to be here with you. Benedict's been working in networking all over the world. And then we have Mo. Mo is a Cisco certified internet expert and an expert network architect as well. Together, the 4 of us have over 60 years network architecture experience, and we want to make it a great experience for you. So kind of keep this in the back of your mind. We're going to have fun. We're going to do approximately 20 to 30 minutes of lecture, and then we'll leave about 10 minutes after each one for questions, because I don't want anybody to leave here without understanding the AWS Advanced Networking curriculum. So we'll lecture, we'll have questions. All of this content will be recorded, so you can go back to it again and again until you master the concept, because you may need twice. I want to keep that in the back of your mind. We're going to be going for 3 hours in the morning. Then we'll take a quick lunch break for about an hour, and we're going to come back for 3 more hours in the evening. So it's going to be 10 to 6 for the next 3 days with an hour lunch. I want to make sure you guys eat, so you're mentally fresh, so you're happy, having a good time, so we can turn this into a wonderful learning experience. You'll hear from all of us. We will all answer your questions, and please go get yourselves those free lab demos, because they're AWS labs and they're networking labs. And we've got BGP labs, we've got OSPF labs, we've got VLAN labs, we've got VLAN tagging labs, we've got all of everything that you need to do. This course will obviously, the questions asked, help you pass the AWS Solutions Architect Professional. Easily, you'll be able to pass this. No big deal. You'll be able to have a good time. You should be able to pass this exam. Again, it's a relatively easy exam. It's some intro-level networking content. And with the team we have here, we're going to make it real simple for you. People find this content challenging because it's taught by someone that's not in networking. And if you're not an expert, you won't be able to explain it simply. So we're going to do everything that we can. Now, I'd love to know where you're from, and I'd also like to ask for your help. It costs about as much as a car to put a production like this together. It really does. By the time you're dealing with about 10 full-time staff and the amount of time it put together. So please, if you're here, invite someone, send a tweet, send a text message, invite someone here. We want to help as many people possible, because we know most people would never be able to afford training like this. And that's why we're doing it here for free. If you haven't, please hit the like button if you're going to like our content at some point through the day. And if you haven't subscribed to our channel, subscribe to the channel and hit the bell to be notified of new content to help you in your career. Now, I want to make sure you're here. I want to make sure you're awake. Tell us where you're from. I see we've got lots of India. I see lots of, I saw all over Africa. I even heard of a place called Mississippi that was here, where Chris is actually from, where they talked about Long Beach, which is interesting. Many of us are in Florida. Many of us are in Europe. Many of us are in Asia. I have a feeling. So I'm seeing Kenya and Texas. I love this. Botswana, Nigeria, India, South Carolina, Singapore. I saw some Philippines, Argentina. I haven't been there in a while. Philadelphia, that's where I grew up. Okay, so we've got some people in Maryland and the UK. This is great. So lots of people from all over. Lohit's over there in Toronto, Aberdeen, Scotland. I haven't been there in a while, but I did a lot of work in Edinburgh and Aberdeen as well. Tacoma, Washington. So wonderful. Let me know you're awake. Give me a hashtag AWS Advanced Networking, and then we're going to start having some fun. Actually, before we do, Mo or Benedict or Mark, do you want to say a few words and welcome everyone to the program?
Well, I'll start off then. I just want to say I'm super excited to be here. This is going to be a fun 3-day session. And as Mike mentioned, we have lots of contents, including lots of labs where Mo and Benedict are going to be fielding the AWS labs throughout the next 3 days. On the back end, if you do sign up with the link in the description box, you'll get a bunch of networking labs as well, including OSPF, BGP, both internal and external. Mike is going to go through some of the material today. In the labs, we'll explain a little bit more on the CLI, how all this is put together, why there's certain rules in place, and what we can do to alleviate some of the problems. At the same time, we'll take a look at some basic static routing. You'll need to know that as well. And of course, some of the layer 2 kind of connectivity from VLANs to trunking, and as well as Ether channels or link aggregation. So in any case, I hope you're all excited. Have your coffee ready. This is going to be really fun. And I'll hand it over now to Mo or Benedict if they want to say a few words.
Hello, everyone. Welcome to the bootcamp. As Mike said, we put a lot of effort into this bootcamp. There's a lot of good information. Probably want to review it multiple times. So good thing that this thing is recorded. I would say, more importantly than taking notes, make sure that you're actually watching live and asking questions, because we will be answering questions as well. I'm very excited. I hope that there's something for everybody here to learn. And yeah, let's get this started.
Hello, everyone, and welcome. We're finally here. We've been planning this for months, and I'm excited that we finally have the opportunity to share a wealth of knowledge with you all. I hope that you gain some very important information that will help you in your careers and in your personal endeavors in this bootcamp. And like Mike said, please like and share this video so others can come and join and experience what Go Cloud has to offer. Welcome.
Okay. Tarek, this is my first class regarding cloud. Do I need any intro classes before understanding the session? Absolutely not. We're going to start from the beginning. King, if you don't have any AWS fundamentals, it's okay. The entire AWS Advanced Networking and all the AWS certifications are all honestly fundamentals level. And we're going to start from the beginning, and we're going to make sure you know what you're talking about. So, King, it'll be a great experience for you.
And in addition, for everybody, so you know, while the actual exam itself, when it comes to the advanced networking with AWS, doesn't carry any networking fundamentals, that's why we created the supplemental content, so that we can get you guys a little bit up to speed in regards to what is going to be discussed eventually in the sessions, and you can go back, you can compare and contrast. So just keep that in mind. But normally speaking, if you took somebody else's training content, if you were just to go for the actual exam, they're going to make assumptions that you're going to have some underlying fundamentals already in place. So, but that's not the necessity here for this particular session.
All right, so let's get started and let's have some fun. We're going to begin by discussing networking. Now, I know it sounds strange that I would say discussing networking, right? Well, the reason I'm saying this is there's actually very little networking in the AWS Advanced Networking. And that puts people at a bit of a disadvantage when they're starting, because if you don't understand the basic fundamentals of networking, all the other things that we build on top of it are going to get a little complicated. So we'll talk a little bit about what is networking first and how networking actually works. So networking is about connecting computer systems. You can almost think of networking as the plumbing that enables the servers and the users to talk to each other all over. And networking is not about the servers. It's about the routers, which are devices that take traffic from point A to point B. It's about the switches, which can also take traffic from point A to point B, but they do it in a slightly different manner. It's about the cables that you have, whether they be a physical cable like a fiber optic cable, or a pseudo cable or a pseudo wire like between your data center and, say, Amazon. And it's also all the LAN connections, so the wide area connections, the cabling, everything. This is what goes into networking. And the way networking works, I'm actually going to map it out for you because I actually want you to see it real and live. Here's the way networking works. So let's say we have a server over here. Let me just create it. I'm going to draw it out for you. I had some pre-made drawings, but I actually want to just draw it out for you live because I think it'll give you a better example. So circles mean routers. And that's pretty much the international symbol for a router is a circle. And I want to actually put this into context because if you see this, I think for now on in the rest of the training, it will be much easier. So what routers do is they connect networks. So on the left, you can see we have a router. We'll call it 1. On the right, you can see that we have a router. And let's also say that we have a server on this. And I'm going to put an IP address on the server, 192.168.1.5/24. And I'm actually going to put a user over here, user, and their IP address, and this is just for fundamentals purposes, is 172.16.1.5/24, which means what's going to happen is as follows. Let's just say I'm going to use some ridiculous IP address space over here to make it clear. So imagine now we've got the user, and the user wants to access the information on the server that sits at 192.168.1.5. So what happens is the user, which is a PC, is going to look in its routing table and it's going to say, do I have a route or a path to 192.168.1.5? If it does, it will forward the packet to the next hop, which we'll talk about in a second. If it does not, it will drop the packet and nothing will happen. So if you don't have a route to it, you can't reach it. So the user is going to try to go to this server, and it's going to see that it's off its local subnet. So it's going to look in its routing table and it's going to say, wow, I have what's called the default gateway, which is a route where I send things where I don't know. So the data from the user will be sent to the first router. This first router will look in its routing table and say, do I have a route to 192.168.1.5? And if the answer is yes, it will send it to the next router. And then when that packet gets to the next router, it will look at its routing table and say, do I have a route to 192.168.1.0/24? And it's going to look at its routing table and say, yes, I do. It's directly connected. It will forward the packet to the server. And of course, the server is going to respond. And the server will then look in its routing table and say, do I have a route to 172.16.1.5? If it doesn't, it will drop it. But if it has a default gateway, it will send it to its local router. And that local router will look in its routing table and say, do I have a route to 172.16.1.0/24? And it will say yes, and it will send it to the next router. And this router will look and say, do I have a route to 172.168.1.5/24? And it'll say, yes, it's directly connected, and it will send it out its Ethernet port. And now we have it. We have communication between the server and the user. That's how networking works. So hope to keep that in the back of your mind. So one of the things we need to talk about as we discuss networking is I'm going to do a quick refresher if you're not familiar. And if you are familiar, it's important anyway, something called the OSI model. So whenever we look at any kind of communication, whenever we have any kind of discussions anywhere, we have to all speak the same language. You know, I speak Greek at home. And if I want to speak to my friends in America, I speak to them in English. Sometimes I try my best in Spanish, but if you try to translate Spanish words to Greek words, they're not always the same. And if we communicate to each other in any technology using different words, which have different meanings to different people, what we can find ourselves in an actual position where it's hard for people to understand us and we make mistakes. So throughout this terminology, we'll be using with the OSI model. And with regards to the OSI model, it's a 7-layer model that actually enables you to send your data from point A to point B. Now, when it comes to networking, there's only 4 layers we care about. And it's the physical layer, the data link layer, the network layer, and the transport layer. Other things such as the session layer, presentation layer, application layer are less networking. There's some of it is, but it's not. But let's talk about what it is. The physical layer. When you plug in your PC to the switch in your house or the switch in the office, that is the physical layer. So physical layer is basically a wire or a wireless signal that connects you between point A and point B. Now, if you've ever looked in your computer, you notice it's got an Ethernet port where you plug it in. Well, that actual card, the Ethernet card that sits in a server, is actually considered the data link layer, and the data link layer is physically addressed. You may notice your computer has something called the MAC address, and every server does, and every virtual machine does as well. Now, the next thing is the network layer, which is basically the address. Kind of like the address in your house. Every system out there needs an IP address. And then on top of that, we have the transport layer, which is typically TCP, UDP, ICMP. TCP is used for reliable transmissions. We can get into this later if you guys have questions. UDP is used for real-time things that don't require reliability. And ICMP, or Internet Control Messaging Protocol, is realistically speaking used for network testing. So physical layer wire, data link layer card, network layer IP address, transport layer TCP, UDP, what have you. The session layer kind of really manages a socket in between systems. Presentation layer is kind of encryption, like TLS type encryption. And the application layer is something that you use. So think of it that way. And these are the kind of things I want to get into the fundamentals. And that way, when we actually get into the networking concepts, you're not going to be lost. So when we send data to transport layer, we've got TCP, UDP, ICMP. So TCP, like I said, is reliable. So if I had to turn in my homework assignment for my MBA, I'd want to know that they actually got the homework assignment, right? We'd use something called TCP. And the way TCP is reliable is we send information and we get confirmation back. So I see Valerie's over there. If I said, Valerie, how are you? And he said, I got your message, Mike, how are you? I'm fine. That's reliable. It's the confirmation. So keep that in the back of your mind. UDP, no reliability built right in. But if we were going to have a phone call and we lose a word from 10 minutes ago, do we really want to retransmit that word? We want to have a real-time conversation and it's okay. And then I mentioned ICMP is for testing. Throughout this conversation, we will use the terminology of LAN or WAN. A LAN is a local area network, meaning local to you. So if you're in a building, it's a local area network. If you're in a data center, it's a local area network. If you're in a cloud provider's data center, which they like to call availability zones, it is a local area network. And a wide area network is across distances. So between New York and London, San Francisco and Bangalore, for example, that is a wide area connection. Now, when we actually are going to get into direct connections, you're going to have to understand the concept of a virtual WAN. So I'm going to do some brief things. Like I said, we don't have a lot of networking to go to today before we get through the AWS Advanced Networking content, but there's some fundamentals that I just want to make sure that you all understand. And that's what we're really talking about here. So let me create a virtual LAN with you because we're going to need it for direct connections, and we're going to also need it for so many things. So in this particular case, let's imagine I had a switch, and it has, say, 48 ports in it. Let's get no fill in here. And the ports look like little Ethernet ports that you plug your systems into. I'm going to create some VLANs dynamically so you guys understand it. And I think this will help with a security perspective. And one day, if we ever talk about the challenges of the cloud security, if you understand this, it'll make it easier for you to understand the differences between private cloud security and public cloud security. Okay, so right now you can see a switch. And every one of these things that you see, all those little blue dots, is where you can plug your stuff in. Plug your server in, plug your workstation in, and understand that right now in the same switch, everyone can talk to everyone. which could be kind of great, right? You got a bunch of ports in your house. You plug in your Mac, your Windows system, your Linux system. You plug in your IP-enabled refrigerator, your IP-enabled TV, and it's all good, right? Yeah, and home. But do we think in the business environment, everybody needs to talk to everybody from a security perspective? No, and we don't want them to be able to. We don't want the engineers to be able to talk to the finance people from a security perspective. And maybe the finance people don't need to know about the quality assurance department. So what we can do is we can create a virtual LAN, and all a virtual LAN is the following. Let's say we decide to take these ports, just the top ones, and group them together where they can talk to each other and no other ports on the switch could talk to each other. That's it. That's a virtual LAN. So I've showed you what a virtual LAN is. Now, when you connect to the cloud provider, and we're going to get into a lot more information with this later, your building's going to be over here. You're going to have a router that sits over here. You're going to have to connect to some connection location. And then that connection location is going to have to go back to your cloud provider. Call it AWS or Azure. Doesn't matter. It all works the same way. All a cloud is somebody else's data center. Now, what's going to happen is they may only have one. They're going to only have a couple connections between the cloud provider's data center and their direct connection location, and let's just call it a direct connection location. And what's going to happen is they're going to want to use one or two cables, and they're going to want to separate your traffic, all on these similar cables going back to AWS. And how are they going to do that? They're going to do it with a VLAN, and they're going to do it with something called the trunk. These are basic fundamentals. And what does this look like? We've got, let's say, a switch with multiple VLANs on one side. That could be your data center. On the right side of this switch, you can see that it's got multiple VLANs or multiple segregated customers. And there's one wire that's connecting these two things. That is called a trunk port. So we discussed very briefly TCP, UDP, ICMP, VLANs, and there. So now let's get into some AWS stuff. And I want to make sure that you know that we've got a lot of free networking training that you can actually do on our website, and you can, on our YouTube channel, so go out there and get it. So now let's talk about the AWS cloud and how it's organized. If you're going to build on these systems, you need to know how it's laid out. And if you're an architect like me and you're going to design them, you're going to actually also have to know how the cloud's laid out, because your architectures or your designs are going to be dependent upon it. So when it comes to the cloud, we've got some terminology. The cloud providers made up the term region. What's a region? A region is a giant geographic area. That's a region. The whole East Coast and the 50% of the east side of the US is a region. 50% of the left side of the US is a region. Half of Europe is a region, that kind of thing. So you can think of a region as a giant geographic area. Now, the next thing we need to talk about is an availability zone. And a lot of the cloud providers love to use this term availability zone. What's an availability zone? It's a data center. So it's a big giant building that is filled from floor to ceiling with servers, routers, switches, load balancers, firewalls, storage area networks like block storage, object storage, and file storage. It's a data center. Guess what? A cloud provider's availability zone and the data centers we've been using for the last 30 years for business, pretty much the same thing. So large geographic area, region. Data center, availability zone. Okay. Now, we also have to talk about the concept of a local zone, and we'll work through this together, so make sure that you guys all get it. And here's the thing. I mentioned local area networks and wide area networks. Well, if you want real performance, don't go to the cloud. Have everything local to you in your data center. Why? Because if everything's next to me, I have access to it faster. If it's further away, what you're running into is something called latency. If I want to go visit Mark in Tampa, even though I'm in Florida, it takes time for me to get to Mark's house. It does. That's called latency. And latency is typically based upon the speed of the light going on the medium that it's at. But there's still latency. So if you want to go to your data center in Florida to AWS in Ohio, it might be a millisecond or two to get there. Now, from normal stuff, a millisecond or two, a thousandth of a second is no big deal. But for many applications, financial applications, a millisecond of latency could be devastating to an organization's profitability. So organizations really have two choices. Keep all the stuff local in the data center, or Amazon made a data center that's in between you and your availability zone, and I'll draw this all out for you in a minute, and that's called the local zone. And then the last thing we want to talk about is something called an edge location, and that's where you will access the Cloud Front content delivery network. We'll go through this. So let's realistically look at this from the big context, the macro context first. Here we've got a region, which is a large geographic area. And inside of that region, you're going to see multiple availability zones. Why multiple availability zones? Well, if they put everything in a single building, guess what? If the building catches on fire or has an earthquake or who knows what kind of disaster, they'd have absolutely nothing in the region. So the cloud providers, all of them, will take a geographic area and they'll pop in a bunch of data centers. The other reason they use multiple data centers is it's very hard to get that much power in certain things, but large area region, small area availability zone. Now, I mentioned the local zone is closer to you. So region, big area, availability zone, data center in the big area. But the local zone is something that's closer to you than the big AWS environment, and basically extends the region for you to run latency sensitive applications. So let's kind of map it out together. First we can look at it like this. You can see this large geographic region with data centers in there called availability zones, and then you can see these local zones. So I want to have a little fun with this picture. I want to kind of draw it in more realistic context. So over here is your campus. This is where all our workers are. This is where we're there. We got a great cafeteria. They've got some good sushi in it and a great salad bar. I don't know, it's a great campus. And here's where our users are. And realistically speaking, we could connect all the way back to the availability zone. So let's say you're trying to connect to US East in Ohio and you're in Miami, Florida. That could be 1,300 miles or something like that. And that can add a lot of latency from point A to point B. But what if there's a local zone in Florida? So your campus is here. You put your latency sensitive applications in the local zone, and you put your non-state latency sensitive applications in the traditional data center, the availability zone. That's really all that we're talking about here. That's it. So I want you guys to not remember this. That's why I go through things a few times. Large geographic area, region. Data center in the region, availability zone. Data center closer to you for lower latency, local zone. And the next thing we're going to talk about is what's called an edge location. So we're going to get into content delivery networks relatively heavily. But I want you to understand a content delivery network for right now is there to get content to you in a lower latency environment, reduce the load on the servers, and protect organizations from a distributed denial of service attack. And an edge location is going to be a place that's close to you. So Azure would call it a point of presence. An edge location is going to be where the content delivery network that you would access to go to the internet actually is. And the reason organizations use content delivery networks is, like I said, scalability, DDoS prevention, lower latencies, and it helps the clients in many, many ways. So I'll walk you through a brief introduction of an edge location and a content delivery network, but understand we're going to get to it on a lot more depth at the appropriate time in the course. So here you go. You can see that you've got edge locations that are closer to you. And you're going to have an edge location for the most part in every major city you can think of where there's going to be a lot of users. So why do organizations use edge locations? Well, let's pretend we're over here and we've got a user in a specific geographic area and the user wants to access some data. If the user is in Miami and the data is in, say, US East in Ohio, what you're actually dealing with is a lot of latency from the time the user actually requests the information to the time it gets to your cloud provider, and then it has to come back. So there's latency that's associated with that. And there's that. Plus, let's say I had 10,000 people that wanted the same piece of information. Well, each time the website would have to respond. So it would have to go a long distance and it would have to do a lot of response. So let's take something a little different. Let's say that, I don't know, a big musician, maybe Taylor Swift, were to make a tweet that had a photo of her cat. And, with a fan base like that, everybody wants to go and see Taylor Swift's cat, right? I like cats. Anything with a cat in it just makes me smile. But so let's say, I'm the first user. There's a tweet, and I want to go see Taylor Swift's cat. The first time I go to the website, it takes me to I attempt to go to the website. It takes me to the edge location because that's my local content delivery network, and the data is not on the content delivery network. The data gets off the public internet, which is slow, runs on the private network or the semi-private content delivery network, and it goes back to the source. The source then responds, and we'll get into much deeper depth about how this truly works. And then the information is stored or cached for a period of time in the edge location. Now my wife, 5 minutes later, finds out that there's a photo of Katy Perry's or Taylor Swift's cat. My wife loves cats, so she wants to go see it. And the information is stored on the content delivery network, and it gets sent back to my wife immediately. And then my cat Cindy, she gets hold of my iPhone and she wants to see Taylor Swift's cat. So she goes to the edge location, this information is cached, and the information is sent back to her. So what you can see here is something very special. The server only responded once. The user got the information closer to them. And there's lots of security rationales which are going to make this better, which we will talk about. So we talked about some basic things. Now we get into the fun stuff for the AWS Cloud. Does anybody have any questions for me before we actually get into the fun AWS stuff? From Jerry. Hi, when the opportunity arises, you can go into why VLANs are not used across the WAN. Trunking for a remote office to a data center is not recommended. So, Jerry, I need a little more clarification of what you mean. There are plenty of organizations that have layered 2 VPLS WANs that actually do trunk VLANs over the WAN, and they can do it in a perfect manner. So it's not that it's not recommended. The question is, what do you want to send over the WAN? And there are advantages of having layer 3 boundaries across your WAN. For example, broadcast traffic won't be sent across the WAN. But in today's world, with VPLS, Jerry, it doesn't matter. Now, when I started in networking about 25 years ago, and we had 56K leased lines, and you had 56K of broadcast traffic that would carry over a wide area network link, you would not want to trunk a VLAN over that. But in today's world, where you can get a 10 gig link, 100 gig link, it really doesn't matter so much. Mo or Benedict, do you have any comments on that either way?
Yeah, I mean, in organizations where I've worked, we've always trunked VLANs across our WAN from the head office to branch locations. So there are different use cases for that. So it's not uncommon to see VLANs being trunked across the LAN.
Yeah.
Of course, the VLAN is segmented to reduce the blast radius in case there's any broadcast on that VLAN so that other VLANs are not affected. So there are use cases for that.
What is the difference between a local zone and an edge location? So a local zone is a data center in between you for you to put your private stuff. So let's talk about, and the reason I say private stuff versus public stuff. When a content delivery network, for the most part, you're putting your stuff that you want the world to see, your website. The local zone is where your private organizational information could be stored. Could actually be public information, but it could be private. So let's say I've got an algorithmic trading application for a bank, and I want lower latency to my campus where the feeds are coming in. And I don't want to do it on my campus for some reason. I stick it in the local zone. I don't want the world to know the bank's internal servers. I don't want access to those bank servers. I need to keep it private and secure. So I would stick that in a local zone. By comparison, the website, say if my cat Cindy, I got a beautiful cat Cindy, let's say she gets a website one day and gets a bunch of social media followers, my cat's a pretty cool cat, that I would put on an edge location. So edge location, public web stuff. Local zone, private data center stuff for the most part. Sunday, absolutely. Those edge locations have servers that cache information. How many days labs access will there be? We're not going to take away any of the lab access that we're going to post up there as long as they're current. So, there's some labs that are there that you can download and sign up for now. And there's going to be many others that Mark is doing behind the scenes to truly enhance your networking experience, close to 2 full days worth. And you'll be able to log in and access those labs as long as you desire. We're not going to take them away from you. We want to give you a good educational experience, even if there's no cost. Are the edge locations and local zones used for IoT? Not typically. IoT devices will typically go to a local zone, whereas edge locations are typically used They're typically used for more accessing of websites and DDoS protection. And Truth Factory popped up something interesting there. By local zone, do I mean co-location? Co-location sites were the first clouds. A co-location site is a cloud. So a co-location site, for those of you that are unfamiliar, is a company that would basically have a big building. They'd fill it with networking gear. They'd fill it with servers, and they'd rent you the servers, or they'd rent you space in there where you could put your own servers. That's a cloud. So these local zones are very, very similar to co-locations, but they're all managed by the domain of Amazon. But very similar. Are trunk lines secure, or would you run the trunk over a VPN? That's a very interesting one. Theoretically and technically, trunk lines are secure. To be able to access it, you'd have to create the equivalent of a man-in-the-middle attack, attach a switch, and then de-encapsulate the VLAN information to get it. But it's still possible. So ideally, we can run IPsec over our connection as well, and that would make it more secure. Do edge locations have a CDN? The edge locations are where the CDN is present, at least the servers and the backhaul networking to get to the rest of the content delivery network. Exactly. Is the local zone very close to an availability zone? The whole goal is for it not to be close to the availability zone. The whole goal of the local zone is to be close to you. Now, if you just happen to be in a place where you're very close to the availability zone, you'd never use a local zone. The point of this is to create a place in between you and the far away availability zone. So hopefully it's pretty far from the availability zones and pretty close to you. Thinking cost perspective, and let's get out of cost perspective and start thinking what we can actually do for our clients instead. Because $1 that you spent that gives you nothing is worthless, but $1 million that you spent that gives you $10 million back is a lot. What is the advantage to put a NAC gateway to make a private subnet talk to the outside world? You really have no choice. You've got to be able to connect to the outside world. Now, if you don't use the internet gateway, you will need to have public addresses on every single device that you have. And they will be exposed to the public internet that is terrifying which means they will be hacked in a matter of minutes, especially if each device hasn't gone through next generation firewalls, IDS, IPS systems, system hardening, and the such. So there's really not an option. Now, could you connect an internet gateway to some next generation firewalls from, say, some Palo Alto, use the Palo Alto firewalls to do all your NAT and give you a much greater security than you could on an AWS NAT gateway? Yes, there. Now, it's not going to cost less, but it will give you much greater security, enterprise grade security. So that would probably be a much better way to go. Are edge locations the same as AWS Outpost locations? AWS Outpost is really a server that they ship to you that you could run in your building. So instead of you calling and buying a server from Dell for, say, $600,000, they can ship a server and put it in your place and charge you a few $1 million over the next few years to rent it to you and manage it to you. Pretty much what we're talking about. Co-location similar to Megaport, Equinox, or any ISP. Co-location is a place where you're going to put your stuff. All right, we'll do one more and then we will get back to the content because I love to teach. So does that mean the local zone is part of the cloud infrastructure? Yeah. Honestly, here's the cloud. All the networks and data centers combined in AWS with the control and orchestration plane that makes it busy. All right, so let's get back into some content for a little while. We'll start having some fun with this. And we're going to get into some basic networking concepts of where you're going to, we're going to start with the VPC. And when we get to the VPC, actually, before we do that, I want to make sure you're still awake. Give me a hashtag AWS Advanced Networking, so I know you're all awake, alert, and oriented. I used to practice internal medicine as a nurse practitioner. I used to ask the people if somebody would fall, where are you? What time is it? You know, what year is it? That kind of thing. So I like to know that you guys are all there. As a reminder, if you just joined us, we have a tremendous amount of labs that we would like you to go through. We'll go through some on Sunday. If we have time, we'll go through a few during the course. But we have almost 2 full days of labs. Labs on AWS and labs that some of our CCIs did off the scenes on real network gear. Because in the cloud, you'll never see what's actually being done because it's hidden from you. And we brought you to the real networking gear so you could see what's going on under the hood, because you need to understand how this stuff works in order to performance tune it and or to design it. So make sure you go download those free labs. So now let's talk about the virtual private cloud. What is it? So, you know, a lot of people have some various definitions for the virtual private cloud. Some people like to call it a virtual private network, but not me. To me, your virtual private cloud is your virtual data center inside of the cloud. I like to call it my virtual private data center because here's where you put your servers. Here's where you put your gear inside of your VPC. And where other environment do you have a lot of routers and switches where you're plugging your servers and your stuff? The data center. So your VPC is like a data center inside of the data center. Remember how I showed you how I created a switch and we created a VLAN? That's all cloud computing is you're renting space in someone else's data center in a virtualized context. Kind of like when you stay in a hotel versus being in your own house. Staying in a hotel has its benefits. You get maid service, typically. You can order room service, typically. You know, they usually have a great pool, what have you. And when you go to your house, by comparison, you've got complete control, complete autonomy. Nobody bothers you. Nobody wakes you up. You got a full kitchen. You have your own comfort, your own bed. So the way there's a strengths and advantages to hotels versus your house. Same thing with cloud computing versus your own data center. So your VPC is your virtual private data center. Now, when it comes to addressing our data center, what we're really talking about is how do we address our systems? Every device on the network is going to need an IP address. It's the only way it can be identified by the network and will be able to be communicated about. So an IP address is a logical address, meaning assigned to an entity. Every IP address, in order to communicate to another IP address, must be unique, which means for a system on the internet to talk to another system on the internet, it needs to have unique addresses. Now, we ran out of IP addresses a long time ago, so we'll get into the difference of public and private addresses in a bit, but understand that every device needs a unique address. It's kind of like mail. If you want to get mail, you have to put your address on the label, because how else will the postal workers know how to take it to you? No address. How are they going to find Cindy the cat? Unless Cindy the cat's famous and being followed around by paparazzi all day. No one will know how to find Cindy the cat. So Cindy the cat, if she was going to get mail, would put down her address, which happens to be my address, because Cindy the cat is my manager and I do whatever my cat tells me to do. So I showed you how packets were delivered over a network, but every device needs its address. And even if you were to tell me, Mike, there's 123 Main Streets, I'd say, yeah, but the zip code or the postal code is different. Now, when we deal with IP addresses, we've got two flavors. We've got IP version 4, which for the most part is what we've been using for the last 30 years and is still the preponderance of what we do. And then we've got IP version 6. IP version 6 is not new. It's been around for decades, but it typically is not used much except for, say, predominantly cell phone use at this point. So when you assign IP addresses on the inside of your systems, you're going to be using private addresses. And private addresses were specified in the Internet Engineering Task Force, RFC, Request for Comments, 1918. You ever want to learn about a networking specification? You want to get the best information free? You go to the IETF.org, and every RFC, Request for Comment, is an actual internet specification. So that'll give you all the good, all the geeky details of any networking protocol you want, and it's all free. So inside of your systems, inside of your VPC, for things that you don't want reachable from the internet, you're typically going to use 10.0.0.0/8. That whole / class A is good for you. You've got the 172.16.0.0/12, and you've got the 192.168.0.0/16. So for the most part, they're what you've got. Now, I'll mention it just in case it pops up on the AWS Advanced Networking exam. We have a really good subnetting workshop that we did, Mark and I'd like you to see it. If you don't know how to subnet, my team will pop in a link to that subnetting workshop. Take it, bookmark it, and go through that until you understand it, because it's absolutely critical information. We no longer use these classes, but if it pops up an exam, understand Class A addresses begin, and I'll actually share this with you to kind of make it a little easier for you from a visual perspective. Class A addresses begin at 1.0.0.0 all the way to 126.255.255.255/8. There, as you can see, there's almost 17 million addresses there, which obviously wouldn't make sense on a subnet. So that's why we have to subnet. You can see that in the subnetting videos from our workshop we did a few weeks ago in preparation of this for all of you. Then the Class B addresses begin at the 128.0.0.1 all the way through the 191.255.255.255/16. And then the Class C addresses, which were the 192.0.0.0 all the way to 223.255.255.255.255, all /24s. Then something I spent a lot of my life in, working at IP Multicast, which I thought was some of the coolest and most fun technology ever. And they use the address family of 224.0.0.0 all the way to 239.255.255.255 for the multicast groups. And then the Class E addresses are above that, and they've been reserved for experimental purposes and never been used. Now, when you actually set up your VPC, you're going to be given a CIDR block, or a classless interdomain routing block. All that really means is it's no longer classful addresses like that class A, B, or C that I just showed you. It is classless, meaning you subnet. That's all it means. So you're going to get your CIDR block. You're going to create an IP addressing plan. make sure whoever creates this IP addressing plan understands what they're doing. This is a CCIE or greater concept on IP addressing plan. If the IP addressing for your systems and your architecture is right, things are going to work beautifully. If the IP addressing plan is wrong, the routing will be wrong. And as soon as you scale just a little bit, the systems will come to a crashing down, and it won't be good for anyone's career or any organization you work for. So make sure that you understand subnetting, you understand supernetting, and whoever does the IP addressing is an expert on networking. So that just needs to occur. And I'll do a brief refresher on subnets. But again, I want you to go back to the things that are much more important. I want you to go back to the video where we spent hours on this. But subnetting is about optimizing IP address space usage. And here's the reason why. Every interface on a device is going to need its own IP address. How do I do this? Okay. It's going to need its own system. So if you've got a server or a router, it doesn't matter, and it's got 4 network ports on it, each port is going to have to be on a different network, otherwise known as subnet. So just to understand the mathematics of this, and you understand why we have to subnet, and then you can go back and watch that video. Mark and I spent 4 hours teaching it a week ago. This interface, this interface, this interface, and this interface all need to be on a different subnet. So if we didn't subnet it and we just used these class A's, like I initially showed you from that list, this interface on this router would be using 16.7 million IP addresses. And then this one would be using 16.7 million IP addresses. And then this interface would be using 16.7 million IP addresses. And then this one would be using 16.7 million IP addresses. So you add all that up, it's about 66 million IP addresses. Not a great idea. And if we were to subnet this down to, say, /24s, because we're not going to have that many more servers that can ever sit on a subnet anyway, because it's subnetted down, each one of these interfaces is now going to use basically 254 IP addresses. So, you can see how we can preserve our IP addresses a lot better that way. And that's really all we're talking about with subnetting. Again, we put together a lot of content on it for you to watch it. Maybe another visual that you could see, I hope it makes sense, is we've got this 192.168.1.0/24. And I can chop that into a 192.168.1.0/28, a 192.168.1.16/28, a 192.168.1.32/28, a 192.168.1.48/28, and so on and so forth. That is subnetting. Now, we're also going to have to talk about supernetting, which is the exact opposite of subnetting. Subnetting is designed to optimize our IP address space that we're going to use in our systems. Supernetting is basically used to optimize our routing information. So, when you connect to AWS, they don't have the most robust networking protocols. And it's not that AWS isn't great, and it's not that they couldn't do it, because they're experts at a lot of things. It's that they have a lot of customers. And if you're connecting to the internet, you might get 900,000 routes almost in the internet routing table. But imagine a company like Amazon having millions of customers, and they'd have to keep all their routes. So they limit the number of routes that you can give them. So you can't give them 9,000 routes. You can't give them 5,000 subnets, which is in a routing table in a typical enterprise. You can maybe 100. So you're going to have to be able to take your routing information, summarize it, supernet it when you send that information to the cloud provider. And supernetting is the exact opposite of summarization. And I want to take the supernetting concept out maybe for a minute. I'll explain it to you. Supernetting is about hiding information from certain parts of the network to enable the network to scale better. So here's an example. If I want to go from my house and I want to go to, I'm not really an opera person, but let's say I wanted to go to the opera in New York City. All I really need to know is the following. How do I get to my local airport? How do I fly to New York? And as soon as I leave that airport, I can look for a taxi or an Uber and say, take me to the opera at this location. I don't need to have all the routes planned in New York City because somebody in New York City knows how to get me there. So that's what summarization is. Without the summarization, I would be able to see every route in the entire system along the way to get to that opera. And that way, but do I need that information? And because if you give me all this information, it's going to take up all the memory in my systems. And then when routes change, my systems are going to have to recalculate them. And can my systems handle the recalculation? In most cases, no. And then the systems fall apart, which is the reason why bad IP addressing that doesn't allow supernetting causes so many network catastrophes. So I'll give you an example of what this actually looks like. So in this particular context, I have 4 subnets that I don't want the AWS cloud provider to see, or the Azure cloud provider. It doesn't matter. I have the 192.168.0.0/24, the 192.168.1.0/24, the 192.168.2.0/24, and the 192.168.3.0/24. And guess what? I can send all of them if there's a reason to, or I could tell AWS, hey, you want to reach 192.168.0.0/22? Come to me and I'll take care of it. And that's really what's going on with route summarization, which is a mathematical function of supernetting. Like I said, we did a 4-hour workshop. We got all kinds of geeky. We had all kinds of fun. At least I love it because I love networking and I love teaching networking. And go watch that to make sure that you're familiar with it. And then the last things we really want to talk about is IPv6. It's a newer form of IP addressing because, we need a lot more addresses. It's been slow to adopt. Not the simplest thing for most people to understand, but it's not that challenging. Here's the key to remember. With IP addresses, we had 2 to the 32nd power minus 2 of IP addresses, which wasn't bad. But you can see it's not enough for every person in the world to have IP address on their phone, their computer, their tablet, their refrigerator, their washing machine, and every other silly thing these days that has an IP address on it. But IPv6 uses hexadecimal addressing, and it's 128-bit. So hexadecimal addressing, if you guys are unfamiliar, is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, Alpha, Bravo, Charlie, Delta, Echo, Foxtrot. So all the way from 0 to 15, which is 16 addresses. So it's basically 16 to the 128th power in terms of IP addresses. That's a pretty big number. We need someone like my wife, who's a genius with math, to go calculate that. Not that we do, but she could do it in her head. But it's a lot more numbers of IP addresses and it's more scalable. Typically used by mobile phones. So we're going to get into some more VPC concepts. Although I wonder how many, are there a lot of questions, Chris, in the back end? If not, I'll continue.
How much do you think your next section is?
If I go into BGP details, it's
never mind. Let's do some questions.
Yeah. What is the difference between a virtual private gateway and an internet gateway? Benedict, why don't you tackle that one?
All right. So for your resources in the AWS infrastructure to be able to access the internet they need a gateway, which is called the Internet Gateway, right? The virtual private gateway is a service that allows you to aggregate connections from, let's say, your site-to-site VPNs. So if you wanted to connect your AWS infrastructure to your branch office, you would have the branch office connecting to a virtual private gateway in order to access the resources in the cloud. But if your resources were just going out to the internet from the AWS cloud, they will go out through the internet gateway. That's the difference.
You're confused. Summarize means put many subnets inside one that can represent the small ones. Exactly. So summarizing and supernetting are exactly the same thing. Typically speaking, we subnet for efficient IP address use, and then we supernet for route summarization. Well, of course, we could potentially supernet because we had a subnet that somebody thought would be limited to 230 hosts. And the next thing we realize we need 400, and we can actually supernet or create a new subnet to fit them in. But typically speaking, it's only for route aggregation. Sam Jones, I like that. 16 undecillion IPv6 addresses. Yes, we've got a lot of them. Benedict, do you want to take that? So you can use a virtual gateway to connect to on-premises?
Yes, you can. I mean, that's the essence of the virtual private gateway, to allow you to make private connections to your branch offices and trusted partners.
What are the security measures? Well, we will get into many more security measures, but understand how to truly secure these systems. I mean, it would take us weeks or months to truly go into the depth of all the layers of defense in depth, all your points in zero trust, your encryption strategies that you would be using, your security policy, your user training. So there's a lot of security matters that are beyond that. But we will talk about the IPsec and the multi-factor authentications and all those other common things as part of this program. In the public cloud, which IP addresses are more common, IPv4 or IPv6? IPv4. Everything is IPv4 for the most part. When creating a subnet in a VPC, wouldn't the management console reject the CIDR if these overlap or any other issue? Yes and no. So if I try to do something really ridiculous and I overlap with one of my own subnets, the answer is it will catch it. But if I put the different subnets in the wrong places in a manner that I can't do efficient routing, that's where the problems are going to become. And it doesn't stop you from doing that. The same way as it doesn't stop you from making an insecure S3 bucket. And 60% of all hack attacks on the cloud are related to misconfigured S3 buckets. So it will stop the big, grossly obvious stuff, but it won't stop the stuff that's going to be the gotchas that's going to cause a network to fall apart, Ronald. Are you going to get an attendance certificate? Chirag, I have no way to know whether you've attended all of it, part of it, or any percentage of it. And we don't do this for AWS. We do this for you. That's why AWS doesn't provide us discount vouchers. If we want to give you good access to information, we need to be fair, unneutral, and biased. If we were to go to a vendor and doing it for the vendor, then in order to get them to give free or discounted vouchers, we'd have to do it the vendor way. And we want to stay fair and unpropriety at all times. I'm assuming you meant discount vouchers for the test. If you're talking... Benedict or Mo for this one?
Yeah.
So it says a virtual
So
private
the
gateway
question
used
is,
to
can we
pair
use
VPC.
virtual private? Yes. So yes, but that's
Go
not
ahead.
typically
Okay, so
what
that's
we
the question.
do. Yeah. So virtual private gateways are typically used. Think of it as a router, right? Think of it as an edge router you can use to connect different sites. And that the connection can be either a VPN tunnel or it can be a private line. Now, you can technically do that, connect two VPCs using a virtual private gateway, but for the most part, when you do that, that means you're using the public internet to connect two virtual private clouds, two AWS resources. So it makes more sense to use something like other resources that we'll talk about later, like a transit gateway or maybe a VPC peering. So that's not the typical setup that you want to do because you don't want to traverse the public internet to access two AWS resources that can be accessed much faster.
Benedict, just curious, if we were to connect two VPCs in two different regions, do you use a VP gateway or an internet gateway, or is it possible to create a VPN between the two? There's actually a lot of ways to do this.
So I think don't get it twisted. The internet gateway allows the resources in your virtual private cloud to go out to the internet, right? So if you want to connect two VPCs together, you want to use a different service. Mo mentioned the transit VPC earlier. That's one option you can use, or you could just do a direct VPC pairing between both VPCs in order to get them to be talking to each other.
And there's other options with regards to overlay networks. So there's a lot of ways that we can actually do this. And we're going to cover a lot of them as we get through the content, when we get to that section. This is a dangerous one, Sam Jones. Is it a better practice to dual stack your IP scheme going forward or just pure IPv6? So, Sam, if I am interpreting what you're saying, you're talking about using both IPv4 addresses and IPv6 addresses at the same time. Here's what you just did. You doubled your ability to be hacked. So the less things that you're reachable on, the less likely you are to be hacked. And the problem is a lot of the cloud providers give you two IP addresses, an IPv4 and v6 by default. And you should shut off anything that you don't use because it's a means to be hacked. How critical is it to become conversant with IPv6? It appears to be all just in the background, a fallback. It depends where you work. If you're going to be architecting IoT devices or mobile phones, the answer is yes, because there's just so many of them, and it's going to be too hard to address them otherwise. But if you're dealing with traditional cloud architect stuff, you could probably know IPv4 fairly well, and then find a good network architect or network engineer to help you with that when it's needed. For now. 5 years from now, 10 years from now, we may have to rediscuss that. Okay, Bantu and Proud, we're not saying any of this. So we're not going to say you don't need a direct connect to outside connections. Determining the wide area network choice is going to be based upon your requirements. What kind of performance do you need? Should you use an IPsec VPN? Should you use a private line, equivalent of direct connection? Should you use a SASE WAN? Should you use a software-defined networking WAN? What are the goals? What are the needs? We can't evaluate any technology until we know that. But we will get involved in these discussions further in the program. We will talk about that Bantu, when you should use virtual private gateways over direct connect. We will talk about that as well at the appropriate time in the program as part of the curriculum. Okay, let's go back to the content. So we're going to talk about the various components. Actually, before we do that, give me a hashtag AWS Advanced Networking. And before we do that, I want to remind you that if you just got here, we have a tremendous number of labs for you. And I mean a tremendous number of them. and almost 2 full days worth. We've got about a day and a quarter right now. Mark is doing some more. He's got a whole bunch of labs he's going to be dropping off by Sunday. We'll be doing some labs together on Sunday if we have time, but if not, we've got almost 2 full days of labs. So please, download them. We want you to get the full experience. And these aren't just AWS labs. They're easy. These are going to be labs that are going to give you the opportunity to see what's going on under the hood, real networking, real things. So kind of hope that's there. Just check. Looks like I'm a little fuzzy here, content-wise. So I'm going to just temporarily mute my camera and turn it right back on. All right, well, let's get back to the VPC. Now we're going to talk about the components of the VPC. Your VPC components are going to be your routing and your routing tables. We'll get involved, discuss internet gateways. We'll discuss egress-only internet gateways. We'll get involved in NAT instances and NAT gateways. We'll get involved with VPC endpoints, VPC peering, access control lists, security groups. We're going to get involved in all of it. And I don't love the way my internet is looking, so I'm going to try going out an alternative internet service provider, see if that makes it any better. So we're going to get involved in routing tables. And I'm going to talk about routing tables before we get to BGP. Because if we don't explain the routing table, I'm afraid the BGP won't make sense. So bear with me while I move some stuff around real quick. So in this particular case, the VPC will have a virtual router. A virtual router is a logical router that sits inside of the cloud provider. The virtual router will direct the traffic to its destination. Remember, I had showed you the routing model in the beginning. You take a packet, you point it forward from point A to point B, and it gets there. Well, routers build a map of the network. Typically, it's going to be, and we're going to use dynamic routing, and we'll get involved in a little of that, but understand we have a routing table. Now, you can actually see, in this particular example, we've got a routing table that says to get to this 172.16.1.0 subnet, it's local. In order to get to the 192.168.0.0/16, go out this port, this interface PCX 123456. To reach the 192.168.1.0/24 subnet, use this other PCX.654321. And then when you don't know where to go, and that's what that 0.0.0.0/0 is, when you don't know where to go here. And what most businesses do is they create a default gateway, and if they don't have a route in the routing table for it, they send it out the internet. And that's why it's going to an internet gateway where it says IGW 123456. So how do we build this routing table? Well, we've got 2 options. We can either manually configure it, or we can dynamically configure it. Well, here's what manual configuration would mean. An enterprise network will probably have 3,000 to 5,000 routers and a good 5,000 subnets. So I'd like you for a moment to think about what it would actually feel like if you had to go to 1,000 different routers and manually configure 5,000 different routes on every single router. So think about that. And anytime one link would change anywhere in this network, you'd have to manually go configure it. You'd have to manually SSH to all these thousands of routers and manually change it. And then as soon as a link went back up, you'd have to go manually go to all these routers and manually change things. Do we think that's going to work? No. Here's the other problem if we manually put our routes into the system. Things don't self-heal for the most part, unless you're really good and you get really tricky with recursive routes. So here's what I mean by this. Without dynamic routing, via static routing, it's going to be what it was like when I used to want to go visit my friends. Here's how I would visit my friends years ago. Let's say I was in Philadelphia, because that's where I was living, and I wanted to go to Palm Beach County, Florida. first thing that I would do is I would write down every possible street. Make a left here. Go 1 mile, make a right. Go 2 miles, make a left. Stay on the straight for 5 minutes. Jump on I-95, get on exit this, get off exit this, get off here, get off there. And darn it, when I'd leave my house in Philadelphia on the way to West Palm Beach, there'd be a roadblock in front of me and I had no idea where to go because the maps that I looked at and the static directions that I had didn't work because there was a detour along the way and I would get lost. All of a sudden, I bought a GPS. It was the coolest thing ever. Go straight, make a left, recalculating. I haven't been lost since. It's the greatest thing. Well, I still get lost, but I get lost a lot less. That's the same thing that we're doing with dynamic routing. We want the routers to be able to calculate the best path for us. Now, in our data centers, we have different kinds of routing protocols. In our private networks, we typically use something called an interior gateway protocol that's designed for fast speed and self-healing. The problem is when you design something for fast and speed, its capability of scalability typically goes away. So think about how much stuff you could haul in a Ferrari from Palm Beach to New York City, or in a tractor trailer from Palm Beach to New York City. I promise you can get there faster in the Ferrari if you didn't mind getting speeding tickets and you didn't get arrested on the way from Palm Beach to Miami. So I don't recommend that, and we care about people's safety, but you get that. But how much stuff are you going to bring there? Not a lot. But because it's not designed to scale, it's designed for speed. Now in that tractor trailer, you're going to get a lot. So internally, organizations will use an interior gateway protocol, OSPF, ISIS, EIGRP for the most part. And externally, they're going to use BGP. Connect to the internet service provider, use BGP. Connect to the cloud provider, use BGP. So we're going to use BGP to build our routing tables. So it's going to look something like this. We're going to have our own organization. Let's say we're on the left side of the screen. And you can see that's our interior gateway protocol running internally. And we've got a router that's connecting to the organization on the right. They're doing their EBGP pairing. And internally, that organization is running their own interior gateway protocol for reachability between their devices. And they're going to connect to their customers, say it's a cloud provider, via BGP. So that's why you're going to be using BGP. Now, what I'm going to do is a brief review of BGP. Brief meaning like 45 minutes to 60 minutes, so it's going to be short. And then we're going to get into all those internet gateways, routing tables, etc. But if you don't understand this, it doesn't matter. You won't be able to do anything with it. So we're going to get here. Now, I'm going to tell you right now, we did a heavy-duty BGP session. And in that heavy-duty BGP session, boy, my screen got very far. Well, we did a heavy BGP session, which my team is going to send you to. And I'm going to do a brief review. But something funny is going on with my internet. So let me see if I can switch to a different internet service provider. I've got several of them here.
It's like ISP roulette back there.
Yeah, it sure feels that way. I've got 2 AT&T links and a Verizon link. I went from my one AT&T to my Verizon. Let me use my backup AT&T link, and we can hope that's better. Also, let me try to do this. Let me reduce my bandwidth needs a little bit. I think that might work better from a latency perspective. Let's see if it changes. Looks like it's getting better. Okay, so now that we've got our internet bandwidth temporarily filled out, let me know, guys. Let me know if anything changes. Let's get back to this concept.
You can do a little dance and we'll figure it out.
A little dance? What was that song? Get down tonight. Get down tonight. Long time ago. Anyway, so we'll do a brief intro to BGP, but Mark and I did a good 8-hour BGP workshop for you guys. Hands-on in there, but I want to go through this because you will see some test questions like BGP being TCP port 179, and they may discuss some attributes on your exam, and I want you to pass it. So go see the good 8-hour video, which is supplemental material to this. go see the subnetting thing, and Alonzo knew which song I was going to sing, and then we'll do a brief review of BGP. So what is BGP? It's a routing protocol. So it's how we connect and learn routing information from other entities. Talked about why we don't want to use static routing, why we want to use dynamic routing. And some basics to remember, these could be exam questions. BGP is unicast. And what does that actually mean? It means that in normal routing protocols, they discover each other. Hey, anybody want to route with me? And they do that via an IP multicast. They discover each other. But with BGP, I have to tell it. So I want to go peer with Mo. I ask Mo, you want to peer with me? Mo says, yeah, Mike, I want to peer with you. You want to peer with me? We connect. We start exchanging routes. BGP uses TCP port 179. Now, why does this matter? Well, yeah, you'll probably get an exam question on it, but that's not the reason it matters. What if you have a firewall in between your BGP speakers? If you don't open TCP port 179, they will never peer. You will never have routes, and the thing will fall apart. We use BGP because of its tunability and its scalability. Internet routers have 900,000 routes. You might peer to 9 different sites. And BGP has what they like to call nerd knobs, which I always thought was a cool term. Change the weight, change the local preference, the AS path. And you could literally turn these little knobs and direct traffic all over the internet. It's kind of the coolest thing ever. At least I found it fun, and I've done a lot of BGP consulting, so you can tell I'm excited about BGP. So lots of tuning. So I'm going to go over the BGP messages. Why? Because if it doesn't work, and you're a cloud network engineer, you're going to have to debug it. And you're going to have to see what's going on. So BGP has basically 4 messages: an open, a keep alive, an update, and a notification. If you see these in your debugging, if you're an engineer, you'll make sense to you. So what are they? What's the open message? Very simple. The open message is as soon as the TCP session is established, the open message is saying, hey, we're opening a BGP session with each other. Here's my version of BGP. Here's your version of BGP. Here's the timers that we have to establish with each other. So I like to think of the BG open message as a hello and welcome. That's what I see. Next, there's something called the keep alive. Well, I've got 2 BGP speakers. They're talking to each other. We need to know they're still there, right? Load balancers run health checks, right? DNS does health checks, right? To make sure that the endpoints are still there. So a keep alive is a message between our 2 BGP speakers that says, I'm still here, everybody. I'm still here. Sometimes I do that with my wife at night. Hey, are you asleep? Are you awake? It's the same thing. It's a keep alive. It's basically just to see, are the neighbors still there? Next is the update message. The update message is, I'm connected to another BGP speaker. I learn a route. I lose a route. I send it in the update message. Now, if the path has changed, for example, it used to go this way and now it's going this way, that's still in the update message. So new routes, lost routes. That's what we're talking about in the update messages. And then here's the thing called the notification messages. I don't like notifications periodically. I live in an HOA. I get a notification, my grass is too tall, my grass is too short, my landscaper didn't show up for a day. That's a notification. Something went wrong. So open, kind of talk to each other. Keep alive, I'm still here, I'm still here. Update, something changed. Notification, something bad happened. Kind of like the letter that you don't ever want to get from your homeowners association. So now you go those messages, and if you're debugging it, it'll make sense to you. Now, we're going to get briefly into how BGP forms a neighbor relationship. So in case it doesn't work, and if you're that cloud network engineer and you're on the router on the other side of the cloud and you see that it's stuck inactive, or it's an idle, or it's an established, you need to know what it means. So here's ultimately what happens. When you start BGP, it's idle, kind of like your car, right? You start it, you turn the key, and nothing's going on till you put it in drive park. That's idle. It's waiting for BGP to start the TCP connection. Connect. Okay. You're starting to, if the BGP sets up a TCP connection between the other BGP speaker, it's connected and it's going to send an open message. Idle, doing nothing. Connect, we're connecting. If it works, we send an open message. If it doesn't, we transition to active, which is kind of this place where we're going to keep retrying. And either it's going to work at some point, we're going to go to open. And if not, it's going to go back to active and then idle. Next, connect. Sorry, I already mentioned connect. Active. So we send this message, we send a message, and then after we send a message, it doesn't get sent, doesn't get received, we transition to active. If that open message goes to active and then it finally gets sent, it transitions to open sent. Open sent, the messages have basically been sent, the open message has been sent, each neighbor has received it, and that's really what's going on in open sent. If the messages have been received, we transition to a state of open confirm. And here we actually send a keep alive notification. And if the keep alive is sent in between them, the session is established. So real quick, idle, we begin. Connect, as soon as the TCP connection is set up between the two routers, we transition into connect. Right after connect, we should transition to open sent because we sent an open message. But if we did not, we will transition to active, and active is kind of like a holding pattern. If in active nothing happens, we go back to idle. And if something happens good in active, we go to open sent. And then open sent, we basically send a keep alive message in this open confirm state. And then at that, it becomes established. And then boom, 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 everything possibly happens. And we're now connecting and exchanging routes. So if you see that, now you know why. I'm going to very briefly go into BGP attributes. I'll talk a little bit about traffic engineering, and then we will get back into the content. Just want to do a very brief BGP refresher. So when the routing information is exchanged, it can be sent with an attribute. These attributes are information about the route. And you can use information about the route to make your determinations. Let's face it. Let's say two networking people try to tell me something. Mo and Benedict tell me something, and I believe them, right? And somebody that I've never met told me something. I'm less likely to believe them. Well, it's an attribute. I'm not sure in the chat box. I'm not trying to share a screen. So there is no screen sharing going on right now other than my video. So the first attribute is the origin. How'd you learn the route? Did you learn it internally from your IGP? Which is, did you learn it from yourself effectively? Great. Did you learn it from somebody else? EGP. Good, but not as good as if you learned it from yourself. And incomplete is, I don't know how I learned it. Think about that. The AS path. How'd the route get to me? Did it go to AT&T, Verizon, NTT, CenturyLink? Did it just come from Verizon? What do you guys think? The shorter the path, right? The more accurate or the lower, the better the performance should be. All things being equal, that's true. The next hop. Where am I going to send the data? All right. Where am I going to send it? If the next hop's not available, don't send it anywhere. Just drop it. The wait. The wait's a manner that you can manipulate your outbound traffic. It's something that's mostly a Cisco feature, but it's supported in AWS. So why am I talking about this? Well, here's how we're going to manipulate our traffic. Prefer the path with the highest weight. If the weights are equal, prefer the path with the highest local preference. If the local preferences are the same, prefer the path that originated locally. If all that's the same, and I'm going to summarize this, then go to the lowest origin code, meaning I learned it internally, IGP is greater than I don't know how I got it, for example. And then after that, if the origin codes are the same, let's look at the lowest multi-exit discriminator. So, there's a couple other things that we can look at, but I'll give you an example, and then we will go back to the we'll go back to the actual content with virtual private gateways. But let me give you one more. I'll just work through a little example with you guys. And then after the example, we'll get back into the AWS predominant content. So let's say in this particular environment, we've got 2 routers. And they've got 2 links on them. Two routers, 2 links, right? Simple stuff. Now, if this link is on AT&T, which is a fairly large American phone company, and this link is on NTT, which is an incredibly large Japanese internet service provider and phone company, do you think there's a chance that the latency or the time on this link would be slightly different than the time on this link? The answer is yes. It's most likely going to be. And I don't care if it's NTT, I don't care if it's Verizon, I don't care if it's Vodafone. Every link that goes through a different pathway is going to have a different latency. So in BGP, the reason we care about these nerd knobs is we could potentially send the data out of a Verizon link, and half of it could come back on the Verizon link, and half of it could come back on the AT&T link. Normally, you wouldn't think that's an issue. But what if this is 2 milliseconds, and this link is 1 millisecond? And it could be either one. This is just, and half of the data comes back. So now 50% of the data goes out and comes back on Verizon in 1 millisecond, and the other half of the data comes back on this link. And in this case, particularly AT&T link had 2 milliseconds, although they should be fairly similar. And one could be faster than the other. It doesn't matter who we're talking about. But now this one comes back in 2 milliseconds. So some of our data is going to arrive out of order. This is not good. We want our data to arrive in order. So typically speaking in BGP, in order to load share across our links, we're going to need to use some of these nerd knobs. And we have nerd knobs that we can choose like wait. So, and BGP routing is done in both sides, but I'll give you an example. If we wanted the top link to serve 172.168, 172.168.1.0.0/16 as a primary, and we wanted the bottom link to support 172.17.0.0/16, we can do that. And we'll do, and the way we would do this is we would say change the weight to 35,000 because over the default. And then we would put the other subnet on the top link with a weight of say 0. And then we would do the exact opposite on the bottom. Bear with me, I'll paste this in and then I'll tune it. And we can make the top link more preferable to the bottom link. By comparison, we could also change the local preference. Let's make this local preference 200, because remember the higher local preference is preferred. Make this 100, change this to 200, change this to 100, and we can still make it the traffic destined for the 172.16.0.0 subnet uses the top link, and traffic destined for the 172.17.0.0 subnet uses the bottom link. So that's really what we're talking about with BGP. Like I said, we did an 8-hour BGP session, and I want you to understand it. I just covered the things here that you might see on your test, like the messages, unicast versus multicast, the TCP port numbers, and I also want you to understand it from a basic debugging perspective. But at this point, we're going to go back to the AWS content, and please do see that 8-hour BGP webinar. Now, next is the VPN gateways. So, Chris, if you'd like to put the next person on the screen for the VPN gateways. I believe that's Mo. All right, let's take some questions in the meantime while Mo gets his system up and running. Ronald, you might be jumping the gun, but do you manage BGP through security groups and direct connection? Will we utilize BGP outside of the direct connection? Ronald, you're going to be using BGP everywhere. We'll get into CloudHub, we'll get into Transit Gateway. BGP is necessary for multi-cloud architectures to work, which is 98% of the cases. So we're going to be using BGP everywhere. And we're not going to manage it through a security group. There's a lot more security we need to do for anything than just a security group. But it's part of it. Security groups are a good way to kind of protect a service like a virtual machine. Do you have any others? We can do a couple more. All right. Well, then, Mel, off to you.
Okay. Okay, I'm sharing my screen. Can everybody see my screen? Okay. So a virtual private gateway. Think of a virtual private gateway as your edge router, right? So you are on AWS, you have a VPC, and you want to your VPC to have access, or your VPC resources to have access to your on-premises and vice versa, right? This is where you would use a virtual private gateway. A virtual private gateway provides two options to connect to your on-premises. You can either use private lines, which is a private dedicated line that you buy through a service provider that will connect you from your cloud to your on-premises, and that's a dedicated line. Or you can use the public internet, right? So in AWS, you're using an internet gateway to access the public internet, right? Well, the IP address on your on-premises router, that's part of the public internet. And so what you can do is use the virtual private gateway as a what we call a VPN concentrator, which is just a point to establish a VPN tunnel or a virtual private network tunnel from your AWS VPC to your data center or remote sites, right? So let's bring a little bit of some diagrams to kind of have like a better understanding through a visual representation. So in this diagram, as you can see, right, we have different figures, and each figure describes or shows a different setup, the different setups for a virtual private gateway. One thing, if you notice here, each virtual private gateway, this icon that looks like a log, right? That's the virtual private gateway. That's what we use to describe it. Notice that it only connects to one VPC or attaches to one VPC. That's one of the limitations of a virtual private gateway. You can only attach it to one virtual private cloud. So if you have many virtual private clouds, such as figure 1B, notice that you would need a virtual private gateway for each VPC. Now, once you have a virtual private gateway, you can connect your virtual private gateway to multiple, you can establish multiple IPsec tunnels or VPN tunnels. That way you have access to through different tunnels to your virtual, through your VPC. Now, in the first example to the left, what we have here is a private line, right? And what we're doing is we have a private line, which AWS calls direct connect, right? And that dedicated line terminates at your virtual gateway. Okay. Now, this is something we'll get back to later, but just keep in mind that with private lines, when you connect private lines to a virtual gateway, you can always only establish private virtual interfaces, which is a private direct connect, because there's a different type that is called a public virtual interface as part of the direct connect. We'll get back to, but just keep that in mind, and we'll get back to it. So as you can see, the three scenarios, 1, A, B, and C, we're using the direct connect to establish a private line, right? And that can be either directly through the private line or through using, as in figure 1B, using a direct connect gateway, which is a different type of router that is specifically used for private lines. So you can use one or the other. And then if you look at 1D and 1E in this case, this is where you would establish an IPsec tunnel over the public internet, right? So notice that to the right, which was a question 1E, which was asked earlier, right? Can we use a direct connect, a virtual private gateway to establish a VPN tunnel between two VPCs? And the answer is yes, but it's not. Let's say it's not the best way to go about establishing a connection between two VPCs. However, it is an option, right? The most typical scenario would be figure 1D, right? Because you have your corporate data center and you have your AWS cloud or VPCs, and you want to establish a virtual gateway. Through your virtual gateway, you want to establish an IPsec tunnel. So what's the benefit of doing something like this? Well, one of the main benefits is that it's almost instantaneous, right? Because if you think about it, if you wanna use a private line, that means a service provider will have to terminate an actual a cable to your data center, right? They have to run the cable, and that can take some lead time that can be up to months, right? Weeks and months. But with a virtual private gateway, it's almost instantaneous, right? As long as you have internet access and your data center have internet access, you can establish an IPsec tunnel. When you use a virtual private gateway, typically what you do, or AWS, what AWS does, they would allow you to establish two IPsec tunnels from two endpoints. You don't see the actual endpoints, but a virtual gateway is a highly available resource, meaning if theoretically one IPsec tunnel could fail because the AWS gateway fails, but there would be another IPsec tunnel as a backup, right? When you establish an IPsec tunnel, you have two options when you use a virtual gateway. You can either, so obviously there's the components of establishing the IPsec tunnel between point A and point B, but how do you go about rounding the traffic or learning the routes through that IPsec tunnel? Well, there are two options. There is static routing, which means you statically point your traffic to reach the VPC. So from your on-premises, you would statically say, if I want to reach, let's say, 192.168.1.0 network, I will point my traffic towards the IPsec tunnel. And the same thing from the VPC side. You would have to statically say, my traffic for the on-premise resources will be pointed towards the IPsec tunnel. But there's a different option, which is using BGP. Mike was just talking about using BGP. You can run BGP over the IPsec tunnel, and that way you have a more dynamic way of learning the routes, right? Now, one of the benefits of using a virtual private gateway is you can dynamically populate your routing tables, which means you have a VPC. Let's say you have one routing table, right? Or one subnet, a private subnet, just in the case of 1D, right? In the figure 1D. What you can do in that routing table, once you establish the IPsec tunnel and you run BGP and you have the routes received through that IPsec tunnel, you can go to the private subnet and ask the private subnet to populate those virtual gateway routes, or the IPsec, the BGP routes learned through IPsec. Okay. We already talked about the different types. We said we described it visually. We can use private lines or site to site. IPsec tunnels. This is a diagram that shows how one virtual private gateway can establish multiple VPN connections. So in this example, we have 3 on-premises networks or offices, and we can establish 3 IPs. We establish here 3 IPsec tunnels over, or VPN tunnels over the public internet, right? But notice there's only one VPC here, meaning your virtual gateway only connects to one VPC, and your VPC cannot have more than one virtual private gateway. So that's a very important thing to keep in mind, one of the limitations with a virtual private gateway. Now, later on, we'll describe a process called AWS CloudHub, and we'll go through CloudHub in details, but just keep in mind that one design architecture or architectural pattern that you can use is for one of your on-premises networks to gain access to another on-premises network through the virtual private gateway, which means you would be actually sending your traffic back here, which means that you would actually be sending your traffic from one office, one on-premises office to another through the virtual private gateway. Right? Later we'll talk about the benefits and the drawbacks. Does it make sense to do something like this or not? Just keep in mind that that's one of the architectural patterns, which is called a cloud hub. It's just an architectural pattern for a virtual private gateway. Well, let's say a feature. Okay, we spoke about private lines, which is called direct connect. Okay, so actually, before we move to the benefits, I want to bring up a few other points, which are, give me 1 second. I'm going to try to draw or sketch. Okay, so we'll go through this real quick. So you have your VPC. Over here you have your virtual gateway, and you have your on-premise. You're connecting over the public internet, right? Now, imagine that, well, let's say on-premise has the IP of X or the network of X. Just keep it really simple, right? Let's say over here you have the network of Y, right? Now, you have a routing table inside your subnets, right? You receive X through your on-premises, right? You receive it through the direct connect gateway. You populate it to your routing table. And then, of course, you have Y, right? Let's say you added a different subnet. Let's say inside your VPC, you created a secondary subnet, and it was also X, right? You can see here that there's an overlap, right? Because this X and this IP, they're both the same. What would happen when you have an overlap, right? When you have the same subnet from both ends? Well, when that happens, there has to be a tiebreaker. There has to be a method for one IP, because they're the same IP, they're duplicate. One of them has to be more preferred, right? So there's an order of preference here. And the order of preference says that if the subnet is local to your VPC, then it's always preferred, even if it's a shorter match. And what I mean by that is, if you think about it, let's say here you have X, but it's a /30, right? It's a smaller subnet, right? And over here, this is a /24. Well, in the typical networking of our understanding of traditional networking or on-premise networking, let's call it, right? Longer match is always more preferred, right? You always go for the longer match. Then if both routes are the same match, meaning they're exactly the same subnet length, then you would prefer whichever has more preference based on administrative distance and so on, right? Now in AWS, and they did this kind of like a way to so that you don't break your VPC or you don't break your routing, right? They said, if I have a network, let's say /24, right? It doesn't matter if I have a longer subnet or not. This will always be more preferred, right? So keep that in mind. So that means your local VPC routes are always more preferred. And then after your local VPC routes, you have static routes, right? Which means routes that you added to your routing table of the subnet. Those are also more preferred if it's the same subnet, if it's the same subnet length. If it's a longer match, then the longer match is more preferred. So this is where we get back to what we know traditionally in traditional networks, where longer prefix is more preferred. But just keep in mind, a VPC, a local subnet on your VPC is always more preferred, regardless of the subnet length or the prefix length. Okay, I'll stop sharing my screen. Do you have any questions related to virtual private gateways?
All right. Well, let's do a little more content and go back to questions in a little bit. Thanks so much for that, Mo.
Thank you.
So let's talk a little bit now about internet gateways. Actually, you know what? I think it's been a long enough time for a question. Let's do some questions real quick.
Okay. So the question is a virtual private gateway mandatory for a direct connect service, right? When we say direct connect, we mean private lines. Is it mandatory? No, it's not. There's different ways you can attach your, you can establish a private line, right? More typically, what you would use is you would use a direct connect gateway, which is a router that is primarily used for private lines or direct connect. We like to keep kind of like the industry standard naming. We don't like to use direct connect and so on. We say private lines, but yeah, you can say that a virtual private gateway is just one way to do it, but more realistically, you would use a direct connect gateway.
Okay, so before we get to the next one, if I can guide you guys just a little bit, try to avoid acronyms, because a lot of people won't know VPG. For example, Michael, who I know, put DX, which to me means diagnosis, versus direct connection. So lots of errors occur when we use acronyms, unless everybody uses the same acronym. So just a thought, because I can tell you I fixed a lot of architectures where people didn't understand each other. They made mistakes through loss in translation and lots of problems.
Okay, so another question is, do we enable BGP on the virtual private gateway, or is it enabled by default? It is not enabled by default. You have the option to either use static routing or enable BGP. Now, once you enable it on the virtual private gateway, so this is one of the features of virtual private gateway. I'll go through very quickly. Once you create your settings, let's say you're doing it on the console, the GUI, graphical user interface, right? You establish the tunnel, and then you get to download the configuration based on the vendor of the router that's on premises, right? You can say, let's say on premises you have a Cisco router, and you say it's an ISR router, so a specific module router. You download that configuration, then you have your configuration that reflects what needs to be put on premises to establish that BGP connection. Kind of went over the question, but hope that answers it. Okay, how does VPC peering affect virtual private gateways, since they can only exist on one VPC? Let me try to attempt to answer, because I'm not 100%, I don't 100% understand the question, but you're asking, how does a VPC peering affect the virtual private gateways? So you're asking if you have two VPCs, let's say, right? And you have different types of connections. You have a virtual private, a VPC peering between two VPCs, and you have a virtual private gateway established between those two VPCs as well, right? So since only one exists, only one virtual private gateway exists, but you can have VPC peering as well. That doesn't mean you can't have different types of connections, if that answers the question. So you can have VPC peering and a virtual private gateway running a VPN tunnel to that between those two same VPCs.
We'll get into much more depth of when we're going to be using these things architecturally through the program. I think it'll make more sense then. Can you use a direct connection along with a VPN? Sure, you can use a direct connection with a VPN as backup. You can run IPsec over a direct connection and effectively taking your direct connection and turning it into a VPN as well. And there's good reasons to do both. Sometimes not either. Thank you for this bootcamp, Mike. Regarding BGP, I understand that it chooses the best path based on settings. In the BGP workshop examples, you set one subnet to use one path and then set one to use the other path. At this point, you understand BGP uses multiple paths for different subnets. Can BGP use more than one path from different vendors to load share? So on the same subnet. I don't know what you mean by that. Now, could we have BGP peering to AWS, Azure, Google? Yeah, we sure could. So there's that we could do. But, you know, the BGP peering session is going to be on the same subnet. But would you have, is the question that you're asking, would you have a point to multi-point connection on the same subnet between your data center, AWS, and Azure? No, because you hopefully would be using different routers for your direct connections. And also, unless you'd be using a pseudo connection, which could potentially be done, you'd have to be on different subnets for both Verizon and AT&T. So no, you wouldn't be on the same subnet no matter what. And the whole point of BGP is to route across domains. So the only thing that'll be on the same subnet with regards to eBGP typically is port to port.
Do I need a virtual private gateway if I don't want to run IPsec? Well, you use a virtual private gateway to run IPsec or private lines. So do you need a virtual private gateway if you don't want to run IPsec, and let's say you only have traffic between different VPCs? You don't need it, basically. It's not necessary, no. That's a very good question. By default, it is not transitive by default, right? But Mike will go through explaining a CloudHub, so I don't want to waste time right now. But it can be transitive if we activate it.
And we'll get into how we would break those rules, much like we would do with the BGP route reflector.
Okay. So what William is asking, what kind of VPN framework does a virtual private gateway support? So is it IKE version 1? Is it IKE version 2? Is it Flex Connect? So AWS, since 2019, they started supporting IKE version 2. Before then, it was IKE version 1. You can use either one, but it makes more sense to use IKE version 2.
Yeah.
So we're talking about IPsec when people, just so everybody knows. Is it a hub and spoke, or can it be a mesh topology? Well, technically what you're doing here, you can call it hub and spoke, but really what you're doing is you're establishing point-to-point IPsec tunnels, right? So it's all point-to-point IPsec tunnels. But you can have a hub and spoke setup.
So can you elaborate on how instances are connected in the AWS cloud? Sure. An instance is nothing more than a virtual machine. It's the same virtual machines we've been using in the data centers for decades. And how does that work? You got a server plugs into a switch, which is plugged into the cloud provider's network. That's it. So same way you would plug your computer into your house into a switch, that's exactly the way the servers are there. Now those servers, become virtualized. And we've got some videos on virtualization and virtual servers where I walk you through a VMware server where you can actually see what happens. But that's all an instant is a virtual machine. When using multiple paths to connect to the same cloud provider, there's got to be a second half to this. Okay, so Cantor Grant, even if we're going to have multiple physical paths to the same cloud provider, they're still going to have to be on different subnets, because if we want them to be on different interfaces on the same router, it would have to be on a different subnet. And ideally, we're going to use two separate routers. And ideally, these routers are so important that they're going to have multiple power supplies, multiple control modules, and we're going to have to put them on different subnets to create two connections to the cloud provider. And they're not going to be on the same cloud provider. For example, it wouldn't make sense to get two connections on Verizon. Wouldn't make sense to get two connections on AT&T. They're going to have to be across different providers, different routers, different power redundancy in the units, different fiber paths under the ground. We want to make sure there's no single points of failure. Next one is the last question, and then we will get back to the fun. Or I think it's fun anyway. If one virtual private gateway is only connected to one virtual private cloud, how can you use it for tunneling between the two VPCs? Or Benedict.
Yeah. Okay. If one virtual private gateway is always connected to one VPC, how can you use it for tunneling between two VPCs? Well, you use it for tunneling between two VPCs because each VPC has its virtual private gateway, right? So think of VPC A with virtual private gateway A, VPC B with virtual private gateway B, right? So they're completely different VPCs. Each one can have its own virtual private gateway, and then they can establish an IPsec tunnel between them.
All right, let's get back to the content. So now let's talk about internet gateways. I'm pretty sure that's me that's next, right?
Yes.
All right, so what is an internet gateway? A gateway is just another term for a router. Gateway, router. They used to call your PC, go to the default gateway. That was your default router. And an internet gateway is nothing more than a router that connects you to the internet in AWS. Data center, router connects to the internet. AWS, router connects to the internet. Same thing, other than it's virtual. It is a basically high availability system. And why are these systems so high availability? They're high availability because they're logical and they don't go down, because they can be put anywhere on the systems. I hope that kind of makes some sense. So there's that. So you create an internet gateway pretty easily. The data center, you take your router, you plug it into the wide area network, you configure your BGP or your default routes to the internet. That's how you do it. So how do you do it in the cloud? The same way. You go and you attach an internet gateway to your VPC. You create a default route, which means if I don't know where to go here to the internet. You put a public IP address on your internet gateway, and now poof, your systems are reachable from the internet. Note what I just said. Your systems, specifically if they have public IP addresses on them, are now reachable on the internet. The internet is not a safe place. It is a scary place. So the second you add an internet gateway into your systems, you're exposed to the internet. So if your systems don't need to go to the internet, or you need extraordinary security, don't use an internet gateway. But you want a web server reachable from the internet, you're going to need an internet gateway. So I hope that makes sense. Now, before we get to an egress-only internet gateway, let's talk about ingress and egress. Ingress is traffic that comes into you or your domain egress is traffic that leaves you. That makes sense. So what if we wanted to allow our IPv6 traffic to go to the internet and come back, but we didn't want our internet traffic to come in? That's when we would use something called an egress-only internet gateway. And an egress-only internet gateway is used specifically for IPv6 addresses. The egress-only internet gateway will allow all your IPv6 systems to go out to the internet and say patch their operating system. Maybe they're going to the Ubuntu or the Red Hat page to patch their operating system, and the traffic can come back. But it will not allow external traffic to come in. So very similar to a NAT gateway without an internet gateway, which we will talk about as well. Now, we're going to talk about a NAT instance. AWS doesn't love to talk about these things, but there is a time and a place for a NAT instance. All a NAT instance is it's a virtual machine that will translate a private address to a public address. But, with NAT, you can translate a private address to a private address, and you might need to. Imagine two companies are using the same private address space. Remember, we talked about addressing your VPC with these RFC 1918 addresses, like the 10.0.0.0/8. Company 1 is using 10.0.0/8. Company 2 is using 10.0.0/8. Companies agree to merge. Overlapping IP addresses, we've got a problem. And we can use network address translation to translate a private address to a private address. Maybe we translate these 10 addresses, 10.0.0.0, for example, to 172.16.0.0, or what have you. We can translate, and that's one of the things we use NAT. But in the NAT instance, the way most people know it is that it's a virtual machine that does NAT, that it will NAT your systems out to the internet and allow your return traffic back. So NAT instances only allow for egress traffic, meaning outbound traffic to go out, outbound traffic to come back. Now, in order to use the NAT instance, you need a NAT instance and you need an internet gateway. No big deal. But AWS tried to make it a little simpler for you. So if you wanted to look at what a NAT instance is going to look like, it's realistically speaking something just like this. You've got your private subnet. You've got a public subnet. The public subnet connects to the internet gateway, which connects to the internet. What if you didn't want to have to use an internet gateway and a NAT instance? Well, AWS is now a fully managed NAT service. Fully managed is they manage it for you. You don't think you have to think about the virtual machines. Here's the thing with fully managed services. As a rule, they're real cheap if you don't use them a lot. And they get real expensive when you use them a lot. So there's lots of ways you can do NAT. But a NAT gateway is a fully managed service, which means no operating systems to patch, nothing to think about, which means less control. And if you use it very little, less cost. If you use it a lot, think more cost. But you create your NAT gateway. It's a redundant logical network address translation device that will translate your private addresses into public addresses. You create the NAT gateway in the public subnet. It will use a public IP address, which AWS calls an elastic IP. And it will maintain that IP address for the life of the gateway. You will tell your systems when you don't know where to go to the NAT gateway, and they will be sent to the internet just like in a network address translation manner. And honestly, it's more of a port address translation manner because you can translate, hundreds of addresses into a single address, which is actually called NAT overload, otherwise known as port address translation, often referred to as PAT. So a very simple solution over here. A NAT gateway is a router that does NAT. It connects to the internet. All in one. Very simple thing to understand. Put your NAT gateway in the public subnet, route your traffic to it, and you're good. Okay, now, I can't imagine how anybody could use the word elastic in so many different things. So every device that's going to connect to the network needs a network interface. The Ethernet port on your server is an Ethernet interface. But in Amazon world, they put the word elastic in it. So you can think of a network card as an elastic network interface. So when you start your virtual machine, otherwise known as an EC2 instance on AWS, an Azure virtual machine on Azure, or a compute engine instance on Google, same thing, you need a network interface. So on AWS, it's called an elastic network interface. Now the default elastic interface on an AWS EC2 instance is ETH0. ETH0. Kind of keep that in the back of your mind. That is an absolute normal interface. So the default. Now, what if you want your server to be on two different subnets? There's lots of reasons you would dual home a server. Well, guess what? You can do that too. You add two elastic interfaces into the same server. People used to do this for Bastion hosts, which is probably one of the worst security things you can do, and we can talk about why that would be at another time. But typically, that's where a use case where you might actually have two network interfaces. Now, that was an elastic network interface, which was just a standard interface on your systems. But now, how about an elastic IP address? What's an elastic IP address? An elastic IP address is a public address that you get from AWS. So, elastic network interface, standard interface. Elastic IP address, public IP address. So let's say you need something to be reachable from the internet. It will need a public IP address. It will definitely need that. Otherwise, you won't be able to reach it. So you'll need to get one from Amazon. And they'll call it an elastic IP address. Basically what happens is Amazon's a large internet service provider, amongst other things. They maintain a pool of addresses. When you need a public address, you borrow a public address from AWS, it becomes your elastic IP address, and you keep it as long as you need it. And when you're done with it, it goes back to AWS, and it goes back to the pool, and then they resell that IP address to someone else. An elastic public IP address can have it mapped to multiple private IP addresses, like in that port overload translation manner, or it could be a one-to-one, meaning one elastic IP address on a web server, assuming you didn't have two and use a load balancer. Or it could be one IP address on a load balancer with many web servers behind it. So what's it going to look like over here? You can see you've got these devices over here, and they all share a common elastic IP address of 2.2.2.2. That's all we're really talking about. So we're going to talk about endpoints. We'll get into VPC endpoints. We'll get into gateway endpoints. There's a couple kinds of endpoints. But what is an endpoint? It's something you connect to in a secure manner. So we always have to terminate or connect to something. If I want to call somebody, I pick up the phone and I call them. I put their phone number in there, right? If in a traditional network, I've got a router which connects to another router, they plug into each other, each thing is effectively an endpoint. I've got a server, I want to connect to a server, that's an endpoint. So when we're connecting things in the cloud and connect one thing to another thing, we create an endpoint. And an endpoint acts as a virtual device to connect to. Here's the thing to remember with an endpoint. The endpoint on the AWS network reaches another endpoint on the AWS network. It's all on the AWS network. So if we don't leave the AWS network, we're much more secure than if we leave the AWS network and we go to the internet. So kind of the same difference between using a private network versus a public network. So I kind of hope this makes sense. So we're going to use our VPC endpoints or any endpoint to enhance our performance, to reduce our latency, to promote security, and to promote cost. So, and this is less of an issue than it used to be cost-wise, but let's say, for example, you've got an S3 bucket, object storage on AWS, no big deal. And you've got your VPC, your virtual private data center. Well, AWS Object Storage, otherwise known as AWS S3, does not live inside your virtual private cloud. It's outside of that. Now, AWS S3 is available from the internet, so you could potentially leave your VPC, go to the internet, connect to AWS S3 like I showed you in this diagram, and then have S3 go back to the internet, across the internet, and back into Amazon. And when you were paying egress fees, you'd actually be paying a lot for this. So kind of keep that in the back of your mind. But here's the thing about the internet. It is a very scary place. There's lots of hackers out there, lots of people that would love to do harm. You want to send your traffic on the internet? No. Now you need to create VPNs across the internet, encrypt it, all that other stuff. But the internet's performance is not guaranteed. Not guaranteed at all. Not even close. So by using the internet, by sending data to the internet, we've got some security concerns, but we also have performance concerns because internet performance isn't guaranteed. But by using the endpoint piece, we're going to send our data across the private network. So by using the private network, we're going to get better security and better performance. Keep that in the back of your mind. Now you know why we're using these endpoints. So when we talk about endpoints, they're going to be gateway endpoints and they're going to be interface endpoints. Gateway endpoints are going to give us good high-speed access to AWS services. So the way a gateway endpoint works is it places a route in the routing table. Typically, I think of S3 as one of the gateway endpoints, and it basically now allows you to get private access to your S3 bucket from your VPC. Effectively, you're going to create something called a prefix list, and the prefix list will have a naming convention. You'll see it as a PL-XXXX, so to speak. You'll see it in the routing protocol. And the routing table will show you a route entry. And when you want to reach S3, it's going to be routed like anything else would be routed in networking to this virtual endpoint. So you can kind of look at this picture. It's not the most beautiful picture in the entire world, but you can see what we've done here. We've got a data center. We've connected the data center to our cloud provider, and we're actually looking at the information that's stored in our S3 buckets outside of our VPC from our actual data center. Because if we connect our data center to the cloud, we should be able to use that for transport if we do it correctly. But that's how we're accessing things in this S3. So how do we secure our gateway endpoint? Well, we set up policies. And if we have a good policy, it'll be harder to reach. First, routing. If you don't have a route to it, you can't reach it. Ever notice really wealthy people live on islands? Can't drive your car there. May have to take a helicopter there. It enhances your security. Same thing in routing. Don't have a route, can't reach it. Keep that in the back. So limit routing information to the subnets that need the endpoint, for one thing. But also, we've got all our IAM things that we can use. Now, that was the gateway endpoint. Think connect to S3. Now, interface endpoints are a way to connect to other AWS services, such as the EC2 Systems Manager, or Kinesis, or Load Balancer APIs, or external services that are hosted by AWS partners or customers. You might want to connect to an AWS customer or a partner, and you can use an interface endpoint for those. Interface endpoints work a little differently. Interface endpoints are local to the VPC. With a gateway endpoint, there's a route in the routing table to reach it. With the interface endpoint, it is local to your VPC. Interface endpoints are really a network interface, otherwise known as an elastic network interface, in your VPC to the endpoint. And when you create the interface endpoint, AWS will automatically create that network interface in your subnet that you specify to use it. And when you create the endpoint, AWS will generate endpoint-specific DNS names. So you're not going to have to remember the IP address you can connect to it via a fully qualified domain name. And we will talk more about fully qualified domain names when we actually get involved into the DNS section. Now, how do these two systems connect to each other when we use interface endpoints? They actually use a service called private link. And what is private link? It is a virtual private wire across the AWS network. Now, I've seen people that get excited by the concept of a virtual private wire across the service provider's network. Understand, virtual private wires are not new. Back in the 90s, we had ISDN networks, we had frame relay networks, then we had ATM networks, then we had VPLS networks. They're all virtual private connections over a public network in some way, shape, or form. So private link creates this network interface, and it will restrict all traffic between the VPC and the private link. So here's an example. We've got a private link between our location, something else, and you can get some pretty big performance to some pretty good services with this AWS private link service. We will get involved in VPC peering, which is one of those things that I love. But I want you to understand you can connect two VPCs together with VPC peering. You can, but you can also connect VPCs together with private link. And there's a difference. VPC peering is effectively connecting two domains together. What do I mean by two domains? Network A, network B connected together, and they can share everything. That is private link. I'm sorry, that's VPC peering. Private link is Mike can share this one specific thing with Mo, and they can only share that specific stuff and nothing else. So private link might be more secure. I could set up a connection between me and Benjamin and share just the stuff I want to share with Benjamin, and me and Mo and share just the stuff that I want to share with Mo. And we can have an incredibly good situation. VPC peering, therefore, would be good if we want to share everything. And there's times where we want to share lots of stuff. Private link is where we want to share one thing. VPC peering also doesn't scale well. We can't have more than 125 connections. And when we get involved in VPC peering and get involved in these formulas of n times n-1 divided by 2, you'll see that that's absolutely nothing. And private link scales better. Basically, the performance of private link is limited by your load balancers and your servers. Private link also does something that's very, very cool here. And what's very cool with regards to private link in the manner that it works is the following. It actually uses NAT, and it does so automatically for you. So by using NAT and doing it automatically, you don't have to worry about IP address overlap. Now think about this. Private link is to connect you to somebody else. Chances are they're already using overlapping IP addresses. So private link is very simple. It's very elegant. VPC peering will require you to have non-overlapping IP address space, not private link. These are unidirectional links, and they allow for NAT. So keep that in the back of your mind. Talk briefly about what is a shared services PVC, and then a little bit about VPC peering, and then the team will get involved and do some more stuff with you. So what is a shared service VPC? What if you're an organization that needs to provide services for multiple VPCs? Or maybe you chopped up your network into multiple VPCs, and why might you do that? In the data center, we've got incredible security control. We can chop our systems into multiple VLANs, route between those VLANs, not route between those VLANs, rate limit our systems, add quality of service to protect against worms and things. We've got a lot of network security we can do in our data center. A lot. We've got very little in the cloud. So there are organizations that will take their domains and the way they used to have VLANs, they'll chop them up into multiple VPCs. So an organization can have 500 VPCs. And then they could create a shared services VPC to actually route between them. or the shared service VPC can offer services to each one of these things. So actually Benedict will probably get involved in the transit VPC, but the shared service VPC might be something that many of your entities would need to use should you segment your systems with multiple VPCs. That's one case where you would use a shared service VPC. Got 500 VPCs, they all have to access certain internal information, stick it in a shared service VPC. Or maybe you're a service provider and you've got a product or service and your clients are already on the AWS cloud. You create a shared service VPC and they connect you. So that's really what we're talking about here with regards to shared services VPCs. And it's going to look something like this. And here you can see all of these systems are available via the shared services VPC. You've got different subnets in different places, and they're ready to go. So keep that in the back of your mind. That's where you would use a shared service VPC. Mo, if you message me in the bottom, I think you're coming up very soon. As far as the next presenter, let me know if that's the case. Otherwise, I will keep going. Or Benedict. Bear with us for a second as we coordinate between us. Actually, I see we're right. All right, well, I will continue and I will transition to Mo when we start talking about Jumbo Frames. Then you want to cover the VPC Frame section, or you want to cover it when we start with the Jumbo Frames?
Yeah, I can I can cover the VPC Peering section as well. Just start from there. Okay. Do you want to take questions, Mike, or do you want to start with the VPC Peering section?
If there's any questions, real quick.
Okay.
If you get an external IP and don't use it, attach it to your NAT gateway, then are you charged for it?
Okay, so you're asking about the EIP. I'm not sure if you mean, again, acronyms. Not sure if you mean external IP or elastic IP. These, we deal with different clouds, so really these acronyms are hard to keep up with. But I'm gonna assume you're talking about elastic IPs, right? If you use an elastic IP and don't use it and attach it to your net, so for elastic IPs, if you don't use it, you're going to be charged for it, right? If it's just sitting there idle, and that's been the case, I believe, since 2023, AWS started charging people for unused elastic IPs because when you don't use it, other clients or other customers can't use it, so they have to charge you for it. Okay. Douglas, that's a very good point. So Douglas said somebody was asked about tagging, right? Or trunk traffic on a WAN, right? And the question, I believe, was, do we use tagging or VLAN trunking or VLANs only on the LAN, or can we use it on the WAN as well, right? And we answered, we said it depends. There's different scenarios. And this is one of those scenarios that Douglas just mentioned. It's a very good scenario, which is when you use private lines, right? AWS service, which is, they call it direct connect. Usually what you do is you have to choose a specific VLAN tag, or you need to tag your traffic with a specific VLAN. right? Especially for hosted private lines. And we'll talk about different types of private lines when we get to that point. But yes, that's one of the instances where you would actually use VLAN tagging so that you have your traffic end-to-end sent through a specific VLAN, which is using when you use private lines, right? Which is technically a WAN, right?
From your VPC, can we not access the S3 bucket without creating an endpoint? Sure you can, by going out to the internet, across the internet, and back into S3. Or you can create an endpoint and use the AWS network and have greater security and greater performance. The choice is yours.
Can I answer that, Mike?
Yes, please.
All right. So you're asking about two different types, right? We spoke about both, and you're asking, do we use a gateway endpoint or do I use an interface endpoint, right? Well, a gateway endpoint is for very, very few use cases. One of them is an S3. One of them is to connect to S3 services, right? So maybe that makes more sense to just use a gateway endpoint, right? An interface endpoint is more general case. You can use it for anything. But most of the time when you talk about S3 buckets and you want to connect privately, you would use a gateway endpoint because that's the use for it. But to kind of like the second part of that question real quick, you said, what's the use case, right? When would I use one versus the other? Well, as I said, a gateway endpoint is for very specific use cases, right? 2 or 3 things. One of them is S3. But what if you wanted to had some other private service and you wanted private access to that service, right? This is when you would need to use an interface endpoint instead. Hope that answers the question.
Actually answered this question.
Okay, so another question goes back to the virtual private gateway, right? We showed a diagram where one virtual private gateway connects to multiple on-premise environments or multiple, let's say, data centers, right? And then, so the question is, was the virtual private gateway acting as a hub, or there is more setting up, more to setting up hub and spoke in that aspect? So with that scenario, the gateway was not acting as a hub. So the virtual private gateway was not transitive, right? I believe William asked earlier, is the virtual private gateway is transitive or not? And we said it depends. So by default, it's not transitive. It doesn't act as a hub. But there is an option we'll go through very soon where it can become a hub, pretty much. Virtual private gateway can become a hub. Is a private link an alternative to VPC peering? No, it's not. Because private links are to give access to give private access to AWS resources that would otherwise be accessible through the public internet, right? Like an S3. An S3 would typically, you access through the public internet. But what if you want private access to your S3 bucket? This is when you would use a private link. I'm not sure if he means a private link as in private line or private link as in, because in AWS with private link is VPC.
No, I think what he was referring to is, so we can connect obviously VPC to VPC to share everything, or we can use private link to share one thing in between 2 separate VPCs.
Yeah.
So it's sort of like an alternative, but not really. It's like you can access my front door and one room, but not the entire house. So VPC pairing is going to be if you need real networking capabilities between it, as opposed to just access to just one thing.
Okay, so cost of data traffic for VPC peering versus a private link. That's a good question. Well, as far as like the cost and so on and so forth, I think you should always look into AWS quotas, you'll find the more specifics there, right? But one thing I want to add here is that with VPC peering, if you have a peering between two VPCs, right, and the traffic is between those two VPCs, those two VPCs are in the same same region and the same availability zone. If they are, in that case, the traffic is free of charge, right? But once you start sending traffic between two VPCs in different regions or in different availability zones, that's when you start getting charged for VPC peering as well. So it can be free, VPC peering, but not all the time.
Okay, so let's do a little more content, then we'll break for lunch. And we'll take it from there. So I'll kick off some VPC peering. Mo's going to talk about Jumbo Frames, which is really kind of cool. And then we'll break for lunch, and then we'll come back in an hour, and we will have a great time and cover a lot of cool stuff. So, and actually, before we do, give me a hashtag, AWS Advanced Networking, so that I know that you're here and you are awake. So VPC peering is a means to connect two VPCs. Maybe they're your own VPCs. Maybe you've got a finance VPC and an accounting VPC. Maybe you are an auto manufacturer and you're connecting to a VPC from a company that makes tires. It doesn't really matter. VPCs are about connecting two different virtual private, I like to call them data centers, even though I call them virtual private clouds. VPC peering is a whole lot like BGP peering, and it's going to be non-transitive. Actually, IBGP peering is non-transitive. eBGP peering is transitive. When we use VPC peering, it is over private IP address space. So region 1 to region 2 is going to be encrypted if it's intra-regional, that sort of thing. When it comes to VPC peering, it will look very similar to this. Got one provider, got another VPC, you connect between them in much the same way you would set up BGP peering, then you can reach each other's things. Now, I mentioned VPC peering is not transitive. What does this really mean? It means that if I connect to something and somebody else connects to something, I can't connect to somebody else through that something. That is the bigger issue that we're talking about. So let me give you an example and I can actually show you why. I think it's a pretty important concept here. Let me bear with me a second. I'll set up a little whiteboard and we'll virtualize this together. And here's really what non-transitive means. And I'll show you why this is the case. So if we have router A, router B, and router C, or VP, let's call them VPC A, VPC B, and VPC C. Let's just say that for right now, 1.1.1.1 is router A, and 2.2.2.2 is router B, and 3.3.3.3 is going to be router C. Now, for router 1 or VPC1, it really doesn't matter. To be able to reach 3.3.3.3, if you're on router 1 either needs to basically would need the routing information that says to hit router 3, go to router B or VPC B, and then send it to router 3. So if VPC A doesn't know about VPC's routes, A can't reach C. If you don't have a route to it, you can't reach it. If VPC C doesn't know about VPC's A's information, it won't be able to reach it either. And the rules of non-transitive routing is when A tells B about its 1.1.1, in a non-transitive world, B won't tell C about its 1.1.1.1, so it won't know about it. Now, B will tell A about 2.2.2.2. B will tell C about 2.2.2.2, but both A and C won't know each other. So that's non-transitive routing. So here's the fix. We move A, we move C, and we make them all connect to each other. And now everybody can talk to everybody. That's transitive routing versus non-transitive routing. So this gets really ugly really fast. And here's the reason why it gets really ugly really fast. Unless we do something to break the rules, and we'll talk about things that we can do to break the rules, me and Mo and Benedict will have lots of fun with this. Everybody needs to talk to everybody. Now we have 3 routers in the example I showed you. No big deal. 3 routers, 3 connections. The problem is the formula on this full mesh thing is n times n minus 1 divided by 2. So if we've got 2 routers, it's 2 times 2 minus 1, which is 1 divided by 2. 1 connection, right? We got 3 VPCs or 3 routers. I don't care. Same thing whether it's BGP or VPC Peering. 3 times 3 minus 1, which is 2. So 3 times 2 is 6, divided by 2 is 3. Now we got 10. 10 times 10 minus 1, which is 9. So 10 times 9 is 90 divided by 2. We've got 45 connections. Now we've got 100 VPCs, which is honestly no big deal. 100 times 99 divided by 2. This is going to get ugly really, really fast. And this is traditionally why in the networking world we use things like hub and spoke. Guess what? You guys all use it all the time when you go to an airport. If I'm in Palm Beach and I want to go to San Jose, California, I use Delta. I fly to Atlanta, Georgia. Atlanta is a hub site, and it then takes me to San Jose, which is a spoke site. So Palm Beach, Atlanta, Atlanta to San Jose. Now, normally in networking, we can deal with hub and spoke sites because our interior gateway protocols allow us to. But IBGP doesn't allow us to, and VPC peering doesn't allow us to. So think about that. VPC-B can't talk to VPC-E. VPC-B also can't talk to VPC-C. VPC-B can't talk to VPC-G. Is this a good thing or a bad thing? I don't know. It all depends on your vantage point. If the VPCs can't connect to each other, won't they be more secure? Sure. But if we want the VPCs to talk to each other, now we've got a problem. And that's why we would have to fully mesh them to get them to talk to each other. I hope that makes sense. In this environment, VPC B, C, and A can all talk to each other because they are fully meshed. And like I said, the formula is n times n minus 1 divided by 2. So I'll talk about CloudHub very briefly. Mo will talk about Jumbo Frames, which is pretty important, and then we will take a break for lunch. So hope that makes sense. And then we will come back and we will go through a lot more AWS stuff. We got our fundamental stuff out and done this morning. So let's talk about CloudHub. Because VPC peering is non-transitive, you can see that all these connections from everybody and everything can get pretty ugly pretty quick. They can become disastrous very quickly. So about 30 years ago, the Internet Engineering Task Force had a fix for this with regards to BGP pairing, and they said, we'll create this thing called the route reflector that'll let us advertise routes to other people that we learn. Fast forward a couple of decades, now we've got cloud computing, and AWS created their own version of a route reflector, and they called it CloudHub. Transit Gateway does the same thing. So what CloudHub enables you to do is to break the rules of non-transitive routing. It enables you to create a bunch of eBGP connections, and I'll show you what we mean by that. And by doing so, you can have transitive routing in a hub and spoke information, just like you would with BGP. So now, here's what we do. We connect to CloudHub via BGP. We use eBGP between our various autonomous systems. And why external BGP versus internal BGP? Well, they are, but because external BGP does not have that non-transitive property. So now we've got a New York location connecting through the central environment, a London location, and a San Francisco location. They all connect through that virtual CloudHub router. Poof, everything's up and running. New York can reach San Francisco through that local location, and now everybody is happy. So we've covered the intro to VPC peering. We've covered CloudHub. Now we've got some Jumbo Frames before we get into other concepts that need to be covered, and I'm going to turn that over to Mo.
Can everybody see my screen? Okay. So Jumbo Frames, right? What are Jumbo Frames? So before we get into what are Jumbo Frames, let's go back one step back. Let's take one step back and talk about what are frames to begin with, right? So we did talk about frames briefly, but just to kind of, so a frame is what you would send. Think of it as a message, right? You're sending data right now. You're watching this bootcamp over the internet, right? So you're receiving packets, right? Or you're receiving the information, right, to your computer's line card, and then your computer's line card is putting that information together and represents it, decodes it and represents it as a video, right? And of course, there's audio too. Now, this traffic is sent over messages, right? And you send millions of messages, right? These messages are what are called frames. And a frame is what, on the layer 2, let's think of between, let's say you have a switch that connects to a router, or maybe between two routers. Between those two routers, when you send that traffic, right, it is encapsulated with a frame. That's what the layer 2 or your Ethernet cable understands. Now, the actual data itself, so this video, that's what we call a payload, right? So for most of web browsing, you're using TCP, so that would be a TCP payload, right? And the size of that TCP payload, or the allowed size of that TCP payload, is what we call the maximum segment size, or MSS, right? As you can see here, it's called the maximum segment size. So typically, you probably heard of an MTU size of 1500, right? You hear the word MTU, right? And 1500, that's because that's what is typically used over the public internet. So what is an MTU, right? So you have your payload, right? And we said the size of that payload is what we call a maximum segment size, right? You encapsulate that payload with your TCP header, right? Just for signaling and being able, that's what makes TCP reliable, right? You have a sequencing and different types of signaling, establishing a session, and so on, right? So once you add an IP header on top of that, the IP header is where you put your source IP and destination IP, right? So the source and destination IP address, right? Once you encapsulate it or put the IP header on top of that payload, that's when it becomes an MTU. So think of it as layers, and that's why we call it the OSI model is different layers, is that you have a payload, which is the data, and then you encapsulate it with the IP address information so you can reach from point A to point B over the public internet, right? That when you encapsulate with the IP address, it becomes a header, right? Now you're sending that traffic over layer 2, so over an actual cable, right? So it goes through multiple routers or sometimes switches and then routers, right? For you to transfer that traffic over between two endpoints or between two endpoints of a cable or between one line or one link, right? That's when you encapsulate it with a frame, right? And a frame is most likely what you're using, connection to your internet, let's say Ethernet, right? So you have an RJ45 cable, right? So that Ethernet header has a source MAC address and destination MAC address, right? And then you have a frame check sequence, as you see right here, which is just to make sure that the traffic the actual sequence of data or the frame that you're sending is not corrupted. So that's the whole concept of encapsulating your traffic. What's a maximum segment size or your payload? What's the MTU, right? Which is the maximum transmission unit, which is the size of your layer 3 packet, right? We call it a packet. And then you add on top of that the frame, and this is where we call it a frame, right? So what is a jumbo frame, right? A jumbo frame is a frame that is bigger or larger than the typical size of a frame, right? So we talked about MTU. We said an MTU, which is the layer 3, right? The header, right? We said the typical size over the public internet is 1500, right? That doesn't account for the Ethernet frame, right? If you use an Ethernet frame, you'll have about 18 more bytes of worth of traffic or data, which is the actual header itself, right? The Ethernet frame itself, right? So this turns out to be actually 1518, right? If you have an MTU of 1500 and then you add an Ethernet header of 14 bytes, and a frame check sequence of 4 bytes, that's a total of 1518, right? And the Ethernet and the frame or the layer 2 header frame can vary depending on the different medium that you're sending your traffic through. So one side can be an Ethernet, and then you can be sending it, let's say, through a different means, and you might have different layer through methods outside of Ethernet throughout your, while you're sending your traffic from point A to point B. So let's focus on MTU, right? Because the concept of jumbo, it just means it's larger than the typical size, right? So jumbo MTU, jumbo frame, right? Let's focus on what a jumbo MTU is, right? We said the typical size is 1500, right? A jumbo MTU, right, is an MTU that can be up to 9,000. Imagine an MTU of 9K or 9,000. Right? 9,000 bytes. So what's the benefit of using an MTU that is larger than 1500? Let's say, for example, 9,000, right? So it's something over 1500. The benefit of that is, if you think about it, let's say you're sending traffic from point A to point B. And let's say all your traffic that you're sending between point A and point B, you're only sending 9,000 bytes worth of traffic, or 9 kilobytes, right? This is oversimplification, but if you are sending that 9,000, right, over a jumbo frame, so you have a jumbo frame enabled all the way from point A to point B, then you only have to send one packet, right? So you only send one packet, and that's it. All the traffic has been received, or point A has received all that traffic, right? Now, if you have a typical MTU that is not jumbo, that is 1500, then you would have to break this MTU, right? Or sorry, you have to break that packet into multiple packets, right? You have to fragment it or break it into smaller chunks of data and then send it over, right? So instead of sending 9,000 in one go, you have to send 9,000 divided by 1500, which is what, six different packets? You have to send 6 different packets, right? So that means you're fragmenting the traffic, you're sending it out. The other end will have to keep track of the sequence of those packets and assemble it again, basically, and put it back together, which can, have a toll on the CPU load as well, right? So there's definitely a benefit of using jumbo MTUs in terms of okay. So one of the consequences of jumbo frames, right? As we said, you're sending your traffic over the public internet. Over the public internet, typically you're using 1500, right? let's say you're sending, again, between, we're talking about two routers, router A and router B, right? And let's say we have router C between router A and router B, right? Let's say router A and router B both support jumbo frames, right? So they're both sending 9,000 something, right? Packet size, right? When you send it through router C, if let's say router C only supports 1,500, okay? Two things can happen, right? The first thing that can happen, and we'll say it's best case scenario, is router C will be able to fragment or divide that 9,000 bytes of packet and fragment it into and split it into smaller chunks of data, basically, right? And then send it over to router B. Now, the problem with this is that means every packet has to be processed by the CPU, right? Which we call in the networking world process switched, right? Which can have a heavy toll on the CPU of your router. And so as you send your traffic, right, every time you receive a 9K or a 9,000 packet size of 9,000 bytes, you're going to have to split it into six different packets and then send it over to router B, and then router B has to reassemble it again. So as you can see, it's not always practical, right, to use jumbo MTUs. You got to make sure that it's available end to end. Now, the worst case scenario gets even worse, right? Sometimes you send your traffic and there's a bit in the header itself. It's called do not fragment bit, or DF bit. And what the DF bit says is, if you receive my packet and it's larger than your supported MTU, do not fragment it. Do not split it into multiple packets. So what can router C do if it can't fragment that packet? Well, it can only drop it, right? So then you get into a point where you have packet loss, right? Even if the packet doesn't say do not fragment, right? Your router, you have control over whether you want to fragment jumbo packets or not, right? You have the option. So if you send traffic, especially over the public internet, you're not going to be able to support jumbo MTU, right? If you send it over a large WAN, even if you own the whole WAN, right? If there's one point in that path that doesn't support jumbo MTUs, then you're going to run into problems where either high CPU utilization because you're fragmenting the packet, or because you literally can't fragment the packet and you just drop it or discard it. Okay. Yeah, somebody said handwriting skills. I don't have the best handwriting skills. So let me delete this. As we just described, right, not all infrastructures support jumbo frames, right? And since this is an AWS bootcamp, let's talk about this from the AWS perspective, right? Well, number one, if you're using an internet gateway and sending your traffic through the public internet, your internet gateway is not going to support jumbo frames or jumbo MTUs, right? Also, traffic over VPN tunnels, right? If you have a virtual private gateway and you're sending traffic over over the virtual private gateway, that IPsec tunnel is not going to be able to support jumbo frames. And then another thing is VPC peering typically can support jumbo frames. It depends on the region. Most of the US regions, they support, or all US regions support jumbo frames. Some regions don't support jumbo frames altogether. Now, there's another issue. If you're sending traffic between regions, even let's say you have VPC A in the region US East 1 and VPC B in US West something, right? So those two different VPCs, even though each one of them supports jumbo frames, because they're in different regions, you won't be able to use jumbo frames. So traffic has to be, for VPC peering, has to be within the same region, and that region needs to be be able to support jumbo frames. And then we get to another issue, right? Not all your EC2 instances support Jumbo Frames. Generally speaking, all your Nitro instances support it, right? So most of the EC2 instances or instance types don't support it, with the exception of A1, C3, G2, I2. So this is an exhaustive list that you can always go to AWS and check their which EC2 instance types support Jumbo Frames or not. All right, so that means your end host itself, your device, right? The line card, for example, my laptop might not be able to support Jumbo Frames, right? Okay, AWS wavelength zones, right? Also, so the AWS wavelength, right? Those zones are not able to support Jumbo MTUs, right? And it has a limit of about 1,300 bytes, right? Okay, so what's the benefit of Jumbo Frames, right? Well, obviously you have an increased network efficiency, right? Because instead of breaking down your data into smaller chunks, you can send it in bigger chunks, right? Kind of the same terminology that Mike described of, having a Ferrari where you're sending your traffic, you can't carry a lot of weight, right, in one go versus having a truck, right? So think of Jumbo Frame as a truck where you can send more traffic in one go, right? Only that it's technically at the same speed, right? So that's one aspect of the latency, right? That's where there's a network efficiency, right? But then there's the other aspect of the utilization of CPU utilization and so on, right? Because if you're breaking the traffic into smaller chunks, then you have to assemble it and deassemble it and so on and so forth, right? Which can be very exhaustive. Okay. So we just talked about the CPU load, right, of assembling and deassembling. And of course, you get the improved throughput, right? Because you have a higher MTU, kind of goes back to the same, the latency argument, right? Because you have a higher MTU, you'll be able to send your traffic in one go, and that gives you an advantage in terms of enhanced throughput. Okay. That is Jumbo Frames. I think we're probably going to be taking questions.
And the lunch break will be 1 hour, and then we will come right back.
Okay.
Well, let's do some questions and then do the break so people don't forget their questions.
Exactly. Who has questions?
Oh, and by the way, it was me that called you out on your handwriting skills, Mo.
They're better than my medical professional handwriting skills, I can tell you that.
Okay. Can one segment be retransmitted without retransmit the entire Jumbo frame? So what Sina is asking here is you send traffic from point A to point B, and then some of the Jumbo frame or the segments of the Jumbo frame were lost in the path, right? Others were received. Can you just retransmit that one part? Well, it depends, right? Because if you're using TCP and the segmentation happened between the actual final destinations, then yes, right? If it's TCP, if the traffic is TCP, then this point A is aware of what it sent and when it hasn't. But think about if you're sending TCP traffic and you send it, and then you have, let's say, point A and B, and you have, let's say, C in between, and C fragmented that traffic. Well, point A is not aware of the the segmentation that's been done on the path. So no, you're not going to be able to truly transmit it because C doesn't keep track. Only what C does, just it splits the traffic into multiple traffic and just sends it along the path. What I'm trying to say is if the fragmentation happens between the actual final destinations and the protocol is a reliable protocol you're using, then yes, there can be retransmission. But if somebody along the path fragments that traffic and then you lose part of that fragment, then, tough luck. There's nothing you can do really. And that's why this is another, it's a good point. One of the drawbacks of using Jumbo Frames without guaranteeing support of Jumbo Frame end to end.
Good question there. All right, we can go to the next one, Chris. Does every architect plan for greater than a /22 or /23 address range? I think we need to be very specific here. Typically speaking, for WANs, we use /30 off of the cloud. Typically, I would recommend a /24, no greater than a /23 for a LAN segment. And the reason is, Mo or Benedict can comment here, we typically get a lot of broadcast traffic from hosts. Apple does its broadcast, Windows does its broadcast, we have ARP broadcast, so we typically don't ever want to go bigger than a /23 on a particular subnet. But, we may have an entity that might need to use a /8 CIDR range or at least a /16 CIDR range. So we need to talk about where we're putting it.
Yeah, it's all situational, right?
Yeah. So for you, Mo.
So use case for Jumbo Frames, right, versus regular 1500 MTU. So when would you use a Jumbo MTU, right? Let's say you're sending traffic. So let me make a quick correction there. We're not saying, because I saw one in the comments, which said, why would we use Jumbo Frames that AWS doesn't support it and the internet doesn't support it? No, well, AWS does support it, right? Let's say, for example, you have two EC2 instances, right? And you want traffic between those two EC2 instances. Then you can use Jumbo Frames then. What if you have two VPCs in the same region, right? Completely different companies, let's say, or completely different data centers, but they're in the same region, right? You can use Jumbo Frames between those two, right? Over a VPC Peering or a Transit Gateway. Now, you can't use Jumbo Frames when you're going out, through the public internet or VPN tunnels. So very few cases where you really can't use Jumbo Frames, right? Well, not very few, but it depends on the case, really, right? Yeah. But Jumbo Frames versus regular, right? It depends, right? Like, for example, if you have traffic between your servers, that for me, if I have it, let's say, you're between your application tier and your storage tier, right? Or you want to, your traffic to the database. Maybe this is when you would use a Jumbo Frame, right? When you have a large amount of data, and it's more of a consistent traffic, I would say, right? So communication between your applications instead of to the client.
Yeah, and one of the things to think about is why, because you mentioned the use case. So Mo talked about the header. You've got a 14-byte Ethernet header. You've got a 20-byte I header. We've got a 20-byte TCP header, a 4-byte frame check sequence. So on a 1500-byte frame, that's 3.3% of it. So the point is when we get to network and we've got 1 gig, we're never going to get 1 gig. We're going to typically get something like 900 meg instead of 1 gig. 10% of that stuff is sort of overhead, our TCP retransmissions, our flow state, our headers. So if we can reduce the amount of headers, we can push more data on that same link. So that's why people might do this.
Yeah.
Rick, how many servers do you need? It depends on the size of your organization. So it's not, max quantity of EC2 instance per VPC based upon a rule. You're ultimately going to run into limitations somewhere, but the point is, your bigger issue to think about is how many VPCs do you need to get the security performance that you actually want in your organization with regards to microsegmentation or segmentation. I know businesses that have 50,000 servers. I know businesses that need 3 servers. Business demands determine every piece of technology we use. And let's talk about the difference between, we can't use a slash. So hypothetically, you could launch up to 65,000 resources if you've got a /16. You'll never get beyond 1,000 resources in a subnet before the broadcast traffic will take your entire domain down. That's why we have to subnet and constrain our broadcast traffic. Because every time there's a broadcast, it has to be processed by the host CPU. The routers hosts, the switches host, the servers themselves. And when that CPU hits 100%, you've got a crash, and it's not a good situation. That's architecturally why we typically do this. Okay, so at this point, any others? Good question from Tunde. Are there any trade-offs in using a jumbo frame over a traditional MTU? Absolutely. If the path doesn't support your MTU, you're going to be in trouble. Moses, if you want to add a little more to that.
Yeah, no, I agree. I agree with what you said. If you can support it, then obviously, there's a huge benefit there. And Mike said a really good point earlier. Not only you get better throughput because you're segmenting traffic less, but there's about 9 to 10% of overhead, which is the actual, the encapsulation of the frame, right? So each frame has to be you have to put a header, you have to put different headers on top of each other, right? And so that adds an extra overhead, right? But if you're sending more payload in one packet, then you get more bang for your buck, or Is jumbo frame only related to a TCP packet, or could a UB packet have a jumbo frame relationship? So a frame, by definition, the word frame, it's layer 2, right?
Yes.
So anything can be encapsulated with a frame, right? Now, TCP, UDP, they're at layer 4. And so you encapsulate your TCP, at layer 4. That's where we talk about the segment or the maximum segment size, right? At layer 3, that's the header or the IP header. So the relationship, it doesn't matter whether you're using UDP, TCP, or something else, right? It can always be encapsulated with the same, with jumbo frame or not. Doesn't matter. So the frame is agnostic of the actual layer 4 information, TCP or UDP. I hope that answers your question. So you would configure jumbo frames. I'll just read it if anybody wants to answer it. So you would configure jumbo frames on any router within your VPC, but not at the Internet Gateway. Yes. So jumbo frame is not something. Yes. Yeah. If you're sending traffic over the public internet, then yes, you would not be using jumbo frames then, right? If you try, your traffic is gonna be dropped pretty much.
Yeah.
Or segmented. Both are not great.
Is subnet summarization aggregation to minimize the number of root entries you set up in the router? Partially. Is it a good practice to have your subnets well planned with contiguous blocks per side? Absolutely. You must plan your subnets so that you can potentially have contiguous blocks so you can subnet it. Part of it, I'd say 50%, is to reduce the number of routes in the routing table entries in the router. The other problem is when you've got a lot of route entries and every time one little link flaps, the routes will have to recalculate the route. So let's say we've got 5,000 domains, 5,000 routes in our OSPF domain, and we've got one link that goes up and down every 30 seconds. That's going to generate, every 30 seconds, it's going to make all the routers recalculate the routes. So by hiding certain subnets, we can reduce the CPU overload and the routing table overload. And that's why we're doing it. Class A, Class B, used by large enterprises. Realistically speaking, most enterprises are going to use a CIDR block, not a class. And they're typically going to use either a Class B size CIDR block or bigger, because there's some organizations that can't get away with 65,000 IP addresses. They've got 100,000 or 200,000 or 300,000. Amazon has 1.5 million employees. So think about that. 1.5 million employees and probably 10, 20, 30 servers per employee. They're going to need a whole lot of IP addresses. So the requirements always make the determination. John, you mentioned jumbo packets increase throughput. What's the effect on latency? It depends. It depends on the data. If you're sending voice or video packets, they're typically going to be small packets because you're going to try to get them on the wire as fast as possible. But you're going to have more overhead. Now, if you have a 8K voice call, do you care if it takes up 9K to send your traffic through if you've got a 10 gig link? The answer is no. You want your packets to go through sooner. But what if you've got to push a lot of data down a pipe? It takes you back to the Ferrari versus a tractor trailer, which is more appropriate for the application you're using. Ryan, I'm assuming you don't mean Research Triangle Park. I think you probably are talking about real-time protocol.
Yeah.
But there's other RTP acronyms as well. So typically speaking, we don't use Jumbo Frames for real-time protocol, which is voice or video.
Usually you want to, for real-time, you want small and steady instead of big and different chunks. Otherwise, you'll hear me talk and then stop, buffer, talk again. You don't want that. But yeah, that's funny because I thought about RTB Office too. Go back to acronyms.
Okay, so one more question and then we're going to break for lunch. So the network rules and practices pretty much the same as the physical world at a private data center. Last question, are there any gotchas using AWS cloud services? There's 1,000,001 gotchas because there's so many limitations on the cloud compared to what we can actually do in the data center. We're about 20 years behind with regards to cloud networking to traditional networking. So that's what this whole course is about, is predominantly about the gotchas on how to do stuff on the AWS cloud versus how you would actually do it in the regular data center. Great question. So we will come back in exactly an hour. Before we do, if you've just joined us, remember, we've got 1.5 to almost 2 full days of labs we want you to get through. You can sign up for them. They're in the description of this video. My team will pop it in the chat box for you. We've got AWS labs, and we'll probably do some on Sunday if we get through enough of the content, because I want to do some with you. And for those that we don't get through, you can do on your own time. We have labs on AWS. Thing with doing labs on the cloud is you don't get to see the underlying technology. So my team of CCIEs has actually created some underlying technology labs for you to see and learn from as well. So see you guys in exactly 1 hour. That is 2:30 Eastern Standard Time. And I look forward to seeing you all back. Give me a hashtag AWS Advanced Networking, everybody, and I'll see you soon. Welcome back, everyone. We are back after our break for part 2 of our completely free AWS Advanced Networking Bootcamp. We had some fun this morning. We talked a little bit about the AWS Cloud. We talked a little bit about the VPC. We had a little bit of fun going over some routing and how routers work and what switches do and a little bit of VLANs. And now we're back for the second half. If you've just joined us, please download the completely free AWS Advanced Networking Lab demos. Here's the reason why. We have a very ambitious schedule for the next 3 days. And we have a tremendous amount of labs. Quite frankly, we have almost 2 full days of labs. Labs on AWS, labs in the data center, labs on routers and switches to truly make sure you get the understanding of the network beyond what you could just do in AWS. So sign up and get your free AWS lab demos now. They're in the chat box on the description. If you're back, please give me a hashtag AWS Advanced Networking. And that way I know you're awake, alert, and oriented. So we're going to get back to the content. Mo is going to get back to some really cool content. He's going to start talking about encapsulations. We'll hear about transit gateways. We're going to get into all kinds of fun stuff. Mo's got a lot coming for you. And maybe you'll hear back from Benedict or me today. I'm sure you will in the questions, but Mo's got a lot of content. And then tomorrow, back at 10 a.m., we got all kinds of exciting networking content for you. As you can tell, I love networking, along with my team of network experts over here. And then we'll be back again on Sunday. So let's make it a great experience. We'll go for a little while. We'll answer your questions, have some fun. So welcome back. AWS Advanced Networking Day 2. It's for the ANS-C01 exam. And this is our full AWS Networking Specialty Course available at no charge to you from Go Cloud Careers. So you know me. I've been a network architect for 25 years, in case you haven't joined me. We're here with Mo, who's a network architect and a CCIE with more than 10 years experience. Benedict, who's a great network architect with more than a decade of experience. And of course, Mark on our team was part of this, and he's another network architect with over 10 years experience. So lots of fun. So Mo, let me turn it back over to you.
Can everybody hear me? Okay, I think everybody hears me now. All right, so we got some exciting topics for you today.
I forgot to unmute you there, Mo. I'm sorry.
No worries at all. All right, so we're going to start with encapsulation, encryption, underlay and overlay networks, GRE and VXLAN, right? That's a lot of topics trying to fit together because they're very closely related, right? Most of these topics are very closely related. So let's start with encapsulation. What is encapsulation, right? We've already spoke about encapsulation a little bit, so you have the basic premise of what encapsulation is. But all what encapsulation is adding layers to your traffic, right? So you're trying to send some data from point A to point B, right? And I'll show you a good visual representation, right? So you have data that you want to send from point A to point B. In order to be able to send that data, right, you need to encapsulate that data with information, right? It's almost like you have a letter you want to send to somebody, right? You have to encapsulate it in an envelope, right? You need to write their address, information, and so on and so forth. It's kind of the same idea, right? So you have your data, which we call the payload, right? You have that data, then you want to send it from point A to point B. You need some sort of a protocol that facilitates that transportation, right? So that's where you use the TCP or UDP, right? The TCP or UDP header. That's layer 4. Then you need an IP address, right? A source IP, destination IP, almost like a phone number or an address, right? So that IP address, that's at layer 3. That's another encapsulation, what we call a header, right? And then you want to send it over layer 2, right? Meaning you actually want to send it through the line, right? Or the cable from point A to point B, right? And in that instance, you want to add a layer 2 encapsulation, which what we call a frame, right? If you're using Ethernet, then that's an Ethernet frame at layer 2. Right. And of course, then it's just a physical zeros and ones, right? Actual digital signal that you send it through the cable, which is, the line card, which is the physical layer or layer 1. So that's basically at a very basic level. That's what encapsulation is, right? So you can see it's the process of adding a layer of information to the payload. Right? The payload is the actual data to be able to carry that data. So as you can see, encapsulation is very important, and it pretty much touches every other subject in the networking realm. Now, just like I said, Ethernet is a very common layer 2 encapsulation, right? Also, we have tunneling. We spoke about tunneling a little bit, right? IPsec is one form of tunneling, right? It's encrypted tunnels. So an IPsec tunnel, which is encrypted most of the time, in order to be able to send an IPsec packet, you need to add an extra tunnel, and then you need to add an extra encapsulation before you encrypt everything that is encapsulated inside that tunnel. Okay. So with tunneling in general, and this is not just for IPsec, there's a lot of different tunneling protocols, right? And tunneling protocols in general, right? If you have, we're keeping it simple. So we're talking about two nodes, point A and point B, over the public internet, right? So there could be 20, 30, maybe 100 pass by to get from A to point B over the public internet, right? Now, in this instance, right, you typically have a public IP on your router, right, on both ends. Let's call this IP X and Y. Okay, that's the public IP. You want to establish a private tunnel, right? For example, you have your private network here, Okay, you have your private network here. And let's say behind this, you have a 192 network, like a private network, right? And you don't want to use NAT to go through the public internet. You don't need an actual direct access, layer 3 access between those two private networks. This is where tunneling can be useful. What you would do is basically establish a tunnel over the public internet, and over that tunnel, you can use network address translation. So this is very useful in cases where you have two sites and you pretty much own both sides, right? And then you want to send or tunnel your private data over that tunnel, right? So in this scenario, we said we have A and B. Let me try to, okay. So you have A and B, right? You have the IP, public IP here, that is X. Over here, you have the public Y, right? The way tunneling works, if you think about it, right? You have your payload. Let's say you're sending data. You have your payload, and then your, let's say, TCP header, and then you have your IP header. Let's focus. So you have a source IP, which is source IP of X, because you're sending data from A to B, right? The destination is Y. This is Y, right? Now, these are the public IPs, right? So what if I wanted to send data? Bear with me 1 second. What if you wanted to send data instead of using X and Y? Give me 1 second to try to. And that's not the most ideal way to draw. But let's say you want to send data from 192.168, the network here. Let's say this is a private IP, which is 192.168, and you want to send your traffic to 172.16. So another private subnet, right? But because if you send this traffic if you send this traffic without actually encapsulating or tunneling that traffic, you're going to end up with the issue that once you send the traffic out, right, it's just going to be dropped because you don't own that. You don't really, a 192 address and a 172.16 address, right? Those addresses are Class C, they're private. So you can't really use these addresses, well, not Class C, but, RFC 1819. So they're private IPs, right? So they're not meant to be sent over the public internet, right? Everybody uses the same IPs, right? And so if you want direct access between those two private subnets, right? So let's say the source here is the 192, right? 192.168.1.0. And over here, the IP is 172.16, which is the destination, right? This right here. In order to traffic, you need to tunnel it or encapsulate it by adding an extra header. So this is already, and in this header, you're saying the source is X, the destination is Y, right? So because the internet already knows how to reach X and Y, every node along the path knows how to reach X and Y, right? So as you send the traffic, that's why we call it tunneling, right? Everybody says, okay, the source is X, but we're focusing on the destination, it's Y, right? Everybody knows in order to reach Y, go this way, right? Once B receives that information and it sees that it's intended for B, B will decapsulate this information or take off this header. It will look at the rest of the information. It will see that there's another IP header, layer 3 header, which has a destination of 172.16, right? It will send it to that the other way around, just switch the IPs associated with the destination. So that's tunneling, right? So obviously it's very useful. Bear with me as I. So that's encapsulation. One of those encapsulation methods, there's a lot of protocols, V protocols, that allow you to do encapsulation, tunneling, right? And one of those protocols is GRE, or generic routing encapsulation, right? It's a very light or encapsulation protocol. So it's very easy to implement. It's not CPU intensive, right? It's a light header, and so all what GRE does is encapsulates your IP packet with another IP header, right? Just like we described, all right? Just as we described here, you're adding an extra header, which is the overlay, right? So what we call the underlay, right? So very quickly, let's go through what before we get deeper into GRE. Let's discuss what is an underlay and an overlay, right? The underlay is basically the actual internet, right? The infrastructure that you're using to go from point A to point B. So that's the underlay, right? In our case here, in our scenario, right, we're using our DIA, or direct internet access circuit, right, to exit out to the internet. So my underlay IP is the IPX, right? My source, my destination is the other side is Y. So that's my underlay. That's the infrastructure I'm running the tunneling on top of. The overlay is the encapsulated IP. It's the hidden IP, right? The IP that will only be seen between point A and point B, right? And when I say seen, this is not encrypted, at least as of now. So when I say seen, I mean who actually wants to interact with that encapsulated IP in a meaningful way, all right? So in this case, the 192.168 IP and the 172.16, those are the IPs that are actually encapsulated inside that tunnel, right? So you can think of them as the overlays. But in general, think of the word underlay and overlay. Overlay, the underlay is the actual, let's say, the infrastructure, and then the overlay is what is built on top of that, right? But you need the underlay in order to facilitate that transportation from point A to point B. Okay, so GRE, right? Generic routing encapsulation. So what GRE does, it takes the actual frame, right? It takes the actual, or not the actual frame, but it takes the actual header that you're sending from point A to point B. And what it does is adds an extra header on top of it. So you would add an extra IP header, right? And that extra header is, in our scenario previously, is the IPs of the public internet, right? The X and Y. So we can say that GRE is an encapsulation protocol or a tunneling protocol, right? That helps us establish a virtual private line, not virtual private line, virtual private network from point A to point B, right? It's a point-to-point tunnel or a point-to-point VPN. Okay. So in order to accomplish that, we're using a GRE header, right, that carries the tunnel's data or metadata, right, the actual information that is needed for the tunnel to actually function on both ends. Now, besides GRE, there are other encapsulation methods that can be used. GRE is one of them, right? Then we have IPsec. IPsec is both an encryption and encapsulation method, but it can be used only for encapsulation, right? It's not typically used, but it can be used just for encapsulation. Now, IPsec is a method of encapsulation. MPLS, or multi-protocol label switching, right? This is more of a service that you buy from an internet service provider, right? Layer 2 tunneling protocols, right? Each one of those protocols has a unique way of doing its encapsulation, but it's still encapsulation nonetheless, right? As we discussed, you're adding layers, just like you would send a message, you add an envelope, you're adding layers to that data in order to be able to send it smoothly from point A to point B. Okay. Now, tunneling the traffic is great, right? And you'll be able to send your traffic from point A to point B over the public internet. The problem with that is that if anybody can eavesdrop on your data, basically anybody can read that header, right? If you run an actual a packet capture, you'll be able to look at that data and actually, investigate and see what's inside that header, right? Obviously, if you're using HTTPS, you can at least encrypt the data, the payload side of that, right? But what if you're running a protocol that doesn't encrypt your data? Or, what if you don't want people to see your overlay IP, right? Remember we have private IPs. So there's a lot of information that is just sent in clear text, and anybody can capture that traffic and see it, right? So if you look at the slide here, right, encryption is a method, right, that can help with that. And what encryption is, it's basically the process of encoding information, right, or ciphering that information so that nobody can understand that information unless they have the decryption key or a key to decipher that information, right? So encryption is a very old, it's not something new, right? We had encryption for probably 1,000 years or more. It's just, encryption is getting more advanced, and, as hackers and bad actors, learn how to decipher, and, as technology advances, we create more advanced encryption methods, right? But at the end, encryption is a way to cipher your traffic, right? So you send your traffic and you encrypt it in a certain way with a key or an algorithm so that only the receiving end, the intended receiving end, is able to decipher or decrypt that information, right? So if somebody eavesdrops on that information and they don't have the actual key, then all they're going to see is just gibberish, nothing meaningful, right? So as we said, encryption and encapsulation work hand in hand, right? For example, if you run GRE over the public internet, more likely than not, you want to add an encryption on top of GRE. So you can run IPsec encryption or IPsec tunnels on top of GRE. Okay. So another thing with encryption, as we said, encryption is nothing new, but the encryption methods and protocols that we use, right? These methods keep on progressing, right? So an encryption that was secure 10 years ago or even 5 years ago is not secure today, right? For example, MD5, right? Pretty sure that MD5 can be broken easily now in today's age, but not 15 years ago or 10 years ago. So encryption methods, as computer power increases, as with AI and different advanced algorithms, right? Encryption needs to be up to date, so that you need to always make sure that you're using the encryption methods that are still considered secure, right? Now, there are many different types of encryption, right? But as far as the mechanics go, there's two different, let's say, methods of encryption. One is called symmetric, and another one is called asymmetric, right? And it's very simple. The idea behind symmetric encryption is that you're using the same key for encryption and for decryption. Hence the name symmetric, right? You're using the same key. So let's say you have point A and point B, right? They have a key. Let's say this key is X, right? And this is a key, right? So you send the traffic and you encrypt it with this key, which is X. Nobody can read it unless they have this key. Once point B receives traffic, since it has the key X, it can use it to decrypt that traffic. So the same key is used for encryption and for decryption. Now, asymmetric encryption is different, or asymmetric keys are different. With asymmetric encryption, you're using one key for encryption and another for decryption, right? A very common use case for asymmetric encryption is what we know are PKIs, or public key infrastructures, right? Like right now, you're using a web browser, right? Your traffic is encrypted, right? You establish a secure connection over HTTPS with let's say, Google or any website, right? You have access to the public key. Now, the server encrypts the traffic with a private key, and the private key can only be encrypted with the public key, right? So you know that the information is authentic because, and let's use Google as an example, right? Because the traffic can only be encrypted with the private key, and nobody has access to the private key except for Google. And so when you receive that traffic, you can decrypt it with the public key, right? But you can't encrypt that traffic. For example, a bad actor can't, just having access to the public key, there's not a lot they can do with that public key except for just decrypting the traffic, right? So that's a use case of asymmetric key encryption. Now, asymmetric key encryption is very resource intensive, right? You need one key for encryption, another key for decryption. So typically it's used initially to establish authenticity. And then once that is established, the actual data is sent using symmetric encryptions, right? Like AES, right? Now, RSA is asymmetric, AES is symmetric. Now, just that, seeing AES, that doesn't mean AES is any AES encryption is secure, right? Encryption is the bigger the size of the encryption, the more secure it is, right? So AES has different, let's say, different versions, right? As you move up, it's more secure. Same thing for RSA. Okay. Let's go to the next slide. Okay. HTTPS, right? As we said, right? HTTPS is one method that uses asymmetric encryption, right? But it's used just initially to establish authenticity, right? So the public, during the initial handshake, right, to establish that the server is, the actual authentic Google server, right? But once you start sending the data, that's when you start using symmetric encryption, because it's much faster, much more efficient, although not as secure as asymmetric. Okay. Okay. You probably hear a lot the word SSL, TLS, right? SSL or Secure Socket Layer is the successor of TLS, which is Transport Layer Security, right? Apologies. TLS is the successor of SSL, right? So you can think of TLS as SSL version 2.0, right? But they have the same basic premise, right? It's an encryption. It's a method for encrypting your traffic, over the transport layer. So this is not a layer 3 protocol, SSL and TLS, right? It's a transport layer protocol. Now, IPsec is another example of encryption, right? IPsec is very commonly used, right? We say IPsec is a layer 3 encryption because you're encrypting your actual header, right? Those protocols that we discussed so far, encryption protocols, these protocols are used in transport, meaning as you send traffic from point A to point B. But there are different other types of encryption. For example, data at rest encryption, right? For example, you have your hard drive and you have data and you want to encrypt that data, right? That's more of a data at rest encryption, right? You still want to have your data encrypted as it's stored, so that if somebody gains access to that storage, they can't read it, right? And there's many different methods for encrypting data at rest. One of them is full disk encryption, or FDE. Okay. VXLAN. What's VXLAN? Right. VXLAN is another protocol that establishes, let's say, encapsulation, right, or tunneling. What VXLAN does is it's a layer 2 encapsulation protocol, which means it can carry layer 2 information or stretch your layer 2 domain or broadcast domain over the public internet, or technically you wouldn't use it over the public internet, but over an IP or layer 3 infrastructure, right? So let's say you have So let's say you have your data center, because it's typically used in a data center, right? Let's say you have your switches, right? Let's say you have a server here. And we're going to keep it really simple, so we won't use a very basic example, right? I know I say switches, but we're using these are layer 3 switches, which means they actually route traffic, right? So you have your infrastructure, you have server A and server B, right? let's say server A is in network 192.168.1.0/24. Let's say over here you have server A, which is on the same subnet. You want it to be on the same subnet, right? Let's say it's on the same subnet. Let's say this IP, this server has a .1 IP, this server has a .2 IP, right? Well, they're in completely, because they're separated by layer 3 domains, right? It's impossible to send, they're not in the same, broadcast domain, right? So you need a method to, if you wanted them to be on the same broadcast domain, you need a method to allow server B to communicate directly with server A without having to route that traffic, right? Well, one method is obviously not practical, but you could just add a layer 2 switch and just connect it, right? But that's not practical, right? Especially what we're trying to establish here is keep the existing infrastructure, but also establish some sort of a layer 2 domain or a layer 2 end-to-end connection. What you can do is use VXLAN, right? And what VXLAN does is it encapsulates your layer 2 traffic over layer 3 so that you would send your header, or you'd send your packet or tunnel it from this server through this switch all the way to, or layer 3 switch to this layer 3 switch. Once it gets here, decapsulates it, you get the layer 2 information. So it's similar to what we discussed with GRE, where you have a layer 3 encapsulated with layer 3, but in this example, you have layer 2 encapsulated with layer 3. So it's very useful, especially for a data center environment, right? Because you have different type of workloads. Without going into too much details, there's different workloads that might require you to stretch a layer 2 domain. For example, if you're familiar with VMware, if you want to do a vMotion, or you transfer a server from one side to another side, you're going to need a layer 2 end-to-end, right? And this is where a VXLAN can be very helpful. Now, VXLAN is a good encapsulation method. The benefit is that it's very lightweight, it's very extensible, right? Hence the name Virtual Extensible Local Area Network, right? Also, there's other benefits from the data center side, right? For example, allows you, obviously, number one, it allows you to stretch layer 2 over layer 3. VXLAN has 2 to the power 24, I believe, or 60 million VXLAN IDs versus pure layer 2. If you wanted to have layer 2 connections end-to-end in your data center, right, you're stuck with 4094 or 4095 VLAN IDs, right? Which for large-scale environments like AWS, let's say AWS data centers, right, that's not enough. This is where VXLAN can be very useful because it allows you for a more extendable layer 2, let's call them VXLAN IDs, which is a layer 2 domains, right? So instead of 4096 or 4095, really, you get up to 60 million something, let's call them VLAN IDs, right? Okay. So what's the use of VXLAN, or why is AWS using VXLAN, right? Well, primarily, AWS uses VXLAN as an layer 2 encapsulation method for traffic mirroring, right? And all what traffic mirroring is that what you're doing is, let's say, and I'm gonna look, I believe I have a good diagram to explain this. Yeah. So traffic mirroring is sending your capturing your traffic from an instance and then sending that traffic to a device to store that information, right? So for example, let's say you have a device or let's say you have a server that does inspection of data, logs the information, or maybe just saves it for whatever policies that you have set in place in your organization, and you want to record all your traffic that exits a certain EC2 instance or machine, and you want to send all that traffic for logging or monitoring, right? That's where mirroring can be helpful, because if you think about it, let's say you have, as shown in this example, let's say that you have the source A, right, and another source B. So these are two different, let's say, EC2 instances, right? And you want to send that traffic so that anything that enters this source, or let's say anything that exits this source, you want to record it and send it to some server, some target, right, for logging. Now the way you want to send this traffic is you want it to be layer 2 end-to-end, right? Or AWS intended method is they want it to be sent as layer 2 end-to-end, right? From the mirroring source to the mirroring destination or the target, right? That does the logging. AWS uses VXLAN encapsulation for that reason, right? Because what happens here is that you have the original packet, right? What VXLAN does, or what AWS does, they add the VXLAN header, they reserve the layer 2 information, and then you have a new source and destination IPs where the source IP here is the actual mirroring source, and destination is the server that does the logging or the mirroring target or destination. Right. So that's the use case for mirroring in the context, or the use case of VXLAN in the context of mirroring. And the reason why they're using VXLAN is because VXLAN is very extensible, right? It has a lot of your number of IDs that you can use within VXLAN is much higher than any other encapsulation method, right? And another thing is because it's aside from it's extensible, it's there's a lot of metadata that you can add into VXLAN. Okay, let's take a break and take some questions.
All right. So thank you all for that. Now, this is some of the deepest and heaviest content during the entire program. So thank you all for being strong. Thank you all for sticking with this. This is some heavy-duty networking. The evolutions of this encapsulation are very old. We'll give you some examples as you go through. We'll answer some questions, and then we'll get into some other stuff. But you may need to watch this once or twice. That's okay. We're going to leave this on YouTube for you. We want you to be helped as much as possible. So we're going to go through questions one by one. If you just joined us and you didn't know that we have an incredible number of free labs, almost 2 full days worth. And I mean, about a day is a little more than a day and a quarter is there now, but we're adding more by Sunday for you. Download them. They're in the description of this video as well as in the chat box. We definitely want to help you with that. So take advantage of those, get those labs along the way. Now let's get to some questions.
Okay. Okay. So first question, I think it's the opposite. Public key is used for encryption, but only the private key can decrypt the information. I believe it I believe it's actually public key, because if you think about it, right? Private key, public key is what you share with all the clients, right? So me in my browser, I have the public key, right? So I use it for my end, I use it for decryption, to decrypt the traffic that I receive from the Google, as we said, as an example, right? But I'll let Benedict speak on that.
And I can help with this one as well. You want to go, Benedict, or want me to do this?
So can you hear me?
Yeah.
Okay, so there are different concepts here. When we're trying to enforce the concept of confidentiality, right? You're going to encrypt the message with the public key of the receiver. And then when the receiver gets the message, he'll decrypt the message with the private key. Okay. When you're trying to enforce the principle of integrity, you encrypt the message with your private key and then send the message to the receiver. And then when the receiver gets it, it decrypts the message with your public key. So there are two different concepts here.
Exactly, based upon what we're trying to do. A good question.
Yeah.
Let's go to the next one.
Okay. So is it safe to say that VXLAN is a multi-layer protocol, layer 2 and layer 3? Also, notice I'm calling it a protocol. Is it really a protocol or just a service? I would say it's a protocol.
Protocol.
It is layer 3, and it depends on what. So when we say layer 3, it's because it works over layer 3, right? But you're encapsulating layer 2 traffic. I hope that answers your question. I think the short answer is layer 3, but the VXLAN header itself is also, has a header in layer 4 as well. So really, like as we alluded to previously, is that the OSI model is not a clear cut where you follow it word by word, right? It's more of a method to establish like a common grounds or a language, so we all can understand, but it can get vague sometimes. Depends on the protocol that we're in question.
Yeah.
I think that's a comment.
Yeah, we're going to work on that since we don't know what it is, Muhammad, out of context. Let's go to the next one. Okay, so let's talk about that encapsulation thing a little different and the GRE tunneling, because, and yeah, we can definitely mention some good books and network fundamentals, but I want to talk about this. Where did all this tunneling stuff come from? It came from a long time ago when we had an IP network and we used to have these other networks like Novell and AppleTalk, and we wanted to push the AppleTalk and the Novell traffic over the IP network. And thankfully that stuff went away. I don't miss that stuff. It was a long time ago. Those other networking protocols, and it all became IP. But anytime we want to push something through something, wanted to create a transit between two clouds and push IP multicast in manners that they don't allow you, and you can do multicast, but you can't do everything, you can just tunnel it through. So think of tunneling as anytime you've got something that you need to push through something else, because either you need to hide the IP addresses, you got stuff that's not routable, you've got IP addresses that aren't routable, and I hope that makes sense. And the way I look at encapsulation, it comes back from my medical days. If I was going to give a patient amoxicillin, it comes from it comes from the manufacturer in powders. I could just pour the powder on them and say, try to take it, right? Or I could give them powder and they could pour it into their coffee and drink their coffee. Or the drug company could take that powder, put it in a capsule and say, here's the capsule, take the capsule. It's easier to transport a capsule. It's easier to take the capsule. And that's really the whole point of encapsulation. Put something in something else and make it a lot easier to send. Hope that helps. Good book on networking fundamentals. Well, yes. So here's what I will tell you. There's one book that I find excellent on basic intro networking concepts. Every Cisco certified internet expert has read it. It's from Addison Wisely. It's TCP/IP illustrated from Richard Stevens. If there's a network architect out there, they've read it. that gets into some very intro level network fundamentals. I will tell you the Wendell Odom, I think it's Odom, the CCNA books are very good. I will tell you the Routing TCP/IP volumes 1 and 2 from Jeff Doyle are excellent. I will tell you the book Internet Routing Architectures from Bassam Halabi are excellent. I will tell you can go to the IEEE and read all the Ethernet specifications completely free. And that stuff's good, Ethernet Wi-Fi. And I would tell you to go to the Internet Engineering Task Force and read the RFCs for OSPF and DNS and BGP and all those other cool things. So that'd be from me. And I'd say that's some good fundamentals. But Mo and Benedict, do you have any other fundamentals you'd recommend?
I think you mentioned the really, really good books. If I were to add one book, it would be actually two. Would be Routing TCP/IP, Volume 1 and Volume 2. But yeah, I mean, if you want to get into like really advanced routing and how routing works, I would definitely recommend Routing TCP/IP.
Yeah, for the fundamentals, I like the CCNA book. It's well detailed and gives you everything you need to get started in the world of networking.
Can I please summarize VXLAN? So I've actually not worked with VXLAN, so I'm going to have either Benedict or Mo explain that one to you. Because I know what it is, but I don't want to be inaccurate.
Yeah, okay. So to summarize it very lightly, right? And somebody asked a good question there. Why would I use VXLAN or instead of just sending the data from point A to point B, right? Because there is a layer 2 header there too, right? But what if you want to reserve that same layer 2 header? Because if you think about every hop along the path when you send your traffic over the public internet or over any layer, multiple layer 3 interfaces, right? You're going to change that header. You exchange the source MAC address and destination MAC address. You're going to keep changing it, right? VXLAN allows you to keep that same MAC address from point A to point B. Even though those 2 points are so far away, right? They can be multiple hops away. You keep that same source MAC address and destination MAC address, right? So that's where it helps. You keep the same broadcast domain. That's different from a layer 3 tunnel. I hope that answers the question. It is a very kind of like a dense topic, right? But we wanted to kind of cover it, at a fundamental level. I hope that answers the question.
You mentioned Todd Lamley's, that's fine. For CCNA, we recommend official Cisco documentation, which is the Cisco Press books, since they make the exams. There's a lot of there's a lot of good books out there. I've not read that one. I haven't done a CCNA since, 25 years ago was when I did my CCNA. But I'm with you on that. But there's lots of good opportunities there. So let's get back to the content. We'll turn it back over to you, Mo.
Okay.
Give us a hashtag AWS Advanced Networking so we know you're awake with all this hardcore networking stuff. I kind of love it, but I like networking.
Okay. Over now is software-defined networking. This is a topic that we have a video on YouTube, I believe, that covers this, right? But let's dive into what is software-defined wide area network, or SD-WAN, right? SD-WAN is all it is. It's a method or a practice of simplifying networking, right? In our traditional networking, right, we have, let me backtrack a little bit, right? Let's say 10 or 15 years ago, most of our traffic was heavily centralized, right? Most of your traffic was branch to data center or branch to branch. So most of your traffic was heavily centralized within your organization. And there was very few services that you use, for big organizations, that you actually use the public internet to access, right? So most of your services and applications were local, were over between your branches or data centers, right? This is changing, right? One evidence for that is the cloud, right? The cloud, you can be working from home. and using Teams, and Teams is on the cloud, right? At somebody's cloud or somebody's data center, right? So as you can see, there's a lot of tools that we use today, right? It could be Teams, it could be Slack, it could be many different applications that you're using that are available in the public cloud or on somewhere on the internet. So the type of traffic changed, right? And that adds a lot of complexities. It means that a lot of your traffic that you used to be able to monitor and or rate limit or do different things on, right? They're not set in stone. They're not static, right? They change. You add and remove new applications. The actual application you use yourself, it can move from one data center to a different data center. So the whole realm of sending traffic, or the whole realm of traffic flows changed. So SD-WAN can be very helpful for that, right? And all SD-WAN is, it's what we call software-defined networking wide area network. It's a software-defined way of almost like reinventing our traditional routing, right? And with SD-WAN, right? In order to explain SD-WAN well enough, we have to take one step back and talk about traditional routing, right? Or traditional networking. With traditional networking, we sometimes call distributed networking, where you have a router, right? Let's say this is router A. You have another router, which is router B, right? And router A has a management plane, which means it has a method for you to log into that router and manage that router, right? So that's what we call a management plane, right? There's also what we call a control plane, right? The control plane, as the name implies, that's what controls the router. These are the protocols. We talk about the different router protocols like BGP and so on and so forth. These are the control plane protocols, right? And then there's the data plane. The data plane is the actual forwarding of data from point A to point B, right? Each device would have the same thing. It would have the management plane. It will have, well, I should be sharing my screen. Okay, sorry about that. So what I was saying, right, you have, with traditional networking, we call it distributed or distributed networking, where your router would have the management plane, right? That's what you use to manage a router. The control plane, this is what actually controls the routing protocols that you use, right? So if you have two routers here, let's say you want to run BGP between those two routers, then you would need some sort of you would need a control plane, right? And the control plane controls the actual routing between those two routers, and it's a session and so on and so forth. So that's the control plane. And then you have the data plane. The data plane is the forwarding of the packets themselves, right? So it's the actual forwarding of the actual packets, right? One good terminology I've heard before is, think of the control plane as the highways to reach from point A to point B, but think of the data plane as the actual cars, right? So it's the actual forwarding of the traffic. That's one good way to look at it, right? And so, as you can see, if you have as networks grow, as organizations grow, right, 20, 30 routers turn into thousands of routers, right, and switches, right? So it can get really, it can get out of hand, right? The management can get very difficult, right? And there's different automation methods that you can use, but still, you're still pushing configuration and managing configuration by pushing configuration into different devices, right? Which can be complicated, right? SD-WAN, or software-defined networking wide area network, is a method of controlling, of simplifying the management and configuration of your routers, right? Or edge devices. We call them edge devices Because typically with SD-WAN, we focus on devices that are at the edge of your network, the devices that connect to your site or data center into other sites. So SD-WAN, the first thing it does is it takes the control plane. If you remember, we spoke about the control plane, and it centralizes the control plane. What I mean by centralizing the control plane is you take the control plane, instead of having one control plane inside each router, you would have one device, almost like a brain, that takes on information from each edge device or router, and then it makes the control plane or routing decisions, and then it would send that information or instructions to each router, right? And that's what the control plane is, right? So SD-WAN, one of the main features of SD-WAN is having a centralized control plane that takes care of the actual routing decisions at a higher level, right? Another very important feature of SD-WAN is a centralized management plane, right? Instead of having to individually go to each device and manage it individually, you'll be able to go to this one controller, right? And then from that controller, you'll be able to manage all of the devices and push your instructions to all your devices, right? So that's where the management plane, centralized management plane. Now the data plane remains inside the routers because you still need the routers to actually make the routing decisions, right? It wouldn't be very practical to rely on a centralized controller to make those split-second data plane or those split-second routing decisions, right? So the data plane is still distributed across routers, right? But those decisions are made based on the control plane, which is used by these instructions are sent by the centralized brain or centralized controller, right? So we talked about centralized management plane, we talked about centralized control plane, but a distributed data plane. Well, typically with SD-WAN, there's another component, right, or another controller. We call it the orchestration plane, right? And what an orchestration plane does is that helps you set up a new device initially, right? So you have a new router, you plug in that new router, and you want that router to connect to the controller, the centralized brain, right? And the way to establish that is using an orchestration plane, right? So typically, a lot of vendors, what they do is they have a hardware embedded certificate on the router itself, right? And the serial number. And then once you plug in that device, all you need is just an IP on that device, right? You can even get it through DHCP. That device then will talk to home, which is, let's say if it's a Cisco device, it will talk to Cisco's data center. Or if it's a Palo device, it will do the same thing, right? Or Prisma, it will do the same thing, right? But what will happen is your device will talk to, it will call home, what we call calling home, right? It will find, and then once it calls home, right, your controller, because your controller has information of the hardware embedded certificate on the hardware itself and the serial number, it will be able to enroll that device with little to no visible or manual interaction with the device. So all you need to do is have that information of that device, and it will automatically enroll. And once the orchestration plane takes care of that, it will enroll it into your management and control plane, right? This is what we call a zero-touch provisioning, right? A zero-touch provisioning is where you don't have to touch the device. You just plug it in, and it enrolls. And then from the centralized management plane, you can push configuration into ultimately into that new edge device, right? So that's what a zero-touch provisioning is, and that's one of the features. if you come from the world of voice over IP, you might have heard of zero-touch provisioning, one-touch provisioning, right? One-touch provisioning is when you add some basic information and then let the centralized controller take care of the rest, right? It's the same method or the same terminology that we use in voice over IP, in the voice over IP practice, right? We're using the same method for SD-WAN. Okay, so we talked about the centralized control plane, centralized management plane, but the data plane is still distributed, right? And then we have an orchestration plane. Now, depends on the solution, right? There's plenty of solutions, right? I don't even keep up at this point, but there's tens of SD-WAN solutions out there, right? But depends on the solution. Those different controllers, as we said, the management controller or the management plane, the control plane controller, the orchestration plane controller, they can be all in one centralized compute or centralized controller, or they can be distributed, right? And there's a case to be made for either one, right? Like you can say that when they're all centralized, right, it's easier to manage from one place, but you can also say that's a single failure domain, right? Because sometimes all you need really is just the controller once you push your configuration, so you can survive without the management plane, right? At least for some time. So that's some of the decisions as you think about as you choose your the flavor of SD-WAN for your organization. That's one of the questions that you ask, and that's some of the decisions that need to be made, right? But with SD-WAN, ultimately what you're doing is you enroll a device, right? If everything's set up properly, you can use zero-touch provisioning. It calls home, it enrolls with your controller, and then you push the configuration from that centralized controller. You have configuration templates. You just add the information that is relevant only to that site, like for example, the IP address, right? Host name, the site number, things of that sort, right? To signify that one site. And you push all that configuration to that device, right? And then from that controller, you also can push the encryption information to establish IPsec tunnels. You can instruct that device to either establish IPsec tunnels with, let's say, with a centralized hub, like a hub and spoke, or you can do a full mesh. These are all things that you can configure from a centralized place instead of having to go to each device individually and configure that device, right? So it's almost has that automation aspect inherent to this solution, right? Okay. We covered the centralized management plane. Okay. This diagram, if you look at if I share my slides, this is a simple comparison of traditional WAN versus SD-WAN, right? So to the left, right, you have your branch offices and you have an HQ office or headquarters. Let's say it's a data center, right? And each device, each of these routers, right, holds all the management plane and data plane information. And in order to establish, let's say, secure tunnels over the public internet, or you can use some sort of a solution, let's say like MPLS, right, where you basically move the tunneling decision, or you move that decision to the service provider and they take care of it. But at the end of the day, you still have multiple devices that are, it gets very cumbersome to manage individually, right? And if you're going to use something like MPLS, well, it can help, right? Because the service provider will take care of managing that MPLS infrastructure, right? It's their infrastructure, and they would give you end-to-end access between all your sites. That can get very expensive, right? Plus, you don't have a lot of control over that MPLS infrastructure, aside from just having it, receiving your different site information from, from one branch to another branch. With SD-WAN, right? Number one, it can save you money by establishing an easily maintainable private infrastructure, which is a bunch of private VPN tunnels over the public internet, right? It's easy to maintain, right? Obviously not as easy as MPLS, because MPLS, the ISP takes care of it, right? The service provider takes care of it. But at least with SD-WAN, it's easy to manage, right? So you get some of that, ease of use, right? Because it's very easy to manage and maintain an SD-WAN solution, right? Of course, we have the centralized controller that takes care of all the routing decisions, so that gives us more of the ease of use, right? But you can save some money by not having to use something like MPLS, right? Because if you wanted to establish the same infrastructure that you have with SD-WAN, which can be done, if you wanted to establish the same infrastructure that would be done with SD-WAN, if you wanted to establish it using traditional networking, it's going to be much more difficult to maintain and actually build, right? And that's really where the true benefit of SD-WAN is everything that's done with SD-WAN can be done with traditional networking. It can be done, right? But with traditional networking or traditional WAN, it can be very difficult to maintain. You're going to need more headcount or more labor in order to maintain that infrastructure. Okay. Now, with SD-WAN, it doesn't mean that you have to use, just one thing I want to clarify with SD-WAN, it doesn't mean with SD-WAN that you have to use the public internet, right? You can run SD-WAN over MPLS, right? Technically, you can run SD-WAN over anything, right? As long as you have that layer 3 connection, or layer 3, you have a layer 3 connection from one branch to another branch, whether it's internet, MPLS, etc. As long as you have that, you can establish your secure tunnels, right? Another thing is, a lot of vendors give you the option of not encrypting your traffic, right? And that would make sense in the case where you're running your SD-WAN over the internet and over MPLS, right? Because MPLS is, if you consider MPLS private, which is technically it is, right? Because you're not sharing that infrastructure with other tenants or other customers, right? Technically, right? You're not just sending traffic over the public internet. So if you consider that private, maybe you don't want to encrypt your traffic over MPLS, right? However, we do recommend that you would encrypt it anyways, right? But again, that's more of an organizational decision, right? Whether the organization considers MPLS private or not. Okay. So why would you use SD-WAN? Well, obviously, first is cost efficiency, right? Although the solution might cost a little bit more than traditional networking, but when you consider the ease of use, right, you can manage it with less headcount, right, with less labor, right? So you save a lot from the operational expenses standpoint, right? But also, if you think about not having to go to a solution like MPLS, that can also save you a lot of money. It's definitely cheaper than MPLS, right? It's very flexible, right? So it's easier to scale up, right? It's easier to scale an SD-WAN solution, right? So that's also a very important aspect of SD-WAN, right? Most of the things that you would do with SD-WAN, you can do with traditional networking, but it's very, very difficult to get the same level of granularity with traditional networking, without overcomplicating that solution, right? For example, there's different data plane, and I don't want to get too much into the low-level details, but there's different data plane policies and that you can push to each device. For example, you can ask a device to, let's say you have 2 tunnels from each site, and you can ask the device to send some traffic through tunnel 1, other traffic through tunnel 2, and you can say for the first tunnel, you want to set a rate limit, don't exceed this, and you can monitor the quality of each tunnel and only send voice traffic over tunnel 1. But if tunnel 1 suffers, let's say it falls below a specific threshold of a service level agreement, you can send it over tunnel 2. So there's a lot of cool things that you can do with SD-WAN, really useful things that can be done with traditional networking, but they're really difficult to maintain and manage with traditional networking. Okay, so simplified network complexity, right? Well, simplified, well, it kind of, the whole sentence doesn't make it. So yeah, so it reduces the network complexity, right? I think I'm kind of beating a dead horse with this point, right? Just saying everything that can be done with traditional network, with SD-WAN can be done with traditional networking. It's just much simpler with SD-WAN. Yeah, that's SD-WAN. Do we want to take questions? Or
yeah, maybe we take 2 minutes of questions, 3 minutes of questions, 5 minutes of questions on SD-WAN before we get into transit gateways, which actually I'm sure everybody's going to be happy about. Get a little out of this pure networking stuff, a little more into the AWS stuff, but this networking concept is critical. And we're going to be using all kinds of WANs in cloud computing, SASE WANs, software-defined WANs, IPsec tunnels, private lines with IPsec tunnels. So let's get a few questions if we need.
so I see.
Will there be an SD-WAN lab? No, we're not going to make an SD-WAN lab. We've got a lot of routing labs, BGP labs, OSPF labs, VLAN labs, VLAN tagging, VLAN trunking labs, and all those other things, but we didn't actually do an SD-WAN lab. We focused more on the bigger technologies that are going to be used in most cases, as well as the technologies that would enable you to learn what's going on under the hood. The key with SD-WAN is you basically click on a couple boxes and pretty much everything is done for you. So all the learning would be removed from the lab that we want you to learn, how packets are forwarded, etc. Were there any other questions here on SD-WAN? Or did Mo cover them today and I covered them with the YouTube video we made a couple days ago, which is quite possible. So before we get back to the content, we'll see if you have any other questions. If not, if you're enjoying something and you learned something, maybe give the video a like, maybe subscribe to the channel and hit the bell to be notified of new videos. For those of you that just joined us, we've got brand new AWS networking labs for you, and a lot of them, nearly 2 days full. They're being added each day until Sunday, and you can get them completely free by registering for them in the description or the chat box of this video. Orchestration. So yeah, let's talk about different kinds of orchestration. In normal networking, and my team can give you help as well, the orchestration's on the router. Inside of your network, you got routers and they're running their interior gateway protocol that says, you know, how to go there. And it might say to me, to get to Benedict, go through Mo. And I know that this interface goes to Mo and that interface goes to Benedict. Here's the thing. The information is stored all on the routers. And the routers pass it to each other like a hot potato. I pass the packet to Mo, Mo passes it to Benjamin. If Mo doesn't have a link to Benjamin, drops the packet. So that orchestration, that control plane is on the devices themselves. What we're dealing with here is the orchestration is sort of like a pie in the sky. I like to view it as a satellite looking at what's going on in the network that's basically telling the devices how to forward their packet. So think of it that way. Is it every man and woman router device, you know, operating for themselves? Or is there some overarching policy that pushes configurations to things and tells people how to forward their traffic? That's the way I look at these orchestration. Either of you want to look at it differently? Or explain it differently?
Yeah, at the end of the day, the way I see it is Mike said, you got different types of controllers, each, and there's no one vendor, there's no that implement SD-WAN the same way. It's not like where each vendor, agrees on uses an open source protocol like OSF or BGP. They don't agree with SD-WAN. There's no agreement on those two protocols, right? Some of those components might be common and they're reused. For example, Ipsec is used for each SD-WAN solution. But really, each vendor does the orchestration part, the control part differently, right? So you can think of the orchestration as just a way to enroll a new device into your network. Just think of it that way, because you need a way to get that device enrolled into your controllers, right? So the orchestration is what that device that does that, right? So you can think of it that way as well.
Go to the next one. You were working with your AWS technical rep, and he said the AWS Advanced Networking exam is one of the hardest and something to be proud of passing. So here's a thought. It's a great exam, and you should be proud of passing any exam. The AWS Advanced Networking is about 500 pages of material. The CCIE that Mo has done is about 75,000 pages of material. Or the CCNP that Benedict done is about 10,000 pages to pass it, at least when Benedict did it, and there were 4 exams. So yes, it is a hard exam. It is a great exam. We love it, and that's why we're teaching it. But if we put it into context compared to other networking things, it's relatively basic. Now, AWS asks questions on exams in a very complicated, convoluted manner. So if you know networking, the biggest challenge of the exam will be trying to understand what they're actually asking in the questions, with all the acronyms, all the abbreviations, and questions that are 2 to 3 paragraphs long when they could be asked in about a sentence or so. Do you guys say that's fair experience? They
Yep.
make it hard?
Yep.
Your network has 120,000 smart devices connected to a control center. They're connected to SIM cards over third-party telecom providers. How to use SD-WAN in this case? Maxon, I don't think we know anything about what this case actually is. What devices need to talk to what devices? Yeah. How are those devices connecting information, and what are they doing with those types of information? How is that information being aggregated? What are the performance needs of these things? What kind of broadcast or multicast traffic did they send, and how do we constrain this? I can tell you that we'd probably be able to talk to that customer that has this, maybe spend 8 hours asking questions, and then we can answer that question. But we don't know what we don't know with what you put in the chat box. And I'm aware that you're limited to basically 200 characters or so, but understand that's a full day's worth of questions to even understand part of what they're doing there. That's why there's so much that goes into architecting these things. And European VXLAN is overrated. There are limited use cases. Virtually everything today is going on layer 3 up to the edge. Not necessarily. Tunde, I can tell you that I thought everything was going to go layer 3. And I literally tell you, in the early 2000s, I ripped out every ridiculous layer 2 bridge network you could possibly think of because I hated spanning tree. A year later, I was working with my team, and we were working on collaborating and creation of a virtual private LAN service. And we were creating layer 2 virtual private lines over IP networks, and we were back to using things. So I think the goal here is figuring out what the business goal is. I don't believe in any hype over any technology. There is no best technology. There is no great technology. There's a place for mainframes. There's a place for ISD and backups still in certain parts of the world. There's a place for private clouds. There's a place for public clouds. My perspective is the customer's needs drive everything. And I don't have a technology preference, but I'm an architect. I'm not an engineer. Either of you guys have a perspective on that?
Absolutely, absolutely. So yeah, I don't agree that VXLAN is over. I think it's a massive. So here's the thing, right? As it has a huge use case in data centers, right? Because in data centers, there's more likely than not, you need to stretch your layer 2, right? And if you're just using layer 2 end-to-end everywhere, it makes no sense, because you're going to have oversubscription. You're going to have, because of spanning tree, right, loop prevention, you're going to have some links that are used, some links that are not used at all. So just the whole setup as a flat layer 2 can work for smaller data centers, but once you scale up, it doesn't work, right? Plus the VLAN IDs, you only get about 4,000 something VLANs. That's not enough, right? For, like, for example, Facebook, they can't work with just VLANs, right? They can't work with the traditional layer 2. That's where VXLAN makes sense, right? You look at it from, and again, VXLAN is a huge topic, right? But once you look at it from perspective of spine setup, what we call a class topology, right? Where you want to utilize all your links, so you layer 3 in your data center, but you still want to maintain layer 2 specific servers or specific virtual machines. So you run you get the best of both worlds, right? You're getting the layer, the benefits of the layer 3, but then you use VXLAN to tunnel layer 3 between those over that layer 3 infrastructure. So it's really useful. It's very useful for
Everything's got its uses.
Yeah.
I love these questions. They're really good thinking questions, which means y'all are awake. So give us a hashtag AWS Advanced Networking, and we will go back to the concept. I believe we're up to transit gateways. Is that right, Mo?
Yes.
Mo, you go wherever you have next. I think it's transit
it.
gateways.
Okay. Okay. So, transit gateways. Think of a transit gateway as a router. That's all it is. It's a router that allows you to connect multiple VPCs together. If you remember earlier today, Mike spoke about that was not what I was trying to do. Give me 1 second. Bear with me. Okay. So earlier, Mike spoke about using VPC peers, right, or VPC peering, right, which was a method of connecting VPC A to VPC B, right, directly, having a direct connection between VPC A and VPC B, right, using AWS infrastructure instead of going over the public internet over a VPN tunnel and so on, right? So if you wanted that direct peering between VPC A and VPC B, you used VPC peering. But if you remember, we had the problem of n times n minus 1 divided by 2, right? Which basically says if you have 10 nodes, that means you need 10 multiplied by 9 divided by 2. We're talking about 45, right? So 45 VPC peers, which it can get out of hand very quickly, right? So what a transit gateway do for you, think of it as a way to have a hub and spoke setup. So if you allow me to add another page, and I'm not sure how, there you go. I'm trying to add a new slide. Okay, there you go. Okay. So if you think of it this way, you have VPC A, VPC B, VPC C, okay? Now, if you want to establish a direct connection or peering between those VPCs with VPC peering, you would have one peering here, another peering here, and another peering here. You can't use VPC B, so if this goes away, you can't use VPC B to send traffic from VPC A to VPC C. It doesn't work that way. VPC peering is not transitive, it's non-transitive, right? So this can easily get out of hand, and you'll find yourself with hundreds and thousands of VPC peering connections, which is highly undesirable. So what a transit gateway would do for you is, we would take off these connections, and what we'll do is we'll add the transit gateway, which is technically a router, and that transit gateway will become your centralized router that can move traffic between your VPCs, right? Now, if you think about it now, if we added 2 more VPCs, all we need is just 2 more links, right? Instead of having to connect each one of these VPCs to each one of the other VPCs, right? So the transit gateway, number one, it acts as a centralized router that routes our traffic between all of our VPCs, right? A transit gateway can also run IPsec tunnels. So you can run IPsec tunnels with your, let's say, your on-premise, let's say this is the data center, right? You can establish an IPsec peering here, or a VPN tunnel, and now you have access to your on-premise. And the big benefit here is that each one of your VPCs will also have access to your on-premise data center, right? Think of this if you didn't have a transit gateway, right? You would need without a transit gateway, you would have needed a direct connect gateway in each one of these sites, and then you would have had to establish multiple IPsec tunnels to your data center. So you see how a transit gateway becomes very useful. So again, think of a transit gateway as a router, as a centralized router that can establish peerings between all your VPCs and data centers, right? You can also connect your transit gateway to a direct connect gateway, which is a private line, right? And have that connection to your on-premise. And now each one of your VPCs have access to that private line. So the benefits are big, right? Now with transit gateways, let's move on through the slides. So as we said, right, it reduces the number of required VPCs. So instead of needing an n times n-1 divided by 2, you would just need n-1, right? So if you have 5 nodes, you'll need five let's call them connections, we call them attachments, right? So it greatly reduces the number of required connections, right? If we go back to our slides, one second. Okay, if we go back to our slide, as you can see here, the topology to the left, this is a full mesh, right? The topology to the left, that's a full mesh, right? This is what you would typically do with VPC peering. The topology to the right, as you can see, this is more of a transit gateway setup, right? Where the transit gateway in the middle, everybody can talk to each other through the transit gateway. Okay. So what's the process of using a transit gateway? Well, you create your transit gateway, right? You create a transit gateway, and the transit gateway is a regionally available resource, meaning within the region, you have access to that transit gateway. So let's say you have an account, an AWS account, right? And you have multiple VPCs in that account. And let's say it's in US East 1 or North Virginia. You create that transit gateway, and then let's say then you can connect your 5 or 10 VPCs to that transit gateway, and now they all have access to each other, right? When you create a transit gateway, the way when you connect that transit gateway, that connection from the transit gateway to the different VPCs, it's called an attachment. Okay, so you create the transit gateway attachment, and when you create it, the transit gateway establishes a network interface, or ENI, inside your VPC. And then when you want to send traffic out through that transit gateway, you just point to that ENI, or that network interface that has been established, almost like transit gateway sets foot in each one of your VPCs, right? And you put your traffic through it. So it's transitive, right? Unlike the Direct Connect gateway by default, not Direct Connect gateway, apologies. We haven't spoke about Direct Connect yet. Unlike the virtual private gateways, which are non-transitive by default. Also, VPC Peering, which is non-transitive. A transit gateway is transitive, meaning if you connect A and B through the transit gateway, A will be able to speak to B. Here's a visual representation of a transit gateway. Over here, you have accounts A, B, and C, right? Each one of them is in a different account, and the transit gateway is in a different account. This is very common, by the way. This is very common, and the reason why it's very common is the transit gateway, when you have a large organization and you have 20, 30, 100 VPCs, right? And each VPC is managed by a different team, let's say different application teams. You have your production VPCs, you have your production VPCs, you have your development and testing VPCs for different applications, right? You don't want one team's mistake affecting the other teams, right? So for example, if somebody runs a Terraform script in account A VPC, right? The worst case scenario is some resources in account A VPC will be deleted, right? If there was an error in that script, but it will not affect your transit gateway and it will not affect your other accounts, right? This is why a typical setup is you have different accounts, and so that one account's mistake wouldn't affect other accounts, right? And it can be a human error. I mean, aside from running an automation script, it could be somebody just going in manually. Maybe they just want to, a bad actor wants to delete your connections, right? So if they gain access to, let's say, account A VPC, they won't be able to affect the other VPC. So that's why we isolate, let's say, we isolate those different VPCs into different accounts, and we put the transit gateway with some other resources in a centralized account, right? Usually that's where you would put like your firewall, if you have a firewall, you can put your network resources, and so on and so forth. So with this scenario here, we have a transit gateway in one account, and then you have 3 different accounts. Each of the other accounts to the left, those are different VPCs, right? So now the VPCs, if you set it up that way, right? And the transit gateway is very flexible, by the way. If you set it up that way, you can have account A and B and C talk to each other. Those 3 VPCs talk to each other through the transit gateway. But you've also established a site-to-site VPN tunnel to your data center. And using this IPsec tunnel, the on-premises or the data center can speak to all your VPCs now. So as we move forward, you see the power of a transit gateway, right? Because it's transitive, because it's highly flexible, it can really open doors for a lot of different setups that wouldn't be available otherwise. Right. Yeah. So with the transit gateway, let's say that using your router, right, you have VPCs A, B, C, and D, right? Let's say VPC A and VPC B need to talk to each other, but VPC C and D also need to speak to each other, but A and B shouldn't be speaking to C and D, right? This is a very common setup where you have, let's say, two production VPCs and two development VPCs, and you want the development VPCs to talk to each other and the production VPCs to talk to each other, but you don't want production to have access to development and vice versa, right? Well, there's a couple of different scenarios here, right? Or a couple of different solutions here, right? Well, you can create two different transit gateways, right? And each transit gateway, create one transit gateway for development, another transit gateway for production. But a more common setup would be using that same transit gateway, but creating two separate routing tables inside that transit gateway. Create two separate routing tables. One routing table is for development and another routing table for production. And that way, development only talks to development, production only talks to production. Now, with this setup, right, this is a very common setup we have in our traditional networking, or let's call it on-premises networking, right? Typically, we call it VRFs, right? Virtual Routing and Forwarding instances. And all a VRF is that you almost split your router into multiple logical routers, right? Where one part of the router cannot speak to the other part of the router. And again, this is very common, right? And this is what we're doing with the transit gateway when you use multiple routing tables. Okay, so why would we use a transit gateway, right? What's the benefit? Why would we use it? Well, centralized management, right? Because now you're, instead of having 100 different tunnels, you have one place to establish, or 100 different VPC peerings, you have now one place to establish all your tunneling. Apologies, I keep saying tunneling, right? You have one place to manage all your attachments, right? Or connections, right? It's much easier to manage, right? Also, you have enhanced security, right? Because of different functionalities like segmenting your routing tables. Also, there are very unique what's the best way to say it? There are very unique methods or that you can use, or they're very unique design patterns that you can use with a transit gateway that allow you to send all your traffic to a centralized firewall and then send the traffic back between different VPCs. So it allows for very unique inspection methods like an east-west inspection. Instead of just inspecting traffic that goes out to the internet and back, you can have a centralized firewall and have all the traffic, even between different VPCs, be inspected through that firewall before it returns. So it really opens up a lot of doors for a lot of different functionalities that can enhance security as well. Okay, and it can be cost effective, and it can actually reduce the cost of your infrastructure if done properly, right? But overall, it's more about adding more functionality and ease of use at the expense of adding a little bit of more cost. Because even a VPC peering can be very costly if not done right, right? And more likely than not, it's gonna cost you about the same, especially if you're sending traffic between different availability zones, which what we spoke about earlier. Okay. That's transit gateway. Do we want to take questions, or do we want to move forward to the next topic?
Address questions before we talk about IP multicast.
Okay.
So If you have some questions, type them in. I know there's a little delay. If you just joined us, make sure you download the labs. They're completely free. Links in the description of the video as well as the chat box. There's a lot of them. So, go download them, watch them, do them, that kind of thing. But just want to make sure you got it. Let's bring in the questions, Chris. I'm trying to translate this. Can 3 VPCs be peered for communication? Absolutely. That is the point of VPC peering, but maybe I'm misinterpreting this question because it was hard to understand. Mo or Benedict, do either of you have a different interpretation of the question?
Yeah, I think that's what he means. Again, I can't interpret it any other way. I think he sent the same thing again. Can the 3 VPC use VPC peering for connectivity? So if you have a full mesh where all VPCs are connected to each other, then yes. But if you have VPC A, B, and C, and you want A and C talk to each other through VPC B, then that doesn't work because VPCs are not transitive.
Exactly. Not without Transit Gateway or CloudHub.
No. How do we implement security and maybe granular security controls with transit gateways since they expose traffic data between multiple sites? Would it be better to implement security controls on a per site basis? That's a very, very, very good question. I love this question. So there is, as I just alluded to previously, I said that there are many different architectural patterns that are supported by a transit gateway, right? So one solution would be, just like you said, is to have, let's say, a firewall in each VPC so that your traffic is inspected before it leaves your network, right? Well, another method or more practical, something that's more useful in my opinion, it can be very cost effective too, is to have a centralized inspection VPC and have all your traffic sent to that centralized inspection VPC and have it inspected before it exits out to the internet, or even between two different VPCs. You send your traffic to that centralized inspection VPC where it hosts your firewalls and then have it sent back. So both east-west or north-south. So that's a very extensive topic, right? I'm sure Mike will cover it at some point, but definitely not within this program, because it's really, really extensive. It's not even something that will be covered that extensively in this exam.
Not at all. But we do have other security training coming up.
Yeah. It is not, no. So a virtual private gateway, if you think about it, does not allow you to connect one VPC to another VPC directly, right? It's more to connect to private lines and VPN tunnels. So that's a virtual private gateway. But a transit gateway, so think of virtual private gateway as an edge router that allows for VPN tunnels and private lines. But a transit gateway is a router that also does VPN tunnels, but it also allows you to connect multiple VPCs to each other using AWS internal infrastructure, right? So you don't have to go out through the internet, encrypt your traffic, and none of that. So think of it two different tools that have different use cases.
I like to think of it, King, a transit gateway as a router that just doesn't have quite as many features as you'd find on a Cisco router and Juniper router that you would use for BGP. So BGP peer to the transit gateway and you route, kind of like we've done for the last 20 some years or 30 years with regular routers. That's all it really is.
So why use a well, think of it, why we use a transit gateway is it's not transit gateway versus virtual gateway. It is transit gateway versus VPC peering, really.
Mm-hmm.
That's the main thing, right? Because with a VPC peering, you would need full mesh. So all your VPCs need to be connected to each other. But with a transit gateway, it's more of a hub and spoke, right? Everybody can talk through that transit gateway, right? Now there is an overlap of the things that Transit Gateway does and a virtual private gateway does, but they're not the same thing. So I would say because a virtual gateway is not transitive.
And Sunday, if you want to look up and get more information, look up a BGP route reflector, because the BGP route reflector 30 years ago is effectively the transit gateway of today. And iBGP, and if you read the BGP RFCs, they're completely free on the IETF webpage, which is why I'm using it. They talk about fully meshing our iBGP peers. And now you've got an organization that's got 3,000 routers, and how do they create a full mesh environment of 3,000 routers? So they came up with a couple ways to be able to chop down the networks to make it scale better. One was something called a confederation, which was chop basically your environment or your autonomous system into multiple smaller ones. And the other was a route reflector, which is peer to the route reflector. It breaks the rules of non-transitive routing, and hence CloudHub, Transit Gateway, same kind of thing. Sometimes if you know where it's coming from, it helps you know where it's going.
Yeah. Do I see any cloud technology that can replace transit gateways? Not really. I think the use of a transit gateway is very important. To replace it, that means AWS has to replace it, really, right?
Yeah.
Because if AWS decided to create something else, because the real benefit of transit gateway is that it has its hooks deeper into the AWS infrastructure than you would, right? For you would need to create VPN tunnels over the public internet. No, AWS uses the internal infrastructure. So it's really hard to replace unless AWS decides to create a new solution. So I think one solution is not really a replacement, but more of an addition, which is AWS's SD-WAN solution, right? Which is called, I believe, Transit Gateway Connect. And with Transit Gateway Connect, it still uses transit gateways, but it using the same transit gateways they're using, it adds the same management plane on top of that. It allows you to do different segmentations. It's literally, it literally is the same thing that you can do with a transit gateway. They only simplify it for you, right? So I would say if there would be something that to replace transit gateways alone, it would probably be Transit Gateway Connect. But it's hard to replace it unless they want to replace it.
And it's hard to replace it because it's not like they just want to give you a Cisco router that's connected to everything and say, here, configure your Cisco router or your Juniper router. That is sort of their router. These are good questions.
Okay.
We may pop a poll into the chat box for you guys. I want you to look at something we're thinking about after some of the questions you've asked us. And some people have asked about slides, and our slides are only to organize our own thoughts. Mo may have fancy slides. I may have 3 words at a time on a piece of paper because that's the way I give a presentation. But there's a potential we'll write a book on it and give the book away free like we typically do, like we've done for the AWS Solutions Architect Associate. So we'll think about it if there's enough desire and potentially enough resources. So, we'll ask you a poll on that. And then we can bring in a couple more questions and then we can get back to the content.
One thing I want to say before, Mike, I just want to, I said Transit Gateway Connect and this AWS Cloud WAN. That's their SD-WAN.
Yeah, that is the Cloud WAN solution. So from Kevin, if a client doesn't have a CCI, would micro-segmentation be too complicated for companies? Kevin, I want to completely segregate competency versus CCIEs. I know many people that have not done a CCIE that are better than CCIEs. You give me Benedict, who's a CCNP, I could find him anywhere, and any company in the entire world would be more than likely to have Benedict. He's that great of a network architect. And prior to that, he also was a network engineer. He's that good there too. So Benedict could do this stuff in his sleep. I'm a CCA, I could do it. I know other people. I worked with this guy, Ted. Ted never got a IT certification his entire life. He didn't finish high school, but he was one of the best network engineers I ever met, and he could do all this stuff. So the key is, yes, you're going to need people to microsegment that really understand networking. Alternatively, you're going to need a simpler solution like an aviatrix. But there's an incredible number of people that know a whole lot, regardless of their certification.
Is a transit gateway, that's a good question. Is a transit gateway a global or a regional resource? If regional, can we create peering between two transit gateways in case we have VPCs in two separate regions? Yes, it's regional. It's highly available. It's regional. So if you wanted to connect multiple VPCs within the same region, you would use one transit gateway. But once you want to, if you have other VPCs in, let's say, in a different region, then you would need to create a transit gateway over there as well, and then peer those two transit gateways, which we call a peering connection between two transit gateways.
All right, so we're going to get back to the content. Mo is going to talk about one of my favorite concepts, which is IP multicast routing, which is something that I've done all over the world. So Mo is going to get geeky into the AWS side of multicast routing, which is very important. If any other multicast routing questions come back after that, maybe with regards to PIM or IGMP or slightly different stuff, we'll tackle them too, and we will have fun with it. So Mo, thank you so much for sharing your expertise, and let's go back to you.
Awesome. Okay. Yeah, AWS multicast. Don't be scared. Don't be fooled. AWS's implementation of multicast is very simple. I think it's smart, but it's very basic, right? As compared to what Mike used to do back in the day at a larger scale, that you can't even compare that, honestly, because the simplicity of the cloud, right? There comes a lot of limitations, right? And even multicast is set up in a very, very basic and simple, limited way, right? But it does the job for the most part. So as we know, there are three types of IP traffic, right? Unless I'm forgetting one. But last time I recall, there's unicast, broadcast, and multicast, right? So unicast is when you have router A, or let's forget about, let's say you have PC, another PC here. Let's say you have a switch here. So it's a layer 3, right? So 1, 2, and 3, right? Unicast is traffic that's going from 1 to 1, okay? A broadcast is you just flooding your traffic and you want everybody to listen to that traffic, right? So you send a broadcast, that means you want it to be received by both. Okay? A multicast is something, you can say something in between. A multicast is you send traffic, it's one to many, right? If you remember, we said unicast is 1 to 1, right? A broadcast is 1 to all. A unicast is 1 to many, which means that you send the traffic, receive it. So you have to subscribe for it, right? So you have your network like this, right? Let's say we have another host, let's say 4. Let's say only 2 and 4 need to listen, or let's say only 2 and 3 need to listen to this multicast traffic. 2 and 3 need to subscribe in order to receive that traffic. And this host sends that multicast traffic, then the switch will know to send that traffic here and here. Now, the switch is able to do that because there's a protocol called IGMB, or Internet Group Management Protocol, right? And what IGMP is a protocol for devices within layer 2, within a broadcast domain, for routers to be able to request multicast traffic, subscribe, or join a specific multicast group, right? And so multicast has a specific IP range, right? I don't remember off the top of my head, but I think it's 224.0.0.0/6. Information that you don't need to memorize because it's readily available. Okay, so it's 224.0.0.0 all the way to 239.255.255.255. So this is the range I use for multicast, right? For example, if there are some IPs on this range that are reserved, right? For example, there's a multicast range that's called the all routers range, which is the 224.0.0.1, and then you have the all hosts, which is 224.0.0.2. So these are reserved, right? Typically what we use for private use, we use the range 239.0.0.1 slash 16. So this is typically the range that we would use for multicast for our applications, but it's not set on stone. We don't have to use only this range, right? So again, going back to IGMP, IGMP is a protocol that you use, or the clients use, or the host, in order to subscribe, right? Because when you send traffic, there's a source or a sender, right? You have a multicast sender, okay? And then you have a receivers, right? In this case, our receivers are host 2 and 3, right? This is where host 2 and 3 needs to send an IGMP join to say, I need to join this group, right? So they send an IGMP join, right? Notify the sender that they need to receive multicast traffic, right? Now the switch, typically switches would run something called IGMP snooping. And some of you might already understand what this protocol does just based on the name. IGMP snooping does is that the switch will listen for the multicast traffic, even though it's not intended for the switch can listen, and based on that information, it will know who wants to join a specific multicast group, who wants to leave a specific multicast group. So instead of the switch just broadcasting the multicast traffic everywhere, it will more intelligently send that multicast traffic to the right people, pretty much, right? And so IGMP snooping, because without IGMP snooping, the router, the switch will treat multicast as if it's broadcast. It will just broadcast it everywhere. And that's why IGMP snooping is very important, right? And it does that as again, I don't want to go too much into details because it really can get granular, but think of it this way, right? Because the switch, it's a layer 2, so it only listens to layer 2, right? So how does it know the actual group, the multicast group? It knows because at the MAC address layer, right, when you send the multicast traffic, each multicast packet is mapped, each IP, multicast IP, let's say 239.0.0.1, can be mapped to a layer 2 MAC address, right? So there's a layer 2 multicast MAC address range too, right? So when you activate the IGMP snooping, the switch will listen for that range, and it will know where to send that traffic based on the IGMP snooping protocol. It will know the senders and the sources and the receivers. Okay, so the source is called the sender or source, which is here, the sender. the receivers are sometimes called subscribers because they have to subscribe for that group. Okay. Okay. So what's the benefit of multicast routing? Well, it's very, very useful for use cases like video streaming, financial trading platforms, in cases where you want to send you're sending traffic from one sender to multiple receivers, and you want to send that traffic in the most efficient way possible, right? And if you think about it, the most efficient way possible to do that is to actually send your traffic instead of having to replicate it multiple times. Because over here, if you think about it, right, let's say I have a financial trading platform, right, and I receive real-time data, right, price changes and stock changes, so on and so forth, right? If I have to replicate that traffic and send it individually to 2 and 4 and to 3, that's not very efficient, right? Because the sender has to replicate that traffic multiple times before it sends it. But if I send it as a multicast, right, then it will go directly only to, number one, I'll only send it once, right? But that traffic will be sent only to the intended receivers, right? Obviously, there's a third solution, which is broadcast, but that's very inefficient, right? But having to send traffic to 100 devices, but you have millions of devices, right? In that case, broadcast is not efficient, and that defeats the whole purpose of the efficiency, right? So that's why multicast, think of it as something between unicast and multicast, right? Unicast and broadcast. Okay. Chris, can you share my screen? Yeah, I just looked back at my screen, so I'm not sure if you saw me when I was drawing this topology. I hope you did. But moving forward.
Yes, that was there.
So
I saw that.
Okay, perfect. All right, because I got lost for a second trying to find my screen. Okay. So another use case of multicast is IPTV, right? IPTV is basically IP, or getting TV broadcasts over IP, right? And you have different subscribers, and those subscribers would will need to watch TV in real time, right? So it makes more sense to just broadcast it only to the desired listeners, right? So it's almost like you have a radio and you tune into your channel, right? And you would only listen to that channel if you need to, right? So you subscribe for it, kind of. But the difference is with broadcasts, like radio broadcasts, that traffic is sent anyway, right? It's broadcasted anyway. And then you choose to listen to it or not. But with this, is even more efficient because the traffic is sent to you and delivered to you in an efficient manner, right? One to many, only if you want to listen to it, only if you subscribe to it. So you actually have to subscribe to it. So we talked about financial trading platforms, right? IPTV. It's very useful for real-time data, right? As you're sending, instead of replicating data multiple times, you want to send it from point A to point B the fastest way possible, right? I see some comments are giving very good examples on what good use cases for multicast, right? Live score updates, example John said, for sports, right? Sina or William said multicast is like TV, right? Just sync the channel, right? It is like TV, except for with TV, that's a radio signal that's broadcast everywhere, almost like a broadcast, right? But with multicast, you actually have to subscribe for it in order to receive it. So how does AWS implement? So before I start this point, I want to point out one other thing, right? In traditional networking, right, we spoke about only of in this example, this is traditional networking. We spoke about only having to send traffic over a broadcast domain or over a layer 2 domain. In reality, you have multiple networks and you have routers, and those different routers connect to each other, right? And you might have a router that's in a different part of the world that connects to your data center through an IPsec tunnel, and you want to send multicast traffic, or let's say over a private line, and you want to send that traffic to that remote site, right? In those scenarios, IGMB alone doesn't cut it, right? You're going to need something else because now you introduced routing into the issue and it complicates things, right? This is where we would use protocols like prefix independent multicast or PIM, and it really gets really granular. That's a huge topic on its own. It's outside of the scope of AWS, and it's not used in AWS Cloud to begin with. But just keep in mind the comparison here when we compare traditional networking or on-premises networking, we're comparing having one layer 2 domain, and then that layer 2 domain, just multicast within that layer 2 domain, right? It's compared to that. It's not compared to having to use like a multicast routing protocol where it really gets gets more complex. Okay, so how does AWS implement multicasts? Well, with AWS, they use the Transit Gateway in order to implement multicast, right? So if you remember from the previous topic on Transit Gateways, we said that a Transit Gateway establishes an attachment in each one of your VPCs, right? And if you remember, I said when a Transit Gateway attaches to a VPC, it sets its foot on that VPC. So it creates an ENI or elastic network interface in each one of your VPCs, right? Now, with that in place, if you have, let's say, 10 VPCs and each VPC has a Transit Gateway attachment, it has an ENI, that means, and because Transit Gateways are an AWS resource, right? So they're more integrated with your AWS infrastructure, right? There's an opportunity here to use the Transit Gateway for multicast. And the way that is done is not really a true multicast, but it's more of what we would like to call traditional networking. I think Mike will agree with me when I say we call it more of a pseudo multicast. So it's not true multicast, more of a pseudo multicast, meaning it's really more of a replication of your multicast traffic. But the benefit here is with the Transit Gateway, your end host or your server or machine does not handle the replicating that multicast traffic. It's the Transit Gateway that does that for you, right? So as far as you're concerned, it is multicast, right? And the packet is multicast, but the Transit Gateway replicates that traffic into your receivers, the intended receivers. I'm a visual person, so I'm gonna go to my diagram, kind of explain from there. Okay. So as you can see here in this diagram, I have VPC A, VPC B, and VPC C. Okay. So between those three VPCs, your Transit Gateway established an attachment to each one. Now it has an ENI in each one of those VPCs. Let's say in this example, you want EC21 and 2, let's call them N3. You want those three to be able to talk to each other, right, using multicast. Let's say 2 is the sender. This guy is the sender or the source, right? and 1 and 2 are the receivers, right, or subscribers. Okay. Now, let's say that the group that we're using is 239.0.0.1. Okay. That's the multicast group, right? The sender first, needs to, well, the transit gateway needs to know where the sender is, right? And there's two methods we can do this. We'll start with the first one, which is statically. We can statically, on the transit gateway, you enable multicast, number one, you enable multicast, right? And then you create what we call a multicast domain, right? And each one of your subnets can only be part of one multicast domain. Okay. Think of the multicast domain as, well, it will make sense as I explain it, right? But the multicast domain is the domain that is shared between different VPCs or different ENIs inside those VPCs, right? So in order for the sender, which is 2, to be able to send multicast traffic to 1 and 3, they all have to be in the same domain, right? And then once I create that domain, it's part of the transit gateway. I need to say, okay, I'm going to attach this subnet, and this subnet, those 3 VPCs, those subnets inside those 3 VPCs, I need to attach them to this domain, to this multicast domain, okay? And then I need to create the group, which is 239.0.0.1. I need to create that and say 239.0.0.1. And for 239.0.0.1, the the instance number 2 is going to be the sender, and those 2 are going to be the receivers, right? And then of course your application itself inside this machine needs to accept or needs to send multicast traffic, right? And then 1 and 3 will be able to receive that traffic. So when we send that traffic from 2 to the transit gateway, the transit gateway is doing true multicast. It's still receiving, but what it's doing is it takes that multicast packet and then it will replicate it to the instance 1 and to instance. That's why I said it's more of a pseudo multicast, not a true multicast from AWS perspective, right? But the benefit here, your hosts, which is host 2 here, your instance 2 here, didn't have to replicate that traffic multiple times. You only had to send, right? So you still get the same benefit. So this is more of a static registration. This is what we call static registration, okay? The other type of registration is dynamic, and it uses IGMB, just like we talked about IGMB previously, right? For when we gave an example for traditional network or on-premises. With that example, we talked about IGMB, right? Well, we were talking about IGMB version 2 in that example, right? And IGMB is, as we said, your host can register or join a multicast group, right? And then your transit gateway can listen to that register message, almost like a switch using IGMB snooping, and it will recognize and record that the specific host needs to listen for multicast, right? And then the sender, in the same way, the sender needs to send the multicast traffic. Now, there's only one thing different here, right? The sender, if the sender is both a sender and a receiver, which means you need to send and receive multicast traffic, then you can use IGMB version 2, and the transit gateway will register you as a sender and a receiver. But if you're only a sender, which is most typical case, right, where a server is a sender and then you have multiple receivers, that if you're only a sender and not a receiver, then you still have to statically register that sender. One other thing is, If you want to be a sender, you have to use an EC2 instance that is a Nitro instance, right? So it has to be a Nitro. It needs to use a Nitro network interface card. It can't be a regular EC2 instance. It has to be a Nitro instance. It can't be standard, right? Because there's standard, there's Nitro instance. Okay. If we go back to our slides, Chris, if you think, thank you. Right. So dynamic registration, right? The Transit Gateway will send IGMB queries, right? The host will send an IGMB join, right? They will ask to join, and then you will register it as a receiver. For the sender, you will have to register statically. Now, one thing I want to point out, by default, all, well, not all, but AWS Linux instances are set up by default to use IGMB version 3. Because IGMB is set up, so multicast or IGMB is set up at the kernel level. It's not at the operating system level, as in, I mean, it's not on your software itself, right? It's not on your application, right? The actual operating system takes care of it, is what I'm trying to say, right? The operating system takes care of it, not the multicast application that you have on top of that Linux machine, right? So you need to change it to IGMB version 2 because that's the version that AWS supports. It doesn't support IGMB version 3. It supports IGMB version 2. So make sure to keep that in mind. If you want to be a sender, you have to be a Nitro instance. And in order to use IGMB to dynamically register your sources, you need to make sure that you set up your instance to use IGMB version 2 instead of IGMB version 3. IGMB version 3, right? I'm pretty sure I'm forgetting one other thing, a very important point. Yes, okay. The third thing is your receivers. You need to make sure that the receivers disable the option for source destination IP check. And what that option does is by default, there's a protection mechanism where an EC2 instance, if it receives a packet with a destination that is not its source IP, it will discard it by default. So if I have an instance and my IP is 1111, but I receive a multicast packet that has a 239, by default, that instance will say, well, 239 is not my IP, so I'll just discard this packet, right? So typically, if you have an instance and you set up that instance as a firewall, for example, right? It's very typical for that firewall to not, it's very typical for that firewall to forward traffic that is not intended to it, right? Because traffic goes through that firewall. So typically in a firewall, you would disable that option. It's the same thing for multicast. As a sender or a receiver, you need to make sure that that's disabled. Only that with a Nitro instance, you don't need to disable it. It's not used by default. But so that means technically the sender, since it's Nitro, you don't really care about disabling that option. You can disable it. But for receivers, you have to disable it if you're not using a Nitro instance, which more likely than not, you're not using Nitro instances. One other thing I want to bring up here, which is if you're using access lists, if you're using security groups, you need to make sure to add those policy, the security group policies and the access list entries to allow for the multicast traffic, right? And the first traffic that you need to allow is a IGMB. So this is IGMB version 2, right? With a source of 0000/32. Why 000/32? Well, that's the IP that the Transit Gateway uses when it queries your instance right? When it sends IGMP queries, when it asks you what groups do you want to join, it will ask you with a source IP of 0000/32, right? So this is the first part that you want to enable. Notice that they don't put the destination. We know the access list has a source and a destination, right? And notice this is straight from the AWS documentation, by the way. Notice that they don't have the destination here. But in reality, when you create, I think this is incomplete information, honestly, but in reality, when you create this, there's usually a destination part of the access list, right? So you need to make sure to either put your IP address over here as a destination, or just leave it open. Actually, in fact, because this is IGMP and you're querying, right? You want to make sure that it's using the IGMP query, which I forgot what's the destination IP, which is well, it's going to use 224.0.0.1. It's going to use 224.0.0.1. If you remember, we talked about the all host IP address and all routers IP address, 224.0.0.1 and 224.0.0.2, right? So 0.1 is all hosts, right? So you need to make sure that the destination here is 224.0.0.1, okay? And then you need to allow the actual multicast traffic itself, right? So in this example, you're using UDP, you're sending UDP traffic, or you're receiving UDP traffic, right? And so when you receive UDP traffic, right, you want, number one, the IP address of the, you want to allow traffic coming from the IP address of the sender or the source, and you want that traffic distant to the destination multicast IP. So in our example, we said 239.0.0.1, right? And now, of course, outbound is the exact opposite, right? Well, with outbound, well, not the exact opposite. It's the exact opposite for UDP, right? Because the destination becomes the multicast group IP, and this is more of for the sender, right? But also you need to allow to send IGMP join or IGMP leave, right? So you need to allow those IGMP traffic as well for the source and destination. So we do have a demonstration for this exact topic, right? And I did go through how to set this up, how to set up the security groups. I haven't set up the access list. I kept the access list open for that example just for brevity reasons, but it's the exact same thing, right? We talked about access lists. Notice that security groups are pretty much identical, almost identical. IGMP is IP protocol 2, so this is the same thing. If you notice, everything else is the same. Okay. So why should you use multicast routing, right? Well, number one, efficient resource utilization, which means you're utilizing your resources better, right? You don't have to replicate that same packet again and again and again, right? Your host will only send that multicast traffic once. It will only be received by the intended users without having to replicating that traffic multiple times, right? Let the transit gateway take care of that. And then enhance application performance, because you don't have to replicate that traffic multiple times, right? This is perfect for real-time traffic because you only send it once and it will be received by all the intended receivers. So that's IP multicast. If you have any questions, more than happy to answer.
Let's come back. Let's ask some questions. And I want to do one thing before we get to the questions. I want to talk about why the stream we're dealing with today is unicast versus multicast. So I want to just give you guys a little bit of an example of how multicast works outside of the cloud. This is a cloud thing. Mo gave you a very good, very detailed cloud. But I'm going to give you a perspective of how it would work in the traditional environment. I think this may help clarify a few things. So right now, this is a traditional local area network. Right now, I've configured it for nothing other than traditional unicast routing. Let's say your users at the bottom underneath R2 want to access information. In a unicast environment, like we're actually in right now on YouTube, the users would basically go and ask for the information, and the source would send the information through the network to the users. So if we've got a host on the left and we're all watching YouTube, we're all connected to the unicast address at YouTube, and then YouTube will literally replicate it for host 1, it will replicate it for host 2, and it will replicate it for host 3. Now, YouTube uses the entire internet. The entire internet does not have IP multicast routing enabled, and that's the reason why you'll see this for YouTube. Now let's take this off of the public internet, let's turn it into our private network, and what we would have to do is we would have to enable IP multicast routing on each router, and we'd have to enable a multicast routing protocol, typically PIM, protocol independent multicast would be used, and specifically sparse mode. But for right now, what's the point of this? We would enable this on router 2. We would enable it on router, well, actually this should be router 3. It might help if I could count. We'd enable it on router 2. We would enable it on router 1. And we would also enable it, and it would be enabled on all interfaces on router 1. So now what would happen is we'd have the source. What was that big show that was on Netflix that everybody liked? Was it Black Mirror? So basically you'd have a source, say Black Mirror, that would post itself if it was a TV show, if it was live broadcast, inside of your corporate, maybe your stock things, maybe your IPTV and your private cable company. The source would start to broadcast and it would instantly register with router 1. Router 1 in its multicast routing table would see that it has the multicast group 239.1.2.3, which was coming from the source IP address of 172.16.1.1. Now, if we owned the network and we enabled IP multicast, the host 1 would like to join. It would send an IGMP join group message indicating that it wants the presence of 239.1.2.3. It would immediately hit router 3. Router 3 would say, I'm going to open the port on my Ethernet to, 239.1.2.3. It would then send this request to router 2. Router 2 would then open what it's called its outgoing interface towards router 3. It would then go to router 1, and router 1 has the traffic on it. It would immediately send the information out its outgoing interface. So now host 1, and I'll enable them as host 1, is receiving the IP multicast. Now someone else wants to receive it. Guess what they do? They go to router 3. They say, send an IGMP join group message to router 3. Router 3 already has the IP multicast. So it just adds that port, or if it's a layer 3 switch, and starts sending it to host 2. Now host 3 wants to watch that same live show, Black Mirror, on Netflix, but it's live, not on demand. It sends an IGMP join group request. Router 3 sends it back. But in order for this to happen, we have to be on an IP-enabled network, a network which would support a network multicast routing protocol, such as PIM or DVMRP, and it would also have to support and enable us to let the routers actually replicate our network traffic. So that's traditional multicast routing. That's why what we're doing on YouTube today is actually unicast, even though it would be a whole lot more efficient if the entire internet was IP multicast enabled. And imagine how many less servers YouTube would actually need. When everybody wanted to watch the same thing, they could subscribe at the same time. Just think about how efficient that would actually be. So hopefully answered that question on why some of it was unicast versus multicast. Let's get into some questions. No questions for real? On IP multicast? On any of that hardcore, heavy-duty stuff that Mo went through? You all awake? And yes, okay. William, we have to enable multicast on every single router along the way and on their list to make it happen.
Yeah, pretty much.
That's why what we're dealing with here is unicast, even though multicast would be more efficient. But now you've got cable TV, right? Or fiber to the home. Now the service provider that gives you your TV has control of the network, so they can enable the IP multicast routing directly in there. And what you typically have is your video plugs into an encoder. It multicasts it on the network. The routers and switches do their thing, and everybody's all kinds of happy. So the next question so yes, you would need to enable multicast hop by hop in order to take benefit of the protocol. So now, Tenacious Bob actually brought in an interesting question. So if he's getting me right, yes, we can't multicast on the public internet because you don't have control over the routers on the internet. And you can't enable IP multicast routing on every different internet service provider's router that exists to get it here, because your traffic goes through many internet service providers or autonomous systems that you don't own. But if it was your own, yeah, you'd be able to control it and you'd be able to do it. Now, if we had to multicast through the public internet, or if we had to do heavy-duty multicast across AWS into Azure, more than the IGMP that Mo talked about, Mo gave you the perfect technology to fix this. We could create a GRE tunnel in our data center across the internet, and we could push our IP multicast across the internet by tunneling it through the internet. And now you know why Mo was talking about these complicated overlay networks and this GRE tunneling, and we networking people love tunneling because it enables us to take stuff and then put it inside of something else. And that way, when we don't have control of the network, we can still give ourselves control.
So I thought I would let you know, Mike, that we have had 79 people vote in the poll for the exam guide possibly being made. 14% said that as long as there are cat pictures. So, there you go.
Anybody wants cat pictures? I got a cat named Cindy. She's absolutely beautiful. I got cat photos for days. It's funny. I have 3 pictures of myself and my wife on my phone and about 1,500 pictures of my cat. But I guess any cat owner knows that. If you have a cat, give me a hashtag cat. If you got a dog, it'd be a hashtag dog. But in any case, any other questions before we go to talk about some more technical content? Okay, I am going to get into access control lists. So bear with me, Chris. I'll come back on screen. Okay, so I'm back, and hopefully my 3 internet connections hold out for the rest of the day. You have no idea what can go wrong will go wrong. I love dogs, cats, anything, you name it. I love anything with fur, feathers, you name it, I love it. So let's talk about packet filtering. We have to add security into our systems, and there's lots of tools. At the edge of our networks, we're typically going to use our next generation firewalls. Inside of our networks, we may not want certain traffic to talk to certain other traffic. Like maybe we don't want subnet A to talk to something in subnet B. So what do? Well, we've actually been creating access control lists on routers. If you did a CCNA, you may have done your standard access list and your extended access list. Well, in AWS, they call it a network access list. And honestly, the term that AWS gave it, network access list, is really better. Because to us networking people, an access list is just an access list on the network, a packet filter. But in the Unix world and the Windows world, they have access control lists, which determine how you would access certain resources and permissions. So they also call them access lists. So for clarity, let's call it a network access list. And it's just the ability for you to be able to tell something that it can talk to something or can't talk to something. So access lists are a bit like firewall. By default, they block everything, which means if you create an access list and you don't permit something, I promise you just broke everything. I promise you. And you can break a lot of stuff really fast with an access list, but you can also add in a lot of security. So an access list, you can enable you to allow or disallow traffic based upon something. Now, what is that something? Typically source address and destination address, protocol and port numbers. So source address, 192.168, talking to 2222. That is the source address and the destination address. Protocol, TCP or UDP. And port number. Are we connecting to port 443 because it's SSL? Are we connecting to port 80 because it's unencrypted web traffic? Hopefully we're not, but you get the point. So an access list enables us to create a policy to protect a subnet from traffic. You may see that on a question, protect a subnet from traffic. So let's talk about something you don't want to do. And believe me, anybody that's ever been a network engineer has done this before. So access control lists work in order, meaning they look at the rule, they take an action upon the rule, and then they do move on to the next rule. So let's say we have traffic coming into an access list, and the rule is deny everything. And then after we say deny everything, we say, oh wait, allow you to connect to the web server, but we already threw out the traffic. It's not going to get to the traffic. So we have to have our permits, typically speaking, before we have our design. Now, the next thing I want to talk about is stateful versus stateless. Access control lists are stateless. The stateful versus stateless is critical. Here's the difference. A firewall, all of them for the most part, are stateful. My iPhone just right now became a firewall so I can alleviate state. Let's say I am here and I want to go to a website, www.gocloudcareers.com. And I'm sitting here and I am having a stateful access list because it exists on a firewall versus a non-stateful access list that exists on AWS. I initiate my traffic. I'm behind the firewall. My finger is the traffic. I type www.gocloudcareers.com in my browser. My traffic goes out through the firewall. My traffic leaves the firewall. The firewall says, that's Mike Gibbs traffic going to gocloudcareers.com. My traffic hits the GoCloudCareers web server. It then comes back, and the firewall says that is GoCloudCareers traffic designated for Mike Gibbs because Mike Gibbs previously requested the traffic. Allow it in. So it's keeping track of my traffic going out and allowing my return traffic. The keeping track of it is what's called stateful. Now, by comparison, we've got Hal the hacker. And if anybody has the name Hal, I don't mean anything. I was just trying to alliterate here. But we've got Hal the hacker that tries to come into my website. He or she is immediately blocked. Why is Hal the hacker blocked? Because they're not permitted by the firewall, and they didn't initiate the connection from the inside, and the firewall didn't have state on the outside. So now that you know what is stateful, we keep track of it. Stateless is we don't. Now, if the firewall didn't have access didn't keep state to know that I initiated traffic to go to GoCloudCareers, it would block it. Well, access control lists on routers, network access control lists in AWS are stateless, so they don't keep track, which means you'll have to apply them both inbound and outbound if you want the return traffic to come back. No big deal. Now, I mentioned they're in order. So I mentioned don't deny all traffic and then permit something. Do this instead. Let's say I only want to allow unencrypted web traffic for whatever reason to the system. I'm going to allow port 80 traffic from any source in, and I'm going to allow the return traffic from port 80 traffic out. By doing so, nope, I don't have any denies because the deny is in place. Let me give you some general guidelines. When you create these rules, they are processed in order. So you might think rule 1, rule 2, rule 3, rule 4, rule 5. You might want to do that and count that in chronological order. I beg you, please don't do this, because what's going to happen is you're going to think you need a rule now, and then you're going to need another rule now, and then you're going to need another rule. And if you have your things processed in order, you're going to get yourself in trouble. So maybe rule 1, maybe rule 10, maybe rule 20, maybe rule 30, or maybe, rule 10, 1, 50, 100, but give yourself some opportunities to create new rules on demand and remove them. That's all we go. Access control list, simple, stateless packet filter. And you use access control list to protect a subnet. The whole point of the access control list is simply to keep traffic out of the subnet. So now we're going to talk about a security group. What's a security group? Well, a security group is very simply a host-based firewall, if you want to call it that. So you've got your server. You could put a host-based firewall on it, and I recommend you do. From an enterprise-grade organization, put a host-based firewall on it. And what a host-based firewall does is it protects the server. Well, AWS offers a concept that's very similar to a host-based firewall that you can use to protect your AWS infrastructure. Want to protect your load balancer? put a security group on the load balancer. And don't believe me, it's not enough. You're going to want to use real other security too, but it gives you something to protect the load balancer. Very similar to a host-based firewall. Now, does this mean we shouldn't use the security group and then a host-based firewall on our servers? No, we should use both because we want defense in depth. The more layers you have to an onion when it comes to a security, the more likely you are to survive an attack. But security group protects a service or a server, and network access control list protects a subnet. So keep that in the back of your mind. Now, because a security group is like a firewall, it is stateful, which means if you allow traffic into the server, for example, it's going to naturally allow the traffic to go back to the source because the security group is stateful, just like a stateful firewall. Now, when it comes to the security group, you only need to create inbound rules. Permit this. Why? It's a firewall. Permit what you want in. Everything else is going to be magically, automatically denied. Because firewalls are security devices. So wouldn't you think if your door was a security device, it would remain locked, and then you'd give the key to the people you want in? That's all we're talking about security groups and access control lists and network access control lists. They're locked until proven otherwise. So while I showed you that we use the access control list for the subnet, we use the security groups protect the host. There you go. Very simple. You see, the instance, which is basically just a virtual machine, is protected by the security group. Now, in real life, I'm going to do a lot more to that server to make it secure. We're going to disable the unnecessary services on this thing, close unwanted ports down, patch it, add some endpoint protection, maybe some anti-malware, maybe an enterprise-grade host-based IPS system and a firewall. But these are the cloud-native security tools that are available for you. Now, let's talk a little bit about VPC flow logs. So what's a VPC flow log? So for those of you that understand networking and been in networking for a while, maybe you're transitioning into cloud, you may have noticed that Cisco had something called NetFlow on their switches, on their routers, say 30 years ago, 25, 30 years ago. And what NetFlow would do, it would show you where your traffic was going from point A to point B so you could figure out your traffic flows. Fast forward 25, 30 years, AWS has something that looks just like NetFlow. They call it VPC flow logs. All your cloud providers do. And basically, it's going to give you information about the traffic going into your system and the traffic going out of your system. You can tie some of this stuff into your SIEM systems from a security perspective to try to correlate certain things. But also understanding where your traffic is going in and out can help you with a lot. It can help you size your applications, considering your network capacity planning, determine server sizing, but here's what else it can do. It can help you figure out when you broke something with your security. You create an overly restrictive access control list, network access control list, I promise you're going to break something. If you're not careful, you create an overly restrictive security group trying to lock systems down, chances are you could break something if you don't know what you're doing. And determining where the traffic is going in and out of your systems and where it gets blocked is a wonderful opportunity for you to fix things that are broken before they become very, very broken. So what are you really doing? You're basically specifying the resource which you want to create the flow for, log for. You're going to tell it the kind of traffic you want. Do you want it to capture rejected traffic, like something that was blocked by your access control list or your security group? Do you want it to tell you the traffic that got through, or do you want to know all about all of that? Personally, I want to know about all of it. You have to tell it the destinations where you don't push the flow log traffic. Do you want to send it to an S3 bucket, for example? Where do you want to send it? So at the end of the day, what's this really going to look like? It's going to look something like this. You can see where the data is coming from. The count number is hidden here. The elastic network interface where we're learning it is here. The source address where it's coming from. The destination address, note it's a private address. You can see the port number. You can see the IP protocol that's used, the number of packets that are there, and the start and time. Note the first line is rejected. Something blocked somewhere, maybe an access control list or a security group. Second packet is accepted. The next two are rejected. So if you're not able to reach something, you're seeing all these things that are rejected in your VPC flow logs, chances are you configured something that you didn't really necessarily want to. So kind of keep that in the back of your mind. So these are typically what we're talking about with regards to VPC flow logs. I'm going to talk a little bit about virtual private networks. And there's going to be a lot of different ones. And I believe, Benedict, this is you on the virtual private networks after the beginning. I think I introduced it and you get into the security, but if not, I am happy to continue. Benedict, just let me know in the box. Pretty sure when we get to VPN security, it's you. So Mo had talked about some other types of VPNs. And a VPN, in all honesty, is when you take a public network and you create a private network. There's a lot of VPNs. This is not new. You know, the ISDN networks, honestly, they created these little circuit switch patterns that we used years ago. You were getting a private line or a private connection or a private DS0 inside of a bunch of switches. It was a virtual private network. We had frame relay. They had these switched virtual connections. You didn't own the frame relay switches. It was a VPN. Then we had ATM, and we switched via cells. But again, it was a permanent virtual circuits or switched virtual circuits. Again, it was through a public network. That was a VPN. When you connect to AWS on a direct connection, and you send them a VLAN, and they segregate your traffic from everybody else's traffic based upon an 802.1q tag, it's a VPN. Now, when you connect with multi-protocol BGP and an MPLS-based VPN, and you've got virtual routing and forwarding instances, that's a layer 3 VPN. So lots of VPN technologies to talk about. But in this particular case, when we talk about VPNs, we're typically talking about IPsec tunnels and traditional what you would think of as VPNs. When you access your work at work, you access your office remotely from work, chances are you're connecting to an IPsec VPN. Potentially, you could be using a TLS VPN, which does work, but there's advantages and disadvantages to IPsec VPNs versus TLS VPNs, specifically as you can look at the flows of the data. So why on earth do we need to create this VPN? Well, think about it. The internet's not secure. So I want to go from point A to point B, and I know we talked about VGWs, but we're just talking a little bit about VPNs here. If we don't encrypt the data, it's not going to be secure. Now, what are we getting out of IPsec? We're getting actually a lot. We're getting three things. We're getting confidentiality, meaning people can't see the data. We're being able to authenticate the users and determine who the user is and who they claim to be. And we're being able to make sure that the person didn't send it. So, for example, Benedict's on the other side of this thing. I want to send a message to Benedict. I really want to know that Benedict is actually Benedict, as opposed to Hallie the hacker pretending to be Benedict, where I'd connect to Hallie the hacker instead of Benedict, and I'm giving information to Hallie the hacker instead of Benedict. That's called the man-in-the-middle attack on cybersecurity. With IPsec, we've got endpoint verification. We can make sure that we know who is whom. So I am connected to Benedict on the other end, not Hallie the hacker. Now, anytime we run encryption, we typically use a hashing protocol. And the hashing protocol basically runs a mathematical hash on our data. And anytime we put our data into a hash, it should come out the same on both sides. Put the letter A into a 256-bit hash, get a 256-bit response, etc. But you can't go from the 256 response back to the letter A. So by hashing the data and coming up with a mathematical hash, when I want to send some information to Benedict, I hash my data, part of my IPsec protocol, and Benedict knows that the message hasn't been changed. How important is this? Well, imagine a doctor that prescribed a medication and the medication dosage was changed by 10 times or 100 times along the way. Or when you tried to deposit $1,000 in the bank, somebody else stole it and they put a penny in your bank account instead. So that's the integrity that we're talking about. The last part of the IPsec protocol is something called non-repudiation, which means that I can't say that I didn't send it because there's a sequence number. Message 1, message 2, message 3, that sort of thing. I hope that makes sense. Benedict talked about the other reasons we're going to be using a VPN earlier. And why are they? He mentioned we can't put private addresses through the public internet. That would be another one. What if we had to push IP multicast across the internet, like Mo was just talking about? These are the reasons we're using VPNs: privacy and integrity. Now, Benedict, is this yours at this point? If so, I'll turn it to you. If not, I will continue to go. Okay, let's go. Benedict, let's turn this over to you for 90 seconds. Please do that with you.
Thank you. Thank you very much, Mike, for introducing the concept of VPNs. So now I want to talk about VPN security. How do we maintain security of our VPNs in the AWS cloud? Now, first of all, we have to understand that security is a shared responsibility when we talk about cloud technology. So there's that part of security that concerns AWS, and there's the other part of security that concerns the subscribers to the service, right? So VPN security is all about protecting the data that is traversing the VPN, and then creating policies to define who can modify, create, and monitor VPNs as well. All right. So imagine if an unauthorized user was able to gain access to your infrastructure and create a VPN endpoint, and then goes back home and sets up a router or a firewall on his end so that he could connect via VPN to your infrastructure. That would be very risky, right? So for VPN security, we want to have strong identity and access management policies that will define who has access to creating VPNs, modifying them, and going through the logs. So in essence, what we're doing is we're trying to enforce identification, authentication, authorization, and accounting. So VPNs use the Ipsec protocol to encrypt traffic that is flowing through the through the tunnel to the destined location. The VPN provides confidentiality and integrity. How does it provide confidentiality? It encrypts the data in the VPN tunnel with a private key known only to the user, so that if it were intercepted over the internet, the threat actor would not be able to decipher the contents of the VPN tunnel. With regards to integrity, it hashes data that is flowing through it with a hashing algorithm, so that it can be authenticated at the other end when it gets to its destination. Because a hash is a one-way function and non-reversible, you can always tell if the contents of the data have been manipulated at the under end when you run the hashing algorithm and then you see the results. So it's also very important for us to monitor our VPN traffic and log traffic as well. I'm sure you're aware that there are some intrusion prevention attacks that can be encrypted, right? So when you notice anomalies in the VPN traffic, it could be a pointer that something is wrong. For example, if you set up your VPN for access from the 10.0 network to the web server, and all of a sudden you see VPN traffic going to the database server instead, it could be a pointer that there could be something going on with your VPN infrastructure, and that's something that you want to check and make sure it's all clean and good.
I think we have some audio issues over there going on right now. A little bit of a tech issue going on. Benedict, while we get your audio straightened out, I'll take over in the short term. Chris will work with you in the back end on that audio piece. So going through this together, the reason that we're using IPsec is we're going to get through those security challenges. I really want you to think of the internet as a terrifyingly scary place. I want you to think about the need to do that encryption, as Benedict mentioned, the authentication of the peer. And this is going to be done with an internet key exchange to determine who is on each side. Benedict mentioned the hashing for message integrity, and we mentioned the non-repudiation, which is you can't say after the fact that you did something. So next, let's talk about VPN advantages. It is so easy to get a VPN set up, and here's what I mean. Do you have internet access at your house? Chances are you do. How many hotels do you go to where there's internet access? Coffee shops where you go to where there's internet access. There's almost internet access everywhere. It's fairly ubiquitous. Even my happy village in Greece, and there's not a lot of people in there, there is internet access everywhere. So as long as you have internet access and the end of what you're going to connect to has internet access, you can set up a VPN. Now, will that VPN perform well? Who knows, based upon the performance of the internet, because there's no guarantees. But keep that in the back of your mind. Now, if I needed a private line, and we'll be getting into private lines, we'll call them direct connections. Azure would call them Azure would call them express routes. Google would call them a direct interconnect. In this particular situation, we could use a private line, but private lines, we have to get them. So I want a private line. I call my phone provider. If my phone provider creates the connection, and 3 weeks later, 4 weeks later, I can get my private line. VPN. I've got internet access. Cloud providers on the internet. A couple of configuration commands, and we'll keep it for the back of your mind. Simple, simple, and effective. So let's talk about the disadvantages of the VPN. There's no guarantee on the internet. And since there's no guarantees, we can't guarantee performance. We can't guarantee bandwidth. We can't guarantee that our traffic's going to get there. We can't guarantee latency. We can't guarantee what all those internet service providers along the way are doing. And there's no guarantee. So once your data gets on the internet, it's best effort versus a private line. I think Benedict's issues are back. So Benedict, I think you've got things taken care of on your end, and I'd love to go back to you.
All right, thanks, Mike. So let's talk about accelerated site-to-site VPNs now. Mike just mentioned that one of the drawbacks for VPN is that it's going over the internet, right? So there's no guaranteed bandwidth. You're constantly struggling with other users for traffic over the internet because it's not a dedicated link, right? Now, AWS has kind of a solution for that, or if I say a mini solution, and it's called the accelerated site-to-site VPN. And what's happening here is that it takes advantage of edge computing to route VPN traffic to the AWS global backbone, right? So it improves the performance of routing traffic through the AWS global network. Now, how does this work? So ideally, if you have a VPN connection between your data center and the cloud, and you do a trace route to see the path that your data takes from your office to AWS, you see that it goes over a number of hops, right? And this hop represents routers, firewalls of different service providers. And because you have different latencies, it creates a sort of bottleneck from your organization to the cloud. Now, what happens in the accelerated site-to-site VPN is that your traffic is routed to the closest AWS edge location so that it does not traverse multiple hops across different service providers to the cloud. So you have from your office, it goes through your primary um, service provider and onto the AWS edge location, then to the global backbone network, which is congestion free and which will help to improve the speed of the VPN connection. So it provides some improvement in VPN connectivity and traffic engineering for end users. So this provides a workaround to the inconsistent performance of VPNs, although it's not still comparable to a private link, or if you like, a direct connection to the cloud. And how do you set up an accelerated site-to-site VPN? It's just a box you check when you're configuring your site-to-site VPN, saying you want to use the accelerated site-to-site VPN, and of course, the cost implications for that. Now let's talk about network encryption options available on AWS. Earlier, Mo talked about SSL and TLS encryption and the important role it plays in protecting data, especially in transit, right? Data on the move. Now, there are encryption options available in AWS to help you enforce confidentiality on your data. TLS or Transport Layer Security, which succeeded SSL, is an encryption protocol that we use to secure data in transit. So it's also used for protocols such as FTP, where you're transferring a large file from one location to the other. So FTP is the insecure version. And then when you add TLS to it, it becomes FTPS, which is secure FTP. And SFTP is another protocol that uses TLS encryption. Secure SMTP, which is SMTPS. These are protocols that employ TLS encryption to protect your data on the move. And these options are available in the AWS infrastructure. Now, the AWS Certificate Manager is another service that you can use to enforce encryption in the cloud. And how does this work? The Certificate Manager allows you to generate and manage TLS or SSL stroke TLS certificates in your AWS infrastructure. Now, ideally, if this service was not available in the cloud, you would have to go to public providers such as GoDaddy, purchase a certificate of them, import it to your AWS infrastructure, and then install it on your application, your web applications, or your database applications, or as it were, right? But AWS has something in-house, which is a certificate manager that you can use to generate these certificates and then apply it to your services as required. Another encryption option is the AWS Key Management Service, which is used to manage the keys associated with your certificates. So we have, I know Mo also mentioned a bit of the public key infrastructure, private and public keys. You need a service that can help you, generate these keys and manage them. The AWS Key Management Service, or if you like, the KMS service, allows you to manage your keys associated with your certificates. Now, applications such as the Elastic Load Balancer, Cloud Front, and different gateways support TLS encryption from traffic that is flowing through them. So if you have a load balancer, for example, you could do what we call TLS offloading or inspection by the load balancer, so that traffic passing through them is encrypted before it gets to the backend server, because that feature is available in the AWS infrastructure. How about the network firewalls? They also employ SSL TLS encryption, and they need this service so that they are able to decrypt encrypted traffic that is coming through the firewall. So you could, there's a DNS attack where you could hide a malicious code in a DNS packet, and then send it through the firewall. And because that code is encrypted, it could go unnoticed if there was no firewall in place. But the firewall can use the SSL TLS decryption to inspect this encrypted traffic that is flowing through it and help you to keep your services safe and secure. So we'll talk about more encryption options available in AWS. Of course, we've spoken about the virtual private network. Now we have two kinds broadly: the site-to-site VPNs and remote access VPNs, or if you like, the client VPN, as AWS calls it. Now they use the protocol Ipsec to encrypt the traffic that is flowing through them, so they keep it safe and secure from eavesdropping, right? Client VPN is a bit different, right, from site-to-site VPNs, although there are some solutions that allow you to use Ipsec, the Ipsec protocol on client VPNs. In such situations, you have to do it in software. So you'll be using maybe a software like 40 clients to implement the Ipsec VPN, even if it's a remote access VPN, right? But ideally, the remote access VPNs or the client VPNs supports OpenVPN, right? Which is an open source software that they use to secure communications from the end user to the AWS cloud. Another network encryption option available on AWS is the AWS Transit Gateway, which Mo spoke about earlier. So you see that you are able to create IPsec tunnels from your branch locations to the transit gateway, so that you have some form of protection from the traffic from your branch locations to the other locations, right? So it uses IPsec encryption to secure this traffic. How about your direct connection or your private link? Now you would ask, it's a private link from your office to the cloud, right? It's a logical wire. Why do you need protection? Well, if you're employing a security in-depth policy, you want to trust no one, right? So even though it's ideally a private link or a secure connection from your office to the AWS cloud, you can still run IPsec, VPN over the direct connection. So that's also another option available for network encryption in the AWS cloud. Now, we've been talking about data in transit. How about data at rest? Now, data at rest refers to that data which is stored in your drives, your S3 buckets, and so on and so forth, right? We have some options available in AWS to help you encrypt data at rest, so that if that infrastructure were compromised, the end user, the threat actor, would not be able to decipher the information, and it's useless to him. So it gives us that extra level of defense, as it were. Now, when it comes to data at rest, there are two concepts which are usually discussed. We have the server-side encryption and the client-side encryption, right? So what happens when you're doing server-side encryption is that you're encrypting the data on the server side. So in this case, you're encrypting the data on your S3 buckets, for example, right? For client-side encryption, you're encrypting the data on your endpoint, could be your PC or a server. You're encrypting it before you send it maybe to an S3 bucket. So it's like adding an extra layer of security for your transfer of data from your endpoints to your storage locations. For S3 buckets, they have what is called the server-side encryption with Amazon S3 managed keys, or if you like, just share my screen here. So they have what they call the SSE-S3, which is basically server-side encryption, and is the default encryption method for Amazon S3 buckets, right? Now you have what you have. You encrypt your data with private keys, right? And you have the option to generate your keys in AWS and then encrypt the data, or generate it on-prem. Maybe your security policy has defined that you have to generate your keys in-house and not on the cloud. But you could import the keys and then use it to encrypt your data on the cloud. So those options are available. You have the server-side encryption with the AWS Key Management Service. So in this case, you are using the key management service in AWS to generate your key and then encrypt the data on your storage, your S3 buckets in this case, right? You also have another encryption option called the dual layer server-side encryption with AWS keys. Now, where is this applicable? Let's say in your organization, you have a policy that says you have to encrypt 2 times. You have to do, you can't just say, we're not comfortable with encrypting once. The dual layered server-side encryption allows you to encrypt data 2 layers in the cloud. So it gives you that extra layer of security. And then you use the key generated from your key management service to encrypt the data. That's why you have it called the dual layer server-side encryption with the AWS KMS. Then you have another option called the server-side encryption with customer provided keys. And this was what I talked about earlier. You could generate your keys on-prem, import it to the cloud, and then use those keys to encrypt the data on your storage, your server, right? So that will be the third option there, which is a server-side encryption with customer provided keys. And then I mentioned client-side encryption, where you're basically encrypting data on your endpoint before sending it over the infrastructure, right, to your S3 bucket, right? So the traffic is encrypted end to end, so AWS cannot see that traffic as it traverses its network to the destination. And it's usually implemented by downloading an Amazon encryption client to your endpoint, installing it, and it does the encryption before you move the traffic to the cloud. So let's talk about implementing network encryption methods to meet application compliance requirements. Now, so for many organizations, they have requirements. So if you're a financial organization, you have PCI DSS compliance requirements. If you work in a hospital, you have PHI requirements. If you serve customers in Europe, you have GDPR requirements, right? AWS has some solutions to help you meet these compliance requirements for your organizations, right? The first of them is the KMS encryption. So the KMS, Key Management Service, is a managed service that allows you to manage your keys, your private keys, right? It is integrated into services such as the S3 buckets, your relational database service, and your EBS volumes as well, right? So that you can just implement the encryption directly from those applications when you're working on them. Now, the Amazon Relational Database Service, RD, or if you like RDS, also has an encryption option available. So if you're if the IT governance personnel in your organization was concerned about encrypting data in the database on the cloud, there's a solution, and it provides server-side encryption for encrypting data at rest. So it allows you to use server-side encryption with the key management service provided by AWS. So what it means that you generate your keys for the key management service, and then use those keys to encrypt the data in your relational database in the cloud. And of course, we mentioned the S3 as well, Amazon S3, right? So it has those encryption options, dual layer, server-side encryption with Amazon keys, and then server-side encryption with customer provided keys. We also mentioned earlier the AWS Certificate Manager, which allows you to generate and manage your SSL certificates. So, like I said earlier, it saves you that bit of going to a public provider such as GoDaddy to generate a certificate, purchase it, and then import it to your cloud. You could just do everything, manage the whole service from the AWS Certificate Manager. And it's integrated with services such as EC2 instances, so that you could just import a certificate and use it on your various applications in your virtual machines on the cloud. Now, there's also what we call the hardware security module, and it's a very important piece of hardware because it helps you to manage your encryption keys and perform operations on them, such as key rotation, deletion of keys, and stuff like that. And in some organizations, you find that it is contained in their security policy that they must manage all their keys with a hardware security module, right? Or if you like, a HSM. So is that not a problem for an organization trying to host resources on the cloud? Well, there's a solution. AWS has what's called the Cloud Hardware Security Module, or the Cloud HSM, which allows customers to manage their keys and perform those operations I talked about, such as key rotations and the rest of them. So if it's required by PCI DSS that you must use a hardware security module, well, AWS has it, the Cloud HSM. So there's no need to panic. Okay.
You know, Benedict, that might be actually a great time to end for the day. I'll show an encapsulation photo, and then tomorrow we can have fun and we can talk about high availability VPNs, and then we get into direct connection. You have to excuse me. I love anything with tech. I love anything related to networking, and I don't, as an architect, I focus on the business, so it's very rare that I get to get geeky like this. So for me, this is fun. Now, I promised a lot of you guys that I would show you encapsulation from my perspective. So I have a slide that I made for you that's going to show you encapsulation. So in order for you to understand my model, and Chris, if you can share my screen I'll share my screen real quick. So in order to understand my model over here, let's say in this particular case, I don't know what just happened there. In this particular case, I wanted to go into a building, and that building didn't allow cats. Well, I could just put the cat in the bag, close the bag, go in the building with the cat, and nobody'd be the wiser. So this is typically encapsulation. You put something into something else. No cats allowed? No worries. We'll put the cat in the bag. Now, bring it back to one other kind of concept. We also deal with containers in cloud computing, right? What is a container? It's like a VLAN, honestly, where you take in information, you put it in a containerized environment where it's separate from everything else. It's a form of encapsulation. Guess what? Here's another form of encapsulation. You put a cat in a basket, and the cat is now encapsulated. That is now separate or segregated from everything else in the room. So, not to do too many Cindy photos, but I wouldn't be me if there wasn't at least one cat photo coming somewhere. But honestly, I hope that explains what encapsulation is. Not allowed to bring your cat with you. Put your cat in a bag, carry the bag. Don't let anybody see what's inside the bag. It's encapsulation. With encryption, we could have envelope encapsulation where we totally encrypt the entire thing. We could just have encapsulation where we put something in another packet, but now you know what is encapsulation.
So in your example, would that be encapsulation?
It's encapsulation, absolutely. While we're
Sorry, I couldn't help it.
That would be encapsulation. That is a great way to do it. So I don't know about y'all. I had some fun. Maybe you guys, if you had a good time, can like the video, subscribe to our channel, hit the bell to be notified. Send these videos to someone else that may have missed it, because we want to know that you guys get as much education as we possibly can. So if you hadn't gotten our labs, please download them. They're free. There's about a day and a half's worth now. We're going to have close to 2 days by the time this is done. Labs on AWS, labs in the data center, labs on networking is good. And we're going to take some questions too. But I just wanted to make sure you all knew that. So we're going to do some questions, whatever questions you guys have, a little bit of them. Then we'll finish for the day. We'll come back tomorrow, and we'll have all kinds of fun on this AWS Advanced Networking course to prepare you for the ANS-C01 exam. And this is our full AWS Networking Specialty Course. So let's see if you have got any kind of question. From Mohammed over there in Somalia. I know where you're at, Mohammed. It's always good to see you. With Transit Gateway, Ipsec VPN, and accelerator to connect by the nearest edge location by the client. I'm not 100% sure I understand exactly what the question is or the comment is. Do either you get that, Benedict or Mo?
I'm not
Okay.
really sure what he's asking, but
So I think I understand what he's trying to say. So what he's asking is a transit gateway IPsec VPN and accelerator to connect site by the nearest edge location. Yeah. So there's a feature on AWS. I think what you're referring to is the feature within AWS Transit Gateways where you can use basically the global accelerator infrastructure in order to speed up your IPsec connections. Yes, that's a possible solution you can use within a transit gateway, not with a virtual private gateway though. Only a transit gateway. I hope that answers your question. It's more of I think a statement than a question because I agree. But yeah.
I wasn't sure. I know Mohammed. He's very smart, but sometimes, in a chat box, you're limited on what you can communicate. Sunday, you said we are awesome. Thank you so much, Sunday. We really are happy to be here and happy to help. Alex, thanks so much for this great session. Alex, thank you for being here. Sunday, you're more than welcome. We're thrilled to be here. Mike, I am giving you guys ideas how to get in trouble with cats where cats are prohibited. I like my cat. I try to bring my cat with me everywhere. And Ken or Grant, you are more than welcome. You're more than welcome. We look forward to seeing you tomorrow. The cat made me out. I'm the plan will fail. Ed, you are totally right. In fact, when I brought this cat home, it was to surprise my wife. And I called home and I'm like, hi, dear. How are you, love? And all she hears is, meow, meow. And she says, is there a cat with you? I'm like, I don't know. And then it never stopped. So, yep, my plan failed very quickly. It was not a big surprise. So, Joseph, these are not downloads. These are things that you can attach in our content management platform. It is there, and they will be available as long as they are current and running. So 6 months from now, a year from now, you should still be able to access them. 2 years from now, we want to make sure you have access to it. Saad, thank you, team. You guys are geeky and great session. Thank you so much. You're going to be awake in the next two nights ascending from Sydney, Australia. Prasad, I've attended U.S. things from Sydney, Australia, and thank you. I'm flattered you're here. I've also done it I've spent a lot of time in Brisbane as well and Melbourne where I got a lot of good Greek food, but Sydney's a beautiful place, so sounds great. Will we expand Cloud WAN?
Well, Cloud WAN is, I think it's its own topic. It's not part of the AWS exam. So that's really up to Mike and Chris. I'm not sure if we have time to cover it, honestly. But, if we have time at the end, then I guess we can.
Yeah, if we have time at the end, we can try it towards Sunday.
Yeah. Yeah, I would love to explain it. It's one of my preferred topics.
Okay. So, I want to thank you all for attending. I had fun with you guys. Hope you guys had fun. We will be back at 10 a.m. Eastern time tomorrow. All bright-eyed and bushy-tailed. The whole Go Cloud Careers gang, which is the three of us. There's a team of people behind the scenes. Mark's doing stuff to create content for you guys behind the scenes. We got lots of people behind the scenes, trying to work with questions and things like that. So guess what? You know what we're going to do next month for y'all? We're going to have a completely free AWS Solutions Architect Associate Bootcamp. What we do is we train careers, we train architects in our paid programs, but I don't believe and we get good results for it, but I don't believe anybody should ever have to pay for certification training. So we're going to have a very nice AWS Solutions Architect Associate Bootcamp coming at the end of the month as well. We'll give you sign-up forms that you can sign up to. So I want to thank Mo for sharing his many years of wisdom. I want to thank Benedict for sharing his many years of wisdom with you all. Thank you all for being here. And give me a hashtag, AWS Advanced Networking, and we'll see you all tomorrow. Take care, everyone. So nice to see you.
Thank you. Have a good day.
Welcome back, everyone. This is Michael Gibbs, and I'm here with Benedict and Mo for day 2 of our AWS Advanced Networking course. This is to prepare you for the ANS-C01 exam, and it's a full AWS Networking Specialty Course. If you haven't joined us yesterday, that's okay. You can go back and watch the day 1, the first video, and the second video. They're going to be here on YouTube for you. And today we're going to begin day 2, starting with Benedict in a few moments. I want to know that you're here. I want to know that you're awake. So if you give me a hashtag AWS Advanced Networking for me to know that you're here, I'll be thrilled to know that you are here. Also, I want to let you know that we have a tremendous number of free labs that we've created for you, some on Amazon and some off of Amazon, actually done in our data center. And why do we do this? We want to make sure that you not only understand how to configure it on Amazon, that's the easy thing, but you actually understand what's going on under the hood. And since what cloud computing really means is you can't see what's going on in somebody else's network in a data center, we did it in our data center, or at least on an EVE-NG server, to make sure you can see the underlying network technology. So you can learn it the AWS way, you can learn it the real way, and by the combination together, you're going to get there. So go download it. It's completely free in the AWS Advanced Networking Bootcamp. And of course, in the description of this video, we've got a tremendous number of free things for you to help build your cloud architect career, cloud network architect career, enterprise architect career, AI architect career. So go download some free things. The format of today will be just like yesterday. Well, we'll go for a few hours this morning. We'll take a 1-hour break, then we'll have a lunch, and we'll come back and we'll have another break. And like yesterday, we got pretty geeky, which was for me fun on the networking side. Mo and Benedict got extra geeky for you. I kind of loved watching them do it. Of course, you know, I love networking, so there's that. So I'm going to turn it over to Benedict. If you haven't liked the video, please give it a like. It'll signal the algorithm to send other people here so they can benefit from our free AWS Advanced Networking training. Hit the bell, share it. We put a lot of time, effort, and money into developing content like this to help those in need. So please go for it. Please get it, and please share. At this point, I'm going to give it back to Benedict, and he's going to continue the discussion on virtual private networks in the AWS cloud.
All right, thanks, Mike, and welcome again, everyone. Yesterday, we began the discussion on virtual private networks, or VPNs, if you like. And we spoke about how VPNs can provide confidentiality by encrypting data in a tunnel, right? We also mentioned that VPNs can provide integrity by hashing the data in this tunnel with a hashing algorithm, right? We spoke about how VPNs provide non-repudiation and authentication as well, because if you encrypt data with your private key, which is known only to you, then the receiver is guaranteed that that data has come from only you, because of course you're the only person who has access to your private keys. Today we're going to talk about another important concept, which is availability, and how AWS provides this in the cloud. Right now, the virtual private gateway where your VPNs terminate is a highly available device, which means it is redundant. So when you set up your VPN connections from your on-premise locations or from your remote locations to the AWS cloud infrastructure, it automatically sets up 2 VPN endpoints on its end to provide this availability. So it puts these different VPN endpoints in 2 different availability zones, so that if there's a maintenance ongoing in one availability zone and that takes down that leg of the VPN connection, you still have another one available to keep your connectivity up, right? So it's pretty important that they've taken this into consideration and built it into their solution. Now, when it comes to redundancy, right? Having two links from the AWS end to your office or your remote location. You could either have a active passive solution, right, or active active. And in active passive, what's happening is that one link is active all the time and your traffic is flowing across that VPN connection. The other VPN connection is passive, which means it's just lying in wait and then praying that the primary link should fail so that it takes over and begins to send traffic. No, I'm just joking. But for the active VPN solution, you have traffic flowing across both VPN links from these different VPN endpoints in different availability zones at the same time. But we have to be careful because when you have active solutions, there's the risk of having asymmetric routing. And what asymmetric routing is that traffic goes out one VPN link and then the return traffic comes back the other VPN link. And we don't want that in our routing because it could be problematic, right? But you could use your BGP to, enforce symmetric routing so that the traffic comes over one link returns via that same link at all points in time. So I'll just share my screen and show you how the virtual private gateway enforces this high availability in the cloud. So Chris, could you just share my screen briefly? All right, so you see what we have here. We have a VPC and we have a virtual private gateway where your VPN, your site-to-site VPNs will terminate, right? So when you set up your VPN connections from your corporate offices to your the cloud, it's set up two VPN endpoints in different availability zones, right? And then you could decide if you want to do active, passive, or active, active, right? So it's a fairly simple process. And the next diagram here, we're looking at how BGP prevents asymmetric routing. So recall, I said asymmetric routing is a situation whereby you send traffic out one link and then it comes back via the other link. We don't want that because we might get out of order packets, right? So in order to circumvent this, we can use BGP to detect that the traffic going over one particular VPN link should come back via that same VPN link and not the other. And we do this by manipulating metrics such as local preference, the weights, and the AS path. So if you look at this diagram, you see that the top link for the 172.16.0 network just has one AS path, right? Compared to the bottom link where the 10.0 network has two AS paths. So what it means is that traffic destined for the 172.16.0 network will always go via the top link because it has a shorter path, right? And then the return traffic always come back via that link. And then if we look at the metric, for example, let's assume we're using local preference, right? And the bottom link has a higher local preference for the 10.0 network, right? So it means that that link will be preferred for the 10.0 network for to and return traffic at all times. So that prevents asymmetric routing in a highly available VPN solution. What would it do without BGP? Now, if you recall, we said that the VPN and the virtual private gateway is a highly available device. So when you set up a VPN, it sets up 2 VPN endpoints in the cloud as opposed to one, so that if one goes offline, if you were to lose connectivity on one of them, you still have a backup VPN connection. But if you look at the other end of your remote connectivity here, you see that they have just one device. Could be a router or the firewall, where they terminate their own end of the site-to-site VPN. So could we say that this is a truly highly available solution? Chris, could you please share my screen? All right, thank you. So you can see that the AWS side of things has handled high availability by deploying 2 VPN endpoints, right? So that if one goes offline, the other one takes over. How about your own side of the connection? There's just one router there. And so this is a bottleneck. For a truly highly available system, you need to have 2 devices instead of one. So what that means is that we are going to have another router here and then connect the second VPN endpoint to this router. So that if one of the link goes offline, you still have your connectivity across the other customer premises equipment. Now, let's talk about load sharing across VPN tunnels. So many people usually get this concept wrong when we talk about load sharing, and especially for people who are not so experienced in networking. So when you talk about load sharing, the first thing that comes to mind is the load balancer, right? When it comes to load sharing of links, we do not use a load balancer to achieve this. What we use is a routing protocol to load share across both links, right? And in this case, since we are connecting to the cloud externally, we're going to be using BGP to load share across 2 links if we are running an active solution. So AWS allows you to load share, right? They make that possibility available for you so that you can get the best of both links, and not that one is always lying in wait for the other one to fill. So we set up load sharing essentially to prevent out of order packets, right? So what is happening here is that BGP will advertise the routes into BGP for our different subnets. And this is where your knowledge of subnetting comes into place, because you're going to be advertising a specific route, right, or route across one link and a less specific route across the other one or both links. So what that means is that if you have a large subnet such as 10.0.0.0/8, and then you've done your subnetting and you've broken that subnet into smaller ones, so you also have 10.0.1.0.0/16. Here is the more specific route because it's contained within the larger route, the larger subnet 10.0.0.8. So what you do is that you advertise the more specific route, which is 10.1.0/16, across one link, right? And then you advertise the the larger route, the 10.0/8 subnet across both links. So it's using it, the way it works is that the BGP will look for the more specific route and send traffic across that route first, right? And then if that VPN tunnel goes offline, or it's there's a problem with that connection, either from the customer side or from AWS side of things, you still have a redundant path that has the more encompassing subnet, the 10.0/8 subnet. And I'll show you the diagram to make you understand this better. So you advertise the specific routes across one VPN tunnel, and there's the summary route to be advertised across both tunnels, right? So the BGP will send the traffic across the specific routes, and then if that VPN link goes offline, there's still a redundant path, right? So we have to be careful when we're setting this up so that we prevent asymmetric routing in our solution. And so I'll share my screen here to throw more light on what I've just explained. So in the diagram here, you see that we have on our on-premise side of things, we have a large subnet, right? 10.0.0/1, 10.0.0.1/15. And they've broken down this large subnet into two smaller subnets, 10.0.0/16 and then 10.1.0/16. So what it means is that these two subnets are contained within the larger subnet. Now, if I want the 10.1.0/16 traffic to flow across the top link, what I do is that I advertise that route on the top VPN connection. Now, this is a more specific route compared to the CIDR range of 10.0/15, right? So once I advertise that link up here, 10.1.0/16, I then go ahead and advertise the summary route, which is the CIDR range, right? 10.0/15 here. And it means that for traffic destined to or from the 10.1.0 network, to always use the top link, right? Now, if you take a look at the bottom link here, change my cursor. If you take a look at the bottom link here, we have the other subnet that has been added, advertised, which is 10.1, 10.0 subnet, right? Oh, sorry, 10.1.0 subnet. So it's been advertised here. It is a more specific route. You can see the subnet is a /16. And then the summary route, which is a /15, is also advertised here. So what it means is that traffic is always going to the 10.0.1/16 network across this link below, right? And then if this link fails, because you have a summary route up here, which is 10.0.1/15, and which contains the 10.0.1/16 here, the traffic will be routed via the top link, right? So this is how we load share across VPN tunnels using the BGP routing protocol. And then for the other side of the connection is the same thing. You advertise more specific routes across one link and advertise the less specific routes across the other link. Now, there are situations whereby you have multiple offices that need to connect to the cloud. And I know Mo spoke about using the Transit Gateway to achieve that yesterday. So there's another solution available to help you achieve this hub and spoke look and feel. And it's what we call the Cloud Hub. So Cloud Hub is an AWS solution that allows you to enable multi-site VPNs, right? So what happens is that Cloud Hub is actually working with the virtual private gateway. So you're going to have connections from your different locations to the virtual private gateway, right? And then you have eBGP advertising your routes from these different locations to the virtual private gateway, and then advertising those routes to other connected locations. So in this sense, the Cloud Hub is transitive because it allows one branch office to reach the other one via these eBGP advertisements, right? So essentially, it's the virtual gateway that works with Cloud Hub and enables you to, share routing information from branch locations to the other. So I'll just share my diagram here so you can see what I'm talking about. Could you share, please? Yeah. So we have a VPC here, and then you have your branch locations on the right, right? So these locations connect to the virtual private gateway via a VPN tunnel, and then they use eBGP to advertise their routes. So if you have this is a 10.0 network here, and then 192.168. I thought my handwriting would be better than Mo, but it seems I'm struggling here. But you get what I mean. And then you have 172.16 network here. You're going to be advertising this route into the BGP, and then these routes will be shared across your infrastructure so that all branches can reach it and reach your VPC as well, right? So you have to take care not to have overlapping subnets, right? Because that could provide a problem here. I mean, if you had the solution such as the Transit VPC that where you could do nothing, then you could get away with that. But here, you want to make sure that your subnets are unique across the branches so that there's no routing problem. Now let's talk about how to set up a VPN in AWS. It's a fairly simple process, especially when you compare it to a solution like the Direct Connect or your private line. So in order to set up a VPN in AWS, the first thing you have to do is to determine the AWS virtual private gateway you're going to connect to. So you have to go to your VPC and then set up a virtual private gateway, right? So it's a fairly simple process. Just set it up, give it an ASN number, and you're good to go. Then you choose a routing method that you're going to use for your VPN connectivity. And there are generally two methods, using static routes or dynamic routes. So using static routes is probably simpler and not so experienced engineers will go for this option, right? So if you just want something very basic, yeah, you can use your static routes and you're good to go. Now, if you want to use dynamic routing for your VPN connectivity, it's going to be BGP, which is a little more complex. So has to be an experienced cloud engineer or network engineer making these configurations. So after you've chosen your routing method, you then go to your tunnel configurations. And AWS has some default tunnel configurations. So when we talk about tunnel configurations, we're talking of things like the encryption algorithm, AES 256, and the likes. Talking about the hashing algorithm, SHA, and the likes. So AWS has a default one you could use. You could also customize it based on your wants. So many organizations would have a defined policy saying you should always use maybe AES 256, SHA 128, for example, for your VPN connections. So in that case, if the AWS defaults did not meet that criteria, then you can go in and make your custom tunnel configurations. So after you do these configurations on the cloud, right, the virtual private gateway will be automatically configured based on these parameters, right? The AWS console, management console, will also auto create a configuration guide for your endpoint device. So you could say use this configuration on your device if it's a Cisco router or firewall, or use this particular one if it's a Sophos or FortiGate firewall or Palo Alto firewall. So it has that support for different vendors just to make your setup fairly easy to accomplish. Now, when it comes to monitoring of VPN traffic, you could use CloudWatch, right, to monitor your VPN traffic. Monitor your VPN tunnels so you know when they go up and down, and see bandwidth, usage, and stuff like that. You could also monitor from your on-premise end or from your remote end, in this case. And usually that will be the dashboard on your firewall or your SIEM solution if you want, right? So these are different ways that we can monitor VPN connectivity from remote locations to the cloud. And it's important that you monitor VPN connectivity because every now and then, especially if you have budget constraints, you have issues with bandwidth usage in an organization. So at some point in time, people will complain that the VPN is slow. At some other points, it's fine. So monitoring the VPN can indicate when there's more usage across the VPN tunnels and then point you towards the right direction into solving such problems. Now, we've spoken about the VPN solution in AWS. Is it possible to have a custom VPN solution in AWS? Yes, it is. So you could have your organization say that the only acceptable VPN solution is the one on the Palo Alto firewall. We're not going to use any other one, right? Or your Cisco firewall, whether it's on the cloud or is on-prem. That's our standard. So AWS has the capability for you to customize your VPN. And what it means is that you go to the marketplace, the AWS marketplace, to look for a VPN solution of your choice, right? So, for example, if I want to deploy a VPN solution on the FortiGate firewall, I'll just go to the marketplace in AWS and search for the FortiGate firewall, and then deploy that firewall in my infrastructure, and then terminate my VPN connections there. So it essentially becomes a VPN concentrator, right? And how this works is that it's actually a virtual machine in the cloud where the VPN software is installed on. So the FortiGate firewall is basically virtualized in the cloud, right? So it's an EC2 instance that has FortiGate operating system running on it, right? And you could do that for Palo Alto, Cisco, and a whole lot of other vendors, right? So you have that capability to customize your VPN solutions in the cloud. So you have to take note that when you are going in this direction, there will be license requirements from the vendor you're patronizing, right? And so you have to be ready to take care of all of this and pay the required license and subscription fees. Now let's talk about remote access VPN, which is popularly called client VPN in AWS and in some on-premise locations as well. So you can set up your VPNs to allow individuals remotely connect to your AWS infrastructure. So now we're not talking about remote offices connecting, right? And that will be a site-to-site VPN or remote partners connecting to your VPCs. We're talking about individuals connecting, okay? And it's very similar to the way it's done on-prem, right? So you have a VPN concentrator, could be a server, could be a router, could be a firewall, could be any device where you can just run that VPN software and then allow end users connect remotely. AWS allows remote access users to connect directly to it, but it does not use the virtual private gateway to achieve this. I mean, in the case of a site-to-site VPN, it uses the virtual private gateway to terminate those VPN connections, but it's quite different from remote access VPN. So to do this, like I said, you need a VPN concentrator in your AWS VPC. Could be a router or a firewall or a Windows server running Windows or Linux server running OpenVPN software that allows remote VPN connection. So there are quite a number of variety here when it comes to deploying remote access VPN in AWS. So if you look at the diagram here, you see how remote VPN differs from the site-to-site VPN. So you have your remote users here connecting directly to an instance in your cloud in your AWS infrastructure that is running that VPN software, right? You can see that there's no virtual private gateway in this diagram because the remote access VPNs do not work with the virtual private gateway. You just have your VPN concentrator. In this case, is a EC2 instance running a VPN software in the VPC, and then from this instance, you can now grant access to other resources within your VPC. So this is how the remote access VPNs work. Yep. So we're done with VPNs now. And we want to talk about direct connections to the cloud, right? So yesterday we looked at some disadvantages with running VPNs or establishing VPN connections to the cloud. And one of the disadvantages we discussed was the inconsistencies of the internet. So if you have a 1 gig link in your office, right, and you are connecting to AWS over a site-to-site VPN, there are certain times in the month where they need to patch Windows PCs and Windows servers. I think Microsoft releases Windows Update every second Tuesday of the month. So there'll be a process in place to patch all Windows PCs just to keep them secure at the endpoint level. So you'll find that in some organizations, if there's a constraint in bandwidth, right? During the time of patching PCs, for example, your site-to-site VPN to the AWS cloud will become slow. And so if someone is trying to copy a file to object storage at that same time, it begins to complain of slowness. It begins to see things like 48 hours left. The direct connection provides a solution for that, right? It's a guaranteed bandwidth link. So it's a dedicated link. It's a dedicated link, right? And before we really delve deeper into direct connection and how it works, I'd like to see if you have any questions on high availability VPNs that we just discussed about.
Welcome back, everyone. So Benedict talked about VPNs. He talked about some high availability VPNs. Starting to get into direct connections, which is something we're going to talk about next. But does anybody have any questions? From Tariq, why not use BGP attributes other than wait or local preference or AS path prepending to differentiate an active path versus a passive path? So there's a lot of ways we could do this, Tariq. We could have a more specific route on each side that we prefer to use and leak an aggregate route on both sides. We could modify the wait. We could AS path prepend. We could change the multi-exit discriminator. We could change the origin code. We could do a lot of things. So it really is about what is it we want to do and why are we doing it? AS path, is going to traverse, but other ASs, but wait is local and local preference is local. So we have to think about what we're trying to do, why we're trying to do it, and whether we're trying to influence others or basically influence our own decision. And then we make a choice, but we could use a lot of different options here. That was just one we chose. Who else?
Sammy says, how would you load share between two links when you have more than two subnets in your data center using BGP route summarization? Well, you can advertise 20 subnets in your BGP advertisements. It's not limited to two subnets when you're advertising. So that will work.
Absolutely. So let's assume, in your data center, you've got 1,000 subnets. Yeah, you can do a couple of things. One is you can't send all 1,000 to AWS. You could keep it in your IGP. But as Benedict said, you could create two supernets and then an aggregate route for all of it and send one supernet for a certain number of subnets on one link and another supernet for another set of subnets on that link. Or you could tune it and leak one specific thing. So lots of opportunities here, Sammy. Who else? Do we have any other questions there?
So Town Scott is asking, can the EC2 instances for the VPN concentrator be scaled? So you're asking about now, is this vertical scaling or horizontal? Generally speaking, when you have a customized VPN concentrator, such as the FortiGate firewall or Palo Alto firewall, right? When you're setting it up, you have the ability to choose whatever you know requirements you want to deploy for this particular situation, and then it's because it's a customized solution. The There's a limit to the flexibility of what you can do on this EC2 instance. Remember, you're subscribing to a FortiGate or a Palo Alto solution, and it's not you're not dealing with an EC2 instance that you have created on your own. So there's that limitation there.
Right. So we can play with the size of the instances, and they're all limited. For example, there's actually one provider of virtual firewalls and VPN concentrators, a major provider, that is a single-threaded application, so it can only run on a core. So even if we wanted to put it on the system with 128 cores, we can only use the single core anyway. And that type of application does better with higher CPU frequencies. But yeah, there's options, but it's limited, as Benedict was describing. Good questions.
So Felix is asking, you mentioned you set up 2 tunnels, right? Can you configure one with IPsec and the other with another protocol? Or is IPsec the most secure standard? Yeah, I mean, you could play around with these things, right? But generally speaking, you want to use IP security for your VPN connections because it's just the standard, right? It's been tested and trusted. So why would you want to use another standard?
Yeah, and there's basically your TLS option and your IPsec option. There's slight enhancement, and generally speaking, IPsec's a little bit more secure than TLS, even though they're both fairly secure. So why wouldn't you use the protocol that was perfectly designed for it? Unless you need some other kind of things, you could always generate your own kind of encryption for specific needs.
So does the virtual private gateway have the VPN concentrator functionality? Can you name some VPN concentrators? So remember I said that when you have your remote access VPNs, they do not work with the virtual private gateway, right? So it's your site-to-site VPNs that work with the virtual private gateway. So let's put that in perspective. Can I name some VPN concentrators? I'll name some solutions. You have FortiGate VPN, Cisco VPN, Palo Alto VPN, Open VPN. These are some VPN concentrators you can use.
Yeah, and if I understand it correctly, does the virtual gateway have a VPN concentrator functionality? It's a virtual VPN concentrator. So anytime you need to connect to a device to terminate your VPN, it's typically a VPN concentrator. But whether it's physical, whether it's virtual, kind of very similar in essence, the same thing.
Okay. Tariq is asking, can we use FQDN instead of IP on the client side for setting up a VPN on AWS? I remember AWS didn't have support for FQDN in the past. Not sure if it has changed recently. So if you're having an FQDN on your side of things, it means that you're going to create a DNS record in a global DNS record for that FQDN, so that the AWS side can reach that record on the internet. If there's no DNS record available, then FQDN will not work on the client side. So you have to keep that in at the back of your mind. Yeah, I think it supports it now. Mm-hmm. Name not found says when you use 2 VPN connections for redundancy, Why do you use only one tunnel of each as shown in drawing? So I talked about the problem of asymmetric routing, right? And that's a situation whereby you have two links going to a particular location. And then when you send traffic over one link, the return traffic comes back the other link. Now, we don't want that. We want a situation whereby you send traffic over one link and then the traffic comes back that same link. So it prevents out of other packets. So I was just illustrating the different connectivity types we have. If you're running an active solution, then you can send traffic out both links and then use BGP to prevent asymmetric routing. But if you're running a passive and active solution, you always want to run the traffic across one of the VPN links.
And name not found, there's another reason why this is different on a direct connection than a VPN. In a direct connection, if I buy two 10 gig links to AWS, I'm paying for 20 gigs. And in many cases, I'm going to want to load share on those two links to get my money's worth for these two 10 gig links that I'm buying. When we're dealing with a VPN, let's say we have a 10 gig link to the internet. No matter how many tunnels we were to create to try to load share through that 10 gigs, we can never get more than 10 gigs because that's our max internet connection. So if the direct connection, it's going to make sense to load share. But on a VPN, in most architectures, it's not going to make sense to load share because not only do we have the asymmetric routing we have to deal with, but it's not like we're going to get more throughput by taking a pipe and dividing it into two halves. It's the same pipe. And we can never go faster than the speed ultimately offered by the initial internet link on a VPN. I hope that makes sense.
Sammy is asking, you mentioned that you can supernet multiple subnets and advertise them on a link. But don't you also need to send a specific subnet on one link?
I think I
You
know
want
where.
to take that?
Yeah, I think I know where Sammy's lost because I know Sammy real well. So Sammy, let's say I have the 172.16.0.0.12. That's my CIDR range. I can take a 172.16.0.0/13 and pop it on one link. And I can take the second half of that and pop it on the other link. So supernetting is just, and summarization is, how big do we want to summarize it? I can take two things and summarize it into one. I can take four things and summarize it into one, or have two medium-sized things. I can take 8 things and create 2 supernets that are 4 and 4, or I can create 8 links and create one supernet that's just one. So we're just talking about using a less big supernet.
Okay, I think that was the last question for now. So we can go back to the content now. Chris? Okay. So we started talking about the direct connection and what exactly is a direct connection, right? So a direct connection is basically a dedicated link from your on-premise location to the cloud. All right. And what advantage does this have? It gives you guaranteed bandwidth. So you don't have any congestion issues because you're not, congestion in the sense that you're not sharing the link with other users. Like, for example, in that scenario I presented earlier, Windows patches, right? It's just dedicated for connectivity to the AWS cloud. And here you have consistent latency. And latency is that feature that you can use to measure the speed of your link. So if you were to go to your command prompt and then ping a website, a random website, you can see the statistics that tells you the latency of your link, right? So because there's a dedicated link, you have a consistent latency on this link, and it's very reliable, right? Because it's not dependent on the internet. Now, is it possible to connect multiple direct connections? Because direct connections are usually in the 1 gigs and 10 gigs range. So if you wanted to connect, establish a direct connection to the cloud, it will either be a 1 gig link or a 10 gig link, right? But there's situations whereby the organization needs a 5 gig link or a 4 gig link. What can you do in such a situation? You could create a link aggregation group. And what that means is that you take a couple of direct connections and bundle them into one logical wire, right? So AWS supports up to 4 links per group. Now, there are some terminologies that you often hear when you're discussing direct connection. One of that is the fiber optic connection, right? So I think Mike touched on it a little yesterday, where he described how direct connection works. So from your organization, you go to a colocation center, and there's a cross connect from the customer router to the AWS router. And usually the cross connect will be a fiber optic connection, right? So fiber optic connection here, because they are usually they usually provide faster connectivity when compared to copper copper connections, right? So it's one of the underlying technologies for direct connections, fiber optic connection. And it means that the customer router in the colocation center will need to have a fiber optic port, right? So the ports for fiber connections are different from copper connections, right? So generally, copper connections will be ports will be called RJ45 ports and stuff like that. Fiber optic ports will be called SFP ports. So not all routers have that functionality. So you want to look out for SFP ports when you are talking about direct connections, so that you can have that fiber optic cable run from the customer equipment to AWS router or multi-layer switch. And usually we have different types of connectors. So a connector for a fiber cable is called an SFP module, right? And earlier we mentioned that direct connection links could be either 1 gig links or 10 gig links. So it means that if you are going to connect a 1 gig direct connection link to AWS, you need a 1 gig SFP module, right? Or a 1 gig fiber connector module, right? If you're going to set up a 10 gig link between your organization and AWS, you need a 10 gig SFP module, usually called 10 gig base long range and stuff like that. Now, when it comes to fiber, there's usually a send and receive. They are usually send and receive lasers in the fiber connectivity. Of course, fiber is designed to transfer data using light, right? So it's generally faster than traditional copper that sends the data over the wire, right? So you have lasers going in 2 directions. One is send and one is receive, right? Now, if I don't know if you've ever worked with someone who's installing a fiber, link. So one person will stand at the other end of the fiber link, and then it will shine a light, right? And then the other person at the other end will tell if he can see the light or not. So that in this case will be a send laser. And then when he confirms connectivity on the side, then the return process will happen. The other person will shine his light and then ask his colleague at the other end to confirm that he can see the light. So once you have the send and receive lasers working, then the fiber channel is through and up. If you can send from one end of the fiber link to the other one, but you can't receive the laser from the other end to the primary end, it means that there's a problem and the fiber would not work, right? So it's possible that one end of the fiber link is up and the other end is not up. AWS has what we call the bidirectional forwarding detection, right? Which can help you detect whether there are problems in your send and receive lasers. Now, we also touched a bit on VLANs yesterday and talked about trunking and tagging. So at the colocation center, let's say you have a vendor like Bell in Canada, right? They'll have a switch in their data center, and then you have 10 organizations that have requested from Bell direct connections. These 10 organizations are going to plug into the Bell switch in the colocation center. How then does Bell differentiate the traffic coming from company A to company B? It does this using tags. So it tags the traffic from each organization and then sends it over a trunk link. So when the return traffic is coming, the tag is still there. And then traffic destined for each location does not get lost, but is able to get to its location. So that's on the line technology that is used in direct connections as well. So I'll just show you a little diagram here that basically shows you how the direct connection setup looks like, right? So on the left here, you have your organization, and then it will connect to the AWS infrastructure via a direct connection, or a private link. Remember, this is the internet here, right? This traffic does not go via the internet to AWS. It goes via a private link to your AWS infrastructure, right? So it terminates here. And then from there, you can reach your resources in the AWS cloud. So what really happens when you are purchasing a direct connection to the cloud? Now, direct connection locations are like point of presence, like I mentioned, the colocation center. So you have a building, and then you have service providers there. You have Bell, you have Rogers, you have TELUS. These are service providers in Canada, and all of them have probably dark fiber connectivity to this house, and then they have their switches and routers there. And then you also have AWS infrastructure coming into these points of presence or colocation facility, right? So once you need to have a direct connection to AWS, you probably need to get a letter of authorization, which we'll talk about later on. first, and that's like authorization from AWS to the service provider, in this case Bell, Rogers, and Telos and the likes, to establish a direct connection. So what it means is it's giving authority to those vendors to connect that cross connect cable from their equipment to AWS equipment to allow your connectivity. So from there, the traffic is backhauled over the AWS backbone network with a guaranteed bandwidth. I'll just show you a little diagram here of what direct connection location would look like. So here you have on the right your on-premise location, and then you have the direct connect location here, the point of presence or the co-location facility. So like I said, you have the service provider equipment here, and then you have AWS equipment here. And then when you get that letter of authorization, the service provider would tell you connect to port 2 of our router in your data center for direct connection to AWS, and then that connection will be taken from the router here, and then you have a cross connect from the service provider's equipment to the AWS equipment. So that's how it works in a nutshell. Once it gets to the AWS router or switch, it's routed through the AWS backbone to the cloud. So you see that this traffic does not traverse the internet, and so you don't have that bandwidth bottleneck and inconsistency of the VPN connections. So now let's talk about a letter of authorization. And what does it mean? It's basically authorization to establish a direct connection from your office location to AWS. So in order to get a letter of authorization, right, you generally will have to go to your AWS management console and then make an application for it, right? So once AWS looks at your application and approves it, you can download this letter of authorization and then share it with your service provider. So if, for example, my service provider is Bell, right, and I've decided I want to use the Bell to establish this direct connection to the cloud, I'll go to my management console, go to the letter of authorization, make an application, and then when AWS approves it, I'll download this letter of authorization and hand it over to Bell, my service provider, and say, I have authorization to set up a direct connection between my organization and AWS, right? So that will give Bell, in this case, the authority to connect a cross cable from their equipment to AWS equipment in the direct connection location or the point of presence, as it were. So you need a letter of authorization in order to be able to establish a direct connection from your office to the cloud. You do not need a letter of authorization if you were trying to set up a VPN between your office and the cloud. So that's one of the advantages of VPN connections over direct connections. You can set it up in minutes. It's usually faster than direct connection. So you have this. So you keep that at the back of your mind. Now, I mentioned earlier that the direct connection links between your office and AWS are available in 1 gig and 10 gig ranges. Now you could have a company that does not need that capacity, right? Because ideally, a 1 gig link, a 10 gig link is going to be more expensive than a 1 gig link, right? So you might have an organization scratching their head and saying, why do I need to pay for a 1 gig link when I just have, I just need a 100 Mbps link, direct connection link to the cloud, but I don't want to use VPN. I need something guaranteed. Now, here steps in AWS direct connection or direct connect partners, right? So if you find yourself in that situation, you need to establish a direct connect to the cloud, but you don't need 1 gig capacity or you don't need 10 gig capacity, right? You just need 100 Mbps. You could go to a direct connect partner and say, I just need 100 Mbps link to direct connect link to AWS. And they because they are partners with AWS, they would make provisions to connect you to AWS using a direct connection. So what they're going to do is that they'll connect you to a certain port on their infrastructure, and then rate limits that port to 100 Mbps. So you can't push more than 100 Mbps of traffic on that port, right? And then it connects you to the AWS backbone. So usually it will be more expensive. Like when you try to break down a 1 gig link, right, and compare it to a 100 Mbps link, right? But it gives you that value of not paying for the full 1 gig link and still having a direct connection or a private link, a private line to AWS. So they just trunk your traffic on the VLAN on that port you're connecting to in their infrastructure, and then send the traffic over a trunk link to AWS to keep your traffic segregated from other customers. Now, when it comes to direct connections to AWS from your organization to AWS, you have two options when you're terminating your direct connections to the cloud. Now, if your aim is to connect to AWS public services, right, in the region where the direct connection is established, you need what we call a public virtual interface, right? So you're going to be terminating that one end of the direct connection in your AWS infrastructure on a public virtual interface. And that this will give you access to AWS public services such as the S3, the SQS, and public endpoints. But for this to be achievable, you need a public IP on your own end of the direct connection, right? So you can have a private IP on your end of connection and then a public IP on the AWS end of the connection. It has to be publicly routable IP addresses on both ends, and then you just advertise your routes from your data center from your office location to AWS, and advertise the routes from AWS to your office location. So it's a limited BGP implementation so that your AWS does not become a a global routing transit for the internet, right? Now, AWS would not normally accept more than 1,000 routes from the customer, so you have to keep that at the back of your mind. Now, what if you want to just access your private infrastructure in the cloud, your VPC, your virtual machines, right, in the cloud? Do you need a public virtual interface in this case? Nope. You need a private virtual interface in this case. So what that means is that on the AWS end of the direct connections, you terminate it using a private virtual interface. While on your own end of the direct connect, you can assign a private IP address as well. So you see that if you want to access just the private stuff on your infrastructure, you use your private virtual interfaces. And if you want to access public services on AWS, that's when you need to use a public virtual interface. So that's basically the difference between both. So a private virtual interface is typically used to connect to the virtual private gateway, right? And then you can advertise your routes. You can advertise up to 100 routes over the BGP peering session. So in this case, you have your VPCs pairing with your virtual gateways, right, using BGP, and then you have your office location connecting to that virtual gateway using a private IP address, right? So you have to, plan your IP addressing properly so that you don't have some overlapping subnets anywhere. Now let's talk about the direct connect gateway. Now, a direct connect gateway allows you to, aggregate connections from from multiple virtual gateways, and to connect it to a private virtual interface. So in this case, let's say you have two VPCs, right, in two different regions, and they have virtual gateways, right? These two different VPCs have virtual gateways, but you want your direct connect to be able to reach these two different VPCs, even though they have two different virtual gateways, right? So it's like a point to multi-point, right, connection. What you can use here is the direct connect gateway. So you terminate your direct connection private virtual interface on the direct connect gateway, and then from your VPC, you pair you do the VPN connection from your virtual private gateway to the direct connect gateway. So that way, your office is able to reach both VPCs, right? Even if they have different virtual gateways, and then from your VPCs, you can reach your office at the same time. So you can use your direct connect to connect it to your multiple VPCs, even if they're in different availability zones and regions. So it's quite flexible in that regard. The diagram here shows you how the direct connect gateway functions in the light of what I just discussed. So on the left hand side of this diagram, you have your data center, and then it has established a direct connect with your with the AWS infrastructure using a point of presence location, or if you like, a colocation location. So you have a cross connect from the provider to AWS and then onto the AWS backbone. So you have the direct connection gateway here. You terminate your connection from your office location to the direct connect gateway using a private virtual interface. Remember what we talked about, the private and the public virtual interface. Assuming these were public services such as S3, to be terminated on a public virtual interface. And then you have your VPCs in different regions, EU West 1, East, South. And then you have the virtual private gateways from these different regions, terminating on the direct connect gateway. So you see the direct connect gateway is aggregating these connections from your different VPCs so that your office can reach all of them, right? If the direct connect gateway were not available, it means that you need 3 direct connects to these different VPCs, right? And which is more cost. So AWS has helped you with some cost savings here. Now we talked about designing a highly available solution for your VPN, right? So that instead of having one VPN connection, you have 2. Now, it's also possible to have a highly available system when using direct connect. And what that means basically is that you're not using one direct connect to AWS, you're using 2, right? Or more, typically 2, right? So now there are different models, and it will usually be driven by the business requirements of the organization. So if an organization needed a direct connection to the cloud, right, and they wanted a backup solution which was not as solid as a direct connect, right, you could have an architecture that has a direct connect to the cloud, and for backup purposes use a VPN connection to the cloud, right? So if that direct connect link were to go down for any reason, right, and there could be a couple of reasons, especially from the customer end, your router going offline or stuff like that, or there's a fiber cut on the infrastructure of the service provider providing that direct connect, right? If that were to happen, you have a backup solution in place. It's not as solid. The VPN backup solution is not as solid as direct connect, but it's a solution available to help you meet your business continuity requirements. So what would that look like, right? I have a diagram here to show you what it means. All right, so in our diagram here, you have the corporate organization, right? And it has its primary link, which is a direct connect, right? To the cloud. And then it has a backup link underneath, which is the VPN, right? To the same infrastructure. You can see that we've terminated both links on different gateways here. So if this were to fail, traffic is now routed through the VPN connection, right? If either were to fail, traffic is routed through the redundant path. So this is one model we can employ when building our high availability architecture from our on-premise locations to the cloud. Now, it's also possible that you come across organizations that are sensitive, right? So they tell you, we just want a direct connection. We just want a dedicated link to the cloud. We can't deal with the inconsistency of the internet for cloud connectivity. We can't deal with VPN connection. Even if it's a backup link, we can't deal with that. In fact, it's not in our security policy that we use VPN connections to the cloud. It has to be a direct connection. There's a solution for that as well. In this case, your primary and backup links are direct connections, private lines, right? Now, you have to be smart about this. If Bell was my primary service provider, would I tell them I need 2 direct connections to AWS, 2 separate direct connections to AWS, so that if one goes offline, the other one is online, right? And the availability of my operations is guaranteed. What if Bell has a major disaster and then their whole infrastructure crashes? It means that both links would go offline, right? That is not a truly highly available situations. So when you're thinking of building high availability with 2 direct connection links, you're typically thinking of 2 different service providers, right? Bell and Rogers, for example. And then you make sure that they do not their backbones are not running through the same path, right? So I mean, if Bell is coming in from the east end of the building, Rogers should be coming in from the west end. So that way, if there's a fiber cut on all the fiber infrastructure coming from the east end, the Rogers is not affected. So those are some of the things we need to keep at the back of the mind. So if we want to build that solution, right, for the direct connect, it will look like something like this. I'm sharing my screen now. So you have from your on-premise locations, you now have 2 direct links to AWS, right? You have one Bell and one Rogers. And then if Bell goes offline, traffic goes through Rogers. Or that's if you're running an active passive architecture, all right, solution. If you're running active, then traffic will be flowing across both direct connections, and then you use BGP to prevent asymmetric routing. So keep that at the back of your mind. Now, is this a truly redundant solution? Remember, we said that to have a truly redundant solution, you can't use one device. You have to use more than one, right? So if you look at this here, we have the direct connections terminating on a virtual gateway, and probably here you have direct connections on a router. To have a truly redundant solution, you need to have 2 separate routers. This will be the Rogers routers terminating the direct connection from Rogers, and this will be the Bell router terminating the direct connection from Dell to the cloud, right? It could be direct connections across both link, or it could be a VPN connect backup link from one location to the other. So you have that redundancy here. If there's a failure on this device is still up and running, and then you're truly able to secure availability for your organization. So kind of keep that at the back of your mind. Now, recall that I said we can also load share across direct connection links. So if you have an active architecture where you want to utilize both direct connection links at the same time, you could have load sharing across these 2 links. And what this means is that, recall we said we use a routing protocol to load share across 2 links. So in this case, we're going to use BGP to load share across both redundant direct connection links. We also talked about the risk of asymmetric routing. So traffic going out one of the direct connection links and coming out through the other. BGP handles this using the earlier methods we spoke about, aggregation, route summarization, and the likes. So if I share my screen here, you see what I'm trying to talk about. So here you have two direct connection links, one on top and one underneath, right? And then if you're running an active solution, you just advertise the more specific routes across one link. You advertise the summary route also across that link. Then you take another specific route and advertise it on the other link, and then take the more specific route and advertise it here as well. So traffic for this route is always sent across the first direct connection link, and traffic for this subnet is always sent across the second direct connection link. So this is how we achieve load sharing across redundant direct connection links. And this if you're running an active solution, right? Now let's talk about link aggregation. If you recall, I gave a scenario earlier when I said a company might need a 4 gig link to AWS, and direct connection link comes in 1 gig and 10 gig. Now, the next best solution for such a company is to subscribe for a 10 gig link, which is much more expensive than what it needs. Now, is it possible to save some cost for the organization here? We use what we call link aggregation groups to achieve this. So you can bundle up to 4 direct connection links, right? In this situation, the company needs a 4 gig link. So what it does is that it reaches out to its service provider, gets the letter of authorization, and says, I need 4 1 gig direct connect links to the cloud, right? And when the service provider provides this, it then bundles these 4 links into one logical 4 gig link to the cloud. So physically, it has 4 1 gig links, right? But logically, it has a 4 gig link to the cloud. So that saves you going to buy a 10 gig link when you just need a 4 gig direct connection link to the cloud, right? How about a company that needs a 30 gig link to the cloud? Remember, we said AWS direct connect links comes in 1 gig and 10 gig ranges. So in that case, in that case, they would tell their service provider that they need 3 10 gig links in order to be able to achieve this 30 gig link requirement from the office to the cloud. So once the provider provides this 10 gig links, then it bundles the 10 gig links and it gets a 30 gig connection to the cloud. Now, the good thing about link aggregation is that it provides some sort of fault tolerance. So if there's a failure on one of those links to the cloud, for example, you have a 30 gig link which is bundled, 3 individual 10 gig links. So there's a failure on one of the 10 gig links for whatever purpose, for whatever reason, you still have 20 gig, right, between your organization and the cloud. So there's that fault tolerance there, which could be an advantage to an organization. So what does this look like? Let's see if I can get you a diagram. So share my screen now to show you what this looks like, right? So in this scenario, this company needs a 20 gig link, direct connect link to the cloud, right? But it's also taking care of availability. So it says I need 2 pairs of 20 gig links to the cloud. So it's going to get 4 10 gig links from the service provider. Each gig is 10 gig. So it bundles the first 2 links and it gets a total of 20 gig. All right. It is connected to one router. And then it bundles another set of 20 gig links here. It bundles another set of 10 gig links here to get a total of 20 gigs, right? So you have 2 pairs of 20 gig redundant connections. So you have this kind of flexibility when you are working with direct connections. So I'll pause here now and get some questions, if there are any, from the community.
I was trying to respond to somebody in the chat box. Bear with us. So, welcome back, everyone. Benedict covered a lot about VPNs this morning, around direct connections. I actually enjoyed watching it, even though I'm very familiar with these. So it was really great to see him do it. So at this point, let's bring in some questions that you have. And I will also address the RGB Tech one as well. We'll get there and talk about that and what it means in context for you. So bring us your questions, and if you want a little more in a direct connection, we can also, whiteboard it out. I kind of like to whiteboard the direct connection should you need anything. But let's get to the questions.
Okay, so Samson is asking, you showed VPN instead of direct connect to the direct connection location for the secondary link. Is that correct? I thought anything going into direct connection location must be direct connect and not VPN. Yeah, you're right. So for a direct connection, you need to terminate that connection in the point of presence or direct connection location. For the VPN connection, it does not go to a direct connection location. It goes directly to the internet.
I think what you did is inadvertently had a slide which we used for BGP illustration purposes, not to actually be looked at that deeply, and that's where I think he came from. That's what I was trying to put in the chat box.
Oh, okay. Yeah.
RGB Tech, is this entry level like the Net Plus? So RGB Tech, I'm going to explain this since I've been training network engineers and architects for about 25 years now. The Net Plus, I typically tell people to skip. It's a good certification, but it's kind of like an intro to entry-level networking. I typically tell people to skip the Net Plus and take the CCNA as kind of their intro to networking, something like this, and then ultimately get a CCNP. And at that point, you kind of have the skills in most cases to actually do networking. So yes, this is a cross between intro level and medium level. That's the way I would look at it. But if you can learn this and anything that you don't know, you can go look up, and you can do that in maybe a CCNA and use the CompTIA Net Plus if you want along the same time as extra reference material. I think you'll do great. How about you guys?
No, I agree. I'm honestly, I'm very familiar with Network Plus, so I can't make a comparison there. But from my understanding, Network Plus is a very, very entry level. Although, I heard good things about it.
Yeah, I mean, I didn't take the Net Plus as well. I went and did the CCNA directly.
Yeah.
And it taught me the basic foundations of networking. So I would think that the CCNA will give you a stronger foundation in networking than the Net Plus.
Much better.
Now, William is asking, is there any advantage to put a network load balancer or application load balancer before the direct connect gateway? Now, why would you want to do this? Um, so the direct connect gateway is aggregating connections from your VPCs, right? From the virtual private gateways and the VPCs. It's almost working like a load balancer in that sense. I mean, it's just aggregating the connections. So why do you want to place another device after it? Doesn't make any sense to me.
Yeah. Also, you can't place a network or an application load balancer. So application load balancer would make no sense because you're doing TLS termination on an application load balancer. So you're not really what you're looking for. Now with the network load balancer, that also wouldn't make sense because think of this as a private line, like from point A to point B. So really there's no purpose. But Benedict did go through other methods to kind of aggregate links, like using link aggregation. Your connectivity provider can provide you with, can support MLAG as well if you want a more highly available setup. But yeah, definitely not a network or an application level. It's not possible, and I agree with Ben here.
Truth Factory. How does the billing work for Direct Connect? You pay two bills, one to the service provider and other to AWS for Direct Connect. That's why we said the VPN is cheaper because you're leveraging the internet that is already um, existing in your organization. But the direct connection gives you better bandwidth, guaranteed bandwidth, better latency. So there's some trade-off here.
And Truth Factory is kind of interesting. So at least in America, if I buy a 10 gig link, I buy a 10 gig link, I pay the monthly fee, and that's it. With AWS, it's a little different. You still have to pay for the 10 gig link. Then you have to pay a daily port fee because you have the link, and then you actually have to pay to use the link. So you can think of it that way, as it can be a lot more expensive connecting to the cloud than it would be if you just needed to connect two data centers together. Before we get to the next one, I should mention that if you've just joined us, we have almost 2 days of networking labs for you that you can download completely for free, do on your own time, on your own schedule, and we'd love you to. They have two kinds of labs in there. AWS labs, which will teach you how to configure things on AWS. And then we had one of our expert network architects do some labs in a data center environment on Cisco routers. And he walks people through the technology, how the technology is working at the underlying level, so you can truly learn it at a much deeper level than you could just by configuring. So please download them. They're in the chat box in the description of this video.
So Samson V says, Mike, I'm trying to understand your comments. Are you saying it is possible to have VPN links into direct connection location facility too?
No, what I was saying is that when you popped up something, I think it was a cut and paste graphic that we had that was sitting in our presentation from a network architect that was trying to demonstrate BGP as opposed to an AWS thing, and he read it with attention to detail and context.
Joseph, I'm a little lost on link aggregation for AWS. If AWS only supports 1 gig and 10 gig connections, that means that the organization can't achieve the 30 gig requirement.
Actually, go ahead, Benedict.
Okay, so I actually explained this, but let me re-explain. So it allows 10 gig connections, right? Now you need 30 gig connections. It means that you need 3 10 gig connections, right, into your organization. And then you use link aggregation to bundle those 3 10 gig connections to get your 30 gig requirements. That's what it means. Valerie, I knew someone would come up with an odd number.
Yep.
How would you get a 5 gig connection if you can aggregate only 4?
Well, actually, here's the way this is going to work, Valerie. What you're going to do is use as a direct connection partner, and you're going to buy a 10 gig link, and then you're going to rate limit it to 5 gigs, and that's how you're going to get a 5 gig link.
Mohammed, for active for public virtual interface, will load sharing between traffic? We're going to be load sharing between traffic, right? Not sure I fully understand.
Well, let me take an attempt at answering that. I think what he means is you have two public virtual interfaces, meaning going to an AWS resource, right? And so what he's asking is, can we load share between those two? Meaning send half of your traffic to the first link and the other half to the second link. I don't see anything that would stop us from doing that, right? Whether we split our advertised subnets so that half of them go this way, the other half goes the other way, or we're doing load sharing packet by packet. Because at least from your side, if you don't have any issues with asymmetric routing, then that shouldn't be an issue, because asymmetric routing here is pretty much might be unavoidable in this case. So yeah, it's doable, and there's nothing that would prevent you, unless you have a firewall before your connection, which shouldn't be, but it's definitely
Exactly. Shouldn't be, but we've seen it.
Yeah. Yeah.
So William is asking, what's the relation between direct connection and cloud on ramp, if there's any? I'm not familiar with cloud on ramp, to be honest. Mo, have you come across that?
Yeah. So cloud on ramp, that's more of a SASE solution. Direct connect, that's a private line. I see where you would think that maybe there is a there's some sort of a connection there, but there's not really. So both methods, so direct connect, you're running a private line, it goes through a co-location between AWS and the service integrators, right? Cloud on ramp is more of your SD-WAN at the edge routers, the SD-WAN edge routers would be able to, based on the SD-WAN solution, what they would do is they have a list of, let's say you want to access Teams, right? You want to access Teams online. And what the service provider would do is that they maintain the fully qualified domain list for all of those different applications, let's say, for example, Teams, and they would be able to send your traffic to the nearest point of presence for those applications. So it's really completely different technology from, unrelated to Direct Connect.
So Samson is asking, I might have missed this. To make two direct connect links truly a HA solution, wouldn't we need a second virtual private gateway for the VPC? So you're terminating the direct connect on your direct connect gateway, and you're terminating your from your VPC, you're terminating the virtual private gateway to the direct connect. So if you recall, when we spoke about VPN earlier, we said that the virtual private gateway is a highly available device, so it's redundant. So there's redundancy built into that part of the AWS solution.
So let's talk about that for a second. So Samson, have you ever worked with a router and you put a loopback address on the router, because as long as the router's not dead, the loopback address is always up, as opposed to like an Ethernet port? Well, when we deal with virtual devices, they could be on 1,000 different servers. So if a server goes down, they're not going to go down. So when we deal with our routers connecting to the cloud, we need very high availability devices, because if they go down, we have a problem, and they can and will go down. But a logical device like a virtual private gateway goes down when the cloud goes down. Now the cloud can and will go down, but it only goes down when the cloud goes down. So that's why it's not really a weakness in the system.
Mohammed, can you explain to us how we manage the hybrid DNS connection in an organization with several accounts, and how VPC endpoints are managed in an organization with several accounts?
I mean, I do know we're going to be doing a lot more DNS coming up soon.
Yeah, we can take this question later.
Okay, so we're going to get back to the content so that we know that you're awake, alert, and oriented. If you can make sure to give us a hashtag AWS Advanced Networking, and that way we know you're here. The team will get back to the training. Hope you guys are having fun. I know I'm having fun. Okay, who is next?
It should be me.
I think that's you, Mo.
Yes. Okay. So we're doing a little bit more on direct connect gateways, private virtual interfaces, kind of like put things together just to drive. So, okay. So Pennington explained what a direct connect gateway is, right? What it basically is a way for you to use private lines or a direct connect lines to establish a private dedicated connection from the data center, from your data center to your AWS cloud, right? Now, let's start by describing the solution itself, the gateway, right? The AWS Direct Connect Gateway is a globally available resource, which means that you can use the same Direct Connect Gateway to connect multiple VPCs from different regions, right? So that's one of the benefits. So for example, you can have one Direct Connect Gateway that terminates a connection to your, let's say, your Asia Pacific or APAC data center, and then another connection that connects to your Americas data center, another one for EMEAs, and it can all be concentrated on that one direct connect connection, right? The direct connect gateway by default is not transitive, right? What I mean by that is that you have a direct connect gateway, and let's say you have multiple VPCs that connect to that direct connect gateway. Now, those VPCs can't talk to each other through direct connect, at least by default. There is a workaround, and I'll discuss that workaround. But by default, they can't talk to each other through that direct connect gateway. So it's non-transitive. The other thing is your data centers. Even though your data centers, we said you have an APAC and EMEA and America's data centers, right? Those data centers, they can't talk to each other through the direct connect gateway. But that also can be changed. And this is a newer update from AWS. I think they added it in 2022, where there's a new feature that allows you to connect multiple, or not to connect, but allow your data centers that are connected to the same direct connect gateway to talk to each other. Or even if you have two direct connect gateways and you pair them together, then you'll be able to allow those data centers to use AWS internal infrastructure to talk to each other, right? Okay, so we have three types of, actually before I say this, let me backtrack and kind of do another quick review of Direct Connect. So this is one example. You have your data center here, right? And then over here you have your AWS cloud, and then you have this co-location facility. So AWS has its network racks and this co-location. Same thing for your connectivity provider, let's say AT&T or Megaport or whoever you're using, right? And then there is a meet me room. Let's think of it of the actual co-location, right? And then there's a cross connect that runs between those two providers, right? Between AWS and the connectivity providers, right? Now, the actual cable that runs between those two, we just call it a connection, right? So this actual cable that runs all the way here and then goes up here. Now, this is what we call a connection. Okay. So for connections, we have two types of connection. We have dedicated, if I can write dedicated, and then we have hosted, right? Imagine that this says hosted. So dedicated and hosted. What's the difference between dedicated and hosted? The simplest way to describe this is, think of dedicated as an actual dedicated line for you. So when they say it's layer 2, it's layer 2 end-to-end, right? And they maintain that for you, right? So it's not shared with anybody else. It's only for you. And there are some benefits to that. So let's discuss the dedicated first. So with dedicated, you have three options of bandwidth, right? You can have 1, 10, or 100 gigs. And over that dedicated connection, this dedicated end-to-end is layer 2, and it's running 802.1q, meaning there's trunking. It's a trunk, right? So once you run that, then you can have up to 50 virtual interfaces. You can have up to 50 virtual interfaces over that connection. So what you can do once you have that connection is, let's say you would run a, let's say VLAN 10, VLAN 20, and 30, and so on and so forth, right? You can have multiple private, multiple virtual interfaces, and in each one of these interfaces is running over a specific 802.1q tag, right? So a different VLAN. So you get more control. This is more of a, if you want a more scalable design where you have a link and you know that you want to add more virtual interfaces in the future, that's one way you can do it, right? But it allows for speeds of 1 TB and 100. Okay. Another benefit of a dedicated circuit, because or a connection, because it is dedicated, you have the option of running layer 2 encryption, which is max security or MACsec, right? Max security, think of it as an encryption just like IPsec is encryption, but IPsec happens over layer 3, right? So it takes the header and everything before it and encrypts it. MACsec encrypts everything after the frame, so everything, right? So it just leaves the source and destination MAC address, and then it encrypts everything after, right? So that's something you can do with a dedicated connection. Now with a dedicated connection, we said you can have up to 50 virtual interfaces, right? So in reality, you can have 50 public or private virtual interfaces, and we'll go through review what public and private means, but you can also have one transit virtual interface as well. So we'll talk about that as well. So this is a dedicated. Now hosted, you can have anything between 50 megabits per second to 10 gigabits per second. Now with hosted, because it's shared, meaning it's not solely used just by you, so the layer 2 link is done through layer 2 tunneling, and they guarantee you a bandwidth, but really in reality it is a shared connection through the co-location. You're sharing that connection here, and so because it's shared, because they're doing layer 2 tunneling on your behalf, so you can think of it as more of a virtual layer 2 link, and you cannot run max security over that. So layer 2 encryption is not an option. So if you wanted encryption, you would want to do something over layer 3, so layer 3 encryption. So the hosted connection can support private, transit, or public virtual interfaces, just like a dedicated. But you have less bandwidth options, and you can't run layer 2 encryption on top of it. Okay. So let me share my screen. Give me 1 second. Okay. So a private virtual interface. What exactly is a private virtual interface, right? We said there's 3 types of virtual interfaces, right? So we established that connection, that line, as you see here, right? We established that actual connection, which is the physical connection end-to-end. Now over that connection, you want to run some sort of a peering between the direct connect gateway and the your on-premise router, right? So in order to do that, you have to choose which type of peering this is, right? Is it private, is it public, or is it transit? Now with private, and I'll show you that, and I'll demonstrate it with a diagram. With a private VIF, this is a virtual interface or a VIF that only connects your on-premise to one virtual private cloud or one VPC. So if that's what you're looking for, if you want to connect only one VPC, then this is your option, right? So this would be, and I'll zoom in a little bit here. This would be option 1 and 2, actually. So those 2 options. If you look here, this is the co-location. This is your data center, and you want to run a private VIF. Notice that you have one that goes up here, and it's connected through, you see this symbol for a virtual gateway, so it connects to a virtual gateway. And then if you wanted to connect the other VPC as well, you would need to run a secondary line, right? Or a secondary virtual interface, right? But this means you need a new termination or a fiber optics cable, another cable that runs from your connectivity provider to you. So that means you're going to have to pay the cost, for each installation. That's another physical line that terminates at your site. And of course, there's a lead time. If you want to get this weeks, it could take months, right? So it's not very ideal, right? Just the fact that I need a new line for each connection is just not scalable. Another thing you can do, well, before we go there, now let's look at this connection using a direct connect gateway. So with a direct connect gateway, it's without, if it's still a private line, just as we had it, that means I'm still going to need a new private virtual interface for each VPC. So this peering, think of the virtual interface, whether it's private version, think of it as the actual BGP peering, right? When we set connection, hosted or dedicated, that's the actual cable. But when I say virtual interface, think of it as the actual BGP peering. So you would need to run multiple peers, one for each VPC with a private. And that's why it's called private, because it's only for one VPC. Now, if you wanted, let's say if I had 20 VPCs and I wanted those 20 VPCs to have access to on-premise through the same connection. This is where you would use a transit virtual interface, which is option 3 here. And now a transit virtual interface, as the name suggests, connects to a transit gateway. And once you connect to a transit gateway, that transit gateway can have access to 20 or 40 or 50 VPCs. That way, those VPCs can share that virtual interface or transit virtual interface. So that's the benefit of the transit virtual interface. And then, as you can see here, there's a lot of different setups you can do once you have this, right? Let's say you have another region and you have resources in a different region. You can set up a transit gateway peering, right? Yesterday we talked about transit gateways. You can have attachment to VPCs and you can have peering to peer with other transit gateways. And this is what you're doing here, right? So now you give your other account with different VPCs access to your resources, right? Now in this example, actually, this is a very good example because you have some AWS resources like an S3 bucket, and through a transit gateway peering, you can give those your on-premise customers, you can give those customer or on-premise users, you can give them direct access through private access through this direct connect gateway to your AWS resources like S3, right? And you can do that by setting up an AWS private link, right? Okay, so using a private link, which we discussed yesterday, you give private access to your AWS resources through your direct connect or private link or private line. What if I wanted dedicated public access? Now, this might sound a little bit weird, but what if I still wanted to access my AWS resources publicly, but not through the public internet, meaning I wanted to reach those resources through public IP. So in that case, you would need to set up a public virtual interface. This is the third type. We said there's private virtual interfaces, there's transit virtual interface, and then there's public. Now with the public virtual interfaces, what you do is, and I'll use a different color to, what you do is you run another direct connect, right, from your on-premise, right, to AWS. And when you run this, because this is public, what you do is the service provider, the AWS will advertise the public IPs of those resources. Let's say it's S3 they will be advertised through the direct connect. So establish VPCs, and those resources will be advertised, right? So now you know, when you have a default route through the internet to reach those resources versus a more specific public IP received through this a public VPC peering, and you'll obviously go through the more specific this way, right? For the S3 bucket, for those resources to reach you through the same direct connect, you have to make sure you also advertise your source IP, your public IPs this way. And that way, you'll be able to use the public VPC to reach those resources directly. As you can see, we have multiple options, right? This is more of a what I've seen in real life. People use this option. They use a transit VPC, and then they set up a private link, and then they advertise the route of the private link so that they can reach it through on-premise from this dedicated transit VPC. So those are the different types of, just wanted to give a visual representation of those different types of connections and virtual interfaces, right? Okay, a couple of points I want to bring up. One of them is, remember that it's not transitive by default, right? Which means one VPC can't talk to another VPC, okay? So this is one of the recent updates, and this has been the case since November 2021, right? This is more of something that we typically do in traditional networking, right? So since November 2021, AWS has started allowing customers to, let's say, adjust routing in a way where you can use the Direct Connect gateway as a transit resource or a transitive resource. And here's how it's done. If I go back here. So this is a good example I can use, or this diagram. If you remember from this diagram, right, we have multiple VPCs, and those different VPCs can use the Direct Connect gateway, right, to reach on-premise, right? Imagine that there is behind this Direct Connect gateway, imagine that there's another VPC that's here, right? Let's call it VPC 4, okay? Because the Direct Connect gateway is not transitive, if you send traffic from VPC 4 to VPC 3, this is not going to work. The Direct Connect gateway will not allow you to send traffic this way. Even though both of these VPCs are behind the Direct Connect gateway, right? They can't talk to each other. Now, the new kind of workaround that AWS allows you to do now is you would, let's say this subnet is, you say if I can, okay, no. Let me write it down. Let's say this is 10.0.0.0/24. This is VPC 4, and VPC 3 is 10.0.0, or actually 10.0.1.0/24, right? So 10.0, 10.0.10 and 10.0.0.0, right? So you establish your transit virtual interface, and from the Direct Connect, you say that you're advertising those two subnets, right? You're advertising through BGP 10.0.0.0 and 10.0.1.0, right? And then from your side, you want to advertise your networks. Let's say you have a 172 network, a bunch of 172.16 network. So you're just going to advertise 172.16, let's say /24 or /20, let's say. This is your data center. Let's say it's a /20, right? Now, what you can do now is from your on-premise, if you advertise a supernet, let's say 10.0.0.0/23, right? /23 will account for the 00 and the 10, right? And then you would advertise it this way. Now, if you send your traffic from 10.0.0.0 all the way to the Direct Connect Gateway, the Direct Connect Gateway will still not send it this way, right? But what it will do is it will send it downstream. And once it's sent downstream here, this router will look around and see that it knows that 10.0.1.0 should be sent this way. So we'll send it back up to you. And then the Direct Connect Gateway from this side, it will look at the actual more specific route and send it up here. Now, if you've been involved in networking at, at any capacity, this might trigger some of your spidey senses, and you will think, okay, this is a loop. This calls for a recursive loop where I send you a route, you send it back to me, right? But it doesn't, and the reason is the Direct Connect Gateway doesn't act as a typical router, right? When you send the traffic this way, all it's looking at is the more specific route. It doesn't see this side, right? So because it's non-transitive by nature, right, it can never send the traffic this way. So think of this as a separate routing table pointing to VPC4 from the routing table pointing to VPC3. But this is just shared routing table from this side. So when you send traffic this way, it can only see the longer subnet, the supernet. So it can send it downstream. But this router knows that it doesn't own anything outside of 172.16, but it's seeing that it received those two advertisements, the 10 and the 00, the longer prefixes. So we'll just send it back, right? And then when it's sent here, this is a different routing table from this one and this one. So in this routing table, this Direct Connect Gateway knows to reach 10.0.1.0 this way, right? Now for this to work on your on-premise router, you have to make sure that unicast RBF is disabled. Because with unicast RBF, you would not receive routes, right? Basically, it's a loop prevention mechanism for unicast traffic. And it also helps against attacks where somebody would source traffic from a source that is not intended, that shouldn't be intended to you. So you got to make sure that unicast RBF is enabled pretty much. Okay. Yeah, that's everything. So benefits of the Direct Connect Gateway. Well, it can obviously performance, right? Number one, the biggest thing is performance, right? So while the internet is best effort, right? Even though you have a bandwidth, guaranteed bandwidth maybe from your service provider, but they can't really guarantee your traffic will reach point A to point B without some traffic being dropped. So the quality is really It's not guaranteed, right? Because it's public. It's a shared infrastructure, the internet. So you obviously get a consistent performance because that's a private line dedicated to you, right? The second thing is enhanced security, right? Because it's a dedicated line, right? There's less risk of dealing with any sort of man-in-the-middle attack or some bad actor getting having access to your data and just storing that data, right? There's aside from regulations and laws, right, there's nothing stopping a service provider from um, logging all your traffic, right? Mirroring all your traffic, and then they can just hold it in a storage facility and try to decrypt your traffic, right? So you get that enhanced security, right, or added security. And so one other thing, and this is strictly a benefit of a direct connect gateway, because you can still have private lines without a direct connect gateway, right? The benefit of a direct connect gateway is that it can reduce the cost because of instead of running multiple private lines and having to pay for multiple private lines, you can potentially use one private line and share that line across many VPCs, right? And you can use one connection and use that same connection to establish multiple virtual interfaces, right? Up to 50, as we described previously. So there's obviously that added benefit of using a direct connect gateway versus just running private lines straight to your VPC. Okay. Any questions?
Welcome back, everyone. We are here to take some questions, and then we'll get into some DNS. But let's get to some questions first. From Muhammad. I'll read it. You guys can answer this. Direct Connect Gateway would help connect to co-location using virtual interfaces. I think that's a question.
Yes. Yeah. That's an accurate statement. So Direct Connect Gateway will help you connect to co-locations. Well, help when connecting to co-location using a virtual interface. Yes. So yeah, the co-location will establish that line that terminates at your data center, right? That's what we call a connection, and then you run a virtual interface on top of that. Yes, I think that would be an accurate statement. How would you connect two organizations other than VPN? I'm not talking about connections of account under the same organization. Okay, so you have two organizations, right? So I'm guessing you mean an organization in two different companies running on AWS, but they're completely different organizations, because there's a meaning of the word organization inside AWS. So I'm assuming it's two different companies, right? They're running two different organizations, two different accounts, and you want to connect those two companies to each other. You want something other than VPNs. Well, as we described previously, you have you can use a VPC peering, but do you trust the organization, right? So with that, do you trust them to run VPC peering between you and that organization, right? VPN might be one of your better options, but VPC peering is an option. Transit gateways, you can give them a transit gateway attachment, share your transit gateway as a resource, give them an attachment, and then they can use that attachment. And if you want to add an extra layer of protection, you can set up an east-west encryption, east-west inspection, so that their traffic is inspected before it can see the rest of your VPCs. But yeah, that would be another option. I wouldn't say using direct connect in this example. That's not a practical option to to have direct connect.
If they're both on the same cloud.
Yeah.
Okay, so Samsung, and I'll get it. I'll actually do this, and I'll whiteboard it out with you. So a trunk really means that you're carrying multiple somethings on a single wire. So in voice trunking, we might have multiple lines go out a port to the phone provider from the phone switch. And in network trunking, we're actually talking about trunking VLANs. I'll draw this out for you. I know we did it on the first day, and that's okay. It's a pretty important concept that you need to know for a lot of things, so let's draw it out. Bear with me while I set up my screen. I will draw this out, and then we'll get back to answering questions, so bear with me. So let me do this. Oops, over here. We'll go to scene 2. Okay, great. So here we're on my fancy whiteboard over here. And what we're going to do is we're going to take a switch. This is where VLANs come from. So we're going to consider the box to be a switch. And then what we're ultimately going to do is put some ports on the switch, because switches basically have a lot of ports where you'd plug your routers into the switches. If we were dealing with classic routers, you'd plug your servers into the switches. Bear with me. Okay, so now we put some ports on this switch. Now let's populate the switch with ports. And I'll show you the two alternatives we would actually have to provide two sets of connectivity. So in this case, we're going to connect switch to switch, but we could have also connected to the cloud provider. It's realistically the same thing. Let's say, for example, we want these top 10 switch ports to be isolated from every other port in this switch, because by default, all switches are on a VLAN, which means a broadcast domain, and every port in a switch can technically talk to every other port, unless we virtualize that switch by chopping it up into mini switches called VLANs. So in this particular case, we've got the top 10 ports that can only talk to each other, the next 10 ports that can only talk to each other, because we're going to create 4 VLANs here, the next 10 ports which can only talk to each other, and another 10 ports that can only talk to each other. So we've separated everybody into 4 different categories. Now, let's say on the left side of this, which is the cloud provider, or it's the switch, it really doesn't matter, the point is the same. We decide to create these 10 ports, and only they can talk to each other. And then only these 10 ports can talk to each other. And then only these ports can talk to each other. And now only these last 10 ports can talk to each other. So now each switch, the top ports can only talk to each other. The medium ports on each switch can only talk to each other. The lower, the penultimate ports on the closer to the bottom can only talk to each other. And the bottom ports can only talk to each other. What if we wanted the top ports to talk to the top ports? We'd have 2 options. We could run a cable from the top ports to the top ports, and then those 10 could talk to each other. We could then run another cable for these ports to talk to each other, and another cable for these ports to talk to each other, and then another cable, and then we'd have the equivalent of 4 VLANs. Or we'd be letting those 4 systems talk to each other. By comparison, a trunk port does something a little different. We create a single cable or a single piece of fiber between the ports, between the 2 switches. And then we tell the switches that they can send all the information off of all those 4 individualized virtual LANs all on the single cable. And what happens is how this works is when we take a frame from this particular VLAN, we actually put something called the tag on it. And typically speaking, it's going to be an 802.1q tag. And when the frame goes on this wire, they put the tag goes placed off. The tag stays on this wire, and as soon as it leaves the wire, the tag is stripped off, and the frame goes exactly where it was supposed to. So when we use a direct connection, what we're really dealing with is a VLAN, because we send them a VLAN, and that VLAN goes on the wire, and we give them an 802.1q trunk to segregate the traffic. And that is technically a form of VPN. It's a layer 2 VPN. Chris, we can all come back on the screen. I just thought that would help for Samsung.
Can you say that a direct connect company uses VXLAN to separate the various shared mediums? Or how do they separate the bandwidth? Well, I would say they probably it's probably some sort of. It's definitely okay. Let me say this. It's not definitely not just 802.1q, right? It has to be some sort of. So it could be VXLAN, but there's a lot of different methods to do this, right? So yeah, more likely not. Well, there's a high probability it's VXLAN. I'm trying to say yes, but that's not public information that And I've asked. Trust me, I've asked different service connectivity providers, and that's not information they disclose. Can we have two direct connect gateways in two separate regions? And how would you connect through one transit VIF? So yes, you can. What you're trying to do here is have two separate direct connect gateways, right? And then each direct, you want to peer between those two direct connect gateways, right? But then you want traffic. So what you're trying to establish here, this is not how you would do it. No, but I'm thinking that this is what you mean. But if you have two direct connect gateways, right, two different regions, right, and you have two data centers, right, and you want those two data centers. Actually, if you don't mind, can I whiteboard this real quick?
Yeah, go ahead. Good idea.
Okay. I think this is a very good question.
No need to share a screen.
Okay. Okay, I'll start sharing my screen. Now, use slides. Okay. So let's say you have one direct connect gateway here, another direct connect gateway here, right? Let's say this is US East 1, right? Let's say this is US West, some other region, right? And then over here, you have a private line going to one data center. Let's call this data center 1. Okay. Well, can you have a connection between those direct connect gateways? Yes, you can. Right. And of course, you have multiple VPCs. Let's say here you have multiple VPCs, right? But for this scenario, let's assume you have one VPC each, right? Now, you can obviously, you can talk, this VPC can talk to on-premise and vice versa. Same thing for this side, right? Can this VPC talk to this VPC? No, this is not possible, right? This is where you would use something like a transit gateway, right? So maybe you have a transit gateway in this region, right? And a transit gateway in this region. You connect those transit gateways to each other. That's how you would set something like that up, right? Which means your direct connect gateway doesn't connect directly to your VPCs, but it connects to a transit gateway first. Because with a transit gateway, otherwise you would need multiple virtual interfaces. You're going to end up paying for more, right? So usually you would have a transit gateway, and then all your VPCs connect to that transit gateway, and the transit gateway connect to a direct connect. In that scenario, then, if you wanted VPCs in one region to talk to VPCs in another region, it would make sense to just run a peering between those transit gateways. Okay. Now, your question may have been, how about, because I'm answering two questions, right? So that was answering question 1. How about connections between data center 1 and data center 2? Well, by default, this is not available. But as of 2022, AWS introduced a new feature where data center 1 can talk to data center 2 using AWS private infrastructure. So instead of going and buying a DCI or data center interconnect line, right? between your data. You can use AWS as your DCI, right? And then end up using AWS private infrastructure to run from Direct Connect your Gateway 1 to Direct Connect Gateway 2 all the way to your data center. So that's possible. But obviously it comes at a cost, right? So you got to keep that in mind as well. Hope that answers your question.
Okay. Are there any others? Oh. How many backups should we have when creating a database for a client? Okay, so the business requirements are going to drive this. You know, how many databases does a client have? It may have 5 different databases. What is the value of the data for that organization? What is the risk if that data is compromised or lost for that organization? What is the likelihood of risk for that organization? We can take these things and a whole lot other questions, and then we can analyze that information and we can make a determination. But it's not something we're going to get very simply or very quickly. It's not like we can say 1 or 2 or 10. It's going to be highly dependent on the mission.
Okay. Would this work around the SuperNet through Direct Connect Gateway have a higher latency as the traffic goes to the office location before being directed back to the other VPC? Yeah, it definitely would have a higher latency than having, VPCs connected through a transit gateway or peering transit gateways together, right? But it's still, and you end up using your direct connect link or private link for traffic that is not intended from on-premise to cloud. So it's really, I don't see a lot of use cases for this unless you're limited with your current design. For example, you have an existing design where you don't have a transit gateway and everything is connected through the direct connect. And then it's kind of like, an option that's available. But if you were to set this up properly, you probably want to use a transit gateway and then peer everything through the transit gateway. Mike, you are muted. I'm not sure if it's your
Mike, you muted yourself somehow.
Go figure. So no, these slides are internal and personal to us. We each make slides not for the point of sharing them. This content is available for sharing and you can go watch it free. And we have some free ebooks that you can get as well and attend a lot of free webinars. But these slides personally, I have only 4 words per slide on the majority of my slides. Just reminds me to go talk about something. Benedict's slides are personal to him that he's created, and most slides are personal to them. We only put down on slides what we truly need to be able to remind us to deliver what we need. We're not in the business of doing what's called death by PowerPoint, where we read PowerPoint slides for you that are written word for word. We're really here about trying to make you have a good education. So watch these videos as many times as you like. Come to some pre-webinars and learn. And we're not going anywhere. We've got lots of opportunities for you to be able to ask questions and learn more. So the next question, the challenge though, that a single direct link is a single point of failure. Absolutely true. Any single link is a single point of failure. So maybe you need more than one direct connection based upon your bandwidth needs. Maybe you can do a direct connection with a VPN backup. But absolutely, anything is a single failure, including a single cloud, no matter how many availability zones and regions you use. And here's why. It's all on a common network. So if a single cloud gets hacked, it goes down. If the network were to collapse, the whole cloud goes down. If the cloud's control plane goes down, it's a single, and that can take the cloud down, the whole cloud. So, yep, single point of failure.
Okay, so second question, I can answer that one if you want. So is there a one-to-one relationship between VPCs and virtual interfaces, right? Meaning, if there are 10 VPCs, we need to connect 10 virtual interfaces. It depends. It depends on the type of virtual interface you're using. If you're using a private virtual interface, then yes, that's a one-to-one. But if you use a transit virtual interface, then no, you can use that transit virtual interface to connect to a transit gateway. And then behind that transit gateway, you can have as many VPCs as the transit gateway allows you or permits. These updates from AWS, are they implemented through the CLI, or do we need to redeploy a new script for an infrastructure with a transitive connection? I'm not sure what you mean here. Does anybody understand the question?
I'm not actually sure at all. What he means, which updates?
Yeah. Oh. I don't know. I really I'm not sure what you mean by this question.
Why don't you ask that question on Slack, Valerie, and we'll happily answer it, since you might be limited with what you're able to say and we don't understand it.
If I get a 9 gig, no.
If you get a 9 gig rate limit on a 10 gig direct connection, you get billed for 9 or 10. Well, you're going to pay for the link to the cloud, to the provider is still going to be 10 gigs. You're not going to pay for the full 10 gigs. But, you know, if you're going to rate limit at 9 Samsung, it's going to get real funny, because the maximum throughput on a 10 gig link is about 9 gigs when you account for headers. So that's an interesting one. I don't think you'll be saving much at that point. And actually, you'll probably pay for more, because here's the way the business model works on these direct connection partners. They charge you a higher rate per data than you would normally charge, because they're giving you fractional data. So you would probably pay more for 9 gigs on that 10 gig link to be rate limited than you would by getting the 10 gig link directly straight from the provider. What's the difference between bandwidth and speed? There really is technically no such thing as bandwidth. It's technically the speed. You know, we started coming with baseband and broadband, and a lot of that had to do with the frequencies that we were actually changing, that we were sending the data, and then it got colloquially termed, oh, the bandwidth, you have the speed, but it wasn't technically the bandwidth.
Okay, so this is the second part of the question, Mike. And then after he's asking the difference between bandwidth and speed, I'm asking if this as AWS asks for the speed every time, and it confuses me what to say.
I would say the speed, and the speed is going to be in bits per second, megabits per second, gigabits per second. It's always going to be the speed.
Yeah. Usually, for example, on let's say network devices, you see both speed and bandwidth. Usually a speed is the actual speed, the rate limit of the interface, but the bandwidth is really more of a software. Think of it as it's something for different routing protocols to use. Different routing protocols use it differently, but it doesn't actually affect the speed of the link.
No.
When you put the bandwidth command, for example, on a CLI of a router, but the speed definitely does affect it. That's the actual physical speed.
And say what Mo's actually referring to here is, on your routers, they have the ability to calculate the speed and determine the best path through the network. And it's actually the speed of the link. A 10 gig link is 10 gigs. But one of the software developers at Cisco thought that it would be fun to use the bandwidth command. So you can modify the link speed by telling it the bandwidth, and the routers would know to calculate that bandwidth software command that somebody put in there and consider it to be the speed, but it wasn't actually the speed of the link. That's a good point, Mo. Folks, get some additional books and materials for study. Yep, that's exactly what we said in the beginning. Never rely on one source. When you were preparing for your first CISSP back in 2006, you used 10 books to prepare. Knowledge is power. Completely agree. Now, the reality is there's not a lot of good books on the AWS Advanced Networking, but we referred you to the most authoritative sources. We referred you to the IEEE for the Ethernet specifications. We referred you to the Internet Engineering Task Force, and we refer you to the AWS documentation, which is the source of the material. That's where you go. you get your highest and best rated things. So we strongly, strongly agree. And every time we teach a course, we always talk about our books. We recommended the Stevens TCP/IP book. We recommended the Internet Routing Architectures book at the beginning of this course from Bassam Halabi. We recommended Routing TCP/IP volumes 1 and 2 from Jeff Doyle. And absolutely, completely agree. We're architects. I've read hundreds of, actually I read thousands of books in my careers, and I think it's a great thing. Read, and learn, and try to get better at every day. Completely agree.
Does the transit gateway connection goes through an ISP before reaching another region? No, it does not go through an ISP, because if you have a connection between two transit gateways, this is using AWS global infrastructure. They have a global infrastructure. They use it for many different services. And so this will be a private connection from one transit gateway to another transit gateway.
One more question, and then I am up, and then I'll go for a little bit, and then at some point I think we break for lunch, and then we come back.
Okay. So I can summarize this question. I read it briefly. So basically, if you're using a VPC endpoint, right? And usually VPC endpoint, you point it to a service. What Samson is asking, can I use that same VPC endpoint or VPC interface endpoint and for multiple services, not just for one? And the answer is no. The VPC endpoint and interface endpoint is only for one service. So if you wanted one for just like you said, you wanted one for a Lambda function, another one for an S3, then you would need two VPC interface endpoints, one for each.
All right. Well, you know what? Let's do some DNS. I will start the DNS, then we'll go to lunch, and then the rest of the team will do some more DNS stuff with you, which is, to me, is kind of great. Kind of fun. Anytime we talk about anything network related, I become pretty happy. Okay, so now let's talk about DNS and Route 53. So, DNS, what's the point? The domain name system was designed to make it easy for us to remember how to reach things. See, every device on the internet needs an IP address. And it's totally possible, if you've got the memory, to just pop an IP address into a web browser to connect to a website, for example. It's totally possible on a server, if you're trying to map a network drive to a server, to put the IP address of the server versus the server name, and it's going to work. The problem is, how do you remember all those names? And that's where things get on the fairly complicated side. So if you wanted to figure out how to go to Amazon.com, you could remember their IP address, or, and here's the or, you can type www.amazon.com into your browser. And DNS, or the domain name system, could then translate the IP address, which is really what you're trying to connect to a user-friendly name called Amazon.com. And that's really what we're talking about here. So the whole point is to map a name to an IP address. So I'm going to give you guys a little hands-on thing to play with real quick. Think we'll have fun with it. And then after that, we'll start talking. So I would like all of you on your computers, if you're on a computer, if you're on Windows, get me a command prompt. If you're on a Mac or a Linux system, get me a terminal window. And in that terminal window, I want you to type something. I want you to type www. I'm sorry, don't type that. Type NS lookup, NS November Sierra, L Lima, O Oscar, K Kilo, U Uniform, P Papa. So NS lookup, and then type www.amazon.com and hit enter. And you know what you're going to see? You're going to actually find the IP address, or at least the content delivery network's IP address for Amazon.com. I'll do it as well. Amazon.com. And the IP address that I'm getting for my local CloudFront distribution, and we'll get into content delivery networks, is 18.161.75.84. And they could be using various flavors of DNS routing, but that's the IP address that I get when I do an NS lookup for Amazon.com. And it's a lot easier to remember that than it is the actual Amazon.com than it actually is that. So if a domain name maps something friendly to an IP address, what goes into this? Well, there's actually three parts of your domain name. The host name, which is the name of the system, the domain name itself, and then the top level domains. So a host name could be Mike EC2. The domain name would be gocloudcareers.com. Would be gocloudcareers, and the top level domain would be .com. So if we're dealing with a web context, the fully qualified domain name might be www. The domain name might be gocloudcareers, and the top level domain may be .com. And of course, other top level domains like .edu, .co, .uk, .gr for Greece, like where I'm from. And that's really what we're talking about when we talk about the domain name. The host name, domain name itself, and then the top level domain. And that's what we call a fully qualified domain name. And a computer and a DNS system can resolve a fully qualified domain name for you. Now you can also create a subdomain. For example, you could buy gocloudcareers.com, and I can have a subdomain called training.gocloudcareers.com. It's called a subdomain. And many times organizations buy a domain and they create little mini subdomains inside of their domain. So that's something you can deal with to just put it into context. So now let's talk a little bit about top level domains. The top level domain is the highest part of the domain thing that you're going to hear about. And that's typically where you hear something that ends in .com for US sites, or .net, or .edu, or .co, or .uk. Now, where's the control of these top level domains? They're typically controlled by ICANN, which is an acronym for the Internet Corporation for Assigned Names and Numbers. So, global organization. And they typically own the assigning of the names. Now, the top level domains are going to be the second highest level of DNS because DNS is hierarchical. And all of this, of course, comes under the root domain. And then the root domain will be the overarching structure that contains all of the subdomains and every single folder that would belong to, say, a website. Now, lots of top level domains used today, more of them coming. Even .aws is a top level domain. So top level domain servers are going to be groups of servers that are going to facilitate the generation of websites' IP addresses. So hopefully that kind of explains some of it. Now, when we talk about DNS, we also have the concept of a DNS zone. DNS is going to be broken up into multiple zones, and these zones are going to be managed separately in the DNS namespace. And they're going to be managed, of course, by different entities. And by dealing with it this way, it's going to allow for simple and more authoritative and more fine-grained control of all the components of the DNS. And this doesn't mean that zones necessarily have to be geographically isolated. It means they are logically separated to separate degrees of control itself. And this is going to tie into the fact that the domain name space is going to be a hierarchical system with the root domain situated at the top. So I typically look at it like this. I see these, you've got your root domain, and then your first level domain, and then your second level domain, and then your third. So here you've got your DNS, and then your first level domains are your .com, .net, .edu. And then your second level domain could be .google. And then Google has these subdomains, drive.google.com, mail.google.com, etc. So that's typically what you're dealing with. Now, we're going to get involved into domain registry and domain registrars and domain registrants. You may see these kind of questions pop up. Kind of important to understand it anyway. So what is the domain registry? The domain registry is really just a database that contains all the DNS names and all of the associated information from the top level domains. And, there are organizations that manage these top level domains. For example, VeriSign manages all the .com domain names. And these organizations are all under the umbrella of, ICANN, the Internet Corporation for Assigned Names and Numbers, which is a nonprofit organization to kind of manage all the vital DNS resources. And ICANN will also create a policy and define a policy of how the names and numbers of the internet should run, and has to some degree centralized control of the DNS system. So that's domain registry. Now, who is the domain registrar? When you want to go buy a domain, you go to a domain registrar. GoDaddy is a domain registrar. You go to Amazon and you can buy Route 53, buy a domain from Route 53. And then, so they're going to be the domain name registrars. They will handle the reservation of domain names and mapping them to IP addresses. And they don't actually manage or maintain the domain name. They act as a vehicle for the end user to use their domain name. And then, of course, there's the domain registrant. The registrant is the person who purchases the domain and uses the domain. Usually it's a corporation or an individual or anybody that has the ability to want to buy and use the domain. Registry at the top. Registrar is the people that sell it to you, like GoDaddy or AWS, and registrant, the actual user. So hopefully this makes a little more sense graphically. At the top, you've got that domain registry. Then you've got your domain registrars that you purchase from, like GoDaddy or AWS. There's lots of companies that resell the domain. And then the registrant is the actual user. So I think we timed this almost kind of perfectly. We have the next component of what we're actually dealing with here is going to be the DNS record types. We're going to get pretty heavy into this, and it's very important information as you plan on your routing your information back and forth, your failover policies, your performance policies, potentially red, green, blue, blue-green deployments, and so many other things. So I think this is a natural point to break. Right after lunch, we will get involved into the DNS record types, and from there, we'll have a lot more content to cover today. So we'll begin again at exactly 2 p.m. Give me a hashtag AWS Advanced Networking. If you enjoyed the videos from lessons this morning, please give it a like. If you're not a subscriber, please subscribe and hit the bell to be notified of new videos. And of course, get your free labs. We have almost 2 days worth of labs. We have about a day and a quarter right now, but behind the scenes, one of my CCIAs is creating a lot of networking content for you guys to learn networking, more networking. So go download it. They'll be available and they'll keep getting updated. We'll see you back in 1 hour at exactly 2 p.m. Eastern Time. Welcome back, everyone. We are here for part 4 of our AWS Advanced Networking Bootcamp. This is to prepare you for the ANS-C01 exam, and this is a full AWS Networking Specialty Course. For those of you that are back, that are new, my name is Mike Gibbs. I am joined by Benedict as well as Mo. We're on the 4th section of this. If you've just joined us and you haven't been here before, you can go back and watch the first 3 sections anytime you desire of our AWS Advanced Networking Bootcamp. They are stored on our YouTube channel, so you can go back and watch them at any time. If you've just joined us, I wanted to let you know that we have a very aggressive agenda, and we've got a lot of labs for you to go through. Maybe we get time to do them tomorrow. Maybe we run out of time, but no matter what, it doesn't matter. You can sign up and you can go through these labs. There's nearly 2 full days of labs. And in this free bootcamp, effectively, that means we've had nearly 5 full days of training from start to finish by the time this is done. So if you've not gotten the labs, please go and get the labs. You can get them in the chat box as well as the description of this video. So kind of keep that in the back of your mind. So this morning, we talked about a lot, but we ended talking about some intro level things to DNS. We talked about registrars. We talked about registrants. We talked about, for example, about the DNS hierarchy. Well, what's left? Now we're going to talk about DNS routing and DNS record types, for example. So we're going to get to that. So make sure you're here. If you're not a subscriber of the channel and you want to watch more videos like this, please subscribe. If you enjoy our content today, please hit the like button, and it'll signal the algorithm to send this to more people. We want to help as many people as we can with our free AWS networking training. So we're going to get back to the content. Thank you all for being back. And we'll be back in a little bit to answer any questions you may have. Okay, so we're going to talk about DNS records. So DNS records are also called zone files, and what they really are is they are a particular set of instructions that are located in the DNS servers that are going to provide information about a domain. This can include things like the IP address that was associated with the domain and how to handle requests. Now, these requests are going to be in a particular format. It's going to be called DNS syntax, and it's basically a text file. But the DNS syntax is going to tell the DNS server how to carry out its actions. And when we have a record, there's typically going to be something called the time to live. And that's going to be how often the DNS server will need to refresh the records. It's basically instructions. And you can think of it as that, if the time to live expires, it's considered bad information and it's removed. So a lot like a health check. Now, time to live is going to be normally measured in seconds unless it's going to be confirmed otherwise. So kind of keep that in the back of your mind. See if I can do something about my video here. Not much I can do. Let me try doing that, see if it gets a little bit better. So let's begin with the type. There's several types of DNS records that you do need to know. And there are others that, are nice to know. We're going to go through the ones that really matter. So when we have DNS records, there's several that you need to know. And they're going to be the alias record, the CAA record, the TXT record, the PTR records, the NAPTR records, the SPF records, and the NRV records. And we're going to explain what all of them are. The first thing is an alias record. And an alias record is similar to a scene name record, where we're going to map one thing to another thing, but it's going to be at the root domain level. And you typically use these to point AWS resources such as load balancers to other domain records, maybe inside of the same hosted zone, inside of AWS anyway. We're going to have a CAA record, or a Certificate Authority Authorization record. And that's going to enable domain owners to be able to specify which certificate authorities are going to be allowed to issue certificates for their domain. And again, why are we issuing these certificates? We're issuing these certificates for SSL/TLS encryption. And we often talk about SSL, but actually SSL we haven't been using for a while. It's now TLS, even if it often goes by the SSL name. So, okay, that did not improve my video at all. So let me try going back to the previous video setting that might have actually been a little bit better. I have no idea what's going on with our video here. So the next thing that we're going to talk about is a TXT record. And these records are going to be used to store the text information. And it's going to be used for a variety of purposes. But typically the TXT records are going to be things like domain ownership, which you could verify, to provider email sending policies, and implementing any of their services requiring, say, textual data. Now, there's going to be some other records called PTR records, or pointer records, and they're going to be used for reverse DNS lookups, allowing the mapping of an IP address back to a domain name. So you've got the domain, the IP address, now you want to know which domain it works with. You can think of this as like a reverse directory in phone world, where you've got the person's phone number, and then you go look it up to see who it actually is that called you. There's an NAPTR record, which is a naming authority pointer record, and that's going to facilitate the complex redirection of services. It's often used in protocols like voice or SIP, which is a session initiation protocol to set up voice calls. And they're often used alongside SRV records, which are going to be used for advanced routing. Another type of record we should talk about is the Sender Policy Framework, or the SPF record. And that's going to be used to help prevent email spoofing. And it's going to be used to specify authorized mail servers for a domain. And if we know who the authorized mail servers are, and we're going to be setting up these SPF records to reduce spam and phishing attempts. And then, of course, there's the NRV records, which are the negative response verification records. And these are typically less common, but they're going to be designed to authenticate negative responses in DNS queries, ensuring that such responses are actually from who they're supposed to be, the authoritative sources. Now, these records are kind of more of your specific functions in DNS management. And you can think of them from domain verification all the way through email security. So now let's talk about Amazon and their version of DNS. So you can always set up your own DNS servers. And if you've got a multi-cloud environment, you might actually need to maintain your own DNS server as part cloud. But for the purposes of this exam, AWS has their own fully managed DNS servers, and that's going to be Route 53. Now, AWS also does have an EC2 DNS, which is what gives you your fully qualified domain name for your virtual machines. But in this particular case, we're going to be talking about Route 53, not the EC2 DNS, which is used to map fully qualified domain names to your EC2 instances. So let's talk about Route 53. It's going to be a highly available platform because it's going to use the entire cloud. So as long as the AWS cloud is up, it's probably going to work. And with DNS, we use something called Anycast services, specifically Route 53. And Anycast is going to give us some very good latency and very good performance. Now, I'm actually going to draw out Anycast because it's going to be a little bit on the complicated side to explain without a picture. And if I gave you a static picture, I don't think it would be very helpful. So here's what we mean by Anycast. So I'm going to have two DNS servers, and I'm going to put the same IP address on them. Now, Google uses 8.8.8.8 for their DNS servers. So I'll just use that example because Google has extremely good DNS. And realistically, what happens is you've got the entire internet and in this particular environment. And I'll show you why this gives you great performance. And it also gives you incredible redundancy and failover. And AWS does the same thing. So in this particular environment, we have two servers. And both of these servers have the identical address on them, the identical IP address. Now, you might say, Mike, every address needs to be unique. Absolutely, every IP address needs to be unique, because if we don't have unique IP addresses, we're going to go to the closest one, and we might not miss the server. So here's what Anycast is. We have two servers with the same public-facing address that are synchronized to each other in the backend. I've got a user, and when the user wants to look at a lookup, the user is going to send their data to the router, just like I showed you on day one, where the router will forward the packet. It's going to go to whatever has the best path in the network's routing tables, which under normal circumstances, let's say this is the East Coast of the US. And I think this will help. Let's say this is the East Coast of the US, and over here we're on the West Coast of the US. Places, let's just say like California. And the East Coast, let's say we're near Florida. So I've got a user over here which is sitting in Florida. And Florida's on the East Coast of the US. And when they do their DNS lookup, they are routed to the 8.8.8, which is configured as their DNS server. They hit their closest DNS server, and the DNS server responds. And that works absolutely terrific. Now we've got a user in California that wants to actually go to someplace on the internet. They go to www.gocloudcareers.com. They enter it in the browser. The DNS servers, which are using Anycast, are located on the West Coast. They send a response back to the user who was sitting in California. Everything is working normally now. This is the way it's supposed to be. So now I've got a user who's sitting in California, and the user wants to go to www.gocloudcareers.com. But for some reason, this DNS server that's sitting on the West Coast is down. It's down. So what'll happen is the user will try to create a DNS request. It will get forwarded to the local network. The local network will realize that there is no local DNS server 8.8.8, and it will forward the request to the East Coast, which is on the opposite side of the country where the other server is, and that server will respond. So when we use Anycast, what we're actually doing is we're creating two of everything, or three of everything, or 10 of everything, or 100 of everything. We're all giving it the same address, knowing that routers will route you to the closest environment that you need to. So I hope that makes sense. Now I want to go over some other key records. I want to go over the A record. And with DNS, I gave you some of the deep, more meaty things. Let's go to the simple things. Here's an A record. Is it maps a name to an IP address. So an A record is very simple. Map the IP address to GoCloud Careers to GoCloud Careers. That's it. Standard DNS. Now, if we're dealing with IPv6 versus IPv4, they'd call it an AAA record. But for IPv4, it's called an A record. No big deal. Another type of DNS record that you can typically think of is something called the CNAME record. And it's a domain that it's very similar to an alias record where it maps a domain to another domain. And it enables you to, let's say you've got a website and the website's been up and running for years, and then the company changes names because they buy a company and they don't want to lose all that website traffic. They create a CNAME that says go to the old company to the new company. All that. So that's really all you're doing with the CNAME record. Now we will also have these NS records, which are name server records that we need to create. And these name server records are going to be the name servers that are going to be responsible for our DNS on when we create them. That is the name servers of record. And these are the authoritative name servers that are going to propagate our organization's official DNS information. Then we're going to have an MX record. If you want to be able to send and receive email, you're going to need an MX record. And then you're typically going to also need a start of authority record. And this is going to talk about the primary name server for the domain, who is the responsible party for the domain, and it's going to include a timestamp that changes anytime you update your domain. And of course, the number of seconds before domain zone information should be refreshed. So going back to AWS Route 53, it is the AWS managed DNS service. It gives users, typically speaking, a low-cost way to deal with DNS routing as opposed to doing it themselves and maintaining their own systems. But there's times where you want to maintain your own DNS records, like multi-cloud solutions, which is what 98% of organizations use. And maybe they need a DNS server in each cloud if they're looking for extreme availability. Or maybe it's a simple solution in just the AWS cloud, and we can use Route 53, and it's fully managed, and we don't have to think about it. So Route 53 supports IPv4 and IPv6. And we can use it to route people inside of AWS resources, like our AWS stuff to our other AWS stuff, or it can be used to map to things outside of AWS. And DNS, like Route 53, like any other form of DNS, is going to use a health check. And the health check is going to be really important to understand things. And we'll talk more about health checks in DNS. We'll also talk about health checks in as it pertains to load balancers as well. And we also, to some degree, talked about some health checks as we were dealing with in BGP. So keep that in the back of your mind. Now, you can register your domain with Route 53. You can purchase a new domain with Route 53. And when you do so, it'll actually automatically configure a hosted zone for each domain, which is quite easy for you. One of the benefits of using Route 53 to register your domain is you get privacy protection on your whois records at no charge. You know who is the owner of this, which is kind of nice. And the other benefit is that you can manage all of your other resources and get it still in the same bill as AWS. Now, that's not enough of a benefit for me to use it if it's the wrong service, but if it's convenient, that's terrific. And with Route 53, you've got access to a whole lot of top-level domains, approximately 150 or more of them when you register your domains. Things like .net, .edu, .co, .aws, that kind of thing. Now, you can transfer a domain that you have from another organization to AWS. Maybe you purchased a domain from a company like GoDaddy, and now you want AWS to manage it. That's completely possible. Now, when you do so, there's going to be some prerequisites for transferring one domain from one registrar to another. And that's going to be fairly based upon the specifics of where you are transferring to and who you were on prior to the transfer. But some general guidelines are that you must have registered the domain with the current registrar, or transferred the domain to the current registrar at least 60 days ago. So it can't be a brand new domain. If the registration domain expired, it's going to have to be restored for at least 60 days before you can transfer it. If you want to transfer the domain, a couple of things that are going to be here. You can't transfer it if the following are listed in your domain status. Client transfer prohibited. You don't transfer. Pending delete, pending transfer, a redemption period, a service transfer prohibited. And the registries for some top-level domains just don't allow transfers until these changes are going to be complete. And so keep that in the back of your mind. Now, what is a hosted zone? A hosted zone is going to be a concept in Route 53. And a hosted zone is comparable to a traditional DNS zone file. And this is going to represent a collection of records that can simply be managed together they can belong to it, or they can belong to a parent, they can belong to a single parent domain. And all resource record sets within a hosted zone must have the hosted zone's domain information, domain name, and its suffix. For example, Go Cloud Careers hosted zone may contain records named www.gocloudcareers.com and potentially docs.gocloudcareers.com, but this would not include a record named www.gocloudcareers.net. We don't have a docs.gocloudcareers.com, but that was just used as an example. So when we're on AWS, we've got a lot of ways for which we can direct our traffic with Route 53. And they're going to be simple routing, weighted routing, latency-based routing, failover routing, geolocation routing, multi-value answer routing, and geo-proximity routing, which is really about traffic flow. So let's talk about what these are. Simple routing, real simple. You create a route entry for your website. You've got one record. You type www.gocloudcareers.com, and it takes you directly to GoCloud Careers as if you had a single web server. That would be a simple routing policy. Standard thing, map one IP address, and it always goes to the same destination. No, that's great for simple stuff. But let's talk about some other DNS routing options. We're going to talk about weighted routing. Weighted routing enables you to determine how much traffic you want to send to one location versus another location. So think about it this way. You've got a private cloud. You're connected to the public cloud. You've already paid for the gear on your private cloud. It's going to give you better performance and lower cost than the use of the public cloud for your website. Send 80% of the traffic to your data center because you know your data center has got the capacity, and you don't have to pay to use that capacity because you already bought it. And send 20% of the capacity to AWS and pay for what you use in AWS and use the majority of it where it's cheapest, where you already own it. That's an option. What about rolling out new applications? Let's say a company's got a new website they want to try out and some new software on it. Do you think you should take the entire world and send it directly to that new website and hope the new website doesn't crash? Or might you use a weighted routing policy and say send 90% of the traffic to the current website, 10% of the new traffic to the new website, or at least the load balancer of the new website, and see what happens. If the new website works well, the users adopt the new website, you cut all the traffic over to the new website. And then when you want to test new code, you can keep doing this again and again with various routing policies. Or send 50% of your traffic to AWS. Send 50% to Azure. Instead of, if you needed a 5.9 system, why would you use 2 availability zones in 2 regions in AWS and still have a single point of failure when you could do 2 availability zones in Azure and 2 availability zones at AWS? You're purchasing the same content, and basically the cost is almost the same, and now you've got 2 clouds, much more high availability situation. Now, the next type of routing we can talk about is latency-based routing. And latency-based routing is going to allow you to direct traffic based upon the latency of the network. So you could have a web-based application that's hosted in London and one that's in Tokyo, and send your users in Asia, specifically Japan, to the Tokyo one, and to users in, say, Greece, like where I'm from, send them to the London-based one because it'll have less latency and it'll be closer. And that's something you could do as well. Next, we're going to talk about failover routing. Failover routing should be pretty simple. Point everything to my data center. Data center goes away, move it over to the cloud. Or have everything in AWS because we're an AWS shop. AWS fails, route everything over to Azure. That's failover routing. And the way these things are going to work is going to be via a health check. And actually, all these DNS policies that are going to need anything are going to work with a health check. So I'll show you what that means as soon as we go through these policies. The next thing is going to be a geolocation policy. Well, geolocation is going to route to you where you're closest. So when you get on the internet, you're going to have an IP address, right? It's going to see your IP address and it's going to identify where you're at. So if I'm in Florida, it may make sense to send me to a website in Florida. If I was in England, it may make sense to send me to a website that's in England. If I was in India, maybe send me to the Indian website or something to that. So that's when you're dealing with geolocation routing. It's going to identify your source IP address. Now, many of you have tried using VPNs, those public VPN services that are out there to mask your IP address. So I want you to understand this. If you use a VPN service and it sends you out and it sends you to Athens, Greece, even though you're sitting in Palm Beach, Florida, you're going to be perceived as coming from Athens, Greece, and you're going to get things that look much more like Greek websites than if you were in New Jersey or Florida, for example. So understand that it's going to work on the source IP address. So if you're using a VPN and connecting to another part of the world, you're going to be served by things that are in another part of the world. Now, you can also do something called multi-value answer routing. And that's very similar to simple routing, but we're going to have health checks. And if an application is not healthy, it's just not going to receive it. It'll go somewhere else. So we'll talk about geo-proximity routing. And geo-proximity routing enables you to route resources kind of based upon the geography that you're in. And it's not a very hard and firm kind of thing. What happens, you go to AWS and you get to create something called the bias, and it reshapes regions of the world based upon the bias that you create. And by doing so, that's where it's going to prefer your traffic. You know, this is a graphic that we got from AWS, and you can see those regions 1, 2, 3, 4, and 5. And that's what you're talking about in that geo proximity there. So I want to actually draw a health check for you to see if it makes any sense, because I think it'll help you understand some of the more complicated DNS concepts as we go further. So let's say I have 2 data centers. I don't care if it's 2 data centers or it can be 2 clouds, it doesn't matter. I'll make it 2 clouds because that's more realistic, with 98% of organizations using more than 1 cloud. And how do you make multi-cloud work? It's networking. So this is networking training anyway. So let's say we've got DNS up here. And let's say we want to send 50% of the traffic to each location, 50%. So as it stands right now, 50% is weighted routing, right? Goes to Azure. And on the other side, we're going to send our 50% of the traffic to AWS. Now, I want to make it very clear to everyone. If Azure goes away, we don't want to send our 50% of traffic to Azure. We want to send it to AWS. And if AWS were to go away, we want to send the rest of the traffic to Azure. So how does DNS know? Well, DNS kind of runs like what's called the health check. And it's very simple. So the DNS health check will look just like this. From the DNS server, we're going to get a request to the AWS. AWS, are you awake? You alert? You oriented? You alive? And AWS is going to say, yes, I'm here. And the health check has been passed. And at the same time, DNS is going to say, Azure, Azure, wake up. You there? Yeah, I'm here. I'm here. Everything's good. So now everything's going to be sent back and forth. Now we have a health check that the next health check is sent to AWS. AWS, are you there? It says, I'm here. Life's good. Then the DNS health check goes sent to Azure. Are you there? I'm here. And then either one of these cloud providers goes down for whatever reason. Say Azure goes down. The DNS asks Azure, are you there? Azure doesn't respond. The AWS, are you there? AWS responds, I'm here. Azure, are you there? No response. AWS, are you here? Yeah, I'm here. Azure, are you there? No response. DNS marks Azure as unhealthy because it missed a certain number of health checks and starts sending all traffic over to AWS. Now, if AWS has an auto-scaling policy for this web app, which you have in 2 different clouds, all that traffic will shift over to AWS. It'll run great at 50% capacity. The auto-scaling will scale out, and now your solution is up and running, and it is doing absolutely wonderful. So that is the way the health checks work. So let's talk a little bit about Route 53 Resolver. So Route 53 Resolver is going to be the equivalent of Route 53 for the on-premise environment. And Route 53 Resolver will make hybrid clouds easier by enabling seamless integration between your DNS query resolution along your entire hybrid cloud. Again, this is one way you could do it. You could also have your own DNS systems that maybe you would get from, say, F5 in your data center and your cloud and have some independence and freedom and more control. But you could also use Route 53 Resolver, which is going to allow customers conditionally forward DNS requests from your VPC to your on-premises environment. And Route 53 Resolver is going to include DNS server information, which is available by default in all VPCs, and it will respond to DNS queries from AWS resources and from public records. Okay, so I talked a little bit about DNS health checks. So let's take some questions at this point, and then we'll get into some of the fancy stuff like Mo will take us through. I believe it's Mo that'll take us through multi-account roles and things like that. So let's do some questions, because I'm sure there's some questions on DNS. Okay, who has questions? Does Global Accelerator use Anycast?
Global Accelerator, right? Yes.
Yes.
To answer your question, yes. Can a centralized domain name between multi-cloud, for example, using Azure DNS and Route 53, use the same name server records for query DNS requests and giving percentage traffic to distributed? Well, if I understand you correctly, you want to use Route 53, a public hosted zone, and an Azure public hosted zone, and then load balance between them. I'm not sure how, that's a strange setup. I haven't seen it done that way. I'm going to have to think about it. Mike, do you have a...
I was kind of not understanding the question completely.
Yeah, I'm not sure exactly what he means, but what I'm understanding is a little bit counterintuitive.
So, let's try this. Can you rephrase that, Mohammed? Maybe make it a little simpler. And if you struggle to rephrase it, let's try if you rephrase it. If not, I have a backup plan so we can understand your question. Name not found. I'll have Benedict or Mo answer this. Does the DNS resolver live as a virtual machine on premise and map to the cloud resources?
So the DNS resolver, it can be a virtual machine on premise. Yeah. What you're asking about is using an inbound endpoint where you would resolve your on-premise DNS request for a certain zone to AWS. That can be done. So yes, that can be done. It's actually one of the slides I'll go through in a minute. So I'll demonstrate that for you.
What kind of records do you create to route traffic between servers on two public clouds?
So this is one of the things that we'll discuss in the next slide, but you can, it depends what you mean by records, right? If you mean by servers, right? Do you mean like a DNS server, or do you mean an actual application server, right? If it's an application server, it depends on your traffic. If it's IP version 4, you can create an A record, right, to point from Route 53 to that server. Also, also if you mean to route traffic from one DNS server to another DNS server, right, then you might need an NS record or a name server record. So it depends on what you mean there. Mohammed, if you want to write it in Arabic, that's fine too. If you couldn't rephrase it in Arabic, in English, you can rephrase it in Arabic, and I understand, so I can try to answer it if I understand you in Arabic better. for me personally, sometimes it's easier to discuss these technologies in English just because that's the language we use to learn. But
And we know Muhammad, and we know where he's at. So if we're having a little communication issue, we thought we would try to make it as possible to use our native language. I know I like to communicate in Greek.
Yeah. Okay. How does Route 53 work when the load balancer comes in between? So you can create your A records, right? Well, you can create your entries, whatever so you have a DNS entry that points to a server, right? But what if instead of a server, you want to point to an application load balancer or a network load balancer? You can do that too. So as long as you have the fully qualified domain name of your application load balancer, then yeah, you can point your traffic to anything pretty much. Okay. So for example, I think this is Mohammed's, for example, domain name example for Azure and route at public hosted. Honestly, I'm not sure if I understand.
I'm still not sure either.
Can't be centralized domain name. Trying to put it together and try to understand it. Can centralized domain name.
Well, we're trying to interpret it because we really want to help. So if it doesn't have the context, it's often really hard for us to figure out what the intent of the question actually is. Is DNSSEC a feature in Route 53? Finally, finally it is. You know, it's funny, a year and a half, about 2 years ago, you almost couldn't use Route 53 if you required good security. But now DNSSEC has finally been integrated into 53. Good question there, good thinking. All right, are there any others? Otherwise, we will get into multi-account Route 53. All right, I don't see any. So if you joined us and you're new and you haven't, make sure you download the free labs. You know, we only have basically 3 8-hour days to run this boot camp. And we've got a lot of stuff that we're talking about in these 3 days, including some things that are outside of the curriculum because we truly want to help you. So if we have time on Sunday, we'll do some labs with you. And if we don't have time on Sunday, we have nearly 2 full days of hands-on labs, some on AWS and the rest in our data center to truly explain the networking things that you couldn't learn by looking at things on AWS because they hide the underworkings of the technology from you. So please download them. If you're having a good time, please give it a video a like. Please subscribe and hit the bell to be notified of new videos. And we'll get back to the content with Mo.
Okay. Bear with me for a second as I prepare my slides.
Networking people and slides. When I went into tech and I first became a network architect, there was a common thing amongst networking people. Do you know how to use your PC? Yes, for ping, telnet, traceroute, and that's it. Well, that's the whole point of my PC for networking people. We were all network. But Mo's actually got incredible good cloud architecture knowledge as well. You ready, Mo?
Yes. Okay, so multi-account, if you can share my slide. So multi-account Route 53, right? This is actually a very simple concept, and it can prove to be very, very useful, right? let's explain this with a demonstration. So let's say that you have an AWS production account, and it's called Go Cloud with the hosted zone of gocloudcareers.com. Okay, so you have Route 53, and you have your hosted zone that's gocloudcareers.com. Okay, you have another account, which is a demo account, right? This is where you create your demos. Maybe you demo this to your customers or just internally, right? Internal clients and so on. That account needs to use the demo.gocloudcareers.com, right? Okay, so how can we make this setup happen, right? So what we can do is, since we're in two different accounts, we can use what we call a delegation, right? And what delegation is basically, with Route 53, you can delegate a subdomain from gocloudcareers.com into the demo account that has demo.gocloudcareers.com. And to go to the slides and show you an actual demonstration of this diagram, right? So over here, as you see, we have gocloudcareers.com, right? And if you wanted to reach GoCloud, this authoritative server, DNS server, right, you can just query through your recursive server, and you should eventually land at this hosted zone, right, the gocloudcareers.com. So this is what you would have, right? You have a hosted zone called gocloudcareers.com, right? You have an NS record, or the name server record, right? And then you have an A record for your actual server, right? In this example, my A record points to an S3 bucket, right? Or I route my GoCloudCareers to an S3 bucket, right? Now, what you want to do here, you set up a second account, right? Well, not set up you set up as a hosted zone. So you would go to your demo account. You go to your demo account, you set up a new hosted zone, right? And inside that demo account, call that, demo.gocloudcareers.com. So that's your hosted zone, right? With that, you will get, same thing, you'll get, go back, you get an NS record, right? An an SOA record, right? And then you have your A record, which actually points to the demo account's S3, right? Your website or whatever static content you have on S3, right? So now you have those two separate zones, right, in different accounts. You want to find a way to connect the main account of production to the demo account, so that when somebody queries for demo.gocloudcareer.com, they will first hit the authoritative server of gocloudcareers.com, right? So you need the gocloudcareers.com to delegate the demo account to the demo domain to the demo account, right? So you want to send the queries or forward the queries towards the demo account. And the way you do that is you go back to your production accounts hosted zone, and then you create another NS record. And then in the NS record, you just copy the destination, which was part of your demo accounts NS record. So you take those and you copy them. And basically here, essentially what you're doing is you're saying, I'm delegating the demo account, the demo.gocloudcareer.com to the demo account. So if you need to reach anything that starts with demo.gocloudcareers, send it towards the demo account, right? And then the demo account, of course, it has, just like I said, it has its an A entry, right, or A record, DNS entry that points to the final destination, which is a server, an NS3 record, a server or an S3 bucket, and so on and so forth. So it's a very simple way to, create test demo accounts, or maybe just, you want to share your domain across different accounts, right? So do we want to take questions before we move forward, or do you want to keep going? Okay, we'll keep going then. So DNS security, right, or DNS sec, right? So with DNS sec, what you're basically doing is it's a method for you to establish authenticity of a DNS record, right? You're trying to avoid a problem that we call DNS spoofing, right? And basically, give me one sec. Create a new slide. Typically, you have, let's say, you're in an office, you have a recursive server, right? And we call it a recursive server because it recurses, or it does multiple DNS lookups before it gives you the final answer, right? And let's say you're looking for Go Cloud Careers.com. So you have your recursive server here, right? Then you have your root server, right? The root server points to all the different types of top level domains. So the .net, the .com, and so on and so forth, right? So we'll look for the closest .com top level domain, right? And so this will be the .com top level domain, and then under the .com, so this is the top level domain. And then under the .com, or the top level domain, you'll have multiple authoritative servers, right? One of them is Go Cloud Careers. Go Cloud Careers.com. So Go Cloud Careers is the authoritative server. So we have the root server, recursive server, and then the root server, and then we have the top level domain, and then the top level domain should be able to find the your authoritative server, right? GoCloudCareers.com. Now, the reason why it's called recursive is because you first ask for the root, right? You'll ask the root, and the root will get back to you with the .com, or the top level domain, and then you're going to have to ask the top level domain, and then the top level domain should give you the address of the GoCloudCareers.com, which is the address of the authoritative server. And then once you get that reply, and then you'll ask one last time, you'll ask the authoritative server, right? You'll ask the authoritative server, and then the authoritative server should reply to you with the IPs for whatever resource you ask for. Now, and a DNS, so now that you understand that process, DNS spoofing is when an unauthorized server acts as the authoritative server and replies to your DNS request. So it's a malicious DNS response, right? And then what you would do is you start sending the traffic to this malicious server. And then that malicious server, what they can do is they can do TLS termination, right? They will receive your traffic, and then they would establish a session with the actual server website on your behalf, right? And you will not be aware of that. So that can cause an issue, right? Obviously, there's some methods to help you recognize this type of problem or attack, like your certificates, right? But this is still an issue, right? We need to avoid. Now, what you can do is using DNS security or DNSSEC, and all what DNSSEC is that you establish a chain of trust, what we call a chain of trust, right? And basically, what you're doing is, as you can see, we have our root server, the top level domain, and authoritative server, right? The root server creates a digital key, signs that digital key, and then you have your first certificate for the root server. The top level domain would sign the root server certificate with its digital key, and then you're creating basically a chain of trust, right? You're signing your top level domain portion of the of that record, right? And then you're signing the .com, and then you're signing the gocloudcareers.com. So what ends up happening is that you have something like this. How do I write it down? Okay, let's see. Okay. Oh. Excuse me. Okay. Okay. So let's say, for example, we have gocloudcareers.com, right? So what you would do is, give me one second. Give me 1 second. Just bear with me for 1 second. It's not the best way to write this way, so let me use my tablet. So give me just a second. Okay. So in this example, let's say that we have www.gocloudcareers.com. Okay. So in this example, .com would be your top level domain or registry, right? This will be your registry. Top level domain, right? And then you have GoCloud Careers, right? Which is the domain owner. Oh, domain owner right? And let's say www is the service owner, right? It's the service that is part of the domain that is registered by the top level domain, right? So what you would have here is that the .com domain, you have a certificate for .com domain, and then that certificate is signed by the domain owner, right? Let's use a different color, right? Oh, okay. So you have this first certificate, and then this will be signed by the domain owner, but it signs both of them, right? And then the service owner would sign a certificate that is signed by the domain owner. So you have established a chain of trust so that if you have an unauthorized or bad actor replying to your request with a spoofed IP, so the DNS response is not an original response, not from the actual top level domain, then you will find that out based on the certificate, right? So the recursive server will receive the recursive server will receive a response that is unauthorized, and they will know that by a broken chain of trust. So that's basically how it works. And so if you want more information about how it's set up, right, what you need to have in place for Route 53 to support this, you can go to just Google configuring DNS sec for a domain name. If you just Google this, you should be able to find it. Should be the first step. But basically, that's what DNS security is. All right. Okay, let's take questions. Do we have any questions?
Let's see. Does anyone have any questions we can go through?
Okay, so someone rephrased Mohammed's question for him, and he said yes. That's it. So I'm going to put it up to see if it helps.
Okay. Are you saying so? Can I use a single cloud providers like Azure and AWS with the same records in both Azure DNS and Route 53 DNS? So the problem with something like that is who responds to who's the authoritative server here? It needs to be an authoritative server, right? So who responds, right? So if we're talking about careers.com, right? If I'm going to have it in Azure, and so if it's active backup, then maybe that can work. But if we're talking about two servers that respond to the same domain, I just don't see the value of that. I mean, technically, you can do it.
Sorry.
I'm trying to think of any problems that might occur in that, and
let's maybe extrapolate it a little bit. So let Mo think about that from an engineering perspective, and then let's think about this from an architecture perspective. Why would you? If you need high availability across two clouds, why would you use a proprietary AWS thing and a proprietary Azure thing when you can put real DNS servers on a virtual machine in both clouds, own your own DNS infrastructure, and control it? Once you start getting beyond the single cloud, you really want to get out of these proprietary type services. Because if you use two clouds, you want the availability of everything. So think about things like DynamoDB. They don't really work multi-cloud. Amazon Aurora, they don't work multi-cloud. But MongoDB does, or Apache Cassandra, based upon the amount and you would do that based upon your application, your read versus write load. So in multi-cloud, let's try not to put yourself in this position.
Yeah, I would say it can be done. I'm thinking about it from your main registrar, right? You can load balance and say, you know what, maybe geographically, right? Some traffic can go this way, or send this user to the nearest. But just like Mike said, it's just I don't see the value of putting your DNS servers on 2 different clouds, right? I don't see the value of that. For the multi-account DNS, how do you add the IP address in Route 53? That's an A record. If you want to add an IP address in Route 53, right, that's ultimately an A record. This IP version 4. So the demo will be your private. Why delegate? Because how would you do it otherwise? Because the main response is going to go to the authoritative server, which is the main accounts Route 53, right? So how do you, but your server is in a different, you don't want the same, he's what you're trying to avoid here, right? You don't want your main or the gocloudcareers.com, the host zone, your main hosted zone. You don't want it to take care or handle the A records for a different account, which is a demo account. You want the demo account to take care of that, right? And that's why you're doing a delegation.
Is this similar to tunneling? I don't know, is what similar to tunneling? Or does each level have different hashing to add to verify authenticity? Can either of you interpret that? Because it's missing some of the context. Name not found. If you can add the first part of that sentence, what you're referring to, is there. Because I don't know which part of what Mo described that you're referring to. Oh, he says the DNSSEC.
DNSSEC. It's not the same concept. No, it's not the same concept. It's more of, you have a chain of, so you have your certificates, similar to what you do for, web browsing, right? If you look at your, the website you're visiting right now, you should see a chain of certificates, right? To know that this is authentic, right? It's in the same manner you're doing that for DNS now, right? That's basically the concept.
Tico.
How did you say that rogue DNS servers are able to intercept and request in the first place? Well, just replying to your DNS request with DNS response. They saw your DNS request and replied before you get an official response, right? So that's how it could happen.
Yes. Another way DNS hijacking occurs is people actually infect local user PCs and redirect them to the wrong DNS server. And, so there's the way Mo described, there's the way I described. But the whole point of using the encryption piece here, Tico, is you've got your endpoint verification through your certificates so that Mo is whom Mo claims to be. So even if I were to go to your computer and have a little fun with it and send you to Benedict, who's a DNS server, but Benedict wants to play games with you in a practical joke kind of context, nothing would happen because you would see that the endpoint verification wouldn't pass, the certificate wouldn't pass.
Okay, what's the next question?
So the question is how to deal with a chain of trust to subdomains. It's the same thing how it's just an extra level, right? So we went www.gocloudqueries.com. What if we say it's www. So whatever a subdomain of that domain, right? So it's just an extra level. That means a subdomain, for that subdomain to be have an authentic certificate, it has to sign the previous certificate, right? So it needs an actual key to sign that certificate. So, just think of it as just a level higher, right? So we went with top level domain, or you got your root domain, your root server, top level domain, and then authoritative server, and so on and so forth, right? So it's just an extra level in that chain of trust. Yeah, that's what Mike described.
Yes. All right. Well, that's all the questions. Let me know you're awake, alert, and oriented by giving me a hashtag AWS Advanced Networking. And if you just happen to pop in and join us, make sure you download the nearly 2 full days of labs and technology walkthroughs we did for you. Well, it's not really a download. You can sign in, you can watch it on our training platform completely free anytime you want. So the description for that is going to be in the chat box on the description of this video. We'll get back to Mo. He's got a lot of DNS kind of stuff to talk about.
Okay. Now we're going to talk about DNS endpoints, right? And DNS endpoint, all it is a method in AWS, a way for AWS to either resolve DNS requests or DNS requests to on-premise, or for your on-premise DNS resolver to request to AWS, right? And you want this to happen privately, right? Think of this, if you look at this diagram, right? So you can see here, we have a data center. We have our data center. All right. And then I have our AWS cloud. And between the data center and the AWS cloud, you have a virtual private gateway, right? And you're running a VPN, right? So you have a private connection, right, from your data center to the AWS cloud. What if you have let's say a DNS server inside your data center, right? And you want your DNS resolver to resolve privately through your private connection, which is a VPN tunnel, and you want to resolve to this DNS server, right? Well, in order to do that, you need, number one, you need to create an entry here, right, to point to the DNS server. But the problem is you need an IP address for that DNS server, right? You can't just put the IP address of the DNS server's internal address. The way you would do this is you would create an outbound, and what an outbound input is, it's just an elastic network interface, or ENI, that has an IP address, and then your Route 53, when you create that entry, you'll create an entry that points to that ENI, right, which is the outbound endpoint. Now, inbound is the exact opposite, right? You have a DNS resolver, right? You want, instead of resolving out through Route 53's public hosted zone, right? And the way you would do that is you create a forwarding entry that says to resolve to this domain, go to AWS Route 53 DNS server, right? In order, right? What input is, it's an ENI or an IP address that you can resolve to from your on-premise, right? And the way to establish that is the inbound input. So think of outbound think of it from your AWS infrastructure perspective, right? Outbound, you're resolving to an on-premise DNS server. Inbound, your on-premise is resolving to you in AWS. Okay. So as we said, right, we're creating a Route 53 private hosted zone, right? This private hosted zone, right? When you create that inbound endpoint, right, your AWS infrastructure will create an ENI or an interface, right, with a private IP. That private IP is part of your VPC subnet, and once that entry is created, you can just and since you already have end-to-end reachability from your data center to AWS, all you have to do is just point your DNS entries to that server, right? Or to that IP address. Okay. So over here we have an example, right? In this example, as you can see here, we have a private line from your on-premise, right? And this private line is connected to your VPC1, and you have a production network with the IP 10.1.1.0/25. Now, you have a private hosted zone, and what you need to do is you first create an inbound endpoint, right? Inbound endpoint, when you create it, you'll have an IP address that is part of the 10.1.1.0/25. And that inbound endpoint points to your Route 53 private hosted zone, right? In this example, it's called private.gocloudcareers.com. So your inbound endpoint points to your inbound endpoint points to your private hosted zone, right? And you already have a private line, so you have a private reachability to this to your 10.1.1.0/25 network, right? So on your own premises server, right, DNS server, right, your recursive server, what you can do is you can create an entry or a forwarding rule, and that forwarding rule will point towards the IP of the ENI. That way the entries can go all the way to this private hosted zone, to the private hosted zone, right? And then, so the client will query the DNS server. Your DNS server will forward this request to Route 53, and then Route 53 will respond to your query, right? And then the recursive server will reply to the client. Now the client knows the IP address of private.gocloudcareers.com, and it can just send this request privately. So that's an inbound endpoint. An outbound endpoint is the exact opposite. You have an on-premises DNS server that points to web.example.com, right? Your client queries the Route 53 resolver, right? The resolver should have a forwarding rule that points to the outbound endpoint. So you would send it this way, you send it to your outbound endpoint, the outbound endpoint will forward it to your on-premises DNS server. The on-premises DNS server should reply or respond to the resolver. Client gets the response, and then you can access that server through the private line. Okay, let's keep going. Try to clean this up first. Okay, DNS space load balancing, right? So there are different ways that we can load balance our traffic. We can use something like Anycast, right? We could just use regular IP-based load balancing. We can load balance based on DNS, right? And DNS-based load balancing is basically, let me delete this. Just need to do a little, bear with me for a second. Guess it's not working, is it? Okay. Not sure how to delete this, so let me try something different here. Just duplicate. Okay, there you go. So you have your Route 53, right? So this is your, and you have your A record entries, right? And you can point your entries towards both your elastic load balancer that exists in US East region, and then another elastic load balancer that exists in the US West region. So what you can do is right, and then you can balance your traffic, and there's different methods to load balance your traffic, but you can load balance your traffic so that when a customer sends you a DNS request, right, you can, let's say for the first respond with the IP address of the elastic load balancer that's in the US East region, and then for the second response when somebody else has queries the same DNS, since the DNS query for the same domain, you can then respond with the IP address of US West region. That way you create load balancing at the level of DNS. I'm not sure why I see, okay. Duplicate slide again, I guess. Okay. So with DNS-based load balancing, you end up load balancing your traffic, right? Or load balancing your DNS queries, right? Or the requests across different resources, right? So just like we said, right? You have some resources in one region, other resources in a different region, right? And those resources can be anything. They can be public IPs, they can be EC2 instances. You can choose actual EC2 instances. They can be load balancers, whether it's network or application load balancers. But the common thing here is that you can use this method in order to load balance your DNS responses, right? So you're not doing the load balancing at the IP level. And now with this method, right? You need some sort of a process for the application for the Route 53 resolver to know if your resources are healthy, right? What you can do is you create a health check, and you can actually elastic load balancer or whatever resource you have, and then if this is healthy, then you will send your traffic that way. If it's not healthy, then you'll stop giving or responding to clients with the IP address of this elastic load balancer, and only give them the IP address of this elastic load balancer. Now, if you already gave a client the IP address of this elastic load balancer, and then this fails, there's no guarantee that they will send you another DNS request, right? Because even though you can try to control how long before that DNS entry expires, is what I'm trying to say, right? At the end of the day, it's up to the recursive server and it's up to the client, right? Because if you remember, we have a client. The client sends a request to a recursive server. A recursive server typically caches those entries, right? When you get a DNS response, you can have a time to live or a time before this DNS entry expires, but you can't. But this recursive server, which is very typical, they can just ignore your recommendation. Right? You can't force somebody to keep a record for however long you want, right? You can only suggest. So with this in mind, it's obviously a drawback, right? With having a DNS entry that lasts, let's say, for hours or days, versus a DNS entry that lasts, let's say, 10 minutes or 20 minutes. But then if you have a lower, if your DNS entry expires much faster, then that means your recursive server will always be sending forwarding your DNS requests, and that can affect the performance, right? So there's some sort of trade-off there. Okay. So DNS health checks. We spoke about DNS health checks. I have no idea why I'm making these drawings. If somebody remove this, please let me know. Let's try again. Okay. So there are two types of DNS load balancing, DNS-based load balancing rules, right? Or let's say what at least what AWS calls them is routing policies, right? But there is two types, right? There is the simple method and there's the complex method, right? So with the simple method, what you're doing is that you're running a health check, right? And you're just probing the resource, right? Let's say it's an EC2 instance, right? Or just an IP address. You're probing that IP, right? And then if that IP is no longer reachable, then that side, let's say one region, two regions, right? Region A is no longer responding to your probes, then you just assume that region is down, and then you will only reply to DNS requests with region 2 instead of region 1, right? So that's the simple method, right? Now the complex method for routing policies or load balancing, you can take more things into account, right? For example, you can take the latency, right? And let's say you respond with the DNS resource that would have the lowest latency, right? Or maybe based on the geographical location, right? So you can take more things into account when you're doing more of a complex, or when you use a complex load balancing or routing policies with DNS, right? But if you don't care that much, you just want to make sure you're resolving to to servers that are up and are not down, then maybe a simple method would suffice, right? Yeah, and then one of the comments said, this is when we want to make strategy of disaster recovery. Yes, right. DNS is a big part of that.
Okay.
Bear with me 1 second. Let me share my slides. Okay. Okay, so setting up your Route 53 DNS-based load balancing, right? So one of the comments said it's always DNS. Yes, until you have an application that doesn't support DNS-based load balancing, right? But yeah, if you can do load balancing based on DNS, then it's definitely a better option. Okay. So the steps to create a DNS-based load balancing, right? You first want your you create a health check to your resources, right? So in Route 53, you want to create health checks that point to your resources, right? So let's say you want to do like a TCP port 80, right? Trying to do HTTPS, and then you point your or HTTP, right? And you point to your resources, and your DNS load balancer will act as if it's a client, right? And as long as it's receiving responses, then that resource is healthy, right? And then you want to create your A records, and you want to create an A record for each one of those resources, right? And then, so you create A records, and it's basically you're going to create the same record multiple times, but each time it points to a different resource. Let's say a public IP address, right? Or a CNAME. Maybe you want to create a CNAME record. But each time you want to create it, it points to that resource. And then this is when you create your routing policy, or the failover policy, or as we said, the load balancing policy, right? And then you create your policy, whether it's simple or complex. You choose your conditions, right? So how do I load balance, right? And then what you can do, you can say one of those resources, if you wanted to do more of an active standby, you can say one of those resources is primary, the other one is secondary, or you can have an active, right? So that both are active, right? And that depends on whether you choose a simple or complex method of load balancing. Okay. And you'll end up with something like this if I share my screen. Right? So in scenario to the left, both are healthy. Both of your resources across both regions are healthy, right? So if the load balancer or the Route 53 load balancer will respond to your query or DNS queries based on whatever algorithm you use, right? Simple or complex algorithm, right? And then if, let's say, if you look at the diagram to the left, if one of them fails, it fails by failing the health checks, right? Route 53 will no longer respond to clients with the IP address of this elastic load balancer, right? It will only respond with the IP address of the first region, the US East region. Okay. Okay, we went through setting up the process of setting up. Okay. So why would you use a DNS-based load balancing, right? Well, there's a number one, the benefit of having high availability and fault tolerance, right? So it's much easier to load balance across different regions and not actually having to send traffic through one location, and then that location has to physically send you traffic one way or another, right? You're more of delegating the IP reachability to the internet, and you're just saying, if you ask me for the DNS, if you send me a DNS request, you're asking me for the destination, right? I can just give you the geographically closest location, or so you delegate the load balancing to DNS instead of doing it at the IP level, right? Definitely an improved user experience and performance, right? If you're sending your traffic to the closest geographical location or the closest, let's say, topological location, which is based on your latency, then that definitely enhances your experience, right? The user's experience, without having to rely on something like global accelerators or edge, global accelerators, and having to send traffic through a private, or doing some sort of a mid-mile optimization, something of that sort. And lastly, it's the simplest way to do load balancing, really, right? DNS-based load balancing is very easy to deal with. So if your applications support using DNS-based load balancing, then I would definitely go for that option. Okay. So next we'll talk about Route 53 logging and monitoring, right? There are different tools within AWS that you can use in order to monitor your resources. And one of them is CloudTrail, right? So CloudTrail, right, what you can do with CloudTrail is that you can log your Route 53 actions. You can choose actions from Route 53, and then you can have details of who's requesting the DNS, right? From what regions, the IP addresses, at what time, and other details that you can monitor through CloudTrail. As long as you create that, your action logs, you'll be able to monitor those different actions, right? So Route 53 also, so you have CloudTrail, that's more of a looking into like the deep level details and seeing who's seeing the actual IPs and the timestamps of actual requests, right? But also Route 53 has itself, right? And this dashboard can give you the status of your domain, when would the domain expire, so things that have to do with your domain registration, right? And that's very important as well, right? Because you want to keep track of your domains, right? And you want to make sure that it's up to date, right? Or you're up to date. Also, so as you notice, these are different monitoring tools, not necessarily to monitor the same thing, but there are important aspects of DNS that you might want to monitor, right? Of course, we also have, since we're talking about Route 53 and we're talking about DNS-based load balancing, right? And with DNS-based load balancing, you can do health checks, right? So you can, from your Route 53 resource, you can actually monitor, the Route 53 load balancer will keep track of your different resources, right? Because it's doing the health check and it's making the load balancing decision based on those health checks, right? But you can also look at those health checks if you wanted to see if one of your resources is not healthy, when it went down, and then you can start your troubleshooting from there, right? So you get real-time metrics, and then you can see if it failed, why it failed, right? So you can see, for example, if it's an IP reachability issue, if there's an error, TCP error, or something of that sort, right? So we spoke about CloudWatch, right? And we said you can monitor your Route 53 resources, right? You can also monitor your Route 53 resolver endpoints, right? So we have our inbound endpoints, our outbound endpoints. You can also monitor those resources, right, with CloudWatch. So CloudWatch, more of creating a dashboard. You select what you want to monitor, right? You choose your AWS resources that you want to monitor, and then you have a dashboard or a place where you can look into what to look. You set the conditions for what to monitor, and then you have like a dashboard where you can look into these different resources in real time, right? Here's an example, right? As you can see here, we added a dashboard, and then you can see how many queries for this domain versus this domain, right? It will show you that. And it will show you over time, or when it peaked, when you got most of your requests, and so on, right? And you see each color signifies a different entry that you were. So as you combine these different tools together, and Benedict has a lot of slides, and he's going to go through different monitoring methods and so on. But as you combine these different monitoring tools together, you get a more comprehensive understanding of your environment. Okay, we can take some questions.
Welcome back, everyone. And Mo, you held out on us. You have a very pretty cat. I knew you were going to get a new cat, but I didn't know you got the cat. Great cat there, Mo.
It's actually, my friends have it for, but yeah.
It's what? You got it just the other day? Because that is a very cute cat there.
It's my friend.
Oh,
he's very good. He's very shy though. Am I muted?
Now you're not.
I think I'm muted.
Now you're back.
Okay. Yeah,
okay.
He's very shy, so shows up sometimes.
But he joined in on the bootcamp, so he's not shy at all.
That's right. It's always good to see. So, okay, so let's see who has questions. Okay, now, Armana, this is an interesting question. How many DNS servers allow for high availability? It's going to be dependent upon a lot of factors. Let me give you some examples. What if we need 50 DNS servers just to maintain our infrastructure? Then we're probably going to need 100 DNS servers to maintain our high availability. So when it comes to high availability, we have to think about a couple things. One is no single points of failure, which means 2 is 1, means 2 is 1, and 1 is none, and 3 is greater than 2. So always more than 1. But we might need more than 1 if our application depends more than 1. So at least 2. And then we have to determine the kind of availability we need. Do we need 3 nines, 4 nines, 5 nines? And that will determine exactly how many they need to be and at which places they have on the network. Now, that's still not going to be enough, because what happens if I've got Dali, the DNS tamperer, that goes into my DNS server during the day and makes a change and it breaks something? So to get to high availability, we're going to need a good governance structure. We're going to need good change control procedures. We're going to have to make sure that the DNS servers are tested. We're also going to have to make sure that those DNS servers are locked down, patched, have good, strong security protocols and anti-malware protection, endpoint protection, that kind of thing. So it's going to be at least 2, but it could be a whole lot more of them based upon what your needs are. And you're going to actually have to calculate it each time based upon, business needs, level of availability, level of use, that kind of thing. As if you're talking to you're talking to a mute button. So how could you, while you fix your button, how could you use Route 53 for a relational database service?
Yeah, you can use it for any resource, right? So, but one way you can do it, if you, okay, I'll let you, Mike, answer, but then I have my own take on it. I think this is one of those things.
I think that this will take a combination of us. So Route 53 has absolutely zero to do with the database. And one thing, we're talking about how we're going to structure data that's related to each other so we can be queried and used for a business to make better business decisions. And Route 53, we're talking about how do I get my traffic from point A to point B to a DNS name. So they are unrelated, but in the way the applications are coded, you can point something to go to the DNS name of a relational database instead of the IP address. And by using that, if you point to, say, a DNS name versus an IP address, if you need to change the server or something about the server, you don't need to change everything else along the way. You just need to change your DNS mappings, the IP address to the DNS name. But that's kind of the way they would relate to each other, being unrelated technologies. But let's have you, Mel or Benedict, get your perspective there as well.
Yeah.
So I think
I'm going to build up on. Yeah, go ahead, Benedict.
Yeah, I think you're spot on, Mike. In this case, we're going to be creating A records for our database servers so that we can route traffic to them from on-prem or from the cloud locations. So that's how they would relate, in my opinion.
Yeah. So let's say one example, you have an application server that is on-premise, and then you want to use RDS, right? But you don't, just like Mike said, you don't want to use an IP for the RDS. You want to actually use a fully qualified domain name, right? You want to, to make sure that it's, your application doesn't. You don't want to hard code IPs in your application. And so what you can do is, since you have, what you can do is a combination of an outbound endpoint, right? Because an outbound endpoint, you create a forwarding rule in your server that is on-premise, your DNS or recursive server on-premise. So you're forwarding those requests to Route 53, and then in Route 53, right, you can create an entry that points to an interface, to a private link, right? Or interface endpoint. That way you have private access from AWS to that RDS resource. So that's one way, kind of have like a complete private access, and it's redundant because the RDS is highly available and you're not hard coding an IP that might change. Regulatory, that's a big question.
Yeah, so What are the regulatory standards? I don't know what you mean by that, because there's going to be a lot of regulatory standards. In healthcare with privacy information in the US, we have HIPAA, we have GDPR. There's a lot of standards and a lot of different things. So, what type of regulatory standard are you talking about in the context of what industry? Let us know. We'd be happy to help. Not that any of us are expert lawyers on regulations, but for the big common ones, most of us probably know. So we'll do what we can to help.
CNAME record maps to RDS. Yeah, you can do that. You can map, CNAME record. If you have a domain to another domain, you can do that. Or you can, if you create a private link, as we said, then you can create a record to that private link's IP.
Any others from everyone? Because if not, I know Benedict has some content to talk about. And then at some point I get into load balancers. And I love load balancers because anything that improves performance and availability is one of those things that I have fun with. Is there any feature on roadmap to allow to filter content based upon DNS requests? I would ask Amazon that one. Because they know their feature list and roadmap. And I can tell you from working internally at vendors, their future roadmap will be internal, and they'll typically give you certain things via NDA, but they definitely wouldn't give us to us to prescribe it or to disseminate it. And quite frankly, they won't give it to the average account manager and the average solution architect at these organizations either. When you work in one of these organizations, and I was like a principal architect, so typically things get escalated to us. The principal architects are above, and the principal architects above have the connections to internal engineering and internal product that they'll give us information that we can then determine who we can give the information to based upon NDAs and the credibility of the people. So that's something you're going to have to find somebody at AWS from. And that's a great question. And realize the average people won't even know, but a few select few will. If I recall, Benedict, we're going to you for APIs.
Yep, that's correct. So actually, we want to talk about the AWS API Gateway, right? But in order to put that in context, let's discuss about APIs and what they are. So an API is a communication interface, basically, that allows two separate software to share data. So if you think of it, how is it possible that your smart TV is able to gather information about today's weather? It's because it's using an API to get that information from a backend server and displaying it for content. So an API is basically a set of defined rules that allow different applications to communicate with each other. They basically sit between an application and a server, right? And send requests from one location to the other, and then carry the request back to the original location. Now, when we talk about APIs, we're basically talking of two parties here. The party that is requesting the data is the client, and the party that is presenting that data to the client is the server. The API sits between the client and server, facilitating that communication. So APIs are important to organizations because they help them to digitalize their content. It helps them to communicate with third-party vendors. It just improves that overall customer experience. So an application such as, or a provider such as PayPal, for example, they allow you to make purchases on various websites because they have APIs that are making those calls to the web servers of different merchants, right? So it provides a service to the population using these API calls. Google Maps is another interesting one. You're driving and your phone is constantly making calls to a navigation server somewhere else and giving you real-time data and helping you get to your destination faster. So APIs are pretty important and useful to organizations in today's world. With respect to types of APIs, we have different types, right? The two most popular REST APIs and HTTP APIs, right? I know if you go onto the AWS console, you also see WebSocket APIs and another version of REST APIs, which is a private version. But these APIs basically use the HTTP protocol or Hypertext Terminal Protocol to facilitate communication between the two different applications they are connecting, right? A REST API is more robust than a HTTP API, but they basically use the same protocol to operate. Now, another important feature to talk about when talking about APIs is the API endpoints. And what exactly is an API endpoint? Is that specific location within an API that is accepting requests and then sending back responses. So imagine, take for instance, bbc.com is an API, right? If I want to read the sports content on the bbc.com website, I could go to bbc.com/sports. And then I don't see any news. I don't see anything about politics. I don't see anything about weather. I just see sports, right? So in this context, the /sports is the API endpoint, which is receiving the request from me to get sport content and then delivering that content back to me, right? So API endpoints work by connecting API clients and the server. So recall, I said that the entity making the request is the client, and the entity sending back the response is the server. So the API endpoints connect the API clients to the API servers, and they handle the transfer of data between them. So a well-designed API should have a very clear endpoint that can provide a predictable way for clients to communicate with the servers. You don't want to go to bbc.com and then see bbc.com/sports and then see information about politics and sports at the same time. It means that that API endpoint was not properly designed. And API endpoints are very important because they can be compromised. So it's very important that organizations should monitor their API endpoints just to make sure that everything is safe and secure. And then with that said, let's talk about the API gateway now. So the API gateway, which you can deploy on-prem as well, but in this case, Amazon have their own API gateway solution. So the API gateway solution is basically an API management tool that allows developers to create APIs, publish them, and maintain them. So it's basically a management tool that you can use to, just gather your APIs in one portfolio and then perform operations on them as required by your organization. So it's more like a front door for requests to come into the APIs and then get responses back to the APIs, right? Now, because they are all enveloped in one portfolio, it gives you the ability to enforce security measures, right? And do some traffic management for those APIs. So, what does this traffic management mean, really? So there could be a tendency for your APIs to be overwhelmed by requests from end users, right? But having them in an API gateway allows you to do some kind of rate limiting or traffic control. So by default, the AWS API gateway has some rate limiting sets, right? Although you could go in there and customize it to your taste. So why use an API gateway, really? So like I said, you want to protect your APIs from overuse, right? So I talked about rate limiting. You don't want it to be overwhelmed, right? So you can control the amount of requests that can come into the APIs at a particular point in time, right? So you could also implement authentication service to control who has access to those APIs. Now, if the APIs are scattered all over the place and not in a common portfolio, such as the API gateway, that becomes more difficult to manage. Now, you have the ability to run some analytics and monitoring on the API gateway, right? Because ideally, you want to understand how your APIs are being used, right? You want to see which APIs are providing more value or which is receiving less requests and stuff like that. The API gateway gives you that functionality to run some analytics on your APIs and see which ones are doing well and which ones are not doing so well. So that could be an advantage for housing your APIs in an API gateway. Now, also, if you monetize your APIs, you want to have an idea of the cost of these APIs, right? And if you have them in an API gateway, you could set up a billing service for that API gateway, which gives you the overall cost of all the APIs in that portfolio, as opposed to if they were just stand alone. Now, in some cases, there are some microservices that would make API calls to multiple APIs, right? Now, imagine if there were some APIs that were not functioning at a particular point in time. It means that those microservices will be having issues, in completing their services because they've reached out to these multiple APIs and only some are responding back. But if you have all the APIs in the API gateway being monitored as well, you're sure that once this request comes from the microservices, it's going to get a favorable response from the multiple APIs. And then over time, you want to remove APIs from your inventory, build new APIs and add them to your inventory. If you have a central location where you have these APIs, it becomes more manageable for you. And in terms of audit purposes as well, the auditors could have a central dashboard where they just look in and see all the APIs for your organizations, right? By looking into the API gateway. So these are some of the reasons why you would use an API gateway. So I'll share my screen real quick to show you how the architecture for the API gateway looks like. So you see that you have the API gateway over here, and then you have the clients on one hand making calls to the different APIs. So for example, I'm on my phone and trying to get to Google Map, right? So my phone is a client in this case, and then it contacts the Google Map, right? Google Map application on the phone, and that application is going to make an API call to the back-end server, which is my navigation server, right? It's going to make the API call to my navigation server. The next client comes and is trying to access today's weather. It goes to the same API gateway. The weather app API responds to its request, goes back to the backend servers, queries the server for the current weather, and then relates that information back to the API client. So this is what the operation of the API gateway looks like in Amazon. Now, how about fault tolerance? How do we implement fault tolerance? So I'll share my screen again. So you see that we have an API gateway here. What happens if this service goes down? Highly unlikely, but not impossible. Well, you can have another API gateway in a separate location, right? In a separate region, separate availability zone, if you like. And then it's going to be like an active standby system. And then you use your Route 53 health checks, right, to monitor the standby API gateway, right? So the primary is receiving traffic all the time. And then you have a CloudWatt metric that you create for the API gateway. So once the primary gateway fails, the CloudWatt metric that you have created is going to change, and that will trigger the failover, DNS failover to the secondary API. So this is how we enforce fault tolerance for API gateways in our infrastructure. So that's all I have regarding the API gateway. If you have any question, you could put them in the chat box now.
All right. Well, we're back. We're going to answer some questions, and then I will happily get into some load balancers, which is something that I love talking about. But let's have some questions. First question I have is, what is the name of Mo's cat?
Okay, I forgot the name. It's not my cat, it's my friend's cat, but I forgot the name. I'm going to have to ask him again.
All right. Well, okay. Well, then we can actually get to the real questions then.
Oh, we could give you a name.
Or we can come up with a name for the cat. One of the two.
Yeah.
Let's call it a security group.
I mean, it is walking around like it's patrolling the place. So
Or we'll call it BGP.
Yeah.
Actually, that's a good name for a cat. My next cat's going to be BGP.
BGP.
So Omar is asking, what's the criteria for a network access list to use in application? So do you mean the API gateway here? Right. So could you be more specific?
Yeah. So let's maybe we extrapolate this, because they're kind of unrelated contexts. A network access list is used to protect a subnet from a certain kind of traffic. That's it. That's all it's for. It's the same thing as a packet filter or an access list that we put on routers for the last 30 years to keep traffic out of a subnet. So while it's unrelated to the application, how do we secure the application? We could do a lot of things. We could use firewalls to secure an application, and we'll talk about that a little bit. We could use a network access list to try to secure the application. We've got things in the identity and access management world to help secure applications. We could do IDS, IPS systems. So there's a lot of things that go into enterprise-wide security. But an access control list, which is filtering packets to make sure that the only traffic that needs to enter the subnet enters the subnet and nothing else, can definitely enhance security. So we didn't really know what you meant. And if you've got a bigger question about it, that's fine. And Benedict or Mo, if you knew what in the context of where I was referring to it, please answer that as well. But I thought I'd take it to a higher level first.
No, I couldn't.
Yeah, I think
I don't sound.
I think he's speaking in relation to the API gateway and how we secure it. So basically, you're going to have a layered security defense for your cloud architecture, right? You're going to have a firewall. You're going to have identity and access management. You're going to have two-factor authentication. So you have compensatory controls in place to protect your AWS resources. What's the difference between the WebSocket API and REST API? So I know the WebSocket API is used mainly for applications that deal with chatting. So, for example, Facebook chats, WhatsApp chat, and stuff like that. They work more with the WebSocket APIs, as opposed to REST APIs that make API calls to backend servers and give you data. So WebSocket APIs are used more for chatting and stuff like that.
So I think we can rephrase it and say WebSocket is more for two-way communication, while REST API is more of a stateless request and response, right?
Yeah, you can say that. William, can I put a public certificate on API gateway, or I need to use my own public key infrastructure? Not sure what you mean here, but in AWS, there's always that flexibility to use your custom certificates or use AWS generated certificates from the certificate manager. So that flexibility exists.
Yeah.
Sunday, how do we secure API based on connectivity between two software? So that's an interesting question. And it happens that I'm not a software engineer. But from my studies in security domain, I know you could use what we call input.
Yeah. So there's a lot of things that will go into this Sunday. Benedict's was thinking about the input validation with regards to application codes. We know each other real well around here, but there's a lot of things. There's going to be secure code checks that are going to go into this, code reviews that are going to go into this. Ideally, you should try to break these things and see where things are going to go into this. If they're going to be in a different subnet and they have routing between them, what are you going to do to these things? Are you going to filter packet based upon an access list? Are you going to encrypt between the two APIs that you're actually dealing with? I hope you're getting the concept that it's getting bigger. Do these APIs authenticate to some type of identity access management like Active Directory, which is going to be federated along the way? So Sunday, this is kind of a bigger topic than, unfortunately, that we would do in a certification. This is what we would do in our architect training, because it's not just one thing. We could mention one thing, but what about the other security things, the network security, the application security, the IAM security, the weaknesses of the human security? So there's API security best practices, which you could look up, but please understand security is not one thing or this thing or that thing. It's a combination of hundreds of different things together that really get us to the goal. Because it only takes one weakness. Usually it's the people. And usually you can, through social engineering, and get into a lot of things just by finding weaknesses in people.
Manish, how do applications point to the target API via the API gateway in the cloud? So, in other words, how does my phone know to go to Google Map API when I'm trying to get navigation? So it's all in the software. When you, for example, when you're deploying a web server, right? You're going to set up your server, and then we're going to create a DNS record for your server so that when any user goes onto the internet and say maps.google.com, it's routed to your server, right? So you're going to one of the ways that you can point your applications to target APIs by using DNS records. Mohammed, how do rate limit requests function with API gateway? So that's actually a deeper topic here. How does it work? Now, so for the API gateways, they have like a default rate limit, right? So it could be maybe 1 Mbps, right? Worth of requests from your endpoints to these APIs, right? Of course, it's flexible, so you can go in there and customize it, change the 1 Mbps to 5 Mbps, right? So that helps you to streamline the amount of data that is going to your APIs so that they are not overwhelmed. I think they call it a steady state rate in AWS, right? So that your APIs are not overwhelmed. So that's how it works.
And actually,
Mohammed, will it help to use a web application firewall for API gateway? Not really. So you want to place your web servers behind your web application firewall, right? So that it's protected from all sorts of layer 7 attacks, right? So the API gateway in this situation is just facilitating connections from clients to this backend servers.
but we will be using next generation firewalls as part of our security architecture to really provide enterprise grade security if it truly matters. And something that Umar noticed in the chat box, it's very easy with a firewall or an access control list to totally break an entire network. And not only will you lose access to an application, you literally use access to the entire cloud if you put an access control list in the wrong place. Or you can literally take out an entire network if you block a routing protocol in a core router, for example. And yes, I've seen people do it.
And then you have to console in and try to fix it.
And I wanted to get back to Sunday's question because he had a really interesting question on security. And I asked a lot of questions into the question. And I want to get to the point. I'm not trying to evade the question. What happens is as you're going to learn more Sunday, and you're very smart to be asking these questions because these are great questions, you're going to realize it becomes more important. For example, I had 3 jobs in my life before I went into tech. I was an EMT taking people to the hospital. Then I was a paramedic, and then I basically practiced internal medicine. When I was an EMT, here's what we were asked to do. Put somebody on a board, put oxygen on them, maybe a bandage, and get them to the hospital as fast as possible. And I knew how to treat everything. Oxygen and a fast ride to the hospital. I thought I was good. Then a couple minutes later, I was a paramedic after 9 months, and then I could put oxygen on them and start an IV and give them a couple medications, and I thought I realized something. And you know why? It was very simple. It was basically the same thing for 99% of cases. And then I practiced internal medicine in the ER after 7 years of school. And I realized that every one condition had 10 or different variations of the same condition. And every decision we make would have either 10 trade-offs. This would make something better versus this makes something better. And as we expand, you're going to find out that some of this stuff becomes a lot more complex, and it's not going to be like it is in a certification. because the certification has to simplify things. But you've got to start somewhere. And Sunday, the questions you're asking are the right questions, and I'm super happy that you see them. So I like the question. I just want you to understand what happens as you'll grow more. You're going to start to realize that this piece has an effect on this piece, which has an effect on this piece, which has an effect on this piece. Kind of like Benedict, he puts one routing statement on a router with 3,000 routers in the network. He can do a lot of damage, or he can do a lot of good things based upon what he puts on that one system. It can literally affect that many things.
Joseph, also time-based rate limits work really well, where specific IP is limited to, say, maybe 10K calls per minute or 5 minutes. Yeah, although I'm not sure if you have time-based rate limits on the AWS API Gateway, but definitely on-prem, you can do that.
And we'll get back to the contact. And Mohammed, we are aware of the white papers that you can use WAF to protect an API. Having said that, there's a lot better ways to protect the API to give it a lot more strength, which is what Benedict was referring to. You've got two kinds of tools. Do you use some tools, or do you use the most effective tools? And in architecture, you may have to go outside of AWS to get the most effective tools. Sometimes you can use them, sometimes you can't. It all depends on the actual goal you're looking to. So let's get into elastic load balancers, which are something that I love talking about. I love talking about load balancers because my world has always been designing high availability systems, and I like designing things that always work. So we're going to get into high availability systems, which are load balancers. But before we do, let me know you're awake, alert, and oriented with give me a hashtag AWS Advanced Networking. And if you just joined us and you haven't seen Session 1, Session 2, Session 3, Session 4, please download the free labs that we have for you. There is a huge list of networking labs that we have, and you can come and you can register for the labs and access them for as long as you like. They're completely free on our platform. So give you a chance to do a lot of labs that we may not have a time to cover throughout this program. So let's talk about load balancers. Load balancers, where I come from initially, when I was designing and building the initial clouds, are devices that distribute traffic across multiple devices. So what's the point of a load balancer? Well, if we can share the load between two things, it's got greater capacity than if we just have one thing. And if we can share the load amongst 5 things, it should have greater capacity than just one thing. And even by sharing the load across, say, 5 devices, if one of those devices fails, we have greater availability than if we had none. So typically speaking, that's what we're talking about with regards to load balancers. But now when we want to actually enhance capacity or performance to our system, we can scale up or scale out. Here's scaling up. I'm on a server. It has 64 cores. It's got a terabyte of DRAM. I need more capacity. I go up to a 256 core server, 6 terabytes of DRAM. That's scaling up. And truth be told, we're going to get really good performance out of a server like that. But one of two things will happen. If we only have only one server and that server fails and we lose it, we've got nothing. But if we've got 228 core servers and one fails, we still have something. So that's your higher availability piece. Now, at some point, even if we've got 256 core servers with 6 terabytes of DRAM, there's a lot of applications that are going to need a lot more than that. What happens when we need 50 of them, or 100 of them, or 1,000 of them? Some applications use tens of thousands of servers that are out there on super large global enterprises. And the way we make this happen is using some kind of load balancer. And if we're dealing with Kubernetes, it's got its own internal load balancers. We've been dealing with load balancing forever. But load balancers are devices, whether they be physical devices or software devices, to share load amongst multiple devices. Now, when we talk about load balancers on AWS, we're going to discuss, all 3. And load balancers can either operate onto the network level, at the application level, when we're talking about it. So a network load balancer is going to operate at layer 4. It's going to look at the TCP, or it's going to look at the protocol. Is it TCP, UDP, ICMP? What is the source address, destination address, and typically port number? And that's the way a network load balancer looks. And it'll load share based upon only the information in the network. But what if we want to know more? What if we want a greater degree of intelligence? What if we want to load share based upon the HTTPS method, whether it be push, get, that kind of thing, instead of just TCP protocols and port numbers? Well, that's where we have the application load balancers. And application load balancers are going to be much more intelligent. Great if you want to route between microservices, great if you're going to route between small servers. So think about that. And there's also another type of load balancer that AWS invented, which is really a network load balancer, but they're using it for network things, which is called the gateway load balancer, which we'll get into as well. But understand this, that load balancers on AWS are called elastic load balancers. Want to load balance between two virtual machines? Use a load balancer. Want to load balance between a bunch of containers? Use a load balancer, typically an application load balancer for that. Want to get a high security environment in the cloud and you want enterprise grade firewalls versus cloud provider grade firewalls? And you want to get a couple of, say, Cisco firewalls, you're going to need a load balancer to load balance between these firewalls. Need high performance F5 load balancers in the cloud? You're going to need one of the cloud providers load balancers to load balance between the F5 reverse proxy type things as well. So, keep that in the back of your mind. Load balancer loads are typically auto scaling. The load balancers in AWS can load balance across availability zones, and they support health checks, which is how they maintain high availability. I showed you all how the health check works this morning, and if we need to, we'll do the health check again. And here's the key: load balancers can terminate SSL connections. So I want you to think about this, determining these SSL TLS type connections. Encryption is very computationally heavy. So if we're going to encrypt on the server, we're not going to be able to, it's going to put a lot of computational output on the server to handle the encryption, which means a server that's doing the encryption won't be able to serve as many clients as if it didn't have to do the encryption. So because the AWS Elastic Load Balancers will terminate SSL-based encryption, we can offload the web servers from do that, so the web servers can focus more on, say, serving content as opposed to encrypting content, and they're going to scale better. So load balancers are all typically a very good thing. Now let's talk about the network load balancers. They're fast. Why? So I hope to get this across, that the simpler something is, the faster you can do it. How fast can you add 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30? Pretty quick, right? Now, if you ask me to calculate a derivative of something, I'm not going to be too fast. Truthfully, if I had a calculated derivative, I'd ask my wife, because she's a math genius, how to do it, and I would just buy her shoes or something to get her to do it for me. But, that's the point. Network load balancers, what they do is simple. TCP, UDP, protocol, IP address, source and destination address, port number, so they are very fast. So a network load balancer can handle millions of requests per second. They're incredible with rapidly changing traffic patterns, and they tend to be stateful. And why? Because a flow goes through your load balancers, TCP or UDP, source address, destination address, protocol, or the TCP or UDP, and the port numbers, and it stays the flow. So if the route goes to server 1 and the next one goes to server 2, it's going to stick that way. Kind of keep that in the back of your mind. Now, with our network load balancers, we can put a static IP address on the load balancer. And guess what? That static IP address could be the front end of your website. So what are the ways these looking for, have you look at it from a perspective? So when you're dealing with a load balancer, what you're really doing, here's how it could network load balancer could load balance between, say, availability zones. And it could also load balance, we can also put load balancers in front of those virtual machines or EC2 instances. Now let's talk about an application load balancer by comparison. So application load balancers look at layer 7, and they get really academic and geeky. They're going to look at the path provided in the URL, elements in the HTTP versus HTTPS header, the HTTP method of routing, whether it's push or get. They can route to a specific source IP address. So it's really great for load balancing something specific, like HTTP or HTTPS traffic. They're ideal for load balancing between microservices or containers, because again, we want more intelligence And containers aren't exactly super powerful things, they're small. They can load balance between multiple requests on the same virtual machine. For example, if you've got compute instances sitting on different ports, like you might in a containerized environment, and they can load balance between your virtual private cloud and your on-premise data center. Kind of keep that in the back of your mind. And the way these load balancers typically work is they typically listen for something, and then they route it to a target. And with AWS, you can create a target group where you put multiple targets in a group. But the point is, you got your traffic coming in. It'll hit the load balancer. It'll send some over here. It'll send some over here. It'll send some over here. And by doing so, what we're really being able to do is add capacity, add availability. So maybe I should get through a health check one more time as it pertains to load balancers. Some people find this a pretty hard concept, the health check, and it all comes out of networking. And let's talk about this. So let's say we have a load balancer. It doesn't matter if it's a network load balancer, application load balancer. So let's just call it a load balancer. And I've got 5 servers here, or a couple of servers here. And on a normal basis, the load balancer is sending some traffic to server 1, the load balancer is sending traffic to server 2, the load balancer is serving traffic to server 3. But what's going to happen is, and all routers do this, anything that requires high availability is going to do this, that you should use. It's going to send a request to the server. Are you there? Every periodic period of time. And it's going to check to see if this server is here. And it's going to check to see if this server is here with the health check. And those servers are going to reply, yes, I'm here. Yes, I'm here. Yes, I'm here. And as long as the load balancer is sending those health checks to the servers are responding back to this, yes, I'm here, everything is great. But now we've got the load balancer says to server 1, are you there? And it doesn't respond, no response back. And the load balancer sends a request to server 2, are you here? And the server 2 says, yes, I'm here. And then it sends a request to server 3, are you here? And then another request is sent to server 1, sitting over here on the left side, and there's no response. The next request gets sent to server 2, are you there? And server 2 responds. The next request gets to server 3, and server 3 responds. What ultimately happens is right now the load balancer knows that server 2 and server 3 are working. But after a period of missed health checks, the load balancer will mark server 1 as unhealthy. And what unhealthy means is don't send traffic to it. And from that point on, until we fix this, what will happen is the load balancer will only send traffic to the 2 servers that are available. And that way we only send traffic to good servers, and we've got high performance routing and high availability systems. So let's talk a little bit about internal load balancers versus external load balancers. So not all applications are web-based. And I'm going to tell you that most things that businesses use are not on the public internet. They're in their private systems. So we might have 50 HR servers, for example, and we don't want those servers exposed to the internet. We want them inside of our private network. We might still want to use a load balancer to load balance in between those servers. So using a load balancer internal to your network is typically called an internal load balancer. And that's so an organization can build high performance, fault tolerant, mission critical corporate applications that are private. At the same time, we may have web applications or other things that we want to face the public internet. What if we want a super high security environment and we want to use firewalls with more features and functionalities than, say, an AWS WAF? We're going to need to use a load balancer typically to load balance between virtual firewalls. That could be an external load balancer. So we could be using firewalls for those reasons externally, or we could be using a load balancer externally to front end a web application. So there are external. Internet facing is often referred to as an external load balancer. Could also be called an internal load balancer. So let's talk about some concepts in the AWS load balancer world. And I briefly went into the targets versus listeners. Really what's talking about is listeners going to be a process that's going to wait for connections. And they're going to be just listening and waiting for connections. You know, the network load balancers are going to be looking for the TCP, the UDP information, and the port number. The application load balancers are going to look at the HTTP or HTTPS requests. And that's what they're going to be listening for, traffic coming in. And then they have to make a determination, where do I send that traffic? Do I send it to a virtual machine like an EC2 instance? In which case, you know, you can put in the IP address of the EC2 instance. But I'll tell you this, when the target is going to be an IP address, it's going to need to either be in the private address range or the shared address range. So if you recall, we talked about private IP addressing, which was specified in the Internet Engineering Task Force RFC 1918. And that was the 10.0.0/8 subnet, the 172.16.0.0/12 subnet, or network, whatever you want to call it, and the 192.168.0.0/16. Now, we also have the shared address space, which was specified in RFC 6598. And that is this 100.64.0.0/10 address space. So we can use those target IP addresses for our load balancers. No, listeners where it comes in, targets where we want to send it. But what if we wanted to group our targets together? Well, that's where we come into this concept of a target group. And basically, you might want to say, let's say you had 10 servers that were going to be used specifically for Apple iPhones behind a load balancer. And then you had another 10 servers for Android phones sitting behind a different load balancer. A target group might actually be sending you to a specific set of devices. And you could group them together so you didn't have to manually enable every single target. That's all we're really talking about. I like to think of it the same way as you would create groups in identity and access management and create a group systems administrator and apply all the same permissions to the systems administrator group, as opposed to creating 50 different systems administrator accounts, one for every person on the team, and applying their permissions manually. The next thing we want to talk about is sticky sessions. I had mentioned that network load balancers, keep the same flow. They send it to server 1 this time, server 2 the next time, but the flow is consistent throughout the entire connection. But application load balancers don't just look at the source and destination address, protocol, and port number and build that kind of flow in memory. The application load balancer will, by default, route each request to the server with the lowest load. And that might be different than the server you primarily planned on. So if you want the application load balancers to kind of be somewhat stateful in the way that they say, keep the flow on each server until the flows are done, you can do that. But what you're going to have to do is you're going to have to do it with a cookie. The application load balancer will use a cookie to track a connection. And based upon the cookies, the application load balancers will create that kind of a sticky session. We don't have to do that with the network load balancers. And obviously, I mentioned the concept of the health check that's there to check the availability. Now, we have to talk about elastic load balancer sandwich. And there's going to be a lot of reasons we might need to stack our load balancers or use more than one kind. So one use case would be, what if we needed a lot of features and functionalities in load balancing, enterprise features and functions that are beyond what's offered by an AWS load balancer or an Azure load balancer or a Google load balancer? And we wanted to get something from, say, F5. We can do that. But if we're going to use a virtual load balancer in the cloud, and that virtual load balancer is going to be on a virtual machine, the virtual machine is not a high availability device, meaning if the virtual machine crashes, we lose the load balancer, and that's not going to work. So what we might do is create a load balancer environment where we have an AWS load balancer to front end to, say, F5 load balancers to give us better features and functionality in the cloud. So another time where we may want to use load balancers architecturally is when we need the application intelligence of a load balancer, of an application load balancer, but we need the network performance of a network load balancer. So what are we really talking about with these load balancer sandwiches? I'll give you a couple examples architecturally. I'll demonstrate them for you because these are very common that we would use them. So let me go share my whiteboard that I'll create for you. And let's give you two examples. Example one is I decided to use an AWS network load balancer. They add the word elastic, so they'll call it an elastic load balancer. I'll just call it a load balancer. And I use the network load balancer because I have speed and performance needs. But let's say I wanted to implement a reverse proxy with application load balancer-like functionality, and I wanted the reverse proxy for caching. Very common in an architecture environment. So, and F5 makes great enterprise-grade, reverse proxies. So here I have, say, an F5 reverse proxy that sits on a virtual machine. And behind these things, I've got my containers that are serving some kind of an application. This would be an environment where we would use a load balancer to load balance between two, say, enterprise-grade type reverse proxies. But how about this? What if we're huge and we're at scale and we've got all these container-based and microservice-based applications, but we're huge and we would really love the intelligence of an application load balancer, but we need the performance of a network load balancer? Well, that's no big deal. We can do that too. So here's how we make that work. We take a network load balancer, and then we front end a couple of application load balancers behind it. And you can finally put them, they changed it that you can put a manual IP address on an application load balancer with AWS about a year ago. So they made it easier to do this, which is great. So what you would do is you would use your network load balancer, which has all the speed, to load balance between, say, some application load balancers. And then your application load balancers would then have the capability to manage a reasonable number of containers with high performance. And this would be the kind of environment where you're creating, say, load balancer sandwiches and stacking your load balancers. Because what you're trying to do here is to combine the benefits of the intelligence of an application load balancer along with the speed of a network load balancer. So now you know why we might do these kinds of things in our load balancer architectures. Now we scratched the surface of load balancer architectures, but because that's what you need to know for the curriculum. And then Mo's going to talk about gateway load balancers and a few other things. So come back. Let's see if we have any questions. Okay, welcome back, everyone. Question from Samsung. One AWS certificate question. I see a lot of commonality between the AWS Solution Architect curriculum and the Network Specialty curriculum. What's the real difference and why? So, I mean, which topics are specifically heavy on networking curriculum for the professional exam? You're comparing with the professional curriculum, not the associate. So Samsung, there's a good reason you're thinking this. So here's the reality. The reality is there's not that many things on AWS. And if you're going to split AWS into 10 different certifications, you're going to have a tremendous amount of overlap. Now, nothing works, Samsung, without the network. And nothing works long if it's not secure. So you might see 20 or 30% or 40% of the curriculum similarity between an AWS Advanced Networking and an AWS Solutions Architect Professional. Probably have 20% in commonality with the security one. And if you were to do the database one, they're there. So what is the Solution Architect Professional? It is a systems administration certification, not an architecture certification by AWS. And it covers at a medium level depth, everything, low to medium level depth. And what is the advanced networking? It's a medium level network only focus. So Samsung, if we look at cloud computing, what is cloud computing? It's renting space in somebody else's network in a data center. So yes, you are right. There's going to be a lot of similarity between what you see here and what you could see on the solutions architect. But this is going to have much more depth on the networking side, and that's going to be more broad and focused on a little everything. So yes, you are correct. There is some some similarity with the security one too. And that's really what that solutions architect is. It is a general certification that covers a little bit about a lot of things on AWS. Can I elaborate more on the SSL termination that occurs at the load balancer? What happens to the traffic that goes out from the server to the client? It could be encrypted. I believe it's being encrypted on the load balancer, and that's the point of using the SSL termination. And why is this? It's very computationally intensive to do cryptographic applications. Very. Now, when cryptographic applications are done and processed on a CPU specifically, there's not that many cryptographic applications that you can do on a CPU at a single time. And I'll give you some examples of people that do a tremendous amount of cryptographic calculations or hashing calculations. You can think of blockchain. So blockchain initially started doing the cryptographic calculations on CPUs. And then at some point they migrated to the graphics processors to start doing these cryptographic calculations. And then they moved into the ASIC world, which is specific hardware. And an ASIC can't do a lot of things, but what it can do very well, very fast, at an extreme level of power efficiency. So it's going to be encrypted on the load balancer, and it's going to offload the server, and it can make a major impact in terms of the amount of compute performance you need. That is a great question, Prasad. Does the load balancer continue to pull unhealthy resources that is removed from the distribution of traffic as part of the health checks?
Does the load balancer continue to pull? So, yeah, it does continue. So I think if I understand the question correctly, you have, let's say, multiple resources behind your load balancer, and you have a health check to both of those resources, right? And then let's say one of them is deemed unhealthy, right? And then it comes back again. Does it get reintroduced into your load balancer? And the answer is yes, it does. And that depends on the timers, the threshold. Usually you have a threshold when a low. So if it keeps coming back and up, and basically if it keeps going down and coming back and going down and coming back, you don't want to reintroduce it again. So there's a threshold of waiting before reintroducing that. So there's some sort of a delay for something that goes down to reintroduce it back again into your load balancer.
When to use a network load balancer and an application load balancer. So it's going to depend upon a lot of things, but I'll give you some general guidelines, which won't work all the time, but they'll work probably in 90% of the time. When you need high speed and high performance, use a network load balancer. So if you're working with big servers, meaning servers that have over 64 cores or 128 cores, probably use a network load balancer. If you're going to load balance between a firewall or a router, use a network load balancer. If you're going to load balance between a network device, use a network load balancer. If you need intelligence and you're willing to sacrifice intelligence for the sake of speed, or you're dealing with really small servers or a little container, you're typically going to be using an application load balancer. And sometimes you need high speed and high performance. And that's why we did that demo that I showed you of combining and stacking your network load balancers with your application load balancers. I'm going to try to read this because I don't completely understand it. In case of using layer 4 and layer 7 load balancer for applications, can be immediate firewall between those, for example, DMZ architecture. So I'm not sure that I understand. Now, typically speaking, we would use a firewall in our demilitarized zone or a group of firewalls. And if we're in the cloud, we might actually have to use a network load balancer to run in 2 firewalls. And we might even want to use 2 sets of next generation firewalls, or we would say use a load balancer in front of, say, 2 Cisco firewalls, and then another load balancer in front of 2, say, Fortinet firewalls. Quite frankly, we might also want to use another network load balancer in front of 2 IDS IPS systems. And even though our Cisco firewalls and our Fortinet firewalls have IDS IPS in them, we might want the logging from the IDS IPS system, and we might also want to for the SIEM systems and want an additional form of IDS IPS systems. And so we might do that. Now, we might still want to put a layer 7 load balancer in front of our web application if we really wanted to, a layer 7 firewall. But if we're using a next generation firewall, Mohammed, we don't need to, because the next generation firewalls from a Cisco or a Palo Alto or a Fortinet are going to give us layer 7 and all the layer 3 and 4 and everything we need, and integrated intrusion detection, intrusion prevention. And it's going to give us more than that. So, Mohammed, if we use the cloud providers' firewalls, we have 2 options. Either we get hacked and we get notified because we're getting hacked, or some of the firewalls now can integrate with some other open source things for signature-based definitions for their IDS IPS systems. Here's what a signature-based definition is. Mo's attacked me in the past, and I know what the attack is, so now Benedict tries to attack me the same way. I catch Benedict because I learned about it because Mo attacked me in the first case the same way. Much like an antivirus. And, if Bo and I were to box, he's a better boxer than I am, but I got some good karate, It's going to take me a while to learn how Mo does his thing, and I'm going to catch him too, because he's not going to be used to my stuff. And that's so now let's talk about anomaly based, which is what you're getting from the commercial enterprise grade firewalls. So first, it knows about the previous attacks and it will stop it. It will give you layer 4 through layer 7. And now Mo comes in there and he tries something that looks awfully suspicious. And even though it's never been done before, the firewall says that thing looks kind of scary. Let's block Mo's attack. And then Benedict comes in and it's like, Benedict's traffic's normal. We like him. Benedict, welcome. So, I don't think we have to make it so complicated with so many layers. I think it's about choosing the right firewalls for the right application in the first place. It's a good question you asked. So I'll let you guys answer it first, then I'll add some color or flavor, perhaps.
All right, so Samson asking any guidance architecturally how to decide when to use API gateway versus application load balancer. So you use your API gateways to manage your APIs in a central location, right? You use your application load balancer to spread traffic to multiple web application servers, right? So the use case is kind of different.
Yeah.
Any others? All right. Well, I always love talking all kinds of networking things. They're always fun for me. So if you just got here per chance, this is a reminder that we've got about almost 2 full days of networking lab demos for you to do. And all you have to do is register for them. They are 100% completely free. You can find the description in the link as well as the chat box. I'm going to try to pretend to be Mr. YouTube for 2 minutes and say, if you're enjoying this content, please give it a like, subscribe, and hit the bell to be notified of new videos, that sort of thing, which I'm told I'm supposed to do. So if you haven't liked it, please give it a like if you're having a good time, and subscribe if you're not a subscriber. So Mel, it's off to you to talk about gateway load balancers.
Okay.
All right, we'll start with talking about the gateway load balancers, right? And what is the gateway load balancer? Think of a gateway load balancer as just another network load balancer, right? As we know with the network load balancer, right, you're taking information based on layer 3 and layer 4 information, right? It's the same thing for a gateway load balancer. But a gateway load balancer has a special purpose or a special architectural purpose. And the reason is when you have multiple appliances, network or security appliances, and you want to load balance your traffic across those appliances, right? Whether they're in an autoscale group or you have two or three load balance, two or more, let's say security appliances, right? So let's use a diagram to demonstrate this. If I can share my screen, there you go. Okay, so in this example, right, we have a gateway load balancer, right? In the appliance VPC, we call the appliance VPC, we can call the inspection VPC, right? And then you have multiple security appliances, right? Now you have two or more security appliances, right? And the gateway load balancer will work by sending your traffic to a security appliance, and then the security appliance will inspect your traffic, and they either send it back, send it out to the internet, or send it back to you, depending on the setup and the type of traffic. Now there are a couple of components that make a gateway load balancer work. Those components are, and I'll name them. Gateway load balancer, of course, the gateway load balancer itself, which has, and then we have the gateway load balancer endpoint. And of course, then we have the appliances, right? And there's a specific encapsulation method. We were talking about encapsulation yesterday and describing different types of encapsulations, right? So there's a special encapsulation that is used between the gateway load balancer and the security appliances. And there's a reason for that, and we'll go through it, right? But the encapsulation is called Geneve. It's a very lightweight tunneling protocol, but it's really useful. So with the gateway load balancer, let's focus on this side first, right? With the gateway load balancer, right, you have traffic coming in, and it hits the gateway load balancer, right? And the gateway load balancer, you wanted the traffic to be sent to the appliances, and then the appliances either send it out to the internet, or sometimes you just want the load balance, the appliances to inspect the traffic and return it immediately. And here's an example, right? Let's say you have the source in VPC A, and then the destination in VPC B. And then you want the traffic to go this way, be inspected by the firewall, and be sent this way, right? This is what in on-premise networking we call pump in the wire inspection, right? Basically, the appliance is just a pump in the wire. It will inspect the traffic without actually affecting or routing the traffic anywhere, right? And on-premises networks, usually we run two interfaces up towards those pump in the wire appliances, right? And then send the traffic with one VLAN, and then the appliance will inspect the traffic, change the VLAN, and send it down towards you again, and then it goes to the intended user. Now, you can't do that in AWS, right? You don't have that level of control over your infrastructure. And so AWS introduced gateway load balancers for this reason, right? And but the whole purpose is the same, right? You want the traffic to be sent to the appliance, inspected, sent back, without introducing some sort of a loop, right? Because otherwise, the appliance will be pointing this way, you'll be pointing this way, and you just have a loop. So you can't do it just based on routing. You need to introduce something else. And this is how you would do it. You would use a protocol called Geneve, right? The gateway load balancers, and AWS has partnered with many vendors from from Palo Alto, Cisco, Fortinet, and they have partnered with those different vendors in order to use Geneve encapsulation to basically send the traffic encapsulated with this Geneve encapsulation. And once it's sent to the appliance, all the appliance can do is decapsulate it. So remove that label, right? Look into the source and destination, right? If you have certificates installed and you can actually inspect the application level, you can inspect the application level of that packet, right? And then based on whatever policies you have in your firewall, right? Based on the policies, the firewall can either discard that packet, drop it, or send it, right? But it will not change the headers. It will not change anything. So once the packet is inspected, then your firewall will re-encapsulate it again. It will put the encapsulation again, the Geneva encapsulation, and then it will send it back to the gateway load balancer, okay? Once the gateway load balancer receives that encapsulated packet, then it will remove the encapsulation and send it towards the destination, right? So why do we need a gateway load balancer endpoint? So why do we need the endpoint, right? The endpoint is another component. It's basically just an ENI or an interface, right? So the gateway load balancer doesn't belong to one zone. It's regionally available, right? Which means, if we clear our diagram a little bit, okay, which means the gateway load balancer can exist between two zones. Let's assume that we have two availability zones here, AZ1 and AZ2. Right? You have some appliances here in AZ1, other appliances here for AZ2. You might have auto scaling group so that you scale based on demand, right? But let's say for this example, we have two appliances, two Palo Alto firewalls, right? One firewall is in AZ1 and another firewall is in AZ2, right? The gateway load balancer doesn't sit in one availability zone, right? Gateway load balancer sits between them, right? But you need some sort of an interface for your sources, for your EC2s to be able to send that traffic towards the gateway load balancer. And this is where you would need the gateway load balancer endpoint. So there's a lot of different models to implement this, right? With the same tools, which is the gateway load balancer, the gateway load balancer endpoint, your security appliances, and you're using Geneve, right? But there's too many, there's a lot of different setups you can use, right? This is one of them, right? And what this setup is, each VPC will have a gateway load balancer endpoint. So gateway load balancer endpoint. And then traffic will be sent to this endpoint, which is nothing but an ENI, a network interface, that forces the traffic to be sent to the gateway load balancer. So it's not the natural way of sending the traffic, but you force it to go that way, right? You force it to go to the gateway load balancer. The gateway load balancer keeps track of who sent it, right? Now the gateway load balancer then would look at this traffic and say, okay, this traffic is coming from, let's say, AZ2, so I'll send it to the appliance that's in AZ2, gets inspected, and then sent back, and it will go back here to AZ2, and then let's say if you want to exit out to the internet, you can send it out to the internet. The way this is done is, this is a little bit something it's worth going through with a diagram, so I've created this diagram for it. Right? The way this is done, and let me zoom in a little bit. Okay. So in this example, you have the inspection VPC, and then you have your customer VPC, right? This can be, let's say, and this design or this architectural patterns opens opportunities for a lot of different services, right? For example, let's say you're running a company and you're doing, you're providing inspection or security as a service, right? So you're a SaaS provider, and each of your clients terminates a gateway load balancer, and you allow them to run their traffic to be inspected through dedicated firewalls or a portion of your firewall, like a VRF or routing instance, so that they have a dedicated inspection, right? And then you can send it back to them. Or this could be different teams, right? You can have the security team, right, controlling the inspection in a centralized inspection VPC, and so that way you can separate the administrative responsibility based on different VPCs, right? This could be a completely different account for the inspection, different account for this VPC for internal client, and so on. But if we look into this diagram, you see that in the customer VPC, we have an internet gateway, right? And we have our applications, right? And let's assume that our applications need to access the internet, right? Let's say, for example, for some Microsoft updates, right? You're running Microsoft operating system, and you need to do some MS updates, right? But before you send those updates, you want to make sure that your traffic is inspected first. You don't want to add the firewall here, and then for each of one of your VPCs, you have a separate firewall, right? You want to have a centralized place where it hosts all your firewalls. So this is where we create the inspection VPC. We have a gateway load balancer, right? We send our traffic. We have a default route, but that default route doesn't point to the internet gateway. Your default route points towards the gateway load balancer endpoint, to this ENI. And then the gateway load balancer endpoints, the ENI, without looking at its routing table, this routing table, because remember, these are two different subnets. Notice that the gateway load balancer endpoint is in a separate subnet, right? Once this packet hits the gateway load balancer endpoint, that gateway load balancer endpoint ignores its routing table and forces the traffic to go towards the gateway load balancer. The gateway load balancer is also programmed to encapsulate the traffic with Geneve. Remember, we said Geneve encapsulation, which is a very lightweight encapsulation that's perfect for this. Implementation. It will send the traffic encapsulated with Geneve. The security appliances, your firewall, will then decapsulate the Geneve header. Then it will look at the packet. Based on your policies, it will make sure that this is allowed, right? For example, it will look at the source IPs and will look for a policy that allows for MS updates, right? And then we'll check the destination route, let's say, and they can look at, like, for example, the fully qualified domain name, make sure that you're sending your Microsoft updates to the correct destination, right? So based on your policies, if this is an allowed traffic, then it will be re-encapsulated again with Geneve and sent back to the gateway load balancer. If it's not allowed, then it will be discarded. So let's assume it's allowed for this case. It gets back to the gateway load balancer. The gateway load balancer, once it hits the gateway load balancer again, now this time, the gateway load balancer will send it back to the gateway load balancer endpoint. Now, when it's returning to the gateway load balancer endpoint, the routing behavior is different, and this is why this is how we can get around looping the traffic, bumping a wire, without actually causing routing loops. So you send it back here. Now the gateway load balancer endpoint will look at the routing table, and inside this routing table, you have a default route that points towards the internet gateway. The internet gateway sends the traffic out through the internet. When the traffic returns, the internet gateway has a route that sends the internet traffic towards the gateway load balancer endpoint, right? So you're changing the default behavior here. You're sending the traffic to the gateway load balancer endpoint, and then the same thing happens. You send it towards, and let's use a different color. You send it towards the gateway load balancer. The gateway load balancer sends it to the security appliance. It gets inspected, comes back. So there's already a stateful policy ready for it since it already was inspected. The gateway load balancer will send it towards the gateway load balancer endpoint, and then it will look at the destination. This time the destination changed from the public internet. This time it's the subnet or this subnet. So we'll just send it this way based on the routing table. So this routing table of the inspection VPC will have two subnets, one that points towards the default route towards the internet, and then it has routes from the local routes from the VPC, for example, the routes that exist in this application subnet, and it can send the traffic this way. So as you can see, it's multiple components that work together to make this happen, but it opens a lot of opportunities. This, I would say, it's probably one of the simpler ones. There are a lot of more complex, but really useful, necessarily complex, I would say, setups that can really help you integrate your security appliances and deal with security in a centralized manner. Okay, we already went through and explained this. So why would you use a gateway load balancer? Well, number one, as we've seen, you get efficient traffic management, right? So you get to manage your traffic and route your traffic through an inspection VPC, which is something that's really difficult to implement otherwise, right? You get enhanced security, right? With this type of setup, right? You have a centralized inspection VPC where you can have a lot of inspection resources, and instead of having different firewalls all over the place, which can be very costly too, you also get the benefit of not having to manage your security policies in 10 different things, in 10 different places, I'm trying to say, right? High availability. As you've seen, this gateway load balancer is really a network load balancer, right? And so you can do, you can have different setups. Like, for example, you can have load balance and your traffic and have it inspected over multiple load balancers. Over multiple security appliances, right? So if one security appliance fails, the gateway load balancer keeps health checks, and it will make sure that it will send the traffic to be inspected by the firewall that actually passes the health check, right? And it's still up, right? The healthy appliances. And of course, you can integrate it with auto scaling group, and that way you can scale your security appliances. I'm getting tongue twisters. Horizontally, right? Or scale out, right? Instead of scaling up, so you can add more firewalls on demand. Okay. So the next topic is a little bit different. So I think it makes sense to take a short break, or not a short break, or take questions. That way we can move on to the next topic without having to worry about this. Okay. Let me go through and make sure that. Okay. All right. Let's take questions. Let's take some questions.
Okay, let's take some questions. I'll read this out. Samsung, for egress and ingress traffic makes sense. Just asking about 2 EC2 instances that are internal to the AWS account. I'm not sure what you're actually asking for there. But Mo, you were going through the situation, so maybe you know what he means.
Yeah, I think it depends on when he asks the question. So I think what he means is for east-west versus north-south traffic, right? So when you say egress to ingress, do you agree, Benedict? I think that's what he means.
Sorry?
So ingress,
Yeah, I think.
He probably means that, right? So ingress,
Yes.
egress, he means east-west, north-south, right? So traffic exiting to the public internet, right? So yeah, that definitely makes sense, right? But you also would want sometimes, let's say you have traffic that goes between different VPCs, right? So you have, let's say, 30, 40, 50 different VPCs. And also you have, let's say, traffic that's going to on-premise, right? This is more of an east-west, right? How would you want to manage those traffic, right? You also want to make sure that, this traffic is getting inspected by your security appliances. And so, this is where it would make sense to have that this setup for those instances as well.
Okay, let's bring in the next one.
What are some real life where it makes sense to monitor internal? Okay, what are some real life examples where it makes sense to monitor internal instances, right, to another EC2 instance, like you showed in the gateway load balancer slide? Watch the internal hackers, maybe? Okay, so there's a lot of freezes, right? One of them is, think about having a development VPC and having a production VPC, right? The development VPC shouldn't, might need some access to production, but very minimal, or maybe between a testing VPC and a development VPC. Do you want to, since, let's say, for example, using a transit gateway, you're routing traffic through the transit gateway for different VPCs to talk to each other, but you don't want to just give them complete access to each other, right? You want to limit what they can access. This is where it would make sense to, have this setup with a gateway load balancer for east-west traffic. So there's a lot of real-life scenarios. I think Benedict will be provide better real-life scenarios.
So real-life situation. I worked in an organization once where there was a DDoS attack on one of our servers. And when we conducted the post-mortem analysis, we found out that part of the internal PCs, some internal PCs were part of the botnet, right? So if there was that restriction there for these internal PCs to reach the server, it would have mitigated the impact of that DDoS attack, right? So if an EC2 instance is compromised, right, it could be used to attack another instance. So there's lots of ways it can happen. There could be lateral movement of a worm from one EC2 instance to another, right? So you want to kind of set up a least privilege policy when you're, designing your security architecture.
Yeah. Plus, this is part of more. Sorry. No, I just want to say this is more. Trust. I apologize. There's a 1 second delay from my end, so please go ahead.
I was going to say, go ahead, Mo. But okay, so here's the thing. There's a lot of reasons you may want to monitor people. There's some industries that are highly regulated. There are some companies that produce some very secret or semi-top secret information where they want to see what's going on and where. But most hacks also do come from the inside of the organization. And often they're via well-meaning individuals. I saw a bank that got taken down from a worm when it affected users' PC. And lots of things that we need to do to learn the environment better to further lock it down. So I'll go back to Mo, but there's a lot of good reasons to inspect traffic, because it's not just, we're going to have our DLP systems, our SIEM systems, we're going to be doing other stuff. We might even be doing machine learning and to be able to visualize things in real time. And all these tools help us do that. I go back to you, Mo.
Yeah, this is what Mike is describing is what we call zero trust, right? This is part of a zero trust architecture where you give least privilege, right? You only get access to what you actually need, right? And just as the scenario that Benedict described, right, which happened in real life, that would have been prevented if an organization had more of a zero trust architecture rather than just leave it open, right? Assuming that everything is trusted internally. I'm not sure if this is related to what we're talking about.
Yeah.
Use cases for gateway load balancer with transit gateway. Yes. That's a very good observation, because that's when I said there's more complex but necessarily complex designs. This is one of them, right? You would introduce a gateway load balancer inside the inspection VPC, and then you already have a transit gateway, and then multiple VPCs will be able to talk to each other, but they first have to be inspected through the inspection VPC and come back. Now, this is a very complicated setup. We're probably going to do a session for it. Not part of this bootcamp because it's really extensive, but we're probably going to do something of that sort in the future.
Absolutely.
Is Geneva to optimize traffic between the gateway load balancer and security appliance? Well, that's exactly what it does, right? Geneva forces the traffic to be encapsulated, just to be inspected, decapsulated, inspected, encapsulated back again, right? So literally provides that same pump in a wire behavior that we had in the data center, or on premise, pretty much. We have the same setup now with the gateway load balancer using Geneva. So by optimize, I don't know what you mean by optimize, second part of the question, but it's not in, all it does is encapsulate it, send it, encapsulate it, send it, decapsulate it, send it back again. So there's no more optimization aside from that.
All right, it looks like we don't have any more questions, so we've got lots more content to get through. So Mo will get back to the content. If you haven't given the video a like, please give it a like, subscribe, that sort of thing. And please make sure that if you haven't downloaded the labs or accessed the labs, you get access to them, because it's 2 full days. And it looks like we're going to go 3 full days of content, and then you'll have 3 full days of hands-on tech things that you can practice with, which we're pretty happy to offer that at no cost. So I want to make sure you sign up for these things. And we'll get back to the content now. But so I know you're awake, please give us a hashtag AWS Advanced Networking. I like knowing everybody's awake out there.
Okay. Sticky sessions, right? We previously spoke about sticky sessions. Let's kind of continue that conversation. Sticky sessions, or what sometimes they're called, it's called session affinity, right? And in the context of AWS, right, if you have an application load balancer, right, and you're sending your application, your client traffic to a server, preferably you would want your client to always client's traffic to be sent to that same server, right? And what I mean by that is you want to avoid a behavior where the client's traffic is sent to server A and then it returns, but the next time the client sends the traffic, it's sent to server B, right? Especially for stateful applications, right? Think of an application, let's say like some e-commerce application, and then you have a shopping cart, right? And then you send the traffic here, And then the next time, if you send the traffic to a second server, you might lose this information, right? Information that is relevant to the existing session, right? And so what you do is you use session stickiness or session affinity so that the traffic is sent to the application load balancer. The application load balancer sends it to the EC2 instance. That is the web application, right? And then the application load balancer would keep track of that session, right? Based on session cookies. And what session cookies are, think of it as a hash that signifies your session, so that when you return based on that session cookie, the application load balancer will know to send it back to that same server, right? Now, there's two ways to do this, right? There are applications that support session cookies, and when you establish a session with the load balance with the server, right? The application will reply with a cookie, right? And the load balancer will keep track of that cookie as well, right? So that when you return, the traffic will be sent there, as long as that session cookie doesn't expire, and each cookie expires. So traffic will be sent to that server, right? And then the second client will get load balance to send to an application server, and then based on the session cookie that they have, they'll always go to that server. Okay. What if your application doesn't support cookies, right? So what if application-based cookies are not an option, right? Because your application just doesn't support it. Well, in that instance, the load balancers have what is called a duration-based cookies, right? Your application load balancer can use duration-based cookies, and all it means is the load balancer itself will create or establish that session cookie, and it will send it to you. And then so when you return and you have that cookie as part of your packet, then it will know to send your traffic to server A versus server B, right? So the application load balancer, using duration-based cookies, you can maintain that ability even if your application doesn't support cookies, right? So I'd like to think of it as having sticky sessions as your application, your client traffic is pinned down to a specific application for a duration of time. So why should you use sticky sessions, right? Or session affinity? Well, enhance user experience, right? You get a more consistent experience, right? So that when you send your traffic, if you have any what's the best way to say this? So if you have just like the example we described, right, with the e-commerce, right? If you had like a shopping cart, and the shopping cart existed in server A, right? Using the session affinity, you'll always go to server A. So while the session is still active, you'll always be going to that server instead of going to server B and then losing your existing shopping cart, right? So you get that enhanced user experience because, and this is important mostly for stateful interactions, right? Or stateful sessions, meaning sessions that maintain a state, right? And then improved efficiency, right? Because the session is sent to this, the sticky session is sent to the same resource, right? You get the benefit of a predictable and consistent latency, consistent resource utilization, because instead of having to reestablish that session again and send it to a different server and then a third server, right? You get more of a stable and improved efficiency. Okay. So that's sticky sessions. Let's move on to the next topic, which is SSL or TLS offload, right? You might see this topic as SSL offload, you might see it as TLS offload. In reality, it's the same thing. And, bear with me 1 second. Send the slideshow there. In reality, it's the same thing, right? And here's what I mean. SSL or secure socket layer, is an encryption method, right? Or encryption protocol that happens at the transport layer and at the application layer, right? So between the transport and application, right? But the purpose of SSL is to encrypt your user traffic over the internet, and not having to rely on layer 3 to encrypt your traffic, right? Now, TLS is the successor of SSL. Think of it of the more enhanced SSL, right? It's the same method, but it's a stronger encryption method. Other thing is, so that means when you use an HTTP, right? HTTPS is basically HTTP over TLS. So you're using TLS to secure it, right? Just back in the day, you used to use SSL to secure HTTP. Now using TLS to secure HTTP. So that's basically what HTTPS uses. So moving forward, we'll talk about TLS, right? You can use, so I've noticed that a lot of documentations use the word SSL and TLS interchangeably, but in reality, you're using TLS. So what's TLS offloading, right? Sometimes we call it TLS termination, right? All what TLS offloading or TLS termination is that you have a proxy server, right? Or what we call a reverse proxy server, right? And a server is basically a device that does the TLS termination for you, which means you establish, it's a device that sits in front of your application servers. And to draw this, I'll actually draw this out. So let me share my screen. Okay. So think of it this way, right? You have a reverse proxy. And you have your server right here, right? So this reverse proxy can be anything that performs TLS termination. It can be a CDN or content delivery network, right? Like Cloud Front or maybe Cloudflare, some solution that does supports content delivery network. It can be an application load balancer, right? An F5 or a NetScaler or whatever load balancer, right? And then you're here behind the internet as a client, and you're trying to reach this server, right? So what would happen is that your PC or laptop, right? You'll access let's say in this example, we're using an application load balancer. So you would access the application load balancer, right? The application load balancer will actually initiate a three-way handshake with you. It will create a session with your laptop, right, or with your browser, right? And then it will create that session with the client, with the server on your behalf. So we'll establish this session with the application server on your behalf, right? So you don't have to, so that you offload the process of decrypting the traffic in order to read the HTTP header, right? Or the application layer header, right? The application load balancer will do that on your behalf. And that's why they call it TLS offloading. You offload the TLS termination, right? Which means you need your certificate to be installed on this application as well, right? Otherwise, how are you going to decrypt that, right? So you would offload the TLS termination. And there's other benefits for this too, because what the application load balancer can do now for more advanced load balancers, like an F5 load balancer, right? What it can do is it can establish one session with the application, right? And then it can basically all the client sessions using this one session, right? And this is usually what you see in some of the like a NetScaler or an F5, where you have a virtual IP here behind the load balancer, and then you would have here a source IP, or sometimes, at least for NetScaler, they call it SNP, right? And then you would establish the session here on behalf of all your clients. That way, you offload some of that repetitive process that happens as you keep, your application would establish multiple sessions with the client, right? So you're offloading that load to your application load balancer. So it's the same method that's used for content delivery network or for application load balancers. Now, once your traffic is sent, right? Once the traffic reaches the application load balancer or content delivery network, you have two options here, right? Because you already decrypted the traffic, right? It terminates at the application load balancer. You decrypted that traffic. Now you can send it to your application as HTTP, or you can send it as HTTPS. And sometimes it would make sense to just send it as HTTP if, for example, this application load balancer is in the same VPC as your application, right? But if you don't, or maybe you want to send it through a firewall and you don't want the firewall to handle the TLS termination. You don't want the firewall to you don't want to install your certificates on the firewall again and have it inspected there again, right? But at least you have the option to either send it back, send it to your server as HTTP or as HTTPS, right? So if you're going to send it as HTTPS, that means you do TLS termination here, and then you encrypt it again. So you decrypt it, then you encrypt it again, and you send it to your application, right? So you're doing encryption twice. Okay. Of course, there's an opportunity to use a web application firewall, but that's a business decision whether you want to use a web application firewall or not. But a web application firewall can allow you for some URL filtering and things of that sort, whether it's on a content delivery network or if it's on an application load balancer, right? But definitely don't rely on that. Don't think that a web application firewall is secure enough, right? It's maybe another component you want to add if you want to handle that complexity. But it's definitely not your one-stop shop for security, right? You would need more of a more mature firewall, like a next generation firewall. So why would you use TLS offloading or TLS termination, right? Well, obviously enhanced server performance, because you're not doing the termination at the server, you're doing it at the application load balancer, right? Then it allows you to free up some of the resources on your servers, right? That's definitely one of the biggest benefits, right? So the ability to handle high traffic, right? So because the load balancers are a highly available solution, right? They can handle a lot of they have plenty of resources, right? Again, offloading your TLS termination at the load balancers, has that added benefit of not having to scale up your servers just because of the overhead of the TLS termination or SSL TLS offloading, right? Well, it can be a centralized SSL management, right? Because your load balancer is doing the SSL termination, right? It's, if you go with the option of terminating the traffic at the load balancer and then sending it unencrypted, that means you only have one place to manage your certificates, right? Installing your certificates or renewing your certificates will be done on that SSL, on that load balancer. Although it's not recommended, right? More realistic setup would be actually you're going to have to just deal with the pain of having to install and renewing your certificates on different nodes, because you want that level of security at different nodes, right? From your firewalls, your load balancers, on the application itself, and so on and so forth. Okay, so that's SSL offloading. Now let's very briefly go through TLS pass-through, because you already know what TLS pass-through is. TLS pass-through just means you're not going to do SSL offloading. Or in other means is, for example, you have a network load balancer, right? The network load balancer looks at layer 4, right? So it looks at layer 3 and layer 4 reality, right? You look at the source destination IPs, and you look at layer 4 for the port number, right? Now, protocol type and port number. So with TLS pass-through, it just means to send that traffic without decrypting the traffic at an application level, right? So we can say TLS pass-through just means you're not doing TLS offloading, right? And of course, when you do that, you just pass it through, the performance is going to be better because you're not encrypting the traffic and sending it, so it's much faster, right? Okay. The next topic is proxy protocol. Now, proxy protocol is basically it's a solution to a problem that happens when you use an application network load balancer, right? Let's say you have this network load balancer. Let me change the colors. Okay. Let's say you have a network load balancer, NLB. Okay. And this network load balancer sits in front of your applications, right? And then you as a client, right, send your request or your traffic to the network load balancer. And then the network load balancer sends you traffic to different applications, right? To your load balances your traffic between applications. Now, the problem with this is when a network load balancer sends the traffic from your to your applications, is that it changes the port number, right? It changes the port number at layer 4. And so even though the source and destination IPs are the same, it will change the port number, which in this case is the source port number of the client. And that can cause an issue if you have multiple clients behind one firewall or NAT gateway that's doing NAT, because those clients, when you change that port, right? All of those clients have the same source IP address, right? Because you're doing NAT, right? And so if you have a policy at your organization that demands that you log your client's information, then it's going to be difficult to do that if you don't have the port numbers to map each user to a specific to the port that they used, right? And this is where proxy protocol is used for, right? the proxy protocol will amend the header at layer 4, and it will add a section called proxy protocol. And that proxy protocol will basically keep or maintain the original port number, right? So even though it was changed at layer 4, you have a new section that is amended by the network load balancer. That's called the proxy protocol. And that proxy protocol will have the original source port number of the client. Okay. So biggest reason why you would use a proxy protocol is, as I said, right, if you have a policy in your company, so it's more of a compliance issue, right? If you have a compliance policy that forces you to use to keep the information, this is where, you know, proxy protocol would make sense. Okay. The next subject is X forwarded for, and it's very similar to a proxy protocol. The difference is when you use an application load balancer, right? So when you send traffic using an application load balancer, right? When you send it from the client to an application load balancer, right? The application load balancer will send that traffic to your server with a different source IP. And the reason why is the load balancer needs to be in the traffic path, right? The traffic needs to return to the application load balancer. And so the application load balancer, when it sends your traffic, right? So from the client, from you, it will hit the application load balancer. The application load balancer will take that traffic, right? And it will, since it's establishing a new session with the server, the application server, it will change the source IP to its IP, right? I previously talked about, at least terminology of NetScaler, they call it a SNP, or a source network IP, right? So it will change it to that IP, right? So that the server will reply to the application load balancer, not directly to the client. Well, the problem here is if you have the same regulatory needs to maintain or keep track of the client's source IP, then you lost that privilege, right? By using application load balancer. So there's a header that's called the X forwarded for, right? And the application load balancer will add that header. It's part of the HTTP header, right? And it will add the X forwarded for, so that the application load balancer, when it so that the application, so that the application server itself will find the user's source IP inside the X forwarded for header. So again, right? So you reserve the client's IP, and it's important for security and compliance, right? Also for services that require, for example, geolocation services, right? Services that depend on the location of the client based on their IP address, right? If your application looks at the IP address and then determines the location of the client, right? You lost that, right? Because now you're seeing the IP of the load balancer. But because you have the X forwarded for, you can, you know, the application can rely on the X forwarded for header and look at the IP address and determine the geolocation, and then make whatever business logic based on that geolocation. So, you know, based on the IP address, right? Based on their geolocation. Okay. And we described TLS termination, sticky sessions, TLS pass-through, and finally we went through X forwarded for. Not sure if we're going to take questions or not. Yes, we are.
Absolutely. Always like to take questions. You know, we want to make sure that everybody has a good grasp of it. And we'll end the day with the questions. So get your questions in. because we want to make sure everybody has a good experience. Name not found. Is this why when you were booking tickets on holidays and you don't confirm or pay within a certain period of time, it says your session has expired and you have to start over again filling out all the details? It could be. So there's lots of things that happen when there's high traffic environments, but absolutely that could be one of them. But from a security perspective, you know, I want to think about it this way. You know, you've got some people that if you've got a cart and it's limited supply and you don't buy it, they may want it to go to somebody else. So they may limit how long something is in your cart. And they may choose to limit it more during a period of high demand times. So say Black Friday, that day after Thanksgiving in the US, where people just go buy. If there's a limited supply of something, they're not going to leave it in your cart for a long period of time. That's typically what could be going on from a business logic perspective, but there are other business rationales or other reasons that could be occurring as well. How do you get 100% use of load balancer in case of sticky? 100% use. You're not going to get 100% use of anything if things are actually working properly. Even if I give you a 100 gig network link, 100% use is like 90. But if we tried to get to 100% use, we're never going to truly get there. Now, what happens when you get to 100% use of your CPU and your systems? They often crash. Not always, but they may crash. So we're going to try not to get to 100% use.
Mo, I'm confused. You said if your application does not support cookies, then Elastic Load Balancer, application load balancer creates a duration-based cookie. So not Elastic, but application load balancer creates a duration-based cookie. Then if the app does not support any cookies, how does that help? Well, here's how it helps, right? The purpose of the cookie here from the load balancer's perspective is for the load balancer to know where to send your traffic, right? So if you're client A, right, and I initially sent your traffic to server A, right, application server A, when you return, I need to know that you are the previous client A, so I can send your traffic back to the server A instead of load balancing and sending it to server B or C or D or E, right? So if the cookie, usually the cookies is based part of the application itself. And so the application load balancer, all it needs to do is listen to the cookie that was assigned by the application itself, and then send that cookie. And, and then when I hear the client return, I'll know to send you to application server A based on that cookie. But what if we don't have that cookie, right? Well, the application load balancer will create its own cookie and will assign it to you, to the application, right? And because it's taken care of terminating the session at the so the application load balancer terminates the session on your behalf, it can insert that cookie into the session, into your packets, right? And do we have to make some heavy app code changes to utilize the cookies? Well, most applications, right? It depends on the framework you use to write your application. Like I personally, I'm not a web developer, but I did build websites just to learn based on Flask, right? They have different libraries, and it's usually part of the library itself that you use to build your applications, right? So it's not that complicated. Usually there's different libraries to establish those cookies on your behalf, right? And you can control when it expires and so on and so forth. Does the proxy protocol change the frame size? Yes, it does. So the proxy protocol has about 38 or 40 bytes of traffic, of data. So that header that you're adding, right, or that information that you're adding is going to add about 40 bytes of traffic. So it's not that big of a change. security at the edge with content delivery network. How does it apply? Well, you're using content delivery network, right, as a TLS termination, and it does web caching of your traffic as well, right? Because so how does it apply? I'm not sure what you mean by how does it apply. I'm not sure if I exactly what do you mean how does it apply.
Let me try to give you a little perspectives of content delivery networks adding security. But please understand, Mohammed, that a content delivery network is only 1% of the security. We still need our demilitarized zones. We need our application security. We need our endpoint protection, our operating system hardening. But let's talk about the content delivery network perspective itself. So if we look back at the way TCP works, when we try to set up a connection, for example, we send a TCP SYN. If I want to initiate, if Mo's a web server, I send a TCP SYN to Mo, and he sees the SYN, which means open up a connection, and he does, and then he acknowledges my connection, then he sends an acknowledgement to me and a TCP SYN to me to open up a connection on me, and then I acknowledge that, and then Mo and I are exchanging two-way conversations. But what if I was a bad guy and Mo was a web server and sent 50,000 TCP SYNs to him? Mo would ultimately open 50,000 connections on his web server, which may be more than he can handle, which could crash the server. Or maybe he can handle 50,000 web connections, but I just opened 50,000 half connections. Well, all those connections are going to be waiting, and then nothing can occur. So when we deal with content delivery networks, they're going to look for things that are wrong, like pings of death. They're going to look for things like a bunch of malformed or bad TCP or session requests. By doing so, the content delivery network will look at it and say, this isn't right, and just stop them before it hits the web server and damages the web server. So that's some of the kind of DDoS protection we're getting with our content delivery networks. And Cloudflare obviously has it because it's a content delivery network. AWS has their flavor of content delivery network, which is Cloud Front. And then they use Shield as their DDoS protection to attach to the content delivery network. But that's really what we're talking about. Only sending legitimate requests to the servers and blocking all those typical hacker tricks and tools on the content delivery network before it even hits our load balancers or our firewalls in the first place. Good question, Mohammed. All right. Well, we did it. You guys made it through day 2 of our AWS solutions, our AWS networking specialty course, which is the AWS Advanced Networking course for the AWS ANS-C01 exam. So I had fun with you guys. Maybe you can give me a hashtag AWS Advanced Networking that you're, so let us know that you're here. If you haven't liked the video and you enjoyed it, please give it a like. And while we're at it, please share these videos with a friend. Maybe you've got a friend that wants to learn AWS. Maybe you've got a friend that wants to learn AWS Advanced Networking. Share these videos. It takes a lot of time and effort to bring in a bunch of network architects from all across the world. And our team that put this together is truly from all across the world. My family's from Philadelphia and Greece. We had from Marcus from Serbia who put this together, who was part of this. Mo's from Libya, Benedict's from Nigeria. I mean, we worked all across the world to put this together for you, and we love doing it. And hopefully all of you from all across the world as well. So give us that hashtag. I see they're popping in. Give it a like, subscribe to the channel, and notify some others. We got a lot of other free things that we can do to help you in your career. And check out some of those in the description of this video too. So look forward to seeing you tomorrow. Bright-eyed and bushy-tailed at 10 a.m. Eastern Standard Time. Just like today, we'll have 3 hours in the morning. We'll pause for an hour. We'll have 3 hours in the later afternoon. Don't forget to get all those labs and technology walkthroughs we did. You can find them in the chat box as well as the description of this video. Have a great night, everyone. Take care.
All right, bye, guys.
Mo and Benedict, thank you so much. Welcome back, everyone. We are here for day 3, session 5 of our AWS Advanced Networking course to help prepare you for the ANS-C01 exam, and this is a full AWS networking specialty course. My name is Michael Gibbs. I am joined here by Mo and Benedict, and we are your instructor team for this AWS Advanced Networking course. Before we begin, I'd like to tell you about a few things in case you just got here. What we're doing is we're doing lectures because we have so much information to cover for the 3 full days, but there's also almost 2 full days of labs. labs on AWS for the AWS Advanced Networking curriculum, and also labs that we've actually done in our data center for you. And here's why. When you configure something on the AWS cloud, you're not going to get to learn a lot about how it actually works at the underlying level because it's a cloud and it's hidden from you. So we actually did the AWS labs for you, which we'd love you to do, but we also have those that we've done in our data center. And we're walking through the switching and the routing protocols and how things work at the fundamental level. So you can learn how to not just configure, you can actually learn how things work, which is going to be critical for any type of a cloud architect career or any type of network engineer career or network architect career or cloud network architect career. So we're doing this for you completely free. If you've just joined us, invite a friend. Takes a lot to put these kind of things together. Costs almost as much as a car by the time you're done with all the people be in the back end and the foreground and everything necessary. So please invite some people. We want to help you begin.
Hey, Mike.
Hey, Chris.
So I wanted to make sure. Did you see the student that got the new job, the cloud hired?
I did. The student in Orlando that got a job this morning.
Yes.
Yes, I'm always excited every time one of our students gets a great architect job.
Sorry, it's a Sunday, and it's a great way to wake up on a Sunday.
It really is. You know, our whole point around here is not just to passing a certification; it's to change lives and help people get hired. And every time a student in our cloud architect career development program gets a new architect job, it's kind of like for me, it's like when I got my first job the first time in tech, over 25 years ago. It's a long time. So we're going to continue the content. Chris,
yeah, I've got my camera off because I'm doing my dance. Nobody can see my dance. So.
Well, that's true. We all have a different level of happy dance. My feet are a little goofy, but from some injuries. But we do all have a happy dance every time someone gets me hired. So while we're at it, give me a hashtag cloud hired and a hashtag AWS Advanced Networking, and then we will begin. Okay, so we're going to begin by talking about Cloud Front. And I'll be discussing Cloud Front, and then, we'll go through a lot more content today. But let's begin with Cloud Front. Cloud Front is the Amazon-branded content delivery network. And what a content delivery network really is it's a network plus a geographically distributed group of servers. And the whole point of a content delivery network is to provide fast delivery of internet content. Content delivery networks are often used to reduce bandwidth costs because, especially in the cloud, you're paying for the traffic. At least you were paying for all the traffic egress, but you're still paying for a lot of those inter-region type charges. So if we can push the content directly to the content delivery network, or at least based upon request, we can reduce some of our our network transfer costs along the way. So hope that actually makes some sense here. And the other reason we're going to leverage content delivery networks, and this is probably the most important reason besides the scalability, is the DDoS mitigation. And content delivery networks often dramatically enhance our website scalability. And the reason they do so is they won't send illegitimate requests to the servers. And by doing so, a content delivery network can help mitigate, say, a DDoS attack. For example, and I briefly covered it yesterday, if I want to do an HTTPS request or an HTTP request, and I request data and it's sent to me, life is good. But if I were to initiate, 10,000, 50,000, 100,000 TCP half open requests to the web server, it will take those resources from the web server. The web servers will be waiting to respond to the half open request, and they're not going to get a response, and it's going to use the capacity of the web server. So with content delivery networks, malformed internet requests don't get sent. Any type of anomaly behavior that's typically bad is typically not sent to the web servers, and that can reduce DDoS protection. And if you think about it, if for some reason your web server were to go down for, say, 5 minutes, there's a good chance that the information is actually cached on the content delivery network. So if a web server has to be rebooted, there's a chance that some of that content will still be served. So it can provide some additional high availability information when needed. So let's talk about performance. CloudFront can really help improve website performance, and it's going to be integrated into numerous AWS services. And CloudFront actually has a network of caching servers that's going to be spread throughout the world. And what's going to happen is when a user makes a request to a web page, their geography is going to be determined by their IP address. And then they will be sent to the closest CloudFront server, which is going to be cached to them. And the local CloudFront servers will cache the information until the TTL wears out. So it will minimize the amount of time that people actually have to wait. So we're going to walk through this. Now, I want to make it very clear. In a high availability situation, one content delivery network is not enough. And if you were to open a terminal window or a command prompt in Windows, and if you type nslookup www.amazon.com and all of you did it, some of you are going to see that you're going to connect to the Amazon CloudFront content delivery network. Some of you will be connecting to the Fastly content delivery network. Some of you will be connecting to the Akamai content delivery network because Amazon wouldn't let themselves use a single content delivery network because they need high availability. So they're going to use multiple content delivery networks. So when it comes to high availability, think multiple clouds, think multiple content delivery networks. But we're talking about the AWS content delivery network, which is a great content delivery network. But if it really matters and if it's really mission critical, don't use a single content delivery network. So here's the way a content delivery network is going to work. I've got some data over here from, say, the client. Let's say, for example, the information is going to be common information. So the first request, what you're going to see, is going to be from the host or the user. They want to receive something. So they send a request, and their IP address is going to be determined. They're going to hit the local content delivery network location, and it's going to pass through CloudFront. If it's the first request, CloudFront won't have it. So the local CloudFront area will be sent to the regional cache. If the regional cache doesn't have it, it's going to be sent to the source. So in this case, it's a static website. The source of the internet content is the S3 bucket. It will be sent from the bucket to CloudFront, and now CloudFront will cache the information, and then it will be sent to the client. Now, the next time we have a client that requests the same information, you'll see the request will go straight to CloudFront, and then it'll come straight back. So, for example, let's say we had a Taylor Swift who wanted to tweet a photo of her cat. And who doesn't want to see a photo of a cat? And I know a lot of Taylor Swift's got a big fan base. So Taylor Swift sends a photo to of her cat. Poof. Everybody wants to see it. That first request in a geography goes to see the cat. And all those other requests don't make it back to the website. So we could have 1 million requests coming out of the same area, and only the website has to process the first one. I hope you can see how that will help our web scale. So caching enhances scalability, and it can make a website much more scalable by offloading frequent requests. Now, if a website's serving all dynamic content and it's completely different dynamic content, it's going to change all the time, and none of the users are requesting the same thing, then a cache isn't going to help. Caching is useful when the content is frequently requested. So I hope that makes sense. Now, CloudFront's integrated with a whole lot of AWS services, so it's going to make it easier if you're using AWS. Things like S3, your EC2 instances, your load balancers, your DNS, they all kind of integrate fairly nicely with CloudFront. And CloudFront is often used as a front end for static websites, and CloudFront can also be used for a dynamic website if it's based on EC2 and a load balancer as part of the architecture. So what would it look like in a non-static environment? Well, it would look fairly similar to this. You'd have your users, they'd access CloudFront. The static content would be coming out of your object storage bucket, or S3. And your dynamic content would be served by your virtual machines that are sitting behind the load balancer, otherwise known as EC2 instances. There are some key concepts we want to talk about with regards to CloudFront. And these concepts are going to show up in AWS exams again and again and again. So let's go over them. We're going to talk about the distributions, the origin, and then we're going to talk about the cache control. So when you set up your CloudFront content delivery network, you're going to need to set up a distribution. And the distribution is going to be identified by your DNS name. And this is going to be a very ugly name. If you all go and do an NS lookup, www.amazon.com, what you'll see is you're going to get something that looks pretty ugly. In fact, I'll do it real quick. So www.amazon.com. And what I'll do is I'll actually take this information and I'll paste it into a slide for you to see. I'll share this information with you. Try to make this as big as I can so you can see it. And then I'll share this slide in 1 second. Let's see how big I can make these slides. So in this particular environment, I did an NS lookup from my system right now. You can see that my DNS servers are 8.8.8.8, which are Google's DNS servers. You can see I received an answer for Amazon.com. And this ugly thing over here, that's actually the location of the Cloud Front distribution. See how ugly this thing is? I mean, seriously, who's going to remember this? So the point of this is when you've got something ugly like this, what you're going to do is you're going to create a CNAME record to map Amazon.com to that ugly thing. And then all your users have to think about is Amazon.com. So kind of keep that in the back of your mind. It's not going to be any big deal. So we talked about the distribution. Now let's talk about the origin. When you set up CloudFront, you have to set up the origin. What's the origin? It's where your stuff or your content's coming from. So if your things are stored like you've got videos or photos in an S3 bucket, that's your origin. If you've got a virtual machine, for example, and you've got an EC2 instance, that's your origin. Or it could be the load balancer that front ends the virtual machines of your website. And the origin is going to point to the DNS name of this location. So let's talk about the cache control. Whenever you store information in a cache, it's going to be there for a period of time. And let's talk about caching. So the longer the information is stored in the cache, let's say, for example, I've got static information and it's a photo of my beautiful little Cindy the cat. She's real cute. If you want to see Cindy the cat photos later, I'm happy to share them. But if it's a photo of Cindy the cat and all my website is going to do is share Cindy the cat, and I were to set the TTL to a month, for a month, the photos of Cindy the cat are going to sit in the remote locations after they were requested. And for 1 month, nobody's going to have to, my web servers are going to do nothing. But what happens if each day or every few hours I post a new photo of Cindy the cat on this website? Well, no one will see it or know it because the information will be cached. So think about it this way. The longer the information is on the cache, the less work your servers do. But the less frequently people will see your new website. So you can modify this by setting the TTL. And there are any of you that have ever worked with caches in the past, you may notice the memory in the cache gets corrupted, and occasionally you need to clear it out by clearing the cache, and you can do that with a CLI command. Just keep that in the back of your mind. Now, the default cache is going to be for 24 hours. And what this means is the information won't be refreshed for 24 hours. But you can tune this any way you need to based upon your application. So how do you get this set up? We're going to take our web servers and we're going to put our content on them. Then we'll create a CloudFront distribution. AWS will assign that ugly looking name that I just showed you. And then we can either accept that ugly looking name for our content delivery network, or we can create a CNAME record to map something that's user friendly to it. And then AWS will provision the edge and configure the edge locations. So as you can see, architecturally, it's going to look like this. We've got our giant area, which is a region. Inside of that region, we've got our availability zones, which are otherwise known as data centers. And then we've got our edge locations. And you can also see in this particular example, we've got our users. And again, I'm going to work through this user flow with you one more time. Each one of these locations is different. So here we've got a user over here. They want to go to www.gocloudcareers.com. This user hits the local edge location. It doesn't exist at the local edge location because nobody's requested it that day. It goes to the regional cache. The regional cache doesn't have it. It's sent to the origin. Now, the message is sent back to this user. Now, the next user in that same edge location requests the information for the same thing. Request hits the edge location. The edge location sends the information back, and the user is happy. But let's say the first location is Miami, and the second location is New York. The user over here and now in New York wants to get the information that's not going to be cached on their edge location. So it's going to have to be sent to their edge location. That's going to go to the source, and then it will be sent back. And then until that cache expires, everybody on, say, this New York location over here will receive it. So typical content delivery network things, and this is going to work this way on everybody's content delivery network. It doesn't matter. So let's talk about a few more things. So let's talk about private content. Typically speaking, when you think about a website and a content delivery network, it's for the rest of the world. But what if you don't want to use it for the rest of the world? What if you want to use it for paid website subscribers or a private application? Well, there are really three ways to, there are a few ways that you do this. What you're going to do is you're going to set up an origin access identity in CloudFront, and you're going to restrict access to, say, that S3 bucket to certain individuals. We can also use signed URLs, and we can also use signed cookies. So let's talk about pre-signed URLs. There are times where you want to actually share information with someone, maybe out of an object storage bucket, and you can sign the information with your identity and access management information. And how you sign that information will actually determine how you sign that information will determine how valid it is. So here's your basic methods of pre-signing a URL. You can sign it with your IAM instant profile, and that's going to be good for upwards of 6 hours. You can sign it by using the security token service, which is going to be much more dynamic and more secure because the tokens are constantly changing, and that's why it's good for 36 hours. You can sign it with an IAM user account, and it's going to be good for upwards of 7 days, or you can sign it with a temporary token, which will be good until it expires. So a little more about CloudFront. Any content delivery network can really improve your website's performance because your content's cached. And the AWS CloudFront Content Delivery Network has got a fairly good global reach. When we made this training, there were 217 points of presence or locations where you could access CloudFront throughout the world, pretty much every major city. And the other thing to remember is it's a private network. So normally speaking, when you go to the internet, you get routed all the way through the internet. And that's okay, but internet bandwidth is not guaranteed. With a content delivery network, once you jump on the content delivery network, you are on that content delivery network as opposed to the public internet. And by doing so, you may get better performance because the provider can sort of come up with certain guarantees of their own systems, but not other people's systems. So you get some routing and efficiency. And CloudFront will maintain persistent connections, which means it's going to maintain connections with the stores. So there's no need to start a new session with the web server for every possible request. So it's going to promote some scalability. Now, CloudFront can easily integrate with your web application firewalls and your AWS Shield for DDoS. Look, if you're going to protect your web application, there's a time and a place for a WAF, but please understand that next generation firewalls and those firewalls with the enterprise-grade features and functionality from the security providers like Palo Alto or Cisco or Fortinet probably offer you some greater protection and greater enterprise features over a standard AWS WAF. But it's an AWS certification, so you can secure your CloudFront with WAF and Shield, and maybe use AWS WAF with some other more industrial tools. Or you're going to be multi-cloud and you're going to use more industrial tools for everything, and that way you can run similar security policies. And remember that CloudFront, like any other content delivery network, can really help prevent DDoS attacks. And it's going to do so by distributing your requests through multiple points of presence and only forward legitimate requests to the server that aren't already in the cache. And CloudFront can provide encryption in transit, which is great. It can enforce your SSL/TLS protocols. CloudFront will integrate into the AWS Certificate Manager, and CloudFront will support server name identification. Now, at this point, we'll come back. I'll come on screen. If there's any short questions, we can answer them. And then another member of my team is going to start talking about some really cool things in the world. Question from Jay Waynet. How does the cloud provider know if the request is static or dynamic based upon the information you shared with the load balancer? How does it know where the source is that you configured it? So, it's going to have a location where the information is. So either one of you want to touch that, but to me, it's where you're going to configure it. Benedict or Mo, do you have an answer there?
Not really.
Okay.
Yeah.
Yeah, I'm not understanding the question, honestly.
I didn't either. So maybe if you rephrase the question, we can help answer that. From Emmanuel, what is the difference between CloudFront and the edge location? CloudFront is the content delivery network. The edge location is really a building where the caching servers are stored for the content delivery network, and also a lot of your internet providers are there. So it's something that's going to be called the point of presence, Emmanuel. And what is a point of presence? A point of presence is a building where basically your internet service providers have all their wide area connections in. So let's think of the world's largest internet service providers: Telefonica in Spain, Vodafone, Orange, NTT, AT&T, Verizon, CenturyLink. Etisalat in Dubai is a fairly large one, and there's a few others, but you said that are big. So here's the thing: the way internet routing works, Emmanuel, is if I want to go to a website, if I'm on AT&T and the provider's website is hosted on Verizon, I have to take my AT&T network and it has to connect to a Verizon router somewhere, and then it's going to get on the Verizon network and be taken to wherever the information is. Because a point of presence has every one of these providers go in there, and they put these big wide area connections, and they're all in the same building. To connect them, it's very simple. It's just a switch-to-switch connection, or a router-to-router, layer 3 switch to layer 3 switch, and they are already there. So what happens is Amazon has got these big giant buildings, and they're filled with internet service provider connections, and they fill in with their caching servers, and you can literally jump on off of one of these ISPs and directly onto the content delivery network. So edge location is the building where the CloudFront content delivery network is stored.
What is the purpose of assigned URL in a use case? Well, in the context of AWS, usually assigned URL, you get more control over who accesses that URL. For example, if you have some content that only specific people have access to, you can have that that URL basically, for example, expire after a certain time, or only certain users can access that URL. So you get more, let's say, more control over who can access your content with assigned URL.
So I wanted to come in here. I think Jeremy helped us out here with the original question from Jab WeNet. So Jab WeNet was originally asking, how does the cloud provider know if the request is static or dynamic based on the diagram that you shared? So the diagram that you shared actually showed the content.
Yes.
So the request, so Jeremy added this. He said the request isn't static or dynamic, but the content. So so back to Jab's question, it's not the request that's static or dynamic, it's the content that's static or dynamic.
Yeah, and I think we didn't understand the question, and that's a good point, because if it's going to look for, say, a video of a cat doing flips, it's going to point to something that's probably .mov or .mp4, which is going to be sitting in the object storage where the hyperlink is going to be. If it's looking to run a script, it's going to be on the server where the script is. But yeah, Jeremy, I thank you for translating that. I think that's what he meant. And if it's not, just please let us know. Any others? All right. So if there are no, see if you have any other questions. And if not, I think we're going to get to Mo. I think you're up next.
Yeah.
All right. So if you just joined us, remember to download those AWS labs because there's about 2 full days worth. And otherwise, Mo, over to you.
Okay.
If you could bring in the cat, that would be great.
Right. He's just moving all over the place, just playing. He doesn't like to be held. So, usually he just play around. Actually, I see him right there, but he wouldn't come over. Okay, so we're going to start with geo restrictions, right? And geo restriction or geographical restriction, right? Sometimes called geo blocking. It's a feature of content delivery network. Okay, so as we know with AWS content delivery network solution, which is called Cloud Front, right? You get to use AWS global infrastructure, right? Sending your traffic to the nearest edge location in order to use AWS reverse proxies, right? Reverse proxy is just a word for a server that establishes the sessions on your behalf, right? So with geo restrictions, what we're trying to do here is using those basically restricting access to those proxy servers, right? Or the content delivery network solution. And so what you do is AWS has a database of all the IPs mapped to a geographical location, right? For example, those IPs are, this pool of IPs of range is for North Africa, and this range is for, and even as specific as to certain countries, right? This IP is for Egypt, and this IP is for Libya, and this IP is for Morocco, and so on and so forth. And so with geo restriction, you're able to say, I would, for example, whitelist only certain countries or geographical locations and say only those countries can access my content. For example, let's say it's a government website and they only want people to access their content from within that country, right? So that's one thing they can do, right? Or maybe it's a content that's only meant for European countries and they can make that content only accessible from those countries within that region, right? And according to AWS, the database that they maintain is 99.8% accurate, right? So the accuracy of the IPs mapped for different countries or geographical location. And this is a visual representation. If I share my slide, if you look at this diagram, you see to the left, we're not using a content delivery network. We have a user from Egypt accessing content in France. Now, the server in France, they can have their own logic to say, to permit and deny IPs based on, if they can maintain their own database and they can deny IPs based on geographical location, right? And it is possible. But the benefit of using a solution like, if you're already using content delivery network, right, you get to deny those users access. For example, let's say this content should only be accessed within Europe, right? Then you can just whitelist the European countries and then just deny access outside of Europe, right? And the benefit here is that since you're using a content delivery network,
your server or your data center doesn't have to process information from locations that shouldn't be allowed to begin with, right? So with using content delivery network, you already have that added benefit of only processing requests that are meaningful, right? For example, your content delivery network can scrape that traffic for you. But also, if you want to restrict access to certain countries, and then you can either whitelist or blacklist those countries, and the load on your server will be much, much less, right? You don't have to process information that is not intended to access your content. Now, with content delivery network, we have two types of content delivery networks, right? You have simple geo restriction, right? Or a standard, apologies, let me go back. So you have two ways to do this, right? You can do geo restriction as a whitelist or as a blacklist, right? And it's common sense if you think about it, right? When you do whitelist, that means you only whitelist specific countries if it's a short list of countries, and then everything else is implicitly denied, right? Or you can do the other way around, right? You can blacklist only certain countries and then just allow all other countries. And again, AWS, they handle that database for you. They have a database of IPs, and it's 99.8% accurate according to AWS. Okay. When you deny access to your website, right? By default, the user will see for example, if it's a website and you type that website and content delivery network blocks you, the typical response you get is a 403 status code, which says forbidden, right? But you can change that default behavior, right? For example, if you want to give them a response that says content not found, or maybe deliver the denied user a web page that has a message that says, the content, you're not allowed to access that content, right? And so on. Or maybe you want to redirect them. And so, but the default is that, you just denied, you get an error 403, status code 403. Now, if you can integrate content delivery, AWS content delivery network with third-party solutions, that would allow you to permit access only to certain files or deny access to certain files. Let's say, for example, you have an S3 bucket, and instead of just allowing full access to the S3 bucket, right? Let's say the same example, we're talking about Egypt and France. You want to allow Egypt access to the server, but only to specific file paths and not to everything else. So this is not available within AWS, but AWS does allow you to integrate their content delivery network solution with other services that have that level of restriction or that level of control over who can access your content, or what part of your content do they have access to, right? So what's the benefit of using geo restriction or geo blocking? Well, the first thing is legal compliance, right? Sometimes you have laws that prohibit you from sharing content with certain countries, or maybe prohibit you from sharing content from outside of that country, right? What if you want to restrict content or deliver certain content only to a specific city or a zip code, right? That's also possible, but it's possible by using third-party solutions and integrating those third-party solutions with AWS. But as of now, AWS solution only allows you to block or restrict access to certain countries. Now, the second benefit here is a security enhancement. Since the content is only since you can block content from certain countries, maybe countries of non-interest, right? Or if there's a certain country that you get a lot of DDoS attacks from, then you can just block access from that country, right? And of course, gives you more control over your content, so you can deliver the content only to specific regions, right? Okay, let's move on. So this is what geo-restriction is, or geo-blocking is. It's a feature. It's a content delivery network feature, right? But it's not activated by default. You have to activate it and set it up to allow or restrict access to or from specific countries. Okay. Global Accelerator. What's AWS Global Accelerator? So an AWS Global Accelerator is a service that gives you an optimal, or gives your customers an optimal experience, regardless of their geographical location. So what AWS has a large infrastructure, right? It's a large global infrastructure, right? And they have those internal pathways that allow them to circumvent the public internet and not have to use the public internet, right? And they have over 100, I think about 110 points of presence, right? Which what we call edge locations, right? So they have over 100 edge locations, about 110. And so if you use Global Accelerator uses or takes advantage of those points of presence so that you can allow your clients to access your content as fast as possible. And what I mean by that is, what you're doing is what sometimes is called, for at least in the realm of connectivity providers, what they call mid-mile optimization, right? Because the first mile is the client, the last mile is the website, the mid-mile is everything in between, right? So you want to limit the time the client has to access the public internet before they reach your server, right? And so if the client only has to traverse, let's say, 3 nodes before reaching a point of presence, then that point of presence has a reliable, since once they hit that edge location of point of presence, they're using AWS internal infrastructure, right? You know that you have a reliable and fast customer experience from that point of presence moving forward, right? So that's the benefit of using those edge locations, right? So Global Accelerator, using those edge locations and using AWS internal infrastructure, what they do is they advertise when you want to use global accelerators. What AWS allows you to do is advertise 2 public IPs, right? And those 2 public IPs will be advertised from each edge location, right? So it's basically Anycast, right? IP Anycast. If you know anything about Anycast, it just means that what you're doing is you're advertising the same IP everywhere. For example, if you know Google's DNS address 8888, right? That's Anycast, because it's the same IP advertised from multiple locations, and you just by byproduct of the public internet, byproduct of routing, BGP, you will be able to access the closest server possible that hosts that 888 IP address, right? That's Anycast. And so by using Anycast, AWS allow you to advertise 2 public IPs, and those public IPs are advertised from all of the points of presence, the 100-something point of presence. And so the client will reach the closest node or the closest point of presence, topologically speaking. And the reason why I say topologically and not geographically is Sometimes, let's just take a simple example. Let's say we have Libya and Egypt, right? Libya and Egypt are right next to each other, right? And if I'm running a highly congested cable between Libya and Egypt, and it's a low speed, then even though I'm right next to Egypt, it might make more sense to go through, and again, this is not a practical scenario, but just as an example, it might make more sense to go through Italy and down to Egypt if I have a much higher bandwidth or a much higher speed through Italy, right? So even though Egypt is geographically closer directly, it might be topologically speaking, it might be faster to go through Italy and down, right? So this is why we say, from the network's perspective, right? Topologically speaking, which location is closest, right? Okay. So there are two types of accelerators, right? Or acceleration. So there's a standard acceleration, and then there is the custom acceleration, or the custom routing acceleration, right? So the standard acceleration allows your application to be available and work well for users globally, right? So it does the job, but it just gives you the ability for your clients to reach your content in the fastest way possible, right? So basically, you advertise those same IPs everywhere, right? And then they're advertised through BGP's global routing table, right? And then your edge device will send your traffic to the closest edge location topologically, right? And so with the standard acceleration, that's the benefit that you're getting, right? You reach the point of presence, and then from that point of presence, you get to send your you get to deliver the content through AWS private network. Now with custom routing, you get to do a little bit more, or you get a little bit more control over where to send your client's traffic, right? And here's an example, right? Let's say you're using global accelerators, right? But your servers are not only available in one region, they're available in different regions, right? So let's say you have your content in one of AWS Europe regions, more content in the Americas region, and some content in the Asia Pacific region, right? And so with custom routing accelerator or custom accelerators, you can say, I only want to send my content if my content arrives from or lands at this point of presence. I want to send it to the Europe region. I don't want to send it to the Americas region. And this can be really critical for some type of applications, right? And a very simple example, if you've ever played online games, right? You know that when you play for a certain server, you subscribe for that server, right? All your progress, all your whatever character you're working on, all that progress is in one server, right? So it doesn't make sense to be redirected once to Europe server and then tomorrow to APAC server, right? Because you have no progress in the APAC server, right? Plus you have the latency issue. So let's say if you're in Egypt, it makes more sense to be in the EMEA server than to be in the APAC or America server, right? And so custom routing accelerators will allow you to do is map each region to a specific port number, right? Let's say your application is using HTTPS, but it's using a certain port number, let's say 4343, right? And then you can map 4343 to the EMEA region, right? So if a client in the actual application in the game, if they choose the EMEA server, then when they send the traffic, with a port 4343, and then from the global accelerator, I can map 4343 to the EMEA region, right? And let's say 4545 to APAC region, and so on and so forth. So it gives you that kind of control, right, with the custom routing accelerator. And of course, when you deliver content, you need to deliver your content to something, right? As we said, our servers. So those targets, or what we call them are resources, right? They can be EC2 instances, they can be load balancers, whether it's application or network load balancer, and so on and so forth. Okay. So why would you use global accelerators, right? Well, number one is you get better performance, right? So instead of sending your traffic to the server using the public internet all the way, you get to use AWS global infrastructure to send the traffic to the nearest location possible, right? So you get the benefit of having a more optimal performance, because you're using mid-mile optimization, really, right? You're reducing the time that you have to traverse the public internet, right? So you get mid-mile optimization. The second thing is you get more flexibility control over where you send your customer traffic, right? So you can optimize it based on their geographical location and send your traffic to a certain location. And then the third thing, and I think it's a big reason why you might want to use global accelerators, and I touched on it initially, which is Anycast load balancing, right? We said you're doing Anycast, and with Anycast load balancing, right, because some applications don't handle or don't support using DNS, right? They don't support using DNS-based load balancing. And so using Anycast is an alternative to still, have load balancing without having to support DNS-based load balancing, right? Okay, so that's global accelerators. We touched on geo restriction, which is part of content delivery network. And now we touched on global accelerators, a different type of global accelerators. Now we'll move on to connection draining, right? So connection draining is part of elastic load balancers, right? It's a feature of elastic load balancers. So basically, connection draining allows you to gracefully shut down an AWS instance or a resource, right, without interrupting existing client workloads or traffic, right? So think of it this way, right? You have an elastic load balancer, right? And based on demand, you had 2 EC2 instances, and based on demand, you had to scale out from 2 instances into 6 instances to support the workload, right? So after peak hours, the demand went down, let's say, by 50%, and you no longer need 6 EC2 instances. Now you only need 3. Now the problem here is because your load balancer is load balancing the customer traffic between those instances, if one of your customers is still using one of those servers that we are about to shut off or scale down, right? That can cause an issue, right? Because maybe it's an e-commerce website and they still have an active shopping cart, and if you just shut down that website, they might lose that, right? Or maybe they're downloading a file, right? And they're gonna lose that progress. So you don't want to immediately just instantly shut off that instance, right? You want to have a little bit of a grace period, right, before shutting off that instance. So connection draining basically starts a timer, right, before shutting off that instance. And then it will direct all new traffic to the instances that will remain, and it will not send any traffic to the instances that will be shut off, right? So all the new traffic will go to the existing instances that will stay, but then no traffic will be sent to the instances that will be shut off after, let's say, 6 minutes, right? And then during those 6 minutes, your existing clients will have enough time to download or finish whatever work they're doing, but all their future sessions will be redirected to the other servers, right? And then after that grace time or grace period expires, then you will shut off those instances, and hopefully you've reduced the amount of disruption, right? So it allows you to have a little bit of a grace period so that your user experience will, that will enhance your user experience slightly. Okay. Okay, let's look at this slide. Look at this diagram. As you can see here in this diagram, let's assume that we have 2 users, right? And you have 3 instances, right? And user 1 sends traffic to EC2 instance 1. User 2 sends the traffic, and the load balancer sends the traffic to EC2 instance 3, right? Let's say after some time, the traffic load has dropped by 30%, and we no longer need instance 3, so we need to shut off instance 3, right? If we shut it off immediately, then user 2 loses access, or disrupts user 2's existing session, right? Let's say user 3 is downloading a file, right? Now, with connection draining, your elastic load balancer, before scaling in, I guess you can say scaling in or shutting off instance 3, it will start a grace timer, let's say of 5 minutes. And during those 5 minutes, all the new sessions, say we have a new session, all those new sessions will be sent or load balanced between instance 1 and instance 2. So no new sessions will be sent to instance 3, right? Only the existing clients will be sent, the existing clients that already made a connection with instance 3 will be sent to instance 3. So it's user 2 in this example. So after the 5 minutes expire, this instance will be shut off. And then all future traffic from user 2 will be either sent to instance 1 or to instance 2. So that's basically what connection draining is, right? It can be very beneficial to maintain or to enhance the user experience, right? And not having disruption. So why would you use connection draining, right? Well, as we just said, right, you get a seamless user experience or a better user experience, right? So you avoid an abrupt termination or shutting off because of shutting off an EC2 instance, right? Or whatever resource. You get more reliable application performance, right? And then you reduce the risk of data loss, right? As mentioned in the example, we said because your user is downloading files, right? If you just shut off that instance, all that work, all that progress has been lost. But since you have a grace period, right, the user will have some time to finish the progress, to hopefully finish the file transfer or whatever, right? Okay. Let's move on to the next subject. So the next subject is TCP, or actually let's take some questions first, since it's going to be next topic is a little different. Okay, do we have any questions?
Welcome back, everyone. Do we have any questions at this point? What is the purpose of signed URLs? So I can give you access to information via one of two ways. I can create an identity and access management entity to you, meaning, say, Benedict O, and then I can determine what Benedict O's rights are. But what if I just wanted to send you a video and I didn't want to create an account for you and I just wanted to sign one thing with my URL and give you complete access to it? That's typically why we use signed URLs. Now, Tundi, you actually asked a very good question. How do you ensure geo-restriction is not being bypassed by using VPNs? Now, Tundi, I can tell you a lot of people actually bypass organizations and governments, entities of them. For example, there are countries in the Middle East, wonderful countries that I've worked in, that certain types of content are deemed illicit or inappropriate. And in these typical organizations, they typically run everything through a proxy server. And a proxy server has a blacklist of sites that can't be seen. And by using the local internet, you get sent to the proxy server. The proxy server says, no, you can't see this. So there are people that would actually create a VPN and go back to, say, the US or the UK. And by doing so, they are no longer have an IP address because they've tunneled through the internet of exactly what you're doing. So I'll see, is there any way that you guys can think of to kind of block that? Unless you were to block IPsec and block TLS.
Yeah, pretty much you have to block IPsec, and that's actually something some countries in the Middle East do. I know China does that too. I know Egypt, for a fact, does that, right? I worked on a project where IPsec was blocked, and we had to basically, through the service provider Orange, we literally had to like sign a form and submit to say we wanted those IPs, VPN to be allowed from here to our data center in the US, to our data center in Europe. So we had to actually, submit a request, and it took about a week just to get it approved. So yeah, I mean, unless you're gonna block VPN, there's really nothing you can do, right?
Can you draw out the global accelerator with two public IPs to explain?
Yeah, sure.
Now, we did draw out an Anycast thing yesterday, which will help. But Mo, you want to do that, or would you like me to draw Anycast?
No, that's fine. I'll draw it out.
Okay, great.
Give me 1 second. So let's do an oversimplification here. And let's say we have 3 points of presence, right? Or edge locations. So those are Those edge are buildings or data centers or buildings that are owned by AWS, right? So let's say one is in APAC, one is in EMEA, and is in Americas, right? And so between those points of presence, right, you have very fast channels that connect the whole AWS global infrastructure, right? And this is private. Doesn't touch the public internet, right? And you have, of course, you have connections to all of the AWS data centers. Let's say you have content in this data center here and in this data center here, right? Content in A and B. Okay. So you as a user, right? You as a user, let's say you exist here, somewhere behind APAC, right? Let's use a different color. Right. And you're using the public internet, right, to access this content, right? So using the public internet, you should be able to access this point. You should be able to access that point, right? You can also access this, right? AWS data center, right? It's all available on the public internet. Now, typically without a global accelerator, right, you would just advertise your content, right? The IP address of your content. AWS takes care of that for you, right? They already advertise the content, but those are different IPs based on the location. Now, with content delivery network, what you do is you get access to two public IPs, right? Those two public IPs, if you're using only IPv4, so you get two public IPs. If you're using IPv6 as well, then that means two IPv4, two IPv6, so that's 6 public IPs. So you get two public IPs that you advertise out of each point of presence. We said we have 3 points of presence, right? So you're no longer, this IP is not advertised from here. No, it's advertised from the points of presence, which means it's advertised from here and from here. No, not really. It's advertised to the public internet from here, and from here, right? So it's the same IP, right? So in your routing table over here, this is your office, right? You're a customer. Your routing table, you might see, if you have the full BGP routing table, you might see all of them, right? You might see this public IP that's coming from here, and from here, right? You'll see the 3 of them. But one of them should be have a better reachability, right? Based on BGP's attributes, right? And we're not going into BGP's different attributes, but most likely it's going to be based on the autonomous system path, right? Basically, how many different autonomous systems or how many organizations you pass through to get to from point A to point B. So let's say in this example, this one is the fastest, right? The one through APAC. And so that's the one that you will use because you're coming from here. That's the one you will use to reach that IP, right? And so you will send the traffic through internet to the nearest point possible, which is the point of presence or the edge location, right? And this is what we call it mid-mile optimization, right? So now you reach this point of presence, and then from this point of presence, you'll use AWS Global Infrastructure, not using the public internet, but AWS Global Infrastructure, and send the traffic over here, right? Of course, if you have the same content on both regions, then you get the option to send it to the closer location and send it over here, right? This is also things that you have control over, right? Do you want to send it to the data center in this region or the data center of this region, right? Let's say if we have another customer, but this customer is behind Americas, then as a byproduct of BGP, the public internet, you'll reach the nearest, the closest topologically available, the closest point of presence topologically speaking, and so the traffic will hit this edge location, right? So you traverse the public internet and you reach this location, and then based on the logic that you have within the global accelerators, you can either send it to this data center or this data center, right? AWS data centers, right? So that's basically the idea behind global accelerators. Now, we said there's custom routing policies or custom routing setups or policies that you can use to send specific users to or from specific regions to certain data centers, right? And we give you an example, like having you playing online games, right? And let's say you play an online game, and you, since you're from Americas, you subscribe for the Americas server, right? From the Americas game server, and so the application maps each server to a port number, and so regardless where you come from, regardless what location, if you choose the Americas server, and then you access you hit the point of presence with that special port number, and we gave an example, we said 4343, and so we, in the global accelerator logic, we map 4343 to the Americas server, and let's say 4545 to server, and so on and so forth. So with custom routing policies, you can map users to certain servers in a certain region based on the port number that they come from, right? So that's basically what global accelerators are.
Samsung, as far as the difference between direct connect locations and edge locations, which are both buildings, absolutely. What are the fundamental infrastructure differences between them, as both have POPs, vendor sus ISPs? So Samsung, two things. One is they're not going to allow us into these buildings for security purposes, but knowing what they do, I can explain it. Now, they're going to be very, very similar. So here's your traditional plane of presence. It's a building. Every internet service provider has their high-speed optical links that goes into that building, and they all have their own routers there, and then they just basically run cables between each other's routers through a switch, typically speaking. So there's that. That's your typical internet point of presence. And what's the point? Well, if I'm an internet service provider, let's say I'm AT&T, and I need links, long-distance links to NTT in Japan, and I need long-distance links to Telefonica in Spain, and they need long-distance links to BT in England, and I need long-distance, I'm going to pay a lot of money for these long-distance links. Now, if I just decided to get one long-distance link to England, and while I had that long-distance link to England, all the other internet service providers in the same building, I could create a long-distance link to England, a long-distance link to California, a long-distance link to Asia, and by doing so, each link could connect me to every internet service provider. That's your typical internet point of presence. What's a direct connection location? Well, it's a place where all your wide area network providers go into the same building and you connect to the AWS infrastructure. So it's very similar to an internet point of presence, but instead of every internet service provider connecting to every other internet service provider, every wide area network service provider connects to the AWS backbone. Same concept, slightly different use case. So now we're going to deal with an edge location. We have to have every single one of our internet service providers in there if it's going to be meaningful, for real. So we're going to have all those internet service connections coming in, just like we would in any other internet point of presence. But instead of connecting all the internet service providers to the internet service providers, we're connecting them to CloudFront, And then we have a whole bunch of servers that have a high memory that are doing caching and have lots of memory. That's your typical infrastructure differences, but they're all going to look and feel pretty darn similar, because any data center, any network that's full of network stuff, whether it's a cloud provider or a traditional internet providers, isn't going to be that much different. It's pretty much the same thing. You know, all this stuff kind of reminds me, I think it was The Who. They had a song that says, "Meet the new boss, same as the old boss." Pretty much what we're dealing with here. Now, William, this is actually a pretty important question you asked here. Is there any document that is possible to verify the latency between regions using Global Accelerator? Here's why there can never be a document for this, William. You don't own the network. It is a shared network. And as those routers and switches, you know, have to heal if a cable gets cut, the latency and changes will be different. If there's congestion on the network, it will change it. So you're never going to be able to know exactly what you're going to get on one of these providers' networks. It's a little different if it's your own network and you own all the wide area network links, and you can run a quality of service policy to guarantee it. That's what you have to remember with the cloud. It is somebody else's stuff. So we're going to lose that flexibility and we're going to lose that control. So what you're going to have to do is test. And we're not talking about going to some internet test and using a consumer grade testing website. You're going to have your QA engineers come up with scripts and start sending certain types of traffic and measure at different points of the day, at different weeks, at different months, and your mileage may vary. And then you'll get an average or an aggregate. I mean, don't get me wrong. Whenever you look at a vendor, they're always going to have their numbers. For example, I can point you to firewalls that say they can do 10 gig of stateful throughput. And then you turn on a bunch of features and they literally can't go beyond 100 megs, even though that's 1/100th of what they're able to do. So you're always going to have to test your workflows, but that's how you're going to do it. You're going to test it. These are good questions coming in today.
After the connection, the user still has something in cart. What happens to the user? Give me a second. Okay. To the user cart after the draining, does the user see the draining effect? Well, if the timer expires, right, and then they still haven't finished, and that information is stateful, exists on that server, then they just lost that information. But that depends on the application, right? Is that information shared between different servers, right? And the server can continue the progress on a different device. So it depends, right? But really the biggest problem here would be if they're trying to download some content, and that content exists on that server, right? And that might be that's a bigger issue, right? So you're really buying your customer a little bit more time, while you're scaling down your applications.
All right. Well, I think we're ready to go back to the content. Are we ready to go to Lambda, or did you have anything left over there, Mo?
I have one topic.
I thought so.
Yeah.
I thought you had congestion control, but I wasn't sure. So before we go back to the content, if you're here and you're awake and you know what day it is, please give us a hashtag AWS Advanced Networking so we know that you're here and you're awake. While we're at it, if you just joined us and maybe you've missed the first couple of days, don't worry. You can watch the first few days on our YouTube channel. And if you just joined us, make sure to get your free AWS Advanced Networking Lab demos. You're going to sign up for them. We've got 2 additional full days worth of training, both some things on AWS and also things in our data center, so you can truly understand how the technology works under the hood. I want you to get it. It's all free. So please download them. Mo, back to you to talk about congestion control.
All right. So congestion control, right? What's congestion control, right? As we know, TCP packets, right, or TCP flows, as we know, the protocol is more of a reliable protocol, right? You send traffic, and you can know when you send traffic, you will know that the traffic has been delivered, because each batch of packets that you send, you'll get an acknowledgement for your traffic, right? And of course, because when you first establish a TCP session, right, there has to be some sort of a handshake, right, which is, we all know the three-way handshake, which is the TCP sync or synchronization, and then your server reply to you with a synchronization / acknowledgement, right? And then you would send, and then the client would send an acknowledgement to the server's synchronization, right? So that's the three-way handshake, right? Once that session is established, both the client and the server will acknowledge each other's packets, right? So you request a packet, server will send you traffic, and then you will acknowledge that you received, let's say, packets from sequence 100 to 120, right? So since traffic is sent over the internet, and we're not really guaranteed a certain bandwidth, right? From point A to point B over the public internet, right? It's really, really difficult to gauge the rate at which you should be sending traffic, right? It's not very straightforward, right? So TCP tends to be greedy in a way that it sends traffic, right? TCP tries to send as much traffic as it can, right? And if we just don't limit how much traffic TCP can send, then we might just end up, over exhausting our connection, and then just traffic being dropped, right? Which is not very efficient. So TCP uses a feature that we call TCP congestion control, right? And basically what congestion control is a way for TCP to gauge how much it can send. So we'll work very aggressively, try to send as much traffic as it can, and then once it starts getting dropped, it will drop down, but then it will start less aggressively, knowing that if it go to 50% of what it did before, there won't be any traffic drops, right? But it will do that same idea where it will go up slowly, instead of going aggressively initially, and then we'll go slowly up to the point where it hits a comfortable traffic rate where it knows that it's not going to get dropped, and it just continues on that path. And then we'll slowly keep going up until it gets dropped again and goes down. So you still kind of have that yo-yo effect, or going up and down, but at least now it's more regulated, and the rate between the top or the peak and the bottom is not big, and so you have more of a smooth traffic flow, right? So in this diagram, share my screen, I'll show you this diagram. So as you can see here in this diagram, we have the TCP congestion control mechanism, right? There is two phases of TCP congestion control. We have the slow start and the congestions avoidance, okay? So you start with, you start sending applications. Your application starts, your TCP application starts sending traffic, right? You're just sending packets, right? You start with the maximum segment size of 1, okay? Which means you just send 1 packet. And then once you get an acknowledgement, you double that. So now it's 2. And then you double that. Now it's 4. And then you double that, that's 8, and then 16, and then 32, and 64, 128, and so you can see how it goes up very exponentially, right? It goes up really fast until you hit a point where your traffic gets dropped, right? That's when your traffic gets dropped, you start again, but this time, instead of going doubling your traffic each time, now you are working slowly to basically send the traffic by increasing your the number of packets you send by 1 each time, right? So you go up. This time, as you can see, you're going up slower, right? And you're working your way up, because of the first time you pretty much established a threshold where I can't exceed that, right? And so you just continue on that same half of what you peaked at. And then now you're increasing your traffic by 1. So you're working your way up slower, right? Instead of going 1, 2, 4, 8, 16, you're doing 1, 2, 3, 4, 5, right? So each time you get an acknowledgement. So at first time, and what this means is first time you send 1 packet, you get an acknowledgement. Usually it's not 1 packet, but as an example, right? Let's say it's 1 packet, you get an acknowledgement. So you send 2, you get an acknowledgement. And then you send 3, you basically, you won't send more packets until you get an acknowledgement, right? So the window size, what we call your TCP window size, is how many packets you send before waiting for a response, right? You can't just be sending traffic without expecting a response, right? Especially for TCP traffic. And so let's say you send 3 packets and you get an acknowledgement for the 3rd packet, and then you send 6, and so on and so forth, right? So initially you're just doubling, but once your traffic, you reach congestion, your traffic is dropped, and now you can start again and just working your way up slower, right? And as you can see, the traffic now smooths out until you hit a phase where your traffic gets dropped for whatever reason. If there's no traffic drop, and then you'll just continue on that path of working your way up slower, right? And that's what we call a congestion avoidance, right? So the initial phase is the slow start, and then the second phase is the congestion avoidance, where it's less aggressive and more stable, right? So you do a slow start when you ramping up, you're working your way up, right? And TCP always reevaluates, so it doesn't just work based on the initial congestion. It keeps reevaluating the speed that it can actually operate at or send traffic at. So already went through, we said the slow start phase and then the congestion avoidance phase, right? Now there are other, and this is just a feature of TCP. There are other features, at least from the network side, that we use to deal with congestion, right? One of them is what we call, and it's more of a queuing method, right? And without going into too much details, right? There's by default, what you do is when your link is congested on a router, right? If you have an interface and your link gets congested, usually just by default, you just do what we call a tail drop, which means you have a queue because there's a buffer or there's a limit of how much traffic you can send through your cable, right? So or link. So if you get congested, what would usually happen is you start dropping the new traffic, right? That comes in, right? Because you got congested. What you can do is what we call weighted random early discard, and what weighted random early discard is, it will start randomly dropping TCP traffic. And the benefit of doing that is you signal to TCP ahead of time to slow down, right? You wait for TCP to get to a certain threshold, since you as a router can can decide that, right? What the threshold is, and then once that threshold is reached, you start to randomly drop traffic. And when you start randomly drop traffic, and the reason why you randomly drop traffic, because you have potentially thousands of TCP flows, you don't know if you want to randomize the process so that you make sure that you're more fairly dropping traffic from different flows. And so when you start randomly drop traffic, you force the TCP flow to work into the congestion avoidance phase and work in a more consistent phase instead of just having that yo-yo effect of going up and down, right? So that's congestion avoidance or congestion control, which consists of 2 phases: the slow to start phase and a congestion avoidance phase. Okay. we taking questions or are we moving forward? Okay, guess questions.
I'll take it. Yeah, let's take some questions here, and then I'll move a little bit. Are there any questions on congestion avoidance or that weighted red, which Mo was talking about, which is always a fun topic?
Okay, I have a guest. Look who decided to show up.
Oh,
No?
now that needs to go full screen. Yeah, my cat doesn't like when I pick her up either, but they're always
Yeah.
loving and cute little things.
Okay. He doesn't love to be held. He's very nice. He's very friendly. He just doesn't like to be held.
I completely understand that. Well, if there are no questions, I will go get into the content with Lambda Edge.
All right.
Before we do, if you're enjoying this video, please give it a like. It helps signal the algorithm to show it to more people. Subscribe, hit the bell, that kind of thing, so you can see new videos that we're going to create. And we've got some extra special content coming for you at the end of next month, so please make sure you're subscribed. Up and up, good to see you. And yes, I love the cat too. Okay, Chris, I'll go back and I'm going to start talking about Lambda Edge. So Lambda is basically your typical function as a service. Azure has it as a function. Lambda has certain functions. And we would talk about that much more in, say, a solution architect training. But here's the key. It's a serverless function, which means it's a little piece of code that's uploaded. It does its thing. And yes, it does run on a server. It's just the servers are hidden from you. Now, what if you could run some of your Lambda functions at the edge of your network instead of actually having to bring it all the way back to your VPC? That's really what we're talking about with regards to Lambda at Edge. And it's allowing you to run a Lambda function closer to the user. And the way it's going to work is you'll set it up by, you'll upload your code, and then you'd set up, say, any type of HTTP notifications that you want. And the Lambda function would run whenever the code is triggered, and then you pay for things. So that's the thing with these event-driven architectures and these serverless architectures to keep in mind, architecturally speaking. When you don't use them very much, they are very inexpensive to run. I like to view it as kind of transportation. I like to think of a Lambda function as kind of like taking an Uber versus setting up your own virtual machine and running it, kind of like buying your own car. Now, if you live in New York City and you're only going to take 10 trips a month because you're going to walk around, it's probably cheaper to take $10, $20 Uber trips than it would actually be to buy a car and use a car. But what if, for example, you're like me and you live in Florida where everything is 10 to 20 miles away, and I go places, 3 times a day. I go to, say, PT in the morning, and then I potentially take my wife to dinner at night. Now, in that environment, I would realistically speaking, need 10 Uber trips a week or 40 trips a month, and they'd probably be $30 to $40 each Uber trip. And it's cheaper to, say, buy a car and pay a car payment than it would be to use the Uber. So keep that in mind anytime you get involved in serverless. You must know how it's going to be used. And obviously, you can create similar architectures with virtual machines, and then you'll just pay for the virtual machine where here you're paying as you use them. Keep that in mind. Now, when you upload the code, or I should say your developers upload their code, they can upload the code in, say, C#, Go, Java, Node.js, Python. And Lambda functions do enable that event-driven. If this happens, do this in response to this. So remember that Lambda is stateless, meaning it doesn't keep track of what's going on. So if it performs a function, once the function is done, it's completed. And if another function were to have to occur, you're going to have to set up functions in steps. And there's the ability to do that with something called AWS step functions as a general rule. Think of it this way. AWS Lambda is going to be useful in places where automation can increase the efficiency of your technology, decrease manual intervention. So if you want to process data across multiple systems and you could use Lambda to sequence it, great. I like not that it's Lambda at Edge, but 16% of all cloud attacks, the last time I checked, were actually misconfigured S3 buckets on AWS. And you could have someone that puts in information on an S3 bucket, which is just object storage, and they set the permissions wrong, and the corporation could have a Lambda function that as soon as it sees that, changes their permissions. You could use Lambda potentially to patch operating systems. So Lambda can be run in response to an event. Stick a new file in an S3 bucket, Lambda can run. So kind of keep that in the back of your mind. And here would be an example. So let's say how we could use Lambda functions in AWS. And Lambda Edge is just running it closer to the user. Let's say I have a video service. And I'm going to create a video. And the first thing I want to do is upload the video to the object storage. And the next thing I really wanted to do was then have the video transcribed. I can have a Lambda function send it to, say, Amazon transcribe. Maybe I want the video transcoded from what we recorded, say 200 megabit a second, to say an MP4. And I could use an encoder program on AWS to do that. And a Lambda function could send it there. I could even set up another Lambda function to kick off the AWS simple email service to email me that says video has been transcribed and video has been transcoded. And keep that in the back of your mind. This Lambda is just about automating. So now we'll briefly get into a topic I love to talk about, which is called network security. And when we're getting in this, we're talking about the security from the networking perspective, meaning we're not talking about how to create secure code checks, input validation, on the application development side. We're not really getting involved in identity and access management, meaning who are you? What are you allowed to do and keeping track of it? The authentication, authorization, and accounting. We're covering network security and how you can secure your cloud from an AWS perspective on the network. So we first have to think in terms of threat models. And a threat is realistically anything that can harm your system. A threat model is going to be a structured process that's going to evaluate your threats and your vulnerabilities in a system. And it's going to give you suggestions or countermeasures on how you can mitigate them. Now, we have to think about how complex our IT systems are getting. They're becoming more distributed and they're everywhere. So using unstructured approaches to think about our security, probably not the best idea in today's world, especially 98% of organizations are multi-cloud. We've got our data centers, we've got our cloud providers, our users have information on their systems, then they've got mobile phones and mobile devices that also have data. So think about that. And threat models typically work by identifying your IT assets and the types of threat agents that can cause harm to a system. So think about it that way. Some examples of threat models are Stride, POSTA, and CVSS. So why do we use threat models? Because it's going to help an organization make better security decisions and think more rationally. Because when it comes to determining what your security is, some of it is you need to understand what are you protecting, the value of what you're protecting, the risk to the business should the systems be unavailable, the quantifiable risks, for example, like if we lose a certain number of people's information and it costs, say, $150 on average per user, and we lose 150 million people's information, that's a quantifiable risk. Another quantifiable risk is an organization that's got $10 billion, say, of intellectual property. And if it gets compromised or lost, it destroys the business. That's quantifiable risk. But we also have to think in terms of non-quantifiable risks, such as brand damage and things that we should also think about for an organization when we think about threats. But threat models really help organizations to detect problems early and address them proactively. And that's the key. Nothing's perfect. We want to find it and we want to fix it before it actually becomes a security breach. And threat models are going to be useful in evaluating new forms of attacks, because new forms of attacks do occur. It'll help our organizations highlight the assets, the things that we're trying to protect, as well as determine any kind of controls. And it's going to help us with our compliance requirements. So we'll talk a little bit about AWS security, and I want to talk about the couple of things that we really need to talk about. The principle of least privilege. In this, we're going to get involved into multi-account strategies. We'll get involved in different types of things, IDS, IPS systems. So we'll have lots of fun in this section. But let's first talk about who is responsible. Now, whenever you're dealing with a cloud provider, they all have their version of a shared security model. And what is really meant by that? To sum it up, you protect your stuff, and AWS protects their stuff. But let's try to make it a little more specific. AWS will maintain the security of their cloud. Because if their cloud gets hacked and goes down, you go down, or you may go down, or your information will be compromised. And of course, we've seen cloud hacking events where people's information has been compromised. You have no control over that if the cloud provider gets compromised. You have control of your systems, assuming the cloud provider is whole. So you will maintain the security of your VPC. AWS will manage their servers, their routers, their switches, their physical load balancers, their firewalls, and the underlying technology, all those cables between you and your systems that you can't see. But you will be responsible for your authentication, authorization, and accounting systems. The users that you have, what your users are allowed to do, what your systems are allowed to do to each other, which are typically called roles, IAM roles. You will need to patch the operating systems on every virtual machine you have. Now, if you go serverless, you will not need to patch it because AWS will be patching it. But if it's your system, you will need to patch it. You will need to maintain the security of your applications. You will need to maintain the security of your configured options, meaning, do you have the right security groups? Do you have the network ACLs, those types of things? And you will have to maintain the security of your physical devices that are going to connect you to the cloud. I want you to think about this. Let's say you have the perfectly secured cloud, and you've got a direct connection to your campus. And the router that connects to the cloud is in the middle of the lunchroom, and anybody can just plug into it. All your security would be gone. So you need to make sure that your devices that are going to connect to the cloud are in a secure sort of manner. Now, here is the way you can really think about it, here, graphically speaking, this AWS shared security model. You can see that they manage their servers, storage, databases, networking, their regions, edge locations, and availability zones. That's their stuff. Your data, you have to protect. Your operating systems, your firewalls, access control lists, all that stuff, security groups, you have to control that. Your data, well, obviously from the permissions, and ideally you encrypt it too, although most things are encrypted now by default. Your applications, if you deploy insecure applications, you will be hacked, and AWS can't be responsible for that because it's your stuff. And basically any kind of encryption strategies you choose to use or certificates that you're dealing with, you will be responsible for that. Now, I'm going to talk about a concept called the principle of least privilege. It's very similar to a concept called need to know, but principle of least privilege is basically don't give people access to more information that they need to do their job. Because if you do, there's a chance that that information will get out to the wrong people. They will use that information to hurt you. Kind of similar to, if you look in a military context, most soldiers are not walking around with a ton of top secret information because they don't need it to do their job. And when they do need top secret information, they typically have a clearance level, and they're only allowed what they need to know for their job, but not the extra critical things. Well, realistically speaking, that's kind of what we're talking about right now. So give people the least amount of rights to do what they need and nothing else. And if you terminate an employee, get rid of that as fast as possible. So to me, I look at authentication, authorization, accounting, and really what it is authentication is who are you or who do you claim to be? Authorization is what are you allowed to do? And accounting is what you did. So let's say I invited Mo to my house, and I met Mo in Florida recently. I enjoyed spending some time with him. We didn't have enough time, but to go back to my house and for him to meet my wife and my cat over there, well, actually he's met my wife, but let's just say that. When Mo knocked at the door, I might have a camera that would tell me that it looks like Mo. And I'd open the door and I'd say, hey, Mo, that's you. And I would authenticate him. And then I'd welcome him in. Authorization would be allowing Mo to enter any room in the house or use the use the physical therapy center in the house or whatever have you, because that's authorization, what he did. And then accounting, which is the last component of this, is basically saying tracking what someone did. So when we talk about IAM, even though I said we weren't going to talk about it too much, I wanted to cover the basics. So I'll talk very briefly about ways that you can semi-segment your systems. AWS gives you the ability to do what's called a multi-account strategy. And what is this? Typically speaking, everything in an account is yours. And what if something goofy happened in your account? You could potentially damage your entire account. So you may be tempted to basically just buy 4 different accounts or 5 different accounts and keep them separate and just pair or share information between them. You can do that. But the problem is sometimes the more you buy, the bigger of a discount you get. And it might be nice sometimes to get 1 bill versus 5 bills and trying to figure out which department is responsible for which. So what a multi-account strategy is you can create a master account and effectively have multiple sub-accounts underneath them. And AWS calls those sub-accounts organizational units. And what happens is you can create a basically identity and access management policy. But in this case, it's going to be an identity and access management policy across which accounts can talk to each other. And AWS is going to call that a service control policy. And that's going to allow the master organization to define policies that can restrict at the account level what services and actions member account users, groups, and roles can take, including the root users. So it's really just like an IAM policy, but it's an IAM policy to govern the accounts or the sub-accounts, as opposed to a traditional identity and access management policy, which is for the user. So realistically speaking, you've got one company. And by having the company, all you're really dealing with is you're breaking it down into 4 mini companies and using consolidating billing and giving you permission boundaries in between the organizations. Here's another way to look at it. You've got a root account, and each root account has their own organizational units. And they have like various accounts you can have underneath them. Typically speaking, the point of doing this is you've got your isolation between your organizational units, and you have the ability to share necessary information between these units. And you have the ability to reduce the visibility of one workload to another. And why are you doing this? Because if you've got a big problem here, you want to limit the blast radius to here, as opposed to all these other parts of the organization. It's the ability way to compartmentalize data. And it's very similar to the concept of taking a network, breaking it into 4 separate networks, and then running BGP between them. Very similar concepts. Okay, I think we are at the point where we're going to transition to another member of my team, but let's see if anybody has any questions real quick. Samson, is UDP and not greedy like TCP? In other words, why does UDP not have a slow start and congestion avoidance like TCP? Or is there? So actually, Samson, that's going to get into the reliability and the way TCP works. Mo, I'll let you work with this because you were having some fun with congestion avoidance. And if you need any help, I'm always happy to partake in here.
Of course. Yeah, just like what Mike just alluded to, right? TCP, it's up to what your application is built on, right? When you build an application, you need to decide whether this application needs to be built on a reliable protocol like TCP or an unreliable protocol like UDP, right? And so by nature, UDP is not a reliable protocol. And so the whole idea of more reliability and having traffic be sent and acknowledged, that's not part of UDP. So it makes more sense for real-time protocol, for real-time traffic, right? Like voice, for example. For example, if you have a voice traffic, it doesn't make sense to have a congestion avoidance because you need to send that traffic in real time, right? Regardless of the bandwidth needed for that traffic, you need to send it in real time, right? And then you have different codecs that control your the quality of your traffic, but also the size of that traffic, right? And so it's more, UDP doesn't have congestion control, right? So really the congestion control becomes something that you control on the network itself, right? Rather than the application itself, right? And so, or apologies, what I meant is something that's controlled by the network or the application, but not the protocol that's used by the application. So with TCP, you can still control the congestion on the application itself, but the protocol, which is TCP, in reality is the protocol that inherently has congestion control, right? But you can still control TCP on the network side, on the application side as well. So it's really, it's a design decision that was made for UDP because there's some sort of traffic where congestion control makes no sense, right? And getting an acknowledgement makes no sense because you just need to send it from point A to point B in real time. I hope that answers your question.
Yeah, so Samson, I'll add to this a little bit. So let's look at the way TCP is used for and why TCP exists. TCP is used for a reliable connection. So if I want to send Mo something, or I want to send Benedict something, I need to know that Benedict got it. And in order to do that, I have to send it to Benedict and then ask Benedict, did you get it? And he has to say, Mike, I got it. So for that to occur, so the way TCP works and the way it sends its messages is as follows. I want to send Benedict something. So I send Benedict something. He gets it and he says, Mike, I got it. So now I want to speed up. I'm going to send him 2 of some things. And Benedict's going to say, Mike, I got it. So now I'm going to send 4 of something because my goal is to get it to Benedict as fast as possible, right? And Benedict is going to say, I got it. So now I'm going to send 8 to Benedict and he's going to say, I got it. And I'm going to keep going up. And that's why where Mo says it's greedy, because I want to send it there as fast as possible until I don't hear back from Benedict that he got it. And then I'm going to slow down and I'm going to start this process again. And that's kind of where I'm going to find my maximum throughput. Now, we do that because we want it to know. Now, by comparison, UDP is not meant for reliable transport. So let's say I wanted to send cat videos over there to Benedict over there in Canada. And I'm sending him a cat video. And for some reason, for a quarter of a second, the screen froze. And then it went back to the rest of the cat video. Benedict has no problem with that because it's a live video. So for information that does not require reliable transport like live video, we send it via UDP, and UDP has no flow control because it's just packets that get sent along the wire and they just get delivered as they're sent in. And let's talk about why I wouldn't want flow control on video. Imagine if I said I sent Benedict a message that says, I like cats. Which is completely true. Now, what if I said and it came back and I said I like cats, but all Benedict saw was I and then cats, and then I had to retransmit the like after the fact. Well, that wouldn't exactly say I like cats. It would say I cats like. So any kind of real-time, anything that we need in terms of, say, voice or in terms of video is done typically via UDP because we don't want that reliable transport or retransmission. Can you use, you're just curious if you use threat modeling and threat hunting under interchangeable? Not really. So it's going to depend on how academic you're going to get and how geeky you're going to get. But threat modeling is more of evaluating, and threat hunting is more looking for those threats. So modeling is more at a more managerial level. Hunting is you're going to go out there and find them. More vulnerability scanning and seeing where your weaknesses on your systems, code checks, that kind of thing. So is it you coming up, Benedict, on securing application flows?
Yep.
Okay, so give me a hashtag cloud networking, so I know you're awake, and Benedict is going to start talking about securing your application flows. And if you just joined us and you hadn't found out, or signed in and received any of our labs, sign up for them now. They're in the chat box. They're also going to be in the description of this video, and they're completely free.
All right, thanks, Mike. So Mike started the discussion on security in the AWS cloud, and I'm going to continue from where he stopped. So the first item we want to look at today is how to secure the flow of traffic to your applications in the AWS cloud. So these are the recommendations from AWS, right? So it's recommended that you use TLS encryption to encrypt data in motion from the client to your application servers. Encrypting the data keeps it safe from eavesdroppers or anyone who gains unauthorized access to your account. It's also recommended to use security groups to protect your EC2 instances. In this case, it will be the web applications running on virtual machines, right? So that keeps the bad guys out. It is recommended to use a network access list to control access at the subnet level, so you can determine who has access to these applications and what they can do. Of course, identity and access management is key in securing your workloads in the cloud, as it determines who has management access to your applications. And of course, it is recommended that you use a web application firewall to protect your applications from common web application attacks. Then in terms of monitoring, it's recommended that you use the VPC flow logs to monitor traffic that is coming into your applications and leaving as well. Then AWS also has some recommendations about securing inbound traffic to your VPC, right? So it's also recommended to use a firewall, network firewall, at the edge of your VPC to filter traffic that is coming inbound to your network so that it can drop any suspicious traffic and keep your infrastructure safe. The use of a web application firewall at the edge is also recommended to protect your web applications. The AWS Shield is a service that can offer DDoS protection to your services in your VPC. So it's also recommended by AWS to secure inbound traffic flows. Then, of course, the use of the security groups and the network access control lists as well just gives you that additional layer of defense when you're securing inbound traffic flows. Now, how about outbound traffic flows, right? You also want to monitor traffic that is leaving your VPC, because there could be some instances where some of your internal devices have been compromised. Let's say one of your servers is part of a botnet and is trying to report to the command and control center. The firewall can identify that malicious traffic and drop it at the edge. So use a network firewall to secure outbound traffic from your VPC. It's also recommended that you could use a proxy server, which serves like as an intermediary between internal devices and the outside world, such as the internet. So it keeps the identity of your internal devices safe whilst permitting them access to the internet. It's recommended to use Route 53 Resolver, which is a managed service that can identify traffic going to malicious domains and then drop those traffic. So it's a pretty efficient tool, that one, the Route 53 Resolver. It's also recommended to use VPNs to secure outbound traffic flow. Of course, you know the VPN creates an encrypted tunnel which protects the flow of your data from your VPC outbound. Now, Mike spoke about the private link yesterday. There are some instances where you need to give access to external parties to some services in your virtual private cloud, right? Now, in such instances, there's no need to do VPC peering. You could just create a private link that will give them access to only that service that is specified. So it's also recommended to use the AWS private link to secure outbound traffic flows from your cloud infrastructure. Now, how about inter-VPC traffic? Now, when you do your VPC peering or you use transit gateways to allow connectivity between your different VPCs, do you just want to allow everything? Nope. Like Mike said, information sharing should be on a need-to-know basis, implementing the principle of least privilege. So how do you secure inter-VPC traffic? Use your network access list to define what can come into the subnet and leave the subnet, right? So even if you have a VPC peering, you can lock down access with your network access list to allow particular IP addresses or particular subnets to come in and go out. And that helps you to secure your inter-VPC traffic. Use security groups, which will protect the traffic at the instance level. So the security groups will be applied on individual EC2 instances. So even if you have a VPC pairing, you can create rules on your security groups that just allows certain IPs or certain subnets to, access that instance or that virtual machine. You can also employ the use of a transit gateway, which Mo spoke about yesterday. And the advantage that the transit gateway offers here to connect your VPCs instead of doing VPC peering is that you can create route tables, so you can, manipulate the routing table to determine who can come in and who can go out to your VPCs, and then you can implement security policies at the transit gateway level as well. So it's also a good solution to help secure your inter-VPC traffic. And then, of course, we spoke about VPC peering as well. It allows you to connect to VPCs with private IP addresses, right? So that way, the traffic from one VPC to the other is always across the AWS backbone network. It doesn't go out to the internet to get to the other VPC. So that provides some sort of security and confidentiality for that kind of connection. So these are some of the recommendations that AWS has shared to help their customers secure inbound and outbound traffic flows, application traffic flows, and inter-VPC traffic flow as well. If there are any questions, we can take it now.
Hello, everyone. Do we have any questions from Benedict or from what I had said prior to the break? If not, we'll go back to the content. We just want to check in with y'all. Just want to make sure that you're learning and if there's no questions that we need to address. Okay, well, I'll get back to the content. If you're having a good time, if you could like the video, if you want to get more videos like this, subscribe to the channel, hit the bell to be notified of new videos because we've got a lot of new videos coming. And make sure to, if you don't have a copy of the AWS Labs and that we're dealing with, please sign up and you can get them completely free on our content management platform. Truth Factory, how do you secure all the resources within your VPC using a security group? You don't. The security group is the only way that is designed for you to secure one service. Protecting your VPC is going to be a combination of leveraging next generation firewalls, IDS, IPS systems, endpoint protection, hardening your operating systems, encrypting your data, leveraging a strong identity and access management strategy, training your people on which things to potentially avoid. And that's, I'm only scratching the surface of what's necessary to actually secure your VPC. But the security group is just to secure one service.
Fatin is asking, can we use SCP as a security measure? So what does SCP mean? Secure copy, or the policy to control access to organization units in a multi-account strategy?
Yeah, so let's address this, and that's why we try not to use acronyms like an SCP, because both Benedict and I aren't sure whether you mean a secure copy or you mean SCP. But let's talk about it in the context of AWS, just in case. So the whole reason they came up with these security control policies is a security measure. It's to limit who can talk to whom in between these organizations. So it's an identity and access management measure. Don't count that as enough of security. Count that as one amongst 100 other things that you're going to need to do to secure your systems.
So name not found is asking, what's the difference between endpoints and private links? So endpoints are like entry points, URL entry points into your AWS web services, right? Private links gives you access to particular services in a VPC. So if a third party needs access to your S3 bucket so that they can save information there, you want to use a private link to give them access to only that S3 bucket and nothing else. So that's basically the difference.
Okay, well, I love these questions because you guys are thinking. So we will get back to the concepts, and I'll start talking about restricting network access. Sorry about that. I muted myself right before I was ready to speak. So now let's talk about restricting network access. Part of a good security posture is keeping unwanted traffic out of your network. Let's think about how organizations have done this for centuries. If you've got a castle and say a king and a queen is in the castle and they don't want you to get in the castle, they put up the giant wall around the castle, right? And it keeps people from coming in because it's higher than we can jump. Well, realistically speaking, a firewall is a countermeasure just like that. And, we want to keep traffic out of our systems that doesn't belong, and we only want to allow the traffic that does belong. And what firewalls do, especially modern firewalls, is they will look at the IP address that's coming in. They will look at the protocol, TCP, UDP. They will look at levels now at the application itself and can see what's going on, say, inside of an HTTP or HTTPS header. They can even look at patterns of anomalies that don't make sense and stop it. But typically thinking, and that's going to be in the next generation firewalls and the such, but typically think of this as firewalls keep unwanted stuff out, and they allow you to go out to the internet and come back, but they don't allow outsiders to come in unless you specifically mention them. Now, AWS has their proprietary firewall, which we'll talk about. But understand, if you're a security architect or a cloud network architect or a cloud architect, and you're dealing with enterprises, you're probably going to be needing a next generation enterprise ready firewall. And there's companies like Cisco and Palo Alto Networks and Fortinet that make them, and you'll be able to get them from the AWS marketplace. But this is an AWS exam, so we will be covering the AWS firewall next, which does not have some of the robustness for some of the things that I'm actually describing, but it's there, it's native, and it works well. So keep that in the back of your mind. I want to briefly walk you through the way a firewall will work, just for a moment. In case you're not familiar with firewalls, if you truly understand firewalls, then you'll understand these things a little better. So let's say we've got a user that wants to access the internet. In this particular use case, I decided to use a cat because I thought, who doesn't like cats? And it would make the user kind of happy over here. So now we've got a user over here that decides she wants to go to the internet. And why does she want to go to the internet? She wants to go to the internet because she wants to go buy tuna. And of course, that's her goal over here. So let's talk about the way a firewall will typically work. Let me draw a firewall over here. And then let's just say, and I'm going to make up a website, www.worldsbesttuna.com. So Cindy wants to go here. So the way a firewall is going to work, all firewalls for the most part, is Cindy's going to go to the internet. She's going to go to www.worldsbesttuna.com because she wants to buy tuna of all those things. And her TCP request for the web page is going to go through her firewall out to the internet. World's Best Tuna will acknowledge her connection. They will respond to her connection, and then the connection will be allowed in. And here's the reason why. The firewall knew the traffic was coming from Cindy to worldsbesttuna.com. And the reason the firewall knew it is the firewall took state. And what happened is the firewall built a table that said message from Cindy to worldsbesttuna.com. And because the firewall has that state, which I clearly typed quickly, it knows to allow the response to Cindy to the worldsbesttuna.com. Now, let's just do this, and just for argument's sake, now we've got over here, we've got Sally the hacker. And Sally wants to go through the internet to steal information from Cindy. So Sally the hacker goes through the internet, it goes to the internet, and it hits the firewall. And Sally the hacker's information is not allowed to ever get through the firewall. So Cindy will never see that, and Cindy will be safe. This is because there is no state for Sally the hacker, and there are no rules in the firewall that says Sally the hacker is allowed entry into Cindy's home. So now that you know what a firewall is and what a firewall does and how a firewall works, let's talk about the AWS Web Application Firewall. And a web application firewall is a firewall that typically looks for web threats. And web application firewalls can fit very nicely with your next generation firewalls as well if you choose to use them. But what'll happen is the firewall will run, and it will run on the server, and it's going to be constantly looking for exploits and things that occur. And the firewall will typically stop threats that it knows about. And when it comes to firewalls and the way they stop threats, they can stop them based upon a signature if the firewall supports it, meaning I already know what the issue is, kind of like your antivirus. Or firewalls can use anomaly pattern detection, which is they can look and say, this doesn't feel normal, block. So if any of you guys travel a lot for work, and you've ever, say, left your house in Palm Beach, Florida, and then gone to New York City to give a speech and San Francisco to give a speech, and the next day you're in London, and the day after that you're in Dubai, your credit card company may call you and or shut off your card and say, did you mean to do this? Now, that's happened to me lots of times because that's what my weeks used to be like. And then at one point, the credit card company got used to me just being in 3 countries a week, and it would say, Mike, okay, it would allow my card to charge us through. Well, modern firewalls can do that as well. Now, when we're talking about WAF, and WAF can't necessarily do all these things. It can do some of them, but not all of them. You can put your web application firewall on your CloudFront distribution and block the bad web requests before they even hit the content delivery network, before they even hit the servers. You can put your WAF on an Amazon API Gateway to help protect your APIs. You can put it on a REST API, or you can put it on your application load balancer. And WAF will block connections to these edge locations before they get on your network. And WAF control gives you the ability to control access that users can specify. So it's a firewall, so you're going to design a policy. Now, WAF can get pretty granular because it's a firewall. You can say, who's allowed to talk to whom or who's not allowed to talk to whom. And basically what you're going to do is you're going to create firewall rules. And you're going to be using, web ACLs rules or rule groups to do it. And basically rules are going to be statements that says, permit Sonny the cat to enter our network because we know Sonny the cat's IP address, protocol port number, and we create an entry. Or block Sonny the cat from entering if Cindy doesn't like Sonny the cat. Not all cats like each other. But, we have the ability with firewalls to determine who's allowed in and what we're allowed in. As a rule, in a firewall, don't let anything in except when you need to. So if you've got a firewall and you've got a server that's listening to HTTPS, open port 443 and that demilitarized zone specifically for that HTTPS server, but don't let the rest of that HTTPS or any traffic come into your network. So kind of keep about this. Now, rule groups in AWS WAF are going to be groups of individual rules that can be reused in other places. And you'll be able to monitor your WAF traffic metrics in CloudWatch, which is kind of nice. So you'll enable your WAF on your application. You'll create a policy that's going to determine what filters you need. And then WAF will analyze traffic based upon the policy. And if the traffic conforms to the policy, WAF will allow it. If the traffic doesn't conform to the policy, WAF will deny it. And if an attack occurs, you can create new rules to try to mitigate the attack. So here's kind of the way you could apply AWS WAF. You can pop it on your CloudFront distribution. You could pop it on your load balancers, for example. And you could pop it on your API gateways. Here's an example of if we were going to do an all AWS security environment. Not that we should, but if we could. And, the determining of what we secure is based upon, the organization's assets, what they need to protect, what kind of risk tolerance they have. Are they taking the risk, transferring the risk, mitigating the risk? And there's a lot of business decisions that go into that. But in this particular case, here's what it could look like. We could use WAF and Shield for DDoS protection. And then we can use the network access control list to protect the subnet. And then we can use our security groups to protect our instances. So that's putting some of the AWS security pieces together. So let's talk about preventing a distributed denial of service attack. What is it? Let's first talk with what is a denial of service attack. A denial of service attack is if I try to overwhelm your capability to serve. And by doing so, I make it that you can't legitimately serve your customers. So let's say for a moment, all of you just became web servers. Oh, you're all web servers. I'm a web server too right now. Let's be web servers. It'll be fun. So each one of us can handle 5,000 web requests per second. They come in, we can answer them. They come in, we can answer them. And we can each do 5,000. But we're all individuals and we're all our own little web server companies. Now, somebody sends 100,000 web requests to us, but we can only handle 5,000. What's going to happen? We can't handle the 95,000. We're either going to crash because we're so overwhelmed we don't know what to do, or we'll just be busy servicing some that the majority of the people won't be able to attach our systems. We're typically going to crash. So that's a denial of service attack. When a hacker sends more information than it can potentially be handled, and it overwhelms the server. Now, I can send a whole bunch of half-open TCP connections and overwhelm immediately the server's capability to even respond to anything else. And all I sent was bad information. So there's ways that we can mitigate some of these things that we're talking about. That's a denial of service attack. Now, what's a distributed denial of service attack? Well, right now, let's say all of you out there are servers, and I were to be a hacker. I'm not a hacker, but I were to be a hacker. And I take over all of you, and you're all servers, and you and me together, we all launch an attack on something. That's a distributed denial of service attack. And why is it? Because it's not just the one hacker that's out there. It would be all of us that effectively functioning as hackers, all to overwhelm a single company or a single organization. So DDoS attack, one hacker. Distributed denial of service attack, a hacker hacking into a whole bunch of other systems and then using all those other systems to hack in. Now you can see how easy it is to compromise 1,000 servers on the internet to take down a web server. So DDoS protection really matters. And so now graphically, I can walk you through what previously happened. Here we've got the attacker. The attacker has a control server. They infect a whole bunch of other systems, and then they take down a web application. So let's talk about preventing DDoS attacks. It's not going to be any one thing that you do, just like it's not going to be any one thing that you do for security. Here's some things to think about. In your networks themselves, control the traffic that's inside of each subnet. And you're going to do that with a network access control list. If a hacker gets on one subnet and they can't get anywhere else, the damage is contained. On every server we have, let's put a security group on it to protect that server. Is the server good enough because we put a security group on it? Absolutely not. Every server that comes up for the most part starts out insecure. Servers are listening on all these ports and they've got all these services running and every one of them can be attacked. So your servers themselves have to be locked down. Unnecessary services have to be removed. Open ports need to be closed. Servers need some anti-malware protection, for example, host-based firewalls, maybe some IDS, IPS systems on the servers. So now let's think about auto-scaling. How can auto-scaling help with the distributed denial of service attack? Well, this is one of those great things that the cloud does, and it does well, and auto-scaling can help mitigate against a DDoS attack. So right now, let's say I am a server, and I can handle 5,000 requests per second. And I'm being DDoSed at 10,000 requests per second. I can only handle 5,000, so I auto-scale. And now I add 3 additional servers. Now 10,000 requests are coming in, and I've got the ability and capacity with the 3 servers to be able to handle 15,000 requests. So auto-scaling can actually do a lot to help mitigate against a DDoS attack. Now you're going to pay for that DDoS attack because you're going to be paying for all these additional servers. But if business is critical, keep that in your mind that you can help survive it with auto-scaling. And businesses know their cost of downtime. Firewalls. Adding a firewall that can recognize a DDoS attack and stop it, huge advantage. AWS WAF can recognize common attacks and dynamically apply policies to mitigate them. Common attacks. Some of your next generation firewalls can look for patterns of behavior that don't look right and can do it. And AWS WAF can integrate with some open source abilities to do some of that. So it can do that. But your mileage may vary on firewalls. And then AWS Shield is great DDoS protection that gets placed on the Cloud Front content delivery network. And it's typically available at no additional cost to organizations using AWS WAF. And of course, you can get Shield Advanced, which has got much better protection. And you can add that to, say, a virtual machine EC2 instance, load balancer, Cloud Front distribution, Route 53, and even your Goldville accelerators. So let's talk about the difference between Shield Standard and Shield Advanced, because there's a big difference here. Shield Standard's free, and it's going to protect against common DDoS attacks. Common ones, normal ones. So say 96% of the most common ones, which is pretty good. You can think of your SYNAC floods, your reflection attacks, your HTTP slow reads, common attacks. And AWS Shield Standard is going to block based upon a policy. You set it up. Don't allow this in, and it'll block it. But it's static. It's based upon policy. Now, when we get into Shield Advanced, which you're going to have to pay for, you're going to get much better DDoS protection. Not only can you put on your load balancers, virtual machines, Cloud Front, or REST-3, but now we're starting to get some intelligence into our DDoS mitigation. And it will look for patterns that are abnormal. And and Shield can deploy, say, an ACL to mitigate that attack when it occurs. And Shield will allow visibility and notifications for layer 3, layer 4, and layer 7 attacks. And for organizations that purchase AWS Advanced Shield, they're going to get a team at AWS that will help them if they have a DDoS incident. And that's 24/7. And for that to occur, the organization needs to, realistically speaking, have business or enterprise support. Keep that in the back of your mind. Just see where I'm at over here. Okay, so let's briefly talk about CloudFormation scripts. And in the world of cloud computing, and I don't care whether you're in a Nutanix data center, an OpenStack data center, an Azure data cloud, a Google Cloud, it doesn't matter. You have the ability to deploy what's called infrastructure as code. And what are we really talking about here? The ability for a developer or a DevOps engineer or a cloud engineer to write a script, or even ChatGPT to write the script, honestly, you can use it, that'll write a script that will literally go to the cloud provider and open up or set up a lot of things for you. Now, when it comes to automation, if we're good at it, we do a great job. When it comes to automation, if we don't know what we're automating, which sadly is most of the cases, we automate problems again and again and again. So keep that in the back of your mind. But here's one place where infrastructure as code is going to be very helpful. If I have an infrastructure as code environment, I can create a specification of this is the way something's supposed to be done. Say the operating system has all the vulnerabilities patched, all unnecessary services are turned off, there's no certain use or questionable applications or settings that can potentially be harmed. And if I have one of our engineers launch this infrastructure as code script, I can standardize something good the way I want it to be. And, in a world where 98% of organizations are multi-cloud, your engineering team is probably better off using a infrastructure as code tool like Terraform that will work across all providers. But we're in the context of AWS. So AWS has the concept of a CloudFormation script, which is the AWS branded, AWS managed infrastructure as code solution on AWS. You can still use Terraform, but you could use this AWS service. And it enables your people to basically put their code infrastructures and templates, pop in an S3, launch the CloudFormation script, and infrastructure will be deployed dynamically, just like that. And CloudFormation, you can set up to provision 1,000 virtual machines. It's relatively easy to do. But that's what we're talking about. CloudFormation templates are going to be available with a multitude of options. The code on these is typically written in JSON or YAML format, like you typically would use YAML for Kubernetes as well. You can store the code locally. You can store your code on S3. And the code is going to be either used by the CloudFormation in the console. You can set up via the CLI, or you can set up via the API. And you pop in your code, and your systems will be automatically provisioned for you. Okay, I think it's time for us to switch to Benedict, so maybe we see if there's any questions before we do. Any questions for us? It is a known fact that the security landscape is so fragmented and security personnel can get bored with multiple with a multiple security tools to manage them? Is there a unified platform? So Tunde manage different security in a domain similar to Defender for XDR and Sentinel and Microsoft. So Tunde, it depends on how secure your systems you want to be. And what I mean by this is, look, AWS is a security center, which is good for your AWS stuff. But if you're dealing with an enterprise grade, you're going to need much more than, say, an AWS security center. And now let's look at it in the context of, yes, let's say Palo Alto has their own good systems to manage everything, or Sentinel and Microsoft has their own good systems to manage everything. Would you really use a single vendor's firewalls in a high security environment? And here's the thing, different firewalls are like different martial arts. They each have their own strengths and they each have their own weaknesses and things that they catch. And if I was going to build a martial artist, maybe I'd teach them some jujitsu, I might teach them some boxing, might teach them a little karate along the way, and they'd be better armed. And when I design a high security architecture, I may want some of the things that Palo Alto does best, and maybe some of the things that Cisco does best, or does differently. And that's where you're going to get into your challenge. As you get better and better and better security, you're going to often get more fragmented in your tool set, because that's where things get ugly. So when it comes to security, can we use the cloud native tools? Does it make sense? And if so, we got our security center. Now, for most enterprises, that's probably not going to be enough. So now they're going to have to determine, do they want to look for a single vendor solution like a Palo Alto? And then there's some pretty good options, and a lot of the Palo Alto stuff is integrated natively in AWS. Or do they want to build the best of breed, which will use the best tools from each vendor? And by doing so, they're going to get a much more robust security platform and a whole lot more complicated management. So that's an architectural choice they're going to have to make after evaluating all trade-offs. The capability of their people, their goals, what assets they're protecting, the value of the assets they're protecting, the risk of the access to their business continuity plan. Great question, I think. If either of you guys know of any good tools that are out there, we all tried to make HP OpenView work many, many years ago to make that look good for network management, but it's hard to find really good tools. How do you determine a good source for protection? You test. But I'll also, Lady Godiva, give you some other things to think about. So one of the things that you do is you actually have people try to break into the systems. You hire good you have a proof of concept environment set up, and you have people that are ethical hackers try to break into the systems. You have your QA test engineers try to break in, and you'll be able to see what you get. But let's take it back a step. Who's going to really buy these architectures? The chief information officer, the chief information security officer. They're going to be the people that are there, that are going to be your customers. Now, if you are a chief information officer and you buy from Microsoft, and it doesn't work because Microsoft has a failure, nobody's going to fire you for buying Microsoft. They're the biggest enterprise computing platform in the world. And now you deal with Billy Bob's company. And Billy Bob's got a better product than Microsoft this month. And next month, Microsoft has a better product. But Lady Godiva, nobody's ever heard of Billy Bob. Billy Bob's security company. And you make the investment in Billy Bob's because it is the best. And then it doesn't work because all technology breaks. It's just a matter of when the technology is going to break, not if it's going to break. And now you get fired because you bought Billy Bob's product, not the standard, which was Microsoft. So you're going to have to attend conferences. The organization that you work for is going to have to evaluate the technology and speak to the vendors that are out there on every architecture, because every architecture is going to have different strengths and weaknesses. And in every architecture, we may have to do certain things that would make it a little less secure because of an architectural decision we have to make in order to make it work. And then after we evaluate those capabilities, then we might actually say, okay, given the constraints that we have, the Cisco product is the better one, or the Checkpoint product is the better one, or the Palo Alto product is the better one, or the Fortinet based upon their needs. Kind of like if you were going to buy a car, then you would see what kind of car do you need based upon what you're trying to do. Do you get a minivan? Do you get an SUV? Do you get a race car? Hope I answered that. So Tundi, has AWS leveraged generative AI for security and reverse engineering of malware? Tundi, this has been going on for years where people have been using AI to reverse engineer malware and try to see what's been going on. For the most part, all your good security providers have had AI integrated into their systems for many years, at least 5 years now. Okay, well, if it's time to go back, give me a hashtag AWS Advanced Networking. If you just joined us, we've got some free labs that we'd love you to do, about 2 full days worth, to help solidify the training we've done over the last 3 days. Please make sure to sign up. The link is in the description, as well as the chat box. I think that's you, Benedict.
Yep. It's me again. So let's talk briefly about the AWS Cloud Development Kit. Thanks, Mike, for introducing CloudFormation and how it helps us to achieve infrastructure as code in the cloud. So AWS Cloud Development Kit is actually a tool that is actually an infrastructure as code tool that is offered by AWS. It uses CloudFormation to push code to the cloud and deploy infrastructure. So the Cloud Development Kit is an open source software, right, for developing AWS-based infrastructure, right? So it's an open source software framework used to manage AWS-based infrastructure. So it's proprietary in this sense. So how it works is that it makes it easy for developers to, define cloud infrastructure in the common programming language such as Python, Java, C#, and then deploy them to the cloud using CloudFormation. So what it means is that you go into code and then you write a script to deploy an S3 bucket, right, in the cloud, and then use CloudFormation to push that code to the cloud to deploy the instance. So rather than going through the normal way of building your infrastructure, which is through the graphical user interface or through the command line interface, right? You can just deploy your infrastructure programmatic using this AWS CDK in a program manner, right? Now, how exactly does it work? It works by it does some high-level abstraction here, right? It builds objects, right? And then you can configure these objects as reusable code, which is called constructs, right? And then these constructs are combined together to form stacks and apps. And then you can deploy these stacks and app to the infrastructure using a CloudFormation template. So this is what the diagram is going to look like. Just share my screen briefly. So you have some abstraction which is done here. There's a CDK application, and then you have constructs there which are combined to form apps and stacks, like I said. And then to deploy these apps and stacks, you compile them and then use a CloudFormation template to deploy it to the cloud. So, this is infrastructure as a code typically through the Cloud Development Kit, right? We're still going to talk a little about infrastructure as a code later on, but This is just to give you an idea of a service that employs infrastructure as a code to deploy resources in the cloud. So this way, you just deploy the services from your CDK application, and no need to go into the graphical user interface, the management console, or the command line console. It's all done in code. And why would a company use the AWS Cloud Development Kit? Well, it makes onboarding easier, really. Okay, so you're able to you've already defined code, for example, of an S3 bucket. So if you want to deploy an S3 bucket in the cloud, it's just easy. Just go to your CloudFormation template and then call up the constructs and then deploy it to cloud, right? If you were to go through the management console, you would log in, go to S3, set it up, choose the size, encryption, algorithm, and stuff like that. But if you already have this in code, it just takes a few minutes for you to deploy. So it makes the cloud onboarding easier. It also helps developers to roll out applications faster and with more accuracy, especially in this era of DevOps, where developers are churning out applications day by day in a fast and efficient manner. So it supports that. And then it helps to, enforce security measures, compliance requirements. So if you have a requirement by organization that all S3 buckets must be encrypted with AES 256 encryption, right, by default. Now, if you have this already defined in the Cloud Development Kit, ready to go, ready to be pushed by CloudFormation, there are bound to be less mistakes than if an administrator goes into the cloud and is not really aware of the security policy that says AES 256 and uses something that is less secure to deploy the template. So in that sense, it gives you the ability to maintain your compliance requirements with regards to deploying applications in the cloud. So these are the benefits of using the AWS Cloud Development Kit. Could take some questions now if there are any.
We're back to see if you had any questions before we transition between us. If not, we'll go right back to the content, which is totally fine. All right, let's go back to the content, huh? I will begin talking about the service catalog. Okay, so let's talk about the AWS Service Catalog. So in my first networking engineer job, I was given the name Sniffer Boy because what I literally did in my first week was I took a protocol analyzer, which they used to call a sniffer, and started plugging it into every single port on the network that I could find. I was creating something called span ports and checking hubs so we could find all the things that were going to get you. And I can remember I found people sharing Napster videos and all these other things on a corporate network in my first job. And the key is, why did we do that? Because we didn't know what people were putting on the systems. Now, when you're designing your systems, you want to control what's put on the network. And you ideally want it to be things that you want. That's one of the reasons you would use infrastructure as code. Standardize on a certain way to manage your operating systems. Well, the service catalog is a way to help you control what's going to be placed on the systems that you design. if you're the architect, and on the systems that you build if you're an engineer. And what happens, you take this AWS Service Catalog and you're going to create a list of things that are approved. You can use these certain virtual machines that are pre-made, these kinds of servers, these specific software pieces, these specific databases, and these specific application architectures. So you design it, you create a policy, and then when people actually want to deploy something, they can deploy what you know is right and you know is good versus whatever they want. So for here, we're realistically, what are we talking about? The user is going to access the service catalog. They're in the service catalog. They've got some pre-made AWS Cloud Formation scripts. Poof, launch what you want. It's built, and it's going to be built within the same parameters that are actually that you've actually determined to be successful. So that's realistically speaking what we're talking about over there. So another way that you can think about how to try to make this a little better is you need to store your secret stuff somewhere. I mean, when I was younger and we started to push heavy-duty password policies, people put sticky notes of the passwords on their desk, and they'd have 10 different sticky notes. It was kind of scary if you realized it from a security hole. We tried to push strong passwords, so people put sticky notes where everybody could see it. But where do you put your sensitive information? Where do you put your passwords that matter? Where do you put your license keys and other sensitive information? You have to store it somewhere. So in AWS, we have the concept of the Systems Manager Parameter Store. And this is a place where you can store your secrets or secret information in AWS. And the Systems Manager Parameter Store will provide a means to store your sensitive things in an encrypted manner. You can store, the Systems Manager Parameter Store can actually look at your managed instances and see if they comply with what they're supposed to. And if not, it can report policy violations. It will keep your code separated from your password. We can use it for audit access, and it's a great way to track password use. So keep track of that is something that we're actually talking about. Now, the concept may pop up on an exam, so we'll talk about it. This is not a comprehensive answer for end-to-end security, but this is what you might typically think about from a test perspective on securing an AWS managed database. Use multi-factor authentication to make sure that only authorized users can access the database. Do not use a Bastion host to connect to your database, because if the Bastion host is compromised, then your database will be compromised as well. Make sure for your databases, you've got a strong identity and access management access policy to limit who's allowed to use the systems and what they're allowed to do. When we deal with AWS databases, please use a security group on them as a host-based firewall to protect stuff from coming into them. On your database, enable TLS encryption to protect your data in transmit. Leverage the AWS key management system to make sure, which is a manner to actually manage your encryption keys. But in this case, make sure you manage your encryption keys, which are going to be used to encrypt your data at rest. And monitor and log any activity within your database environment to help detect unusual behavior. Now we'll talk briefly about AWS config. And AWS config is going to be a service that's going to help assess, audit the configurations that you have in AWS. One of the good things about AWS config is it's going to give you a good opportunity to log and track changes. And when a change is going to be made, it'll be noted, it'll be logged, and you can see who did what and when. And if something gets broken because of a change, it's good to know what was actually done, and then you can unbreak it pretty quickly. You can also set up AWS config that anytime a change is made to send, say, a text message or an alert. And you can integrate that into the Amazon Simple Notification Service to do so. One of the things that's really great about config is it's going to provide constant monitoring of your configurations. So you know what they're supposed to be configured out. You know what your systems are supposed to be. And if something changes, or when a change is made that violates your policy, you'll get an SNS alert. You'll get notified of it so you can do something about it quickly before it becomes a big issue. Now, one of the most critical things for high availability and high performance and high security is a very good change management environment. Being able to know what the change is, having the change actually, checked by an architectural review board to see what the impact of the change is on other key components of the environment, determining when to make the change, for example, and how to test after the change. Now, in real high availability, high performance environments, you're going to have to do that. But, lots of times changes get made and you don't know because somebody does it. And for organizations that don't have the best change management policy, AWS Config can really help here because it can give you some information on what was changed. And even on organizations that do have a good change management policy, at least you'll be able to see that the change was made and track the change that was made in your configurations, in addition to the architectural planning that would occur. And AWS Config can integrate with CloudTrail to track changes. And that'll make it much easier to revert should you have an adverse event. So how do we set this up? A configuration change, or how is it going to work? A configuration change is going to be made. AWS Config will note the change, record the change, and it'll do it in a consistent manner, so you'll be able to mine through this later. AWS Config will then check the change against an organization's policies, and then Config will notify you that a change has occurred. And you can get this notification as a CloudWatch event, a simple notification service, or use other AWS features to do so. So I like to visually look at it this way. You make a configuration change. AWS Config will monitor the change, and then you can obviously see the changes that were notified, maybe CloudWatch, S3 logs, and API call. So let's briefly talk about Certificate Manager. And then I think we'll end on Certificate Manager, and then maybe we break for lunch. Actually, you know what? I think we'll go all the way up to Amazon Macy really quickly. So let's talk about the AWS Certificate Manager. In a world where you're going to need TLS encryption and public key cryptography, those kind of things, you're going to need certificates somewhere along the line. And there's lots of places where you can buy security certificates, but you can get them directly from AWS. And if you do so, it's going to be relatively easy to do so for your things that are on AWS. And Certificate Manager is just, realistically speaking, an AWS service to centrally manage your SSL TLS/certificates in the AWS cloud. So you want to put a certificate on your website, you can get one from the AWS Certificate Manager. And Certificate Manager is going to enable the simple provisioning, management, and deployment of certificates, whether they be public certificates or private certificates, for you to check the integrity of your internal applications. Certificate Manager will allow you to deploy certificates on AWS resources quickly and easily. And generally speaking, Certificate Manager provides free public certificates. And you can apply these certificates to things like your load balancers and your API gateways. So kind of the way this would look is you go to Certificate Manager, you order your certificates, and you put them on your load balancer or your Cloud Front distribution. So there's really two options when deploying your certificates. You've got traditional Certificate Manager. And this is what you're going to use if you're looking for security and encryption using TLS for your web applications. And you're going to use a Certificate Manager, put it on your load balancers, your Cloud Front distributions, your API gateways, in order to secure your communications. But there's also the ACM private CA that's offered by Amazon. And this is going to be for communication inside of your organization. And it enables an organization to create an element of hierarchy. And this enables an organization to issue private certificates for certain users or computers or applications or services or servers or devices inside of the organization. You've got to remember, private certificates can't be used on the internet. Public certificates are used on the internet, but private certificates you can get from the ACM private CA from Amazon for an additional cost. We can briefly talk about a couple of, the service of Amazon Guard Duty. Guard Duty is basically an automated security monitoring service. And what happens is you're going to get a lot of logs, CloudTrail logs, DNS logs, VPC flow logs, and Amazon Guard Duty is going to monitor these, and it's going to look for patterns of behavior that are anomalies. And if it finds something that doesn't feel right, it's going to notify a systems administrator so they can do something about it. While we're at it, we'll briefly touch on Amazon Inspector, which is another security assessment service that's going to help improve the security posture and compliance inside of an AWS environment. And Inspector is going to automatically assess applications for exposures, vulnerabilities, and deviations from what it determines as best practices. And after performing the assessment, Amazon Inspector will give you a detailed list of findings and what it ranks in priority level of severity. You can use Amazon Inspector to help with security assessments, check for unintended network accessibility. Maybe one of your EC2 instances on the public internet and you don't know about it, or the systems haven't been patched, that kind of thing. And then we will end on Amazon Macie, and then break for lunch and then come back afterwards, which is a fully managed data security and data privacy service that works by using machine learning to discover and protect your sensitive data. Macie basically provides an inventory of your S3 buckets, including a list of unencrypted buckets, publicly accessible buckets, which is a big issue, and buckets shared with AWS accounts outside of those that you've defined in AWS organizations, because they can be big security holes that you don't own. And when Macie discovers things, it'll apply machine learning and pattern matching techniques to help you select and identify and determine who to alert of sensitive data. So basically, Macie might find some sensitive data or something that looks like it's personal identifiable data, and it can give you a notification. Are all these machine learning systems accurate? Sometimes they give you an alert on good data. Sometimes they give you an alert on bad data. So I feel like it's a good time to break for lunch. Let's see if anybody had any questions very quickly before we break for lunch. And then we'll come back in 1 hour. Okay, we covered a lot of stuff so far today. When would you use the CDK over CloudFormation?
So, hi, Nigel. So, CDK is actually a tool that employs CloudFormation, right? So, you use CloudFormation templates to push code to the cloud. CDK allows you to combine your constructs as apps and stacks, right? And then you use the CloudFormation template to push those code to the cloud. So CDK is a tool that employs CloudFormation.
Why Bastion hosts are not recommended. So William, I want you to think about this. And I have two ways that I could allow access to my systems. Access one is if I've got a direct connection to my cloud provider, I can access my systems through my direct connection. Access two is I've got a highly secure environment from a network VPN device to the AWS environment. Again, highly secure. Here's what a Bastion host is. I got Billy Bob, who's not a security expert, that either takes a Windows system or a Linux system and sticks it on the internet. Billy Bob does not know operating system hardening and how to make a completely secure operating system. They then put two network cards in it, one inside the system and another one inside of my network. And I either Windows remote desktop to the system, which is worst case situation, and jump out of that Ethernet port into, say, my database or my application, or I SSH into a Linux machine and then from there jump onto the network. Now, I just stuck a computer in the middle of the internet and used it as a jump host. Now, it's so easy to hack that system. Now, if I wanted to do it correctly, I might take a network load balancer and front end two next generation firewalls and allow the IPsec protocol to a specific demilitarized zone. And in that demilitarized zone, I can put an access control list to protect that subnet. Now that virtual VPN concentrator that I'm going to use is going to be a Linux system. So I can put a security group on those Linux systems themselves. And then on those Linux systems that are going to be the VPN concentrators, they're going to be pre-made designs from a company like Palo Alto, where they spent experts and millions of dollars learning how to optimize the operating system where their virtual machine is there. And that is going to be a hardened system just to allow IPsec access. And then from there on my demilitarized zone, I can give them control over where I allow them. So the question is, do you stick a virtual machine in the middle of nowhere and call it a jump host? Or do you properly protect a VPN concentrator, which is a security device that's been purpose-built by security companies to do this? And secure that in a very secure demilitarized zone protected by firewalls. That's what I do. But, you know, I didn't spend $15-20 million learning how to perfectly secure and penetration test an operating system like a security company would. So I'll ask them to do it. So it's a good way to share root log on amongst admins.
So it's not recommended to use the root admin credentials for administration of your AWS console. In fact, what is recommended is that you use the root credentials to create administrative accounts for the different admins who are going to be managing the account. And come to think of it, if you're sharing the root account details with all the administrators, if someone goes in and deletes an S3 bucket, who do you hold responsible? There's no way you're going to find out which of the admins did it, because you're using one root account for all the admins. So it's not recommended to do that.
Yeah. Would AWS Certificate Manager be a good choice in multi-cloud? Minesh, almost anything that begins with AWS, like DynamoDB, Amazon Aurora, probably something you don't want to use in a multi-cloud environment. So there's great certificate authorities that you can buy your certificates from. There's nothing wrong with using these AWS certificates as a certificate manager. They're fine. But there's lots of companies that you can buy enterprise-wide certificates from that you could use on and off of AWS. But if you're an AWS shop, maybe it's an organization that doesn't need high availability. Maybe it's a small to medium-sized business. It's all there, very simple to do. Well, if Bastion host can pivoting, can you conclude that a remote access VPN with a slit tunnel? So I don't know what you mean by pivoting, but I'm talking about making sure that your remote access device is much more secure. Now, generally speaking, split tunnels are a bad idea because they potentially allow risks into the system. So whoever's going to be coming in to access our system should never be allowed to be using a split tunnel. But with a good VPN concentrator and a good system, I can make sure when someone tries to initiate a connection into that tunnel, I can check not only who they are, but I can also check and make sure their operating system has a minimum level of security. They have specific anti-malware, anti-patches, and I can enforce a policy on them. So I've got much more control by setting it up as the way an enterprise would. And an enterprise doesn't allow remote access into their critical systems via Bastion hosts. Now that's different than the Microsoft Bastion host service, which is realistically speaking an Azure managed VPN. They just called it Bastion host. What's a demilitarized zone? So when you design an architecture, you know, you don't want anybody to be able to allow anything inside of your systems. Like all public access should be restricted for all your internal systems. But then what about stuff that needs to be reachable from the internet? What you do is you create a barrier network outside of your system that you allow, that you partially protect. So I would create a demilitarized zone, which is for my web apps, which is where I would put my HTTP and HTTPS stuff. Only that would be in that demilitarized zone. I would create another environment for remote access where I would have VPN concentrators and only allow the IPsec protocol in, because that way nothing else could be hacked on there. I might have some other servers for file storage that I wanted intentionally on the internet. I don't want that in my system for sure. So I might take those secure FTP servers and create another special subnet for them where people can upload files. Okay, well, let's do this. I don't want to jip anybody on lunch because everybody loves lunch, right? So we will break now. We will come back at exactly 1:15 p.m. I'm sorry. We will come back at 2:15 Eastern time, and we will get back to the fun. So if you haven't liked the video, please give it a like. Please subscribe if you haven't subscribed, and we'll see you everyone back in about an hour and 8 minutes. Welcome back, everyone. We are back for the sixth session of our AWS Advanced Networking Bootcamp, and this is to prepare you for the ANS-C01 exam, and this is an AWS Specialty Security Course. So we're back, and we're having all kinds of fun with us. Let me know that you're here by giving us a hashtag that says AWS Advanced Networking, and that way we know that you are awake, you are alert, and you are oriented. Also to let you know that if you've just joined us, we have labs that you can do. You know, this has been a very busy 3 fun days. I mean, really busy 3 fun days to be here. And we've had a tremendous amount of content to go over the last 3 days. And we have 2 additional days of hands-on technology content that you can watch, you can learn from, you can do, both in AWS and also on real networking gear, so you can truly see what's going on behind the hood. So welcome back, everyone. And we will begin in about a moment. Benedict is going to begin, and he's going to be discussing network automation, which is a really hot topic in today's world. So welcome back. Strap in. Benedict will begin, and Benedict and I will be going back and forth throughout the day.
Thank you, Mike. Okay, so now we want to talk about network automation. But before we talk about that, I see that there was a question in the last session that we did not address. So I'll just address it quickly. Someone said the administrator with the root account left the company, so they don't have access to their root account anymore. So a couple of things you can do. So first of all, you can be proactive about this and reactive. So let me talk about the proactive measures first. Being proactive means having in your security policy, right? A definition of how administration accounts are kept. So for example, in this case, you can define in your policy that root accounts be kept in a password vault, such as KeePass or LastPass. And in that way, if anyone leaves the organization, the other administrators still have access to the password vault, right? Another thing is that you can implement some form of dual control there and say, instead of one person to have the root credentials, let 2 people have it, and one of them must be senior manager or something. So those are proactive measures to, ensure that your root accounts are not taken by a disgruntled staff who leaves the company. Now, being reactive about this, I assume that the administrator used his company email account to register on AWS and get the root admin account, right? If that's the case, you can enable the user's email and then go on to the AWS console and try to reset the account. It's going to send a link to the administrator's email, and then you just follow the steps to recover the account. Now, if there's 2-factor authentication attached to that account, it could go both ways. I mean, if it's a situation whereby 2-factor authentication apps are only installed on company-held devices, then it is assumed that when that administrator was leaving the company, he dropped his company-managed phone, and then from there you can get the code and get back into your root account. Now, if that doesn't work, you have to contact AWS support. I'm sure they've had issues like that before, and they'll advise you on how best to proceed. So let's talk about network automation. Now, what is automation? It's basically the use of technology to perform tasks with reduced human intervention. So what does that mean? I wake up in the morning and I want to listen to my favorite song, Don't Worry, Be Happy. Actually, that's not my favorite, one of Mike's favorite, right? So I go into my phone, and then if I've downloaded a song, I just click on it and play it. If not, I go to YouTube and, play the song, right? That's human intervention. How about if I have Alexa? Alexa, play me Don't Worry, Be Happy. And there's reduced human interaction with the system because there's an automation system in place to play me my song. So that's what automation is really. It kind of helps to make things easier for the administrators of the network, right? Now, in that light, network automation is the process of automating the planning, deployment, optimization, and operations of networks and their services. So what's going on here is that it's using programmable logic to manage network services and resources. So it takes out all those manual steps of logging into the switch, logging into the firewall, creating an access list, deploying it, verifying that the access list works, and stuff like that, right? Here, you do everything in code. There's a program available for you to carry out all these processes. So it kind of makes life easier. But we have to be careful so that we don't break things in our bid to embrace automation. Now, what do I mean by that? Take, for instance, you have 1,000 switches in your infrastructure, and it's in part of your policy that you take backups once every month of your switches, right? So normally you have to log into these 1,000 switches to take the backup, but you can have an automation policy that says on the 28th of each month, take the backup and save it in the object storage, right? This is an automation policy. It makes life easier for you. But what happens in a leap year when February has 27 days? Your automation policy does not work. And if there's a disaster in the first few weeks of March, it means that the latest backup you have for your switches is going to be in January and not February. So let's kind of keep that at the back of our minds. Now, how does automation work really? And it usually exists between command line and automation software really. And there are a number of softwares that help to enable automation, right? So if you're doing automation on-prem, you have a lot. You can use Cisco Prime infrastructure to configure a bunch of switches at the same time, rather than logging into each Cisco switch to configure it, right? So you have solutions available like that, but it's usually going to be between a software solution, automation software solution, and the command line interface, right? So let's look at it at the basic level using command line interface. So you have a bunch of Windows PCs in your organization. You could write a script, right, to download the latest antivirus on these PCs by maybe 5 p.m. and then deploy it in across these PCs at the same time. So that's using the command line interface to achieve automation, because you're going to run the scripts in CMD to achieve CMD on each individual device to achieve your aim. You could use an automation software policy, and in this case, it would be, for example, a Microsoft service available for you to, patch your systems, right? So there, it's just a series of clicks, select the systems you want to patch, and then start the policy for them to download updates and install them, right? A very popular example of a software automation policy is Ansible, right? And it's very useful for a number of organizations. I'm sure the major service providers, cloud service providers also employ it to drive automation in their data centers. And the way Ansible works is that it packages APIs, inventories, and playbooks that users can browse and then select to run common network configurations. So you'd log into the Ansible software, and then you see options to take backup of all the switches, configure banners across the switches and stuff like that, right? So instead of logging into the switches individually to carry out all these tasks, you could just run the tasks from the Ansible software, right? So it kind of makes life easier for us. So why do companies automate, or why would you automate in the cloud, right? So it helps to reduce configuration errors. So let's take a scenario. In your security policies, it has been determined that all network devices should have a banner saying, this property belongs to Go Cloud carriers. Please log out now, or you can be prosecuted for this. So imagine if I was to do that in 1,000 switches, I could make a mistake on one of the switches, right? And then the text will be slightly altered. But if we're using an automation policy, right, it's going to reduce this sort of configuration errors because it has a template that is deploying to those switches, network devices at the same time. So it has the potential to reduce network downtimes due to misconfigurations by administrators, because you have a standard template that you're just pushing out to all the devices. Now, this is a controversial one. It lowers the cost for an organization because it can reduce the number of administrators managing systems. And what does it mean? Recall the scenario I gave earlier, that if you have 1,000 switches in your organization and you have to manually log in to take backups of everyone, of all the switches, it's going to be a hell of a lot of work for one person to do. So in that sense, you have 5 network administrators, and then they can cover all these switches at the same time, right? But if you have an automation policy in place that can do the backups, right, through a click of the button, then why do you need 5 network engineers? So it lowers the administrative costs for companies in that regard. Now, it allows network teams to become more agile and flexible and support modern business demands, right? So they have more time on their hands because they have automation policies in place to drive the network, and then they can focus more time on research and development to aid the growth of the organization. So these are some of the reasons why you would want to engage in automation. Now, Mike mentioned something about event-driven automations, right? So I'd just like to expand on that further. So what's an event-driven automation? So it's a process of responding automatically to changing conditions in an IT environment. So what does that mean? I have a system in place responding to requests from users, and my CPU utilization is hitting 90%. That's an event. An event-driven automation policy will autoscale this virtual machine and increase the CPU capacity so that it can respond to these requests without crashing. Now, ordinarily, if that was not in place, it means the administrator would have to, maybe put in the server in maintenance mode and try to add CPU resources to it. So event-driven automation becomes very valuable in this sense. That's just a basic instance where we can use it, right? So, I mean, it reacts to triggers, right, such as incidents on your network. So another very popular example of that will be an intrusion prevention system, right? It's a sort of event-driven automation. So it's looking at the network, looking at traffic coming into your organization, and then it sees something funny. It takes an action and drops that packet, right? So there's been an event, which is a funny traffic is seeing, and it reacts to it by dropping the traffic. So it's basically a system, is basically a solution that tells the system that if this happens, right, then that should happen to counteract it. So it could be very, very useful in that regard. And it's we often see it employed in the cloud, where you have auto scaling, right? So if the resources of your virtual machines are being used, or you're suffering a DDoS attack, for example, that is trying to drain your CPU and memory utilization, then upscale till when the DDoS attack is tired, and then you can now contract back. So very good example of an event-driven automation. Now, how does it work, the event-driven automation? When an event is detected, right, the automation policy will initiate scripts and workflows to counter such an event. And there are three main parts of an event-driven response. There's the event, there's the action, and there's the result. The event is the activity that occurs within the system. So take, for example, you have a DDoS attack to one of your servers. That is the event, right? Now, the action is a predefined action which is triggered and deployed as planned ahead of time. So you have a policy in place to auto scale your virtual machine if the resources are running low. This is the action. So that if the resources are running low, then upscale and increase my resources, right? And then we have the result, which is basically the reports or the analysis that is sent back to the administrator saying that event happened and this took place to counter the event, right? So you want to have a full grasp of what's going on in your automation environment. Now, why would you use an event-driven automation solution as an organization or a cloud engineer, right? So first of all, it helps to mitigate risk, right? Because it's kind of proactive than reactive in this sense. So it's responding to abnormal behaviors in your system just to make sure that your systems are up and running and safe and secure at all times. So it helps businesses to become more robust because this proactivity, right? Now, another thing that it can enhance is the accuracy and efficiency of deploying network resources in the cloud, right? So you have some infrastructure in the cloud, right? And normally you have to go in manually through the GUI or command line interface to configure these devices, and you could be prone to making errors. Human error is one of the major causes of security incidents, right, in IT world, and it's pretty understandable that sometimes as human beings we tend to drop the ball or make mistakes here and there. But having some an automation policy ensures that you're always churning out the same configurations to your infrastructure at all times, right? So it improves scalability and overall compliance with minimal manual interference. Now, we also spoke briefly about infrastructure as code yesterday, but we didn't really go deep into it. So let's just have a more advanced discussion here. We're not going too deep because, I mean, you just need to know the basics for the exam and for your daily activities, right? But what exactly is infrastructure as code? Pardon me. Now, infrastructure as code is the ability to manage your infrastructure using code rather than manual processes and settings, right? So I want to spin up an application load balancer in AWS. I log into the console, go to application load balancer, create the targets, create my policies, apply security groups to protect the instance, and stuff like that, right? Place it in a subnet and apply network access lists to protect that subnet, right? With infrastructure as code, right, I just need to write a code, right, using any programming language, Python, for example, and then I define all these characteristics, saying in order to spin up an application load balancer, use this security group, permit traffic from 192.168.10.1 to this, right? For the access list, deploy it in subnet 10.0.0. So I have all this in code, and then it's a code template I have that I can push out at any point in time to create the same version of application load balancer that I want. So if another administrator we are doing this manually, setting up an application load balancer, he could alter some settings, based on his own understanding of the infrastructure, which will not give you a baseline configuration for all application load balancers in your organization. But if you have it in code, you can always deploy and reuse the same code at all points in time. So it uses a coding language, right, to automate the provisioning of IT infrastructure, right? So it prevents that manual work from IT administrators. So you see DevOps teams and DevSecOps teams employ infrastructure as code a lot because they're always pushing new applications and new solutions regularly. So they need something to make their life easier. They don't want to be logging into the console to create Lambda functions and the rest of them. If you have it in code, just push it to the cloud and you're good to go. Now, how does infrastructure as code work? Really, what is happening is that there are configuration files, right, which you define ahead of time. And then these configuration files will be read by software. And then the software will use the files instructions to define and configure infrastructure. So in that scenario I gave you earlier about the application load balancer, you have the configuration file that says deploy this application load balancer with these characteristics, right? And then you have a software picking that configuration file and reading it and deploying it through code to the infrastructure. Now, a very important aspect of infrastructure as code is that when you need to make changes to an application, for example, in this case, the application load balancer, what it does is that it takes the baseline configuration for the application load balancer and then makes the changes on the baseline and deploys it, right? So it doesn't go and start to update and modify existing infrastructure, right? It takes the baseline, adds the changes to that baseline, and then deploy it. So this helps to maintain some consistency between deployments. It enables you to do what we call version tracking, right? Because you have an audit trail of the the changes that you have made on the baseline config at every point in time, right? So very useful to auditors. So infrastructure as code would basically comes in two types, right? There's the declarative approach and the imperative approach. In the declarative approach, you say, you tell the system, I want you to give me a web application firewall. I don't care how you do it. And then the system generates the code and deploys to the cloud. And you go in and log in to see if everything is cool. In the imperative approach, you actually define a sequence of activities or sequence of commands that the infrastructure will use to deploy this web application firewall. So you say deploy in region this, deploy with 2 gig of RAM, deploy with 500 gig hard disk space and stuff like that. That's the imperative approach. And common infrastructure as code tools that you would see organizations use Terraform, Ansible, and in AWS, CloudFormation. So CloudFormation is an infrastructure as code tool. So you might want to keep that at the back of your mind for the exam purposes. And now, why use infrastructure as code? Well, just like as we mentioned when we talked about the benefits of automation to the organization, it reduces IT cost because you're able to do more with less IT staff, right? So administrative overhead is reduced. It improves the availability of the IT systems because it eliminates those errors that are associated with human fatigue and when they are doing things manually, because you're doing things with a standard coding template now. It actually reduces amount of errors and helps to improve the availability of your IT systems. It provides an opportunity for you to have configuration management, and configuration management is basically having the same configuration baseline for all your devices. So, for example, if you want a baseline of AES 256 encryption for your S3 buckets, right? You can use infrastructure as code to apply this, as opposed to when the S3 buckets are being built manually by cloud administrators or cloud engineers who could alter that encryption algorithm, right? So it helps to give you that consistent configuration across your IT infrastructure, which will help to mitigate risk of different personnel manually deploying configurations. And then it helps with accountability as well, because there's version control. You can always go back in time to see what has been deployed in your organization, and it could help you make more informed decisions. And these are opposed to when administrators are going in and doing things manually. So I could go in and set a banner saying, this is Go Cloud Carriers, please do not enter. And then there's a scan that the IT security team does weekly. And the scan picks up that banner on that device and say, no, this is not our standard template. If I see that information ahead of time, I could go quickly into the system and change it back, right? And put the correct template. But because there's no version control, right, it will be an argument between myself and the security team that, no, I did the right thing. Your scan must be faulty, right? If you have version control in place, you just go and look at the last version of code that was deployed to create that banner of that device and tell you if it was configured correctly or not. So these are some of the reasons why we would want to use infrastructure as code. So it gives you that documentation control, because for each code that's been deployed, you have a version that it saves, right? It can help you in your documentation. When so there are different types of auditing, right? So there's a type of auditing, SOC 1 type 1 reports, where the auditor comes in and just asks for your configurations and then goes through it without actually verifying, right? So it says, okay, these are in place. And there's another type of reports whereby the auditor comes in and actually does some tests on your system to see if you're running standard configuration templates. So if you have infrastructure in place, infrastructure as code in place, because you have all these version control templates available, you can hand them over to the auditor as your documentation for your network operations. So these are some of the reasons why we would want to use network automation using infrastructure as code. Can pause now for some questions if you have any before we go on to the next content.
Welcome back, everyone. Does anyone have any questions? Either on what I had covered this afternoon or what Benedict had just covered. So name not found. What's the best way to get more competent with the CLI, especially for someone who hasn't used it before? So name not found. The first thing I'm going to say is let's first figure out what career you want. And here's the reason I see it. I find a lot of architects who will never touch the technology in their career really want to get hands-on, and they work so hard to get hands-on that they don't learn how to design the systems or how the systems work. So let's first just make sure that's the case. Everybody should probably learn how to configure it. The question is, how much time and where you focus your effort really is going to be determined on your goals. So assuming you want to be a cloud network engineer or a cloud engineer where you're going to be in a hands-on position, best way to get used to it is literally to go build stuff. So take a problem, go build it, do it via the CLI. When it doesn't work, go debug it, go troubleshoot it, and you'll learn it. But the more time you spend on that CLI, you'll get there. And try to do as much as you can with the CLI. So for example, I think you're in Egypt. I don't know if I picked that up correctly. So, if you were to go to Greece, which is pretty darn close to Egypt, You know, when you were to live in Greece for 6 months, chances are you'd learn Greek. Likewise, if you take a Greek person like me and you send them to Egypt, we're probably going to speak Arabic after about 6 months because we're immersed in it. And the key is the more you get immersed in the CLI, the more you will pick it up and it will be more of a natural language to you. So, you know, that's one of the reasons at CCIE Labs, people spend all this time configuring things. The job is knowing what to configure, not how to configure it. That's the easy piece. But we have to be fast when we have to configure them. So that's why we spend all those times in the labs configuring, and that'll get you real good at there. Let's go to the next question. Do solution architects need to script? In a normal solution architect role, you'll not be allowed to touch the technology. You will be meeting with clients, you will be asking about their business, you will be facilitating meetings, managing vendors, managing stakeholders, negotiating with vendors, negotiating with stakeholders, leading large teams, getting buy-in, delivering presentations and sales, and you will not be allowed to touch the technology in a real traditional architecture role. Now, there are some people that have engineering roles with an architect title. And in those roles, they might actually need to do engineering things, but they're not really working as architects, they're working as engineers. But as a rule, architects are not a hands-on position. Now, here's the thing, Sonny, you know what? This Thursday, we're gonna have a How to Get Your First Cloud Architect Job webinar. My team will pop in the link. We'll cover everything that we do as cloud architects and solution architects, what our job is like, the specific skills we need, because they're different skills as architects than in these certifications. And we'll do it live, and you can ask me questions live. I can interview you live. We can do anything we can. It's completely free. And this next week, it's going to be me and another major cloud leader that's going to be on there as well to join me. Cantor Grant, do you recommend architects advertise their cloud provider badges and other stuff that shows I did consume some courses, and why? Cantor Grant, I do like my architects to have some badges, some, but not too many, and we have to be careful why. When you take too many AWS training things, you get biased towards AWS products and services, and that makes you really a bad architect. Why? Because if you're too biased towards AWS, you'll ignore all the other things you can do for your clients. If you have too many Google badges, again, it's going to make you biased towards Google. So yes, typically speaking, about 3 good certifications for an architect is good. A nice architecture certification, potentially a TOGAF certification, a cloud provider solution architect certification like the Azure Solutions Architect Expert, Google Professional Cloud Architect, or the AWS Solutions Architect Professional, and potentially one other certification like a CISSP for security. So yes, we do want to show some certifications because certifications build our brand and it makes us look good like we've done the work, which is wonderful. The problem is all of these certifications are geared towards the name of something and how to configure it, which are more based on building or systems administration roles. And when we're an architect, we're an executive that's going to be a strategy consultant to our clients. So if we have 100 certifications, we look like a hands-on techie and not an executive strategy consultant, and we can potentially damage our brand. We'll cover that actually in the free webinar as well. So it's about getting just enough certifications to get that entry in the door and not so many that you get perceived as the techie when you need to be seen as the business executive. It's a great question. Okay, so I can do 1 or 2 of these things here. And I'll do the next one from Cantor, and then we'll go back to the content. So should I advertise certification, but not the small stuff you do with them? Advertise the big ones. So I'd put my CCIE, I'd put my Google Professional Cloud Architect there, and I may put a TOGAF. I'm not going to put a Solutions Architect Associate if I have a Solutions Architect Professional. I'm not going to put a Cloud Practitioner if I've got a Solutions Architect Professional. Only the big ones. And when you get super high in your career and you reach executive architect levels, My manager asked me to remove the CCIE and he removed the CISSP because at that level, we need to be seen as more strategy consultants than tech professionals. But for the majority of you that are taking your first architect job, senior architect before you move into principal architect roles, we want 2 to 3 really good certifications on the resume. It will help you stand out. So, and Sunday, I would love to answer your question here, but the issue is, to prepare you for an security architect interview, that typically takes me about 8 to 12 months to prepare someone for a security architect role. Not something where I'll give you just a couple tips and you'd be successful. If I could, believe me, I would. I really wish I could, but I don't know what they're going to ask you, and I don't know what you know, and I just can't summarize, 800-900 hours of training inside of 5 minutes. I wish I could, because believe me, I would do it. All right. If you're here and you haven't gotten the labs yet, please register for the labs. Want to make sure you have access to everything. And because we've got 2 full days of good tech training that I want you to get in addition to these 3 full days that we had here. Let me know you're awake by giving me a hashtag AWS Advanced Networking. If you haven't liked the video, there's 57 of you. I don't know how many likes there are so far. And I know lots of people come on and off. Maybe give it a like. Signal the algorithm so this free training can make it to more people. Okay, so we are going to get to the content. And as a reminder, I will do next week a How to Get Your First Cloud Architect Job webinar, and it will be live on Zoom. And you can literally go and ask me anything. And I've gotten architects hired at Apple, at Amazon, at Cisco, at Google, at IBM, Accenture, Deloitte, KPMG, Capgemini, PricewaterhouseCoopers, JP Morgan Chase, Barclays Bank, and I will help you on this free webinar. Okay, so I am going to come back and I'm going to talk a little bit about securing your VPC. And I love security, spend a lot of time in security. So we're going to go over some basic principles, and maybe I'll whiteboard it out for you to kind of help. And this will probably help with that security interview tomorrow anyway, to some degree. So the first thing we want to do is keep unwanted traffic out, okay? If the traffic can't hit you, it can hurt you. Kind of like a boxer. If they can't get hit, they don't get hurt. So what we're going to do is we're going to try and protect our systems with DDoS. And then we're going to protect our subnets with access control lists. We're going to protect our hosts with security groups. And then we're going to try and use some host-based firewalls and IDS, IPS systems. So let me kind of map that out for you, live in real time, so you can sort of see what it actually is going to feel like. So let's look at it this way. Bear with me a second. I'll create a whiteboard and we'll work on it together. So let's say this entire thing is your VPC. This is everything that you own in your virtual private data center. And in your virtual private data center, you're going to create multiple subnets. We'll make them different colors. So this is going to be subnet 1. Let's make this subnet. Oh, that's not going to work. Let me undo that. That'll be subnet 1. Over here, we'll have subnet 2. Let's make this another color. Now, there's this guy on my team, Alonzo, where he can make things look beautiful with colors. I wish I had half of his skill. Great guy also. But subnet 3 over here. So bear with me and my graphics. And then we'll have subnet 4. Yellow looks like a happy color. So let's assume this is the edge of our systems before we'd go to the outside world. We're going to put a firewall and protect the organization from the outside world anytime it needs to connect to anything else. So we can do that. Now, if it had been a web application, which we'd have a demilitarized zone architected, which is beyond the scope of a certification. But let's just say for the arguments that you've got a CDN out here. You want to put your DDoS protection on your CDN, whoever CDN you're using, and there's a lot of CDNs. On your firewall, ideally, it's a next generation firewall, something that's got some intrusion detection, intrusion prevention, what have you. Now, we want to protect these subnets, right? And that's where you're going to put in your security group. I'm sorry, you're going to put in your network access control list that are going to protect each subnet. And you can have sub ACLs in between your subnets, so that's going to protect your subnets. Now, inside of these subnets, we're going to have servers. So let's pop a different color server in here. Yeah, we'll have a server over here, and another server in here that sits in the subnet, and another server which sits here in the subnet, and we've got some more servers. So as you can see, we've got some servers in the subnet. We want to protect those servers too. So we can protect those servers, entry and exit of those servers and many of our services with a security group. And then if we want to be really smart, and if it matters in security, we will be, we're going to take these servers themselves and we're going to put a host-based firewall on them. In that way, in case the organization's firewall, the network access control list, and the security groups fail, we're going to have another firewall on them. We're going to have some host-based IDS, IPS systems to stop an attack if it notices an anomaly is going on. We're going to put on some anti-malware software for worms, viruses, ransomware, or what have you. And we're going to harden these operating systems down. Now we've got some control over who's allowed to access what information, right? We can determine what you're allowed. What are you allowed? What are you author? Who are you? So who are you? And that's going to be your authentication. What are you allowed to do? That's going to be your authorization. And then we're going to be, what did you do? And that's going to be your accounting. And that's really what you're going to get from IAM. Now, in an enterprise environment, this stuff is realistically going to be sitting on Microsoft Active Directory. And what you'll do is you'll take your AWS IAM and you'll federate it with Microsoft Active Directory. And that way, all the enterprise's directory information, who's allowed to access what did you do? Well, they'll all be stored in a central place. So you can see what we did here in this environment. On a content delivery network, we put Shield. Our firewalls, hopefully are next generation firewalls. And there's going to be some specifics on how you would have to do that. We're going to protect our subnets with access list. We're going to protect our instances or hosts or load balancers with security groups. And then we're going to protect our endpoints. And then the last thing to talk about is routing from a security perspective. If you can't route it, if you don't have a route to it, you can't reach it. So when we connect our data center to the cloud, does the cloud necessarily need to access every subnet in our data center? If the answer is no, don't provide access to it, because if you can't provide access to it, it can't be hacked. So we're going to only advertise the necessary routes. In the data center, we can do multiple VLANs. In the cloud, if we need to isolate our organizations, we can place them in multiple virtual private clouds and route between them. So kind of think about some of these guidelines as it pertains to security. So lots of great firewalls that are out there. We talked a little bit about it. We talked about Shield, and we talked about AWS Shield and how you have the Shield and Shield Advanced for DDoS protection. We talked about network access control lists to keep unwanted traffic out of your subnets. And we talked about how to structure your network access control lists yesterday. We talked about what a security group is, how it's effectively a stateful host-based firewall to protect your systems. And talked briefly about, well, I don't know if I mentioned network-based intrusion detection, intrusion prevention in the past. I mean, I sort of did. So our next generation firewalls have the ability to monitor patterns of behavior and look for things that look like an attack pattern and stop them. And that's network-based IDS, IPS systems, very robust. We've been using them for a while. But I mentioned host-based IDS, IPS system, and there's really speaking one of two ways these systems can occur. Typically, you put a little agent on the computer, and the agent will communicate with the network-based IDS IPS system. And if the IDS IPS system notices things from the network, it can stop it. But we can also put host-based IDS IPS systems that will actually sit on the server and look for patterns of behavior that are anomalies on that server, and then be able to stop an attack on that server. So that's what we're talking about with regards to host-based IDS IPS systems. I talked about anti-malware protection. I hope it makes sense that you've got to take care of your worms, your viruses, that kind of thing. So I hope that kind of makes sense. And at this point, I think, actually, you know what? No, I'm going to tell you it's not Benedict's. So let's talk about security incident reporting and alerting. A security incident is going to be an event that occurred. It could be an event that actually started to occur and then you caught it and nothing happened. That's an incident. Or it could have been you've been hacked. So basically, anytime the confidentiality of the system, the integrity or the systems being what they're supposed to be, or the availability of the systems goes down, that's an incident. And incident reporting is really the process of documenting the details of a security incident so that organizations can track them, analyze them, and respond appropriately to an incident when it should occur. And a security incident alert is really going to be a notification which is sent to the responsible parties that a particular security incident or set of events has occurred. So how do we automate this? How are we going to automate our incident reporting? Well, the first step to really achieving any kind of robust reporting and alerting systems is by adequately collecting logs and collecting logs in the right place. Now, when we do our logging, we have lots of sources for logs, right? The VPC flow logs, which track the traffic through your VPC, whether your traffic's accepted or rejected. We talked about AWS config and what that's tracking. CloudTrail is your auditing. And of course, there's custom applications and servers that can also send logs. And you can send them to an external information system like a SIEM system, like Splunk, Rapid7, etc. Or you can send them to CloudWatch logs. And then once these logs are collected, they're going to be stored in a central location. And then we can use like CloudWatch logs or Config or GuardDuty or Insights or Amazon Athena or other tools to go look at these logs. You know, any type of business intelligence tool or visualization tool. So these are kind of some of the things we can do with regards to looking at things. Now, why are we going to do automated security and incident response reporting, and why is it so important? Well, you need to be able to respond to incidents quickly, because when something happens, you want to catch it, mitigate its impact, and then remediate it and respond to it as quickly as possible. But also, you know, what if you're a regulated industry? You're going to have an incident report and an audit report. And reality is in any industry, you're really going to need to. And we're going to need to make sure our security teams stay up to date with the evolving threat landscape. And it's going to improve our overall efficiency and response time. So, you know, kind of keep that in the back of your mind. That's realistically what we're going to be talking about and why we're going to do this. So I'll stop for a minute and see if anything popped up. And then Benedict is going to come back and start talking about network performance. Any questions for us? Does MS Entra replace Microsoft Active Directory? Cantor, is that what they call? Is that the new name of Microsoft Active Directory on the Azure cloud? I'm pretty sure. I forget, they have a new name for Microsoft Active Directory. Is federation the same as synchronization? No. So here's realistically speaking what federation is. Let's pretend that Benedict has a database of everything that of something. And I trust Benedict. So if you went to me to log in. And I said, let me check with Benedict because I trust Benedict. And then Benedict tells me, and then I say it's okay. That's kind of federation. So you can think of federation as, so let's say, have you ever logged into a website and they say log in with your Facebook account or your LinkedIn account or your Amazon account? What's going on is the company you're dealing with is then connecting to, say, Amazon or Facebook or Google, and they're saying, do you recognize this user? Could you give me this user's credentials? And then they get sent back to us and we trust them. So that's federation. Yeah, so that is, so if that's the new version of active AD in the cloud. But, you know, we always have to think of what's going to be surviving what and how we're going to be using it across clouds. Let's go to the next one. How does the firewall protect against known patterns? There is something called signature patterns that exist. And basically, signatures are what an attack actually looks like and how it actually occurs. So it kind of works the way the human body does. If I get infected with a particular virus, my immune system will see the virus, it will build up an antibody to the virus, and I'll be protected from getting that virus, in most cases, ever again for the rest of my life, because my body will develop a signature match to it. Now, in the world of attacks, in the world of viruses, we've got software that's trained to actually that look for a pattern that it knows. And we create what's called a signature for it. And then again, anytime it sees the signature, it knows how to defeat it. That is against a known attack. It's based upon a signature. It's kind of like this. It's kind of like if you're a martial artist and somebody keeps coming at you with a hook punch and you just know how to block that hook punch with the right kind of defense, and you're not going to get hit. So that's a known pattern. But all of a sudden that boxer's coming at you with a hook, and they don't come at you with a hook, they come at you with an uppercut, and you don't know how to block an uppercut, and you get hit. But then once you learn how to block that uppercut, you can block now the hook, you know how to block the uppercut. That's kind of what we're dealing with here. Sorry, there's some boxers and martial artists on this on this instructor panel. Good questions.
Cantor Grant is saying, but the Azure service in the cloud completely replaces the Microsoft Active Directory organization used to have in their data center. Not entirely. I mean, you could synchronize your AD on-prem with the Azure Active Directory service in Azure. It's not a complete replacement.
Yeah. And architecturally, I think about this. What if you just completely trusted on the Azure Cloud's directory services for authentication? And you have your own data center, and you also have systems in the Google Cloud. And then the whole Microsoft Cloud goes down. And everything you have that determines who's allowed to access what is now down. Effectively, your Google Cloud and your data center would be down too. So we have to be careful where we choose to architecturally put these services and where we want to spread them. And whether that fully managed thing that's so convenient, because, oh, that's really great, we don't have to think about it, is really the right thing or not for us. Oh, Benedict, am I next or are you next?
I think you're next.
Okay. Sounds good. Then that works okay too. So, how does the firewall protect against unknown patterns? Okay, so now not all firewalls can do this. Firewalls use something called heuristics, and now they're using pattern matching and artificial intelligence, and they look for things that are normal. Benedict, when was the last time you left your house in Canada, decided to go to Paris, Abu Dhabi, stop in Lagos, and then go to Cape Town all in the same week?
Never.
Right. Now, would it be normal to assume that you're going to do this in a normal week?
Nope.
And so the firewall is doing the same pattern matching that your credit card company is. Benedict goes and buys a ticket to London. He's got no problem. It's a normal thing that a person might do. While he's in London, 3 days later, he goes to Paris. Again, it's probably fine. Now, when he goes to Abu Dhabi, which is a beautiful place, I haven't been there a long time, but a very beautiful place. Now, it's not normal for him to be in 3 continents or 3 parts of the world inside of 1 week for Benedict. And that credit card company will flag it. And his credit cards will be shut off, and I'll have to call the credit card company. Oh, sure, we're on a trip. Yeah, we'll open it up for you. Thanks for letting us know. Now Benedict gets a job as an executive architect, and Benedict's that good, he will get one of these executive architect jobs. And now Benedict needs to go all over the world. He starts his day in Canada, then he's in London, then he's in Dubai, then he's in Cape Town, then he's in Sydney, then he's in Hong Kong. And guess what? Now it's normal the credit card company learns that behavior. And that's the way these systems work. They look for those patterns. Okay, these were great questions, and I'm glad you asked them. It took me a minute to recognize one question from another because they were so similar, but they were great questions. Okay, so let's talk a little bit about network performance. I love network performance. So we'll begin talking about networking. Now, no matter what you do to your system, if the network does not have sufficient bandwidth, things are going to fall apart. If there's too much latency on the systems can and will fall apart. And I will tell you that in the last 25 years of being a network architect, most of my time was spent redesigning networks that were not designed to meet an organization's needs. Nearly every network that I ever saw had routing protocol problems because people did not either understand the IP addressing piece or they didn't understand the routing protocols well enough and how to tune them and how to optimize them. Now, the good news is when you're on AWS, most of the network is managed for you, most of it. And because it's managed for you, they typically have very good network engineers. So a lot of the traditional networking problems we see aren't going to be as bad on the cloud. Plenty will be, but some of them will not be. So keep that in the back of your mind. And when it comes down, let's talk about some network performance metrics and reachability constraints. Network performance is basically the analysis and a review of the performance of the network through the eyes of the user. In order to measure network performance, we need to be able to define metrics that would be employed. Networking metrics are going to be quantifiable. How many milliseconds of latency? What % of packet loss do we have? What type of throughput are we achieving on these lengths that we need to be looking at? So think of bandwidth, speed, packet loss, those types of things. Now, we can have a lot of networking problems. If we don't have a route to it, we can't reach it, and then all of a sudden someone calls and say, I can't access this server. That's easy. But we may have other problems. We can have problems related to latency, jitter, insufficient bandwidth, and packet loss. So let's talk about latency. Latency is how long it takes to go from point A to point B. And if I am sitting in my house in Florida, it may take me several milliseconds of latency to reach something in Japan. Several milliseconds may feel like an eternity in damaged user experience. But what if the routing's not so great? We have one of the members of our staff, he's an incredible guy. His name is Eddie. He lives in Bamenda, Cameroon. It took him about 12 hops just to get to the internet. And we're to almost 10 milliseconds of latency before he even reached the internet, before he got off of his internet service provider's network. A lot of applications would struggle under the type of latency he had, especially real-time applications. So the point is we need to understand, latency, how long it takes to go from point A to point B. Most of this time is based on either sending electrons on a physical cable or photons or pieces of light on a fiber optic connection. One way that you can sort of check your latency is by just generally sending a ping. And what a ping is an ICMP echo message that goes to the server and then a reply. So you gotta have to divide that by 2 to try and figure out what's going on. And in a good line, your latency is going to be fairly consistent. So here's a ping that I actually took when off of my network to Amazon. And you can see I've got a really good network here. You can see my first, second, all the ICMP messages I sent, 27, I got them back, so no packet loss. You can see that the TTL, which starts at 255 and gets degraded by every router, is 231 each time. So I took the same symmetric routing hop each time. And you can look at my latency. It's fairly specific, consistent. 20 milliseconds, 20 milliseconds, 20 milliseconds, 20 milliseconds, pretty much the same. So this is what a good line would look like. But a bad line could look a little different. A bad line may have something called jitter, which we'll talk about in a minute. But imagine this latency was 20 milliseconds, and this one was 5 milliseconds, and then the next one beneath it was 50 milliseconds, and then the next one was 100 milliseconds, and then 5 milliseconds, and then 10 milliseconds. Jitter is a disaster on voice and video, and jitter is really just variations in latency. But also consider, what if, for example, the first packet, sequence 1 came back, and then I lost, sequence 0 came back, and then sequence 1 came back, but I lost 2 and 3, and then I got 5, 6, 7, and I was losing some. That would indicate packet loss, which would again be a bad thing. So kind of keep about that. So it's one of the very simple elemental things you can do from any router switch, pretty much any server where you're at. So you're gonna have to look at what your latency is, and latency is gonna vary. Here's a screen grab I took off of my firewall, or the management dashboard from my firewall. You can see what my standard uplink traffic was. You can see it was at a time I wasn't really using much traffic at all. And you could see the latency of my link was pretty consistent, and I had nearly 0 packet loss when I ran this test. Okay, so now let's talk about jitter. As I mentioned before, jitter is variations in latency. So slow, fast, slow, fast, slow, fast, 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 slow. And that causes out of order packet delivery. Because if packets 1 and 2 were sent at 5 milliseconds, and packets 3 and 4 were sent at 100 milliseconds, it took 100 milliseconds, but 4 through 50 got there in 10 milliseconds, you can see that we're going to have out of order packet. So that can wreak havoc on a video stream. Generally speaking, if latency is consistent, it's typically not too much of a problem. Well, some applications it is and some it isn't. But when there's variations in latency, that gets bad. You're watching a video and all of a sudden you've got some jitter and you get that squares pixelization on your screen. That's typically where it's coming from. Now, here's what I did. This was a little more fun. I took my Mac Pro and I opened up a terminal window. Look at this. What I did is, instead of sending my internet data out my internet connection, I used my 5G mobile phone. Now look at this. Look at this difference in latency. Not 20 milliseconds, 62 milliseconds, 59 milliseconds, that's icky. 68 milliseconds, 47 milliseconds, 76 milliseconds, 92 milliseconds, 63 milliseconds. Anybody see a problem with that? I've got a lot of variations in jitter, and this is not good for any kind of voice or video. I also lost a little bit of data along the way. If you note, there's 3% packet loss. Let's see where we lost it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, 11, 12, 13, 14, 15, 16, 20. I don't see where I missed it, but I'm sure I missed one of these packets along the way. If I'd stare at it long enough, but live I can't catch it. But so we missed one packet along the way. So now let's think about the link speed. We need to know how much speed we need, and that's going to be related to the speed. Typically speaking, we're going to have a gigabit per second links. We're going to have 10 gigabit per second links, which are moderately fast links in today's world. we're going to have 100 gigabit per second links, which are going to be very fast wide area network links. And on a dedicated connection, if we buy one of these things, we're going to get about 90% of the speed. The reason I say 90 is the overhead of the TCP headers, that kind of thing, Ethernet framing, those kind of things. And the protocol will also determine, for example, TCP headers and SYNs and ACKs going back and forth takes up more bandwidth than actually UDP, just send it and hope the receiver gets it. So the protocol used will also determine the type of speeds that you're going to deal with. As I mentioned earlier, I mentioned the TCP sliding window, and keep track of this. And this is going to go into some of the things that Mo talked about earlier when he talked about congestion avoidance, and he talked about weighted random early, what do you call it? Weighted red. Can't remember what the acronym means because I was taught it as weighted red. All things, but realistically speaking, this is the way TCP is going to actually set up a connection, and this takes overhead. So if I've got someone that wants to receive something, I have to open up a connection over here, and I just have to say, open a connection, and then they have to acknowledge the connection, and then they have to open up a connection on the other side, which then gets acknowledged. So it's that three-way handshake. I actually don't like this picture. Let me try to do it in a manner that I think will help a little better than the picture that I put over there. So here's the server, and here's the user. User wants to open a connection on the server. So what it does is it sends a SYN, synchronize, open a connection on the server. The server, because it's a connection-oriented protocol, will then acknowledge that. I acknowledge that I received your SYN. Oops. I've acknowledged I've seen your SYN, and it's going to come out like it's going to send that. Ugh. It's going to send this back, and then it's going to say, but I also want to open a connection with you. So then these two messages will be sent back to the person that wants to receive it. Now at this point, the SYN, or the open message, was sent initially from the receiver to the sender. The sender then acknowledged the message, and then synchronized by send a message back. And the last message that needs to occur is the acknowledge needs to go to the server. And now these two are allowed to actually exchange information. That's the three-way handshake. And the sliding window, which we talked about, is the way this will also work. Is the first time after we've had this set, this let's say user is going to send a file to a server. So the user sends one message, and the server says, "Got your message." Now at this point, the user is going to send two messages. Why? Because this is the way TCP flow control works. So it's going to send two messages to the server, and when the server acknowledges it and says, "I've got it," what's ultimately going to happen is this time, now we're going to get, let's bring it back. Now 4 messages are going to go to the server, and they're going to be sent to the server. And assuming the server got it, the server will acknowledge it. And then 8 messages will be sent to the server. I'm just going to use 3 at this point. So now 8 will be sent. And if the server doesn't get it, this process will begin all over again until they find exactly how many messages can be sent without losing data, otherwise known as packet loss. So that was the next thing that I was going to get into. What is packet loss? Packet loss is when we lose data over a network. And typically speaking, we lose data because either there's a problem with the fiber optic connection, meaning it's not perfectly shiny or sharp, or we're losing it because there's a problem with the data link layer, maybe an imperfect card, or there's too much congestion on the line. Any of those things can cause us to have degraded network performance. Let's talk about another place where we can have degraded network performance. Oversubscription. Inside of my network, for the most part, I create as many networking speed, I use as many links as I need. But let's talk about what oversubscription is. Oversubscription can give us poor performance in the cloud computing, and oversubscription can give us poor performance on internet. The way the world works is, typically speaking, not everybody uses everything at the same time. So when a cloud provider is going to build their network, or an internet service provider were to build their network, if they had 1 million customers and each customer had a gigabit connection, it is unlikely that all 1 million customers would ultimately be using 100% of their gigabit connection at the same time. So what companies do is oversubscribe. So instead of having the total capacity of 1 million times 1 gigabit per second, the service provider will typically assume that 10% of their users are using their systems full time, all of the time. And they can basically build capacity for about 1/10 of what everyone is. And that's why internet bandwidth cannot be guaranteed, because all the internet service providers oversubscribe or sell more capacity than they have. Airplanes do it all the time. You show up in the airport and they're offering you money not to board the plane because they sold more seats to the plane than the plane had seats available because they knew some people wouldn't show up. Well, that's oversubscription. But this could cause a performance problem if everybody uses their traffic all at the same time and the internet service provider or the cloud provider does not have sufficient capacity. So kind of keep this in the back of your mind. You have no control once you get on the internet. And if you're using VPNs to connect to the cloud, now you know why you can't actually guarantee them. So let's talk about some other ways we can improve our network performance in AWS. So the further your stuff is from each other, the slower the performance. The closer it is, the better the performance is going to be, all things being equal. And when we're dealing with high performance computing, sometimes you want to get stuff closer to each other to reduce the latency. And that will get us closer together. I may have to sneeze, bear with me if I do. Okay, that's what happens when you love cats and you're allergic to cats, but a cat sleeps on your head every single day. You have a little bit of allergies. But as we were discussing, when you put your things closer to each other, they typically have better performance. So inside of Amazon, they give us the ability to put our stuff or our servers closer to each other. And they came up with a concept called the placement group. And all a placement group is where you're going to group your virtual machines. And that by doing so, you can determine what the latency is and you can plan around it. So if you've got a high performance computing workload, where you put your system can be very important. So let's talk about the options we have. The highest performance option is something called a clustered placement group. And what is a clustered placement group? Well, pretty much you put all your instances as close as possible, which has got its benefits, but it's also got its risks. In many cases, a clustered placement group could have all your virtual machines in the same server. Well, what happens if the server fails completely, like a hardware fire? You got a problem. Often in a clustered placement group, all your virtual machines are in the same rack. You don't get any better performance than in the same server or in the same rack, but if the power distribution for the rack goes down, poof, the whole rack can be dead from a power perspective. So cluster placement groups, really great performance. But understand in the back of your mind, if all your things are that close to each other, there's a good opportunity for things to go wrong. So here you have a visual example of a clustered placement group. In this particular use case, we've got all of our virtual machines all sitting in the same rack, all in a single availability zone. And by doing it that way, what you can see is we've got really great performance, but there's a whole lot of stuff that can go wrong. So what if we can tolerate slightly lower performance and we don't want to be in such a risk of having everything in the same rack or the same server? Well, this brings us to the point where we can do something called a partition placement group. And what is this? Here we can spread our virtual machines and our stuff across a few racks, often in the same data center. But now, instead of everything being in the same rack, it could be in the same building. Well, the reality is when you're in the same building, that's still a local area connection, you're still going to get very low latency. And now if you've got a power failure in a rack, it doesn't matter. If the switch port where the 1 or 2 servers were in that same rack were to go bad, you've got some redundancy here. So much less risk. And you're still going to get some excellent performance with less single points of failure than with the cluster placement group. And this is typically a very good option for high performance. And you can see what it looks like here. You've got virtual machines sitting on servers that are inside of 3 racks, all in the same data center, otherwise known as availability zone. And that is your partition placement group. Good performance spread across a couple of racks. Now, what if you still need relatively decent performance, but now you need a higher availability system? You still want to spread your load across hardware. And you want to spread it in a canal across racks, servers, power distribution units, but now maybe you want to split it across a data center. And if you're in a region and you've got multiple data centers, with a mile or 2 of each other, that's pretty low latency. Even if it's 5 or 10 miles from each other, that's still relatively low latency. So that's where we bring into the spread placement group. And a spread placement group is putting your virtual machines across a couple of data centers. And by doing so, you've got a lot of more protection from any kind of challenge or damage there. So let's look about what we're talking about here. So here in the spread placement group, we've placed our virtual machines in 2 different racks in availability zone 1 or data center 1, and then 3 different racks in data center 2 or availability zone 2. That's a spread placement group. This is going to give us very good performance, and it will also give us a lot better in terms of availability. Not as good a performance as with regards to a partition placement group or a cluster placement group, but much better availability. And now you know exactly where you can choose from. I want to talk about 2 more higher performance options. So anytime we talk about an EC2 instance or a virtual machine in VMware or a virtual machine in KVM or QEMU or an Azure virtual machine or a Google Compute Engine instance, it's the same thing. Basically, we've got our server, we've slapped the hypervisor on it, and now we have all software-based computers. Software-based BIOSes for the computers. Well, BIOS is always software. Software-based video cards, software-based network cards. Software. And here's the thing to remember about software. Software is slow. Software has to go to the CPU. Hardware is fast. So when the world's fastest routers, all the traffic forwarding is done, except for the first packet flow, is done in hardware, not software, because hardware or ASICs can do things much better. Now we enter the world of what kind of network support do we want in our virtual machines. And we can enter the world of hardware network cards or software network cards. So when we need a higher performance network interface, we have 2 choices. One will be something called single root IO virtualization, and the other will be called virtual fabric adapter, and I will talk about it. And I did not make the term single root IO virtualization. Here's what it means. You've got a virtual machine, you push through the PCI interface of the server, the network card into that virtual machine, and now you've got a hardware network card. Now you've got good network. For any of you that have an interest in machine learning and artificial intelligence, a lot of the computing is done on GPUs. Not all of it. It can be done on a TPU, a CPU, an ASIC, but a lot of it is done on GPUs. Now, when you're in cloud computing and you want to rent a server with a bunch of GPUs, does that mean it's a bare metal server and only you can access it? No, they're virtual servers. So the way we actually use GPU-enabled instances or GPU virtual machines is they physically push through the PCI interface a GPU into the virtual machine. That's how you can have high graphics performance in a virtual machine, not software graphics performance. It's the same thing. It uses a technology called PCI pass-through to push a hardware card into a virtual machine. And that's now what single root IO virtualization is. hardware-based networking in your software-based virtual machine. Now, while we're at it, AWS actually made a very high-speed software-based network adapter and driver that can offer very high performance, up to 400 gigabits per second. At least that's what the spec is designed for, though we've not gotten there yet. I think we've reached the end of my content, and Benedict is going to have some more things to discuss with you very soon. So let's come back. Let's see if you've got any type of questions before we go to the next one, and then we'll get to the next content. I know Benedict's got a lot of great things to talk about. Okay, do you have any questions for us? And yes, thank you, Cantor. I was definitely sneezing there. Cantor Grant, I wish you could smash that like button a million times. That would be so nice, and I so appreciate it. This content, and you guys are awesome. Thank you, Cantor Grant. We work very hard to try and make sure we can provide as much training as we can for the community, and I'm very grateful for your comment. Who's next?
I believe I am next.
Okay.
Or you mean a question?
So yeah, I actually meant that next, but yeah. So is an availability set in Azure the same as a cluster placement group? I don't believe so. I believe in availability set, and I actually have to keep track. Hold on, I can tell you what it is if I just look at the name of it. I'm pretty sure it's a set of virtual machines that one takes over after another. Yeah, no, availability sets are groupings of virtual machines to reduce the chance of something being brought down.
So it's like the cluster set or whatever.
Yes. And it can do it in they typically put it in fault domains. So the cluster placement groups are automatically trying to find a way to bring it closer together in some way to reduce performance. And an availability set is more spreading them apart, farther apart for availability. Okay, so Benedict, over to you.
Thanks, Mike. All right, so following off from where Mike stopped, let's look at some more techniques you can use to improve network performance in the cloud. So he spoke about using the fabric adapter interface. So the kind of network interfaces you use for your instances also goes a long way in determining how fast that communication can happen with those instances, right? So we have an elastic network adapter. It's a type of interface that you could deploy for EC2 instances. And it has a high performance in the sense that it gives you up to 100 gigs throughput, right? So that's something you might want to keep at the back of your mind when trying to determine the network interface to use for a critical device that needs, high throughput, right? Of course, he also spoke about the elastic fabric adapter, which provides ultra low latency and high bandwidth communication between instances in a clustered environment. Now, there's another technique that we can use to improve performance of the network in the cloud. And it's a technique that we also use on Prime, but one that you can explore if you're looking for a solution to improve the network performance in the cloud. And that is using caching and compression. So what exactly are these terms? Now, compression is a process of reducing the size of data, right? So, for example, you have a video that is 2 gig, right? You can compress it and reduce the size to 1 gig. Of course, the graphics will be reduced, but if you do not mind reduction of the graphics and your priority is just to improve the flow of that video over your infrastructure, then you can employ caching as a technique to improve network performance. So when you you can employ compression, right, to improve network performance. So when you compress a file, right, the bandwidth and storage requirements are reduced for that file. So it reduces the time it takes for the file to be transmitted over the cloud. The second term there, caching. I know we spoke about caching when we talked about the content delivery network. So it's the process of storing frequently accessed data in a fast and convenient location, typically at the edge of your network. So if there's a frequently accessed data, right, from your database servers, right, you don't want requests from end users traversing your cloud infrastructure all the time to get that same information, right? You can put it at your edge, and it saves the bandwidth for your internal communication. So we typically use caching for static content, right? If you have content that is rapidly changing, for example, you have Amazon, right, .com, and people going to purchase items from different merchants. So a merchant might update the price of an item, right, on his website. And if that information is cached, it means the end user will not get the real-time data, the current price, right? So you don't want to cache that kind of information. So we have to be careful when we're planning our caching and compression strategies. Now, in order to accurately evaluate the impact of the compression and caching on network performance, you should be able to measure key metrics like Mike mentioned, latency, jitter, and the rest of them. So you measure before you compress and cache, and then after compressing and caching, you measure again to see the effect of your caching and compression strategy. So it helps you to, it's like a workaround to improve the network performance in your cloud infrastructure. Now let's talk about network topology mapping, right? And it also could be overlooked sometimes, but it's an important part of the network architecture to have basically a network diagram. So a network topology just describes the physical and logical configuration of nodes, right, in a network, right? The topology mapping now is representing all these nodes in a graphical or pictorial format, right? So you want to have that overview, graphical or pictorial overview of all the nodes in your cloud infrastructure. And why is it important? So you can see where there are potential bottlenecks in your infrastructure and then make corrections to improve the network performance, right? And in AWS, we have the AWS Network Manager that you can use to perform this topology mapping as observed on their topology graph page. So it's pretty important that you have that pictorial overview of your network, right? So on-prem, we have various solutions that can, draw that graph of your network and give you an idea of what's going on. OP Manager is one of them. You have the Cisco Network Assistant, Manage Engine, And of course, you can use some of these solutions in the cloud. You just have to install the software on a virtual machine on an EC2 instance, and then use that to plot the map of your network. Now let's talk about the AWS Event Bridge, right? Event Bridge is a service that provides real-time access to data changes in AWS services, right? So you want to be aware of what is going on in your network. And Event Bridge is a solution that gives you that capability. So what's going on is that it's monitoring the services, and if there are changes, data changes in the services, then it alerts you so you can, monitor the network, right? So if you have an S3 bucket, for example, and someone goes there and deletes a file, right? Event Bridge can send you that information in real time, all right, that such file has been deleted, and you can go in there and make sure everything is working okay. So Event Bridge is also useful in that it allows you to build event-driven applications. Remember, we spoke about event-driven automation. So if this data is deleted, then what happens? Do this, right? So that service can help you to achieve that aim of having an event-driven network architecture. Now, there are some key features of the AWS Event Bridge. And one of that is events. And events are basically any real-time change in a system or environment or data. So going back to that example, if your file is deleted, that's an event, right? And then we have event sources, which are used to ingest events from applications into an AWS customer account. Then we have the event bus, which is like a virtual router that receives events and delivers them to destinations. We have rules, which are sets of instructions created and associated with an event bus to match certain events. And then we have the targets that process events and also can include AWS services such as Lambda functions and kinetic streams. So how exactly does Event Bridge work? So when your resources change state, they automatically send events to an event stream, right? And then you can create a set of rules that match selected events in the stream and then route them to additional targets to take action. So for example, if a file is deleted, you create a rule that if a file is deleted, then send this event to this target to restore the file, right? Send this event to this target to restore the file. That's a rule that you've created. And each rule is associated with an event bus, all right, so that it can work with delivering the events to the targets. And some of the benefits of the Event Bridge is that it helps to allow you build event-driven architectures, because real-time data changes is enabled. It has security features. It can integrate with AWS identity and access management services and the AWS key management services as well. And then you can filter events, allowing you to control what events to target. So you don't just want a flurry of events to trigger alerts, right? So you can be specific as to what you want to monitor with Event Bridge. So Event Bridge integrates with CloudWatch and AWS X-Ray, which we will look at later, making it to monitor and observe the performance of your events-driven applications. Now, there was a question on YouTube about how we can effectively carry out network troubleshooting, right? So we want to talk about network troubleshooting next. And when you are dealing with networks, there will always be problems, right? Things will always go wrong. You cannot have a network running smoothly for infinity, right? So when these issues happen on the network, we should be able to have a systematic approach to troubleshoot the network problem and fix them. So take, for example, your direct connection, right, from your office to the cloud, right? If there's a failure on that logical link from your office to the cloud, where do you start looking? Where do you start looking from? Recall there's a router in your data center, right, where your service provider will terminate the direct connection to the cloud. So you want to check the router. It's called the customer premises equipment router in your data center. You want to check with the service provider to see if they have any outage on their infrastructure. You want to look at the router and the switch ports in the direct connection location. Even if you don't have access to that location, you can work with your service provider to troubleshoot the devices there and isolate the problems. It could also be a configuration problem in the cloud. So, I mean, working from the customer end to the cloud helps you to build a systematic approach to network troubleshooting. So when you find where the communication is broken, you can easily fix it and get your connection back online. Now, generally, when performing network troubleshooting, we have different phases. And the first phase for most people will be to test for connectivity, right? So for example, if you have a website that is down, right, you want to see if the server that hosts that website is reachable, if it's still online. And we use the ICMP protocol to test for this connectivity, right? So you can use your ping requests or your trace routes, pinging from one location, your office location, to the server, or from an EC2 instance to the server IP address, right? So you start at that level, start with that connectivity test, right? Now, if you get a reply from the server, then you know that the problem is not with reachability to the server. What you want to check next is the DNS name, right? So the server is going to have a DNS name. www.bbc.com is tied to an IP address. So you've pinged the IP address of bbc.com, it's reachable. You want to ping the DNS name, ping bbc.com to see if it responds, right? This is the next level of troubleshooting. If you do not get a reply from the IP address or from the DNS name of that server, then you want to be looking at the subnet level or the router level, right? So the router is probably the default gateway of the server. So you want to check to see if that router is up and running and everything is fine. You want to see if other servers in that subnet are up and running. So you do a ping or traceroute test to other servers in that subnet to see if you get a response, right? Now, if you get a response from the router, then it means that the router is fine. You can now move on to the next phase of your troubleshooting. You log into the router and try to ping the server from the router, right? So you're moving your troubleshooting step now from closer to the server, right? You've tried remotely, you can't reach. Now you're trying from the server, which for trying from the router which is closer to the server, and to see if you can reach the server or if there's something blocking the server. Now, if you get a reply from the router to the server, then you know that your connection is probably broken from yourself to that router, and then you begin some extended troubleshooting on that leg of the network to see what the problem is. Now, if you can get to the router and the router cannot get to the server itself, it means there's a problem, probably from the server itself. So you want to log into the server and review the host-based firewall there to see if it's been configured to drop some traffic. You want to review the security group which protects that instance, that server, to see that all the inbound and outbound rules are correct. You also want to review the network access list attached to that subnet where the server is connected. Is it too restrictive, which is preventing this normal communication? Or is there a problem with CPU utilization on the server that it cannot respond to requests anymore? So these are some troubleshooting steps that you want to look into in the phase 1. Now, phase 2 of your network troubleshooting will be to identify where the traffic is stopping, right? Or where the traffic is getting lost. So we use the traceroute command, which also uses the ICMP protocol to carry out this function. So from your PC or from your instance or wherever you're doing the connectivity test from, you want to run a trace route to the IP address of the server, and then it will traverse multiple hubs and then stop at where the problem is, right? So if the problem is at a router in your network, you see that after it hits that router, it begins to not respond anymore, right? You don't see any hops after that. So you kind of figure out that is where the problem is coming from, and then you log into that device and continue your troubleshooting from there. Now, take note that with the ICMP protocol, there are many firewalls, right, that might be in the path of your connectivity to the server, and firewalls by default will drop the ICMP protocol except it is allowed otherwise. So it could be a red herring. If you see your traceroute dropping at an IP address, it might just be a firewall there that's dropping ICMP, and that might not actually be where the problem is coming from. Then we want to move on to phase 3 of the network troubleshooting. And that is where you actually isolate the issue. So you've done your trace route now and you've seen where it's dropping. It's dropping at a particular IP address, and you've identified that that IP address is a router. So you can then log into this router and then check the routes to the firewall, so the routes to the server, and see if there's a route allowing return traffic. Check if there's spanning tree loops and stuff like that. Spanning tree will be on a switch, but on a router, you want to look for routing loops and access lists that are too restrictive. So it's really beyond the scope of the AWS exam to go in depth into troubleshooting, but these are some basic steps you can take when troubleshooting your network. Of course, you want to use CloudWatch as well, right, to monitor activities going on with your instances and stuff like that. Now, another tool that is great for troubleshooting in AWS is what we call the route analyzer or the route analyzer, if you're British. It's a troubleshooting tool that we use to perform analysis of the routes in your transit gateway routing table. So take note of that. It looks for analysis of the routes in your transit gateway routing table. So if you have a transit gateway that is interconnecting your branches and your AWS infrastructure, you want to use the route analyzer to check for any connectivity problems if you can reach AWS from one of the offices. So how does it work? It actually looks at the routing path between a source and a destination. So a source should be a branch office and the destination will probably be the AWS infrastructure. So it analyzes that route, right? Looking at the path that the source you use to get to the destination, and then it will give you information about the connectivity between those components. So if you want to use the route analyzer, all you need to do is to specify the source and destination IP address. So the source IP will probably be an IP address in your office. Destination IP address will probably be a server in the cloud. You just specify that in the route analyzer, and then click run the route analyzer, and it will give you the results. So it's good for validating existing routing configurations and finding routing problems that could be disruptive to your transit gateway global network. Another important tool that is available for troubleshooting in the AWS cloud is the reachability analyzer. And this one now is a tool that is used to analyze the path between a source and a destination in the cloud, right? So if you have an instance if you're trying to verify connectivity between an instance and a database server in the cloud, you want to use the reachability analyzer to, simulate this traffic flow and see where the problem lies if there's no connectivity. So how does it work? It builds a model of the network configuration, and then it uses that model to check for reachability based on the configuration, right? So it's just looking at the configuration, and then once you put the source and destination, then it looks at your routing table, looks at the security groups, looks at the network access list, and it uses that information to determine whether there'll be reachability issues between that source and the destination, right? So you can specify source IP, destination IP, and port number, right? So if it's a web server, you can specify the IP address of the server and the port number. So it just filters your troubleshooting to HTTPS and ignores every other thing, right? Now, if there are multiple paths between a source and a destination, it will usually choose the shortest path and run the test on that path. So the good thing about the reachability analyzer is that if there's a problem of the source getting to a destination, maybe an EC2 instance getting to a database server, it will usually tell you the component that is blocking that path, right? So it saves you more troubleshooting time by pointing you in the right direction. Now let's talk about using packet sniffers and protocol analyzer. So I'm sure that many of you are familiar with Wireshark, right? And many firewalls, next generation firewalls, also have inbuilt in them a solution to perform packet sniffing, right? So that you can easily solve connectivity problems. Now, Packet sniffers and protocol analyzers are very useful tools in helping you analyze the flow of traffic and then showing you where there are potential problems, right? You can use it to do much more, but they are helpful in that regard as well. So if you're able to reach, for example, the subnets where a server is deployed, but you cannot reach that server itself, right? You could run a protocol analyzer, which will capture the packets and then show you where the packets are being dropped, right? So it helps you to further narrow down on the potential bottlenecks for in your network troubleshooting. It could be a security group that's dropping the file or dropping the traffic, or a host-based firewall. A protocol analyzer will usually tell you what the problem is. Or it could just be the handshake not concluding properly because of one or more problems on the server side. Now, in your data center on-prem, it's easy to use a protocol analyzer to capture traffic and then analyze and fix problems. But in the cloud, is a little bit tricky, right? So in order to be able to achieve this on the cloud, what you do is to spin up a server, a virtual machine, right? That's an EC2 instance, and then install the protocol analyzer there on it. And then from there, you can launch the protocol analyzer and then capture traffic that is coming into that subnet, right? So you can install Wireshark on an EC2 instance and then use that for your troubleshooting. VPC flow logs are also good as well. So they give you an idea of what's going on your network, right? After the fact. So I believe we can take some questions now. Before Mike will go ahead and talk a little bit about CloudWatch.
Absolutely. We can happily answer some questions. Use cases for the Elastic Network Adapter and Elastic Fabric Adapter. So I talked about the single root IO virtualization being used for high performance networking because it's a physical card versus a virtual card. And the Elastic Fabric Adapter is for really high performance computing. It's a software based driver. Either of you want to add to that at all?
Well, if I have a storage compartment that needs to receive large amounts of data at every specific points in time, right? Like a data warehouse or stuff like that, receiving high volumes of traffic, then I'll probably want to use an adapter for that instance that can give me above 100 gigs throughput of bandwidth. So that will be a use case for this kind of adapters.
So basically for Elastic Fabric Adapter for high performance and high network performance, right?
Yeah. Monkey Jung is asking, what technique or processes do you use to troubleshoot network issues that brings down a website? So we spoke about a couple of things that you can do using ICMP protocol, ping trace routes to do connectivity tests, using your reachability analyzer to test reachability from one location to the other. You probably have CloudWatch in there that is receiving events from your your website, and you can go to the CloudWatch to get more information about the logs from this website, and that will aid your troubleshooting. Event Bridge, I also spoke about the Event Bridge service that can send you real-time data of stuff that's going on in your infrastructure. So these are some services you can use to troubleshoot issues with your website.
Yeah, I would say that if you already know it's a network issue that brought the website down, then you're very close to finding the issue, right? Usually when the software team or development team, whatever, says the website is down, you want to first ask, like, how do you know it's a network issue, right? Like, what do you have? Can you give me what errors are you seeing, right? Can you look at the logs and see the error, right? Is it DNS? Is it IP, right? And then once we find that out, you want to trace it down to find where the error is, right? Of course, if you have multiple teams working at the same time to find the issue, then I would say as a network, from the network team perspective, we always like to start from layer 1, move it up, right? So having more of a systemic approach, or for troubleshooting, right? You start from layer 1 and move up, right? You don't want to just be all over the place, and doing things from different places. But just like Benedict said, there's a lot of tools that can help you. But I think you always start, when there's an issue, start with, investigate what that team says, right? What's the issue? If they can provide you logs, that will help you understand what the issue is, right? It could be anything from DNS to certificates to power issue, maybe, right? So really, it's like, that's why we like to start. You want to have a consistent process, right? And I think starting from layer 1 and moving up is the most consistent way to do this.
Yeah.
So Omar is asking, what sort of event can we set if an EC2 instance CPU usage is 100%? Well, so the first thing I'll do is that I won't create an alert to tell me when my CPU is 100%, or probably when it's 80% or 70% that I want to receive the alert.
Yeah.
And then you can create that alert in CloudWatch, right, to send you an email when that, or an SMS when that utilization hits that range.
And you want to set up alerts long before they get to 100, and then much more frequent alerts once they hit 90, because if your servers are sized properly, they shouldn't be getting that high.
Yeah.
And if I'll let you guys answer this, the difference between Transit Gateway and Direct Connect Gateway.
Yeah. So a transit gateway is a resource that allows you to connect multiple VPCs together, right? So allows you to have different VPCs connected to each other, right? You can have more of a hub and spoke setup rather than a full mesh where each VPC needs a direct connection to other VPCs, right? And of course, think of the transit gateway as a router, because there's so many different setups you can do with a transit gateway, right? You can also set up VPN tunnels, right? Site-to-site VPN tunnels to your on-premises with the transit gateway. You can set up multiple routing tables, or think of it as separating that one transit gateway into logical routers, right? Instead of one, or multiple transit gateways. So there's a lot of different setups you can do, but think of it mainly as a method to establish VPN tunnels and to connect VPCs to each other. Direct Connect Gateway, on the other hand, attaches only to one VPC, and then from that VPC, then that Direct Connect Gateway, my apologies. I said direct, I was thinking of a virtual private gateway. So a Direct Connect Gateway is used to establish private lines. So you use a Direct Connect Gateway to establish private lines, or connect to your on-premises, right? And so once you have that connection from the Direct Connect Gateway to your on-premises, then you can utilize that connection by connecting that Direct Connect Gateway to your VPC, right? So completely different, two different products that or solutions that provide, give you different connections, right? So think of direct connect gateway for direct connect connections or private lines, and a transit gateway to connect your VPCs. I think that's the simplest solution answer.
Mike, your question did not show up here. I explained federation. Thank you. What is synchronization? So federation is really how you're going to create secure IAM environments by tying your cloud provider's IAM into an identity provider. Synchronization is when you take two IAM systems and you synchronize them so they maintain the same users, the same groups on both. Generally speaking, for high security environments, we use federated identity and access management. Can't think of why you wouldn't want to do that, but from a complexity perspective, but that would be what your synchronization is. It's a good question.
So can we use one transit gateway as a hub to serve many VPCs? Yes, that's exactly what you do. That's the main benefit of a transit gateway, right? It's the hub to serve multiple VPCs. Not only that, you can use the transit gateway to connect to other transit gateways, right? So let's say you have multiple VPCs in one region and other VPCs in another region, right? You have one transit gateway in each side, in each region, and then you peer between those two transit gateways, and now you have access, between those regions.
All right.
Then can a transit gateway connect VPCs in different? That's exactly, I pretty much answered the question by chance.
So this is a great question from Samsung. What's the real difference in responsibilities between your senior architect and a principal architect? It can be a little or a lot, and I'll give you, and there's typically $100,000 to $200,000 difference between these roles as well. So a principal architect is someone that's made it, meaning they're now no longer focusing on, trying to figure out what an architect is, not stuck between an engineer and an architect. You're dealing with a business executive that really understands the client. They've got really good communication skills and really good leadership skills. They typically know one thing and know it fairly well, but it's all about relationships. So it's getting further and further away. So instead of having a direct client, you typically get brought in to help other clients. 99% of my career was as a principal architect. So I was the architect that the architects would call. I was also the architect when there was a $1 billion deal. Go bring in that principal architect. They know what to say to the customer, talk to the customer, show our strengths, and make us look really good. A senior architect could be that good. They really could be. Or quite honestly, some of the people I've trained, I've got several students who are senior architects as their first architect job, and they came from another field. And they could still be great with no background. At the senior level, you're still figuring out your architecture journey. You haven't quite figured out exactly how to get to the top, or you already would be there. And typically at the senior architect level, the people are still focusing a little more on the tech and a little focus on the business. But I got to tell you this, Samsung, when you're an architect and you get the right business acumen, the right leadership, and the right executive presence, you go from architect to principal architect real fast. I did it in 2 years, where it typically takes people, 10 or 15 years that are focused on the tech. So focused on making your customers successful, focus more on those business outcomes, focus more on those business processes, focus more on quantifying the value you're giving your clients, and you'll be a principal architect. And it's going to be a little further away from the technology. It's going to be a lot closer to the business, and it's going to pay a lot more. You'll get a lot of respect too. It's a wonderful job. And honestly, Samsung, I'm going to have that How to Get Your First Cloud Architect Job webinar on Thursday next week. Come to it. There'll be probably a couple of principal architects that I know real well that'll be on that call as well, or people that had one of those on their roles on the way to the top. So let's talk about CloudWatch. And CloudWatch, realistically speaking, is a monitoring service that's going to monitor your AWS resources and the applications you deploy on AWS. And Benedict got pretty deep in some of these things, so I'll talk more from an architecture perspective. CloudWatch is going to give us some metrics to look for things. So that CPU that's using too much CPU, running low on memory. Are we running low on memory? Do we have a memory leak? Do we need to reboot the server? Do we need to, the application people need to fix that memory leak? So these are the kind of things that we're looking for. The key with CloudWatch is you can collect your information, you monitor it, you can act on it, you can analyze on it. So that's really what we're talking about with regards to initially what it is. It's a logging service. So CloudWatch is going to have a couple of built-in default metrics. Not a lot. Your CPU utilization, your disk read write, basically in terms of input and output operations that's going on, and your network utilization. So not that much. Now you can set up custom metrics to actually learn more what you might need to be going on. So here's the thing. We might need to check our memory utilization. We may need to check our AP5 performance and other metrics. And CloudWatch is really a notification system that's going to enable customers and allow them to set events when they reach a certain threshold. And that's the key. Those CloudWatch events, that event bridge kind of stuff, really gives us the ability to do those event-driven things, which is what Benedict had talked about. Trigger auto scaling, a Lambda function, that sort of thing. Now with CloudWatch, we're going to have two monitoring options we can use. We can use the basic monitoring, which is the default. Your data is available every 5 minutes and they don't charge you. And detailed monitoring is if we're going to be able to monitor anything significant, we're going to want to turn our own detailed monitoring and we're going to pay for it. But it's typically available once a minute. Benedict talked a fair amount about EventBridge and CloudWatch events. I'm just going to talk about it a little bit. CloudWatch events is going to give you a near real-time stream of things that are going on. And you can set up those rules and something happens, do something else, those event-driven architectures. And honestly, CloudWatch events and that EventBridge kind of concept and automation is really great. And because CloudWatch events will be aware of any kind of operational change when it occurs. And it can respond to these events and take action. So these things tend to be pretty important. Now, let's talk about logging. So it's a certification exam. So here's the thing to think about. CloudWatch, monitoring, CloudTrail, logging, auditing. So CloudWatch is monitoring and logging, CloudTrail is your audit. So for your compliance things, you're going to have to go back and you're going to do an audit. You're going to go to CloudTrail. And that's an AWS service that's going to keep track of things, which is going to help you with audits. And it's going to basically give you an audit trail. And when it comes to risk management, you've got your audit trail, who did what, when, how, why, that kind of thing. Compliance, great. And if you're in a regulated industry like banking or healthcare, this matters so much more. So CloudTrail will track the changes that are made and can track it to the user, the role, or even if a service role, like if one of the systems made a change to another system. Now, CloudTrail is going to be enabled when your AWS account is enabled and created. And to start it, all you'll have to do is click Start a Trail, or create a trail in the CloudWatch console. You can also do it with the CLI or the CloudTrail API, and it will record every event as they occur. So CloudTrail is going to give you an event history. And by default, it's going to give you a history that has occurred in the last 90 days, which is great. 90 days gives you a long window to go back and see what kind of stuff happened. But what if you're in a highly regulated industry and you need to go back 6 months, 9 months, a year, 2 years? Well, we can do that too. And you might need to do that. And it's probably a best practice to store your information for a period of time anyway. So what you can do is you can set up CloudTrail to send your logs to object storage, otherwise known as S3. And by doing, you can keep it for long-term storage. You can back up your logs, archive your logs, whatever you want to do. When it comes to CloudTrail, there's basically two kinds of trails that can be created. A trail that is local to one region, and that's going to be the default, and it's going to be what you're initially going to do, and it's going to store your CloudWatch logs into a single bucket, default option, if you configure it by the command line interface of the API. But you could also configure a trail that applies to all regions, and that's going to give you your most comprehensive logging and auditing options. It's going to provide a record of all events that occur outside your organization's infrastructure, and it can help correlate events across organizations and the global infrastructure to give you insight on fixing problems. So at this point, Benedict's got lots of things to talk about the Transit Gateway Network Manager. So we'll come back and Benedict will talk, and then I think after Benedict's discussion, we should probably go to some questions.
Yes, Mike, thank you for introducing monitoring and logging with CloudWatch and CloudTrail. I actually delved deeper in monitoring and logging. So the first other monitoring option we have here is the Transit Gateway Network Manager. And it's a network management tool that provides a comprehensive view of your interconnected AWS Transit Gateways. So just like CloudWatch gives you an overview of the instances and applications running your system, the Transit Gateway Network Manager gives you an overview of your transit gateway and the different branches and their interconnectivity statuses as well, right? So how does it work? You have to register your AWS Transit Gateways to the Transit Gateway Network Manager, as well as your on-premise locations, right? So once you register them to the Transit Gateway Network Manager, you are able to have a centralized dashboard to monitor your transit gateway services, right? So it's useful to organizations because it gives you that centralized network monitoring, gives you global network visibility, gives you a unified interface to manage your global network. I mean, you could just have a screen dedicated in your office with the Transit Gateway Network Manager just to show you that everything is working smoothly, right? Another tool that we use for monitoring in AWS is the VPC traffic mirroring, right? And this is similar to what we've come to know as the span ports when we're dealing with switches on-prem. So the VPC traffic mirroring, right, is a feature that allows you to capture network traffic at scale, right? So you want to capture all the traffic coming into your VPC, right? But you don't want to disrupt it, right? So that's the essence of how a span ports work. You just mirror that traffic to another port and then capture the traffic from there, right? So it doesn't affect operations of your infrastructure. So what happens basically is that network traffic from the Elastic Network Interface is copied and then forwarded to another port where you can now analyze the data and do whatever you want with it. So traffic mirroring allows you to capture traffic in real time and analyze it without impacting the performance of your infrastructure. It also supports packet filtering. So you can mirror the traffic to another port and say you only want to capture traffic going to DNS services, port 53, for example, right? So you can filter it down in that way, which is quite useful. Now, how does the VPC traffic mirroring works, right? There are some key terms associated with the traffic mirroring. The first one is that there's a source, and the source is the EC2 traffic to be mirrored or captured, right? Then there's a target, and the target is the instance which will capture the port, which will capture the traffic. So you're capturing the traffic from an EC2 instance and sending it to a target, which is another EC2 instance. You're sending it to the network interface of that EC2 instance, right? And then you have the mirror session, which is the procedure to start directing source traffic to the target. Now, in order to get traffic mirroring working, right, you have to designate a source EC2 instance and a target EC2 instance. So when you specify this source and target EC2 instances, and then you start your mirroring session, it's going to capture the traffic that is going to the source EC2 instance and then mirror it to the interface of the target EC2 instance. So I have a diagram here that can throw more light on the operations of the VPC traffic mirroring. All right, so you see in the diagram here that you have two instances, right? There's a source instance on the left, and there's a target instance on the right. And you want to mirror the traffic going to this source instance to this other, the target instance. So as traffic is coming in, as network traffic is coming to the network interface of this, the source EC2 instance, you just mirror the traffic, right? And copy and forward it, right? You mirror it to the network interface of the target. And then from this target, you can now run your analysis and, do your intelligence, artificial intelligence, and whatever you want to do with that data. So that's how it works basically. And like I said, it's similar to the span ports we use on-prem. Now, why would you want to use traffic mirroring? Well, it's useful as a detective tool to find network and security anomalies, right? So if the server has been having a lot of network attacks, you can mirror the traffic going to the server, the source EC2 instance of the target, and then analyze it there to see if there are malicious bits of traffic going to that server. Then you can take steps to mitigate. So it's helpful for security in that regard. Now, it also helps you to gain operational insights, right, into the network traffic coming into your instances, which will help you to make better decisions. Now, there are some regulatory and compliance requirements that mandates that you must monitor and log all network traffic, right? So that, of course, they can go back and do that audit trail or cloud trail when there's an incident. So the traffic mirroring helps to fulfill these regulatory and compliance requirements because you are capturing all the traffic and sending it to another instance. So you're logging that traffic right in raw form. And it's a very useful troubleshooting tool to help you analyze traffic patterns and see if there's a need to, add resources to that server to cater for an increase in network traffic, or just plan your network infrastructure better. Now, Mike spoke about CloudTrail and how it helps to gather logs for different instances in the cloud. We want to take a deeper look at logs, right? And logs are very important because they kind of tell you what is going on in your infrastructure. So you're not blind to its operations, right? So you want to have that after the fact view of what's going on so that you can improve the performance of your infrastructure or solve problems or potential problems, right? Now, Mike mentioned that CloudWatch is a source of logs, right? You can send logs to CloudWatch, and then from there you can analyze it. There's also the syslog service, right, that you can use to capture logs from different applications or different instances in the cloud, right? So that's also an option to collect logs, syslog. Now, in AWS, we have different kind of logs that can throw more light on the operations of your services in the cloud. The first kind of logging we want to talk about is the transit gateway logging. Now, we've already said that the transit gateway allows you to build a hub and spoke, right, architecture in the cloud. So your branches to your AWS infrastructure. But you want to be able to monitor the traffic or the activities that is ongoing in this hub and spoke technology. So the transit gateway gives you some form of logging so that you can identify what is going on and solve problems and make improvements. So transit gateway logs are detailed information, including the source and destination IP addresses, the port numbers, the protocol type, the timestamps, and collection of metadata, right, on network flows across the transit gateway, right? So logging information is found in the flow logs for transit gateways. I have a picture here of what the transit gateway logs look like, and I'll just share my screen so you can see. So you can see that you can get information such as the interface, where data is emanating from or coming to in the instance on the cloud. You have the source IP address, you have the source port, right? You have the protocol, number of packets that has been received. You have destination IP, destination ports, number of bytes that have been sent across this transit gateway, the time that the traffic started and stopped, whether the traffic was accepted or rejected. So, I mean, it gives you some very important information that you want to have as an administrator of the cloud infrastructure. Then next, we'll talk about the load balancer access logs. So, of course, we know the function that a load balancer performs. It receives requests from users and then sends that request to backend servers based on an algorithm. Could be least privilege, could be round robin, so and so forth. So it's a good idea to have visibility into the traffic received by the load balancer and sent to the server, right? So it gives you an idea of what's going on in that system, right? So in load balancer access logs, you would usually find information such as timestamps, that the time when the request was received, the client's IP address, latency, server responses and stuff like that, right? But in order to get it working, you have to enable logging on the load balancer because it's disabled by default, right? You have to enable the access logs on the load balancer, and then it will ask you to choose a location where you want to store the logs. So at that point, you can then choose an S3 bucket, right, where you want to store the load balancer access logs, right? Now, you have to keep in mind that the health checks requests from the load balancer to the backend servers are not included in the log. So that's something you have to keep at the back of your mind. So they are useful because it helps organizations to analyze traffic patterns and troubleshoot issues, right? Now, you have to be aware that the S3 bucket you are creating for storing your load balancer logs, you have to pay for it. So that's something you have to keep at the back of your mind and, look at when you are setting up logging for the load balancer access log. So I have a demonstration here, or a picture here of what a load balancer access logs look like. So if you look at the log now, it's capturing a request to an AWS Elastic Load Balancer. So it tells you, first of all, that this is a HTTPS request, right? So this is probably a web server from indications or some other services that uses port 443. It shows you the timestamp, right? The date and time when this request was sent. You see the name of the load balancer, the DNS ID. You see information regarding the source IP address. You see information regarding the source port number. You can see destination IP address, destination port number, and other information. So this is probably, load balancer is probably looking at 200 on the backend server, stuff like that. So it can give you some pretty interesting information from a load balancer perspective, whether it's forwarding the request or dropping it, and stuff like that. So yeah, pretty cool log to have as well when you're working with load balancers. Now, how about DNS Route 53? So DNS, it's important that you are able to capture DNS queries, right, that are received by Route 53, because you want to see information such as date and time of the request, once again, timestamp, the DNS record type, is this an A record, a text record, a CNAME record, the domain being requested or the subdomain requested, right? This information could be very useful to help the server owners plan for their services, right? Now, for you to get this working, you have to configure Route 53 for login, right? Then it asks you where you want to send the logs to. You can send the logs to CloudWatch. So when you enable login on the Route 53, then you select CloudWatch as the login platform. So it begins to send the logs to CloudWatch. You can now access the logs directly from CloudWatch. CloudWatch would store the DNS query logs indefinitely by default, right? But you can configure a retention period so that older logs are deleted if you want, right? So you can have a retention period of 90 days, for example, and then after 90 days, it now begins to overwrite the initial set of Route 53 logs that came into CloudWatch. You also have the option to export the DNS queries, right, to an S3 bucket. If you don't want to use CloudWatch, right, to view these logs and analyze the data. Yeah, there's also an option to use CloudWatch metrics, right, which will just show you the total number of DNS queries that Route 53 responds to. So it's not as detailed. It doesn't give you stuff like timestamps or whether it's an A record or not. It just gives you basic metric like the amount of DNS queries I received, right? So that option is also available if you do not need detailed DNS logs. And as usual, I have an example of a DNS log, which I'd like to share with you. So here we see an example of a DNS query log, or some DNS query logs, right? So you see the timestamp, right, which is very important. So you can correlate when Route 53 is receiving these queries, right? I see the time and the date here. We see the domain that it's querying. So it's going to example.com, right? The first one is an A record. The protocol here is UDP. I'm guessing UDP 53. And we see the region and the source IP address, right? You can see that this one is a text record. This one is an A record, AAA record. So you can get some pretty interesting information from here, and then do some analysis on the data that you've captured. Now, how about Cloud Front? Yeah, you have the option to get detailed logs from Cloud Front, right? And this is basically capturing data about the users, right? User requests coming into CloudFront. You want to be able to capture that data. For example, if you have a geo-blocking policy on CloudFront to deny Canada from accessing your website, you want to be able to look at your logs and make sure that you can see deny entries from IP addresses coming from Canada, right? So CloudFront logs are important in that regard. So when CloudFront receives a request from a user, it routes the request to an appropriate edge location, right? Then it writes the data about that request in a log file specific to that edge locations. The log files are saved in an S3 bucket. And you have to specify that S3 bucket when you enable login on your CloudFront. So you can create the S3 bucket ahead of time, and then when you are enabling login on CloudFront, you just select that specific S3 bucket that you've created for this purpose. Now, CloudFront does not automatically delete log files, right, from your S3 bucket. So you can go in and do it manually to delete older files, right? Or you could use automation and use an API to delete older files after a retention period. They are useful, like I said, because they help organizations to monitor and analyze user requests. So in the previous example I gave, if you have a geo-blocking policy, you want to make sure that it's working and preventing users from accessing your content from a specific geographic location. Now, let's talk about implementing log delivery solutions. Now, if you want to implement a log delivery solution, the first thing you have to do is to identify which logs you want to collect. So do you want to collect 53 logs? Do you want to collect load balancer access logs? Do you want to collect EC2 instances logs, right? And then you now move on to the next phase, which is that you choose a log connection method that best meets your requirements. You can collect all those logs in CloudWatch. You could use a SIEM solution to collect your logs, or you could collect your log with a syslog server, right? Then you want to determine how long these logs will be kept in that collection platform, which I just spoke about. So you want to determine a retention period, and that will probably be driven by the policy of the organization. So if the organization says we keep logs for 1 year, for 3 months, right, that will determine how much time you set for your retention period in your infrastructure. You could also define access policies for your log data. So it's important that you control who has access to your logs. Not everybody should have access to your logs, because Someone can delete logs mistakenly or on purpose, right? So you want to use some form of identity and access management process to control who has access to your logs and what permissions they have. And then you test your log delivery architecture to make sure your logs are reporting correctly, and then you can analyze your logs. Now, that brings us to another important AWS service, which is called the Amazon X-ray. Now, when you have a broken bone, you go to the hospital and you get an X-ray, right? And then they can pinpoint exactly where that bone is broken, which will inform the doctor on where to fix the POP, right? Or if a surgery is needed. So the Amazon X-ray is not so much different. It's a management service that helps you to analyze applications in AWS, right? So you kind of X-ray your applications, see where there are problems. So it's probably something that the developers will be using, right? So it helps them to understand how their applications and fundamental services are performing. It can help to identify performance issues and errors in that regard. So it does this by tracing incoming requests to your application and then using that data to make a point-by-point detailed service graph. So if there's a request to a service on a server, it's going to be tracing that request and seeing how it flows across the application, and then able to draw a detailed service graph and identify if there are issues or if everything went smoothly. So the service graph will show how your front-end services are handling data from the back-end services. And that can help you improve the performance of your application. So organizations will use X-ray to analyze applications, identify bottlenecks, view performance analytics, and audit their data in a secure manner. And I'll show you what it looks like in this diagram here. So this is how the AWS X-ray works really, right? So it's going to be tracing requests that are coming into your application. So it's going to be collecting those traces, recording them, drawing that detailed service graph, right? And then analyzing issues if there are any, and then providing you with the results to show you where there are issues. Good too. Now let's talk about implementing a network audit strategy. Now, auditing is very important for all organizations because it helps you to meet compliance requirements, right? So if you're working in the financial sector, you want to have PCI DSS compliance requirements. And if you're working with a company that deals with customers in Europe, you want to comply with GDPR requirements. So you need an audit strategy to show that you are complying with these requirements, for example. So what exactly is a network audit? It's a process of gathering network data, analyzing it, and studying it with the purpose of assessing the network's overall health, right? So it helps organizations meet compliance requirements required for their IT infrastructure. So it's a systematic process that looks at your security, network security posture, looks at confidentiality, integrity, and availability of your systems, and gives you that an idea of the overall performance of your network. Now, how do you implement an or a network audit strategy in the cloud, in AWS in this instance. So to implement an audit strategy in AWS, these are some recommendations that can help you achieve this aim. So first of all, you need to define the scope of the audit and its intended goals, right? You need to keep it down because audits can be really large, right? You want to identify the services that need to be audited. For example, your firewall policies. It's important that you audit them, right? Your identity and access management policies is important that you audit them. Your security group policies, network access list policies, these are important policies that you want to audit from time to time just to make sure that you are in compliance. After identifying the network services that you want to audit, then you now define the tools and processes to be used in evaluating your network services. So are you going to be using CloudTrail as an audit tool here? Would that meet our requirement? Are we going to be using network scanners for audit trail? Are we going to be using AWS config, which shows us when configurations have been made or tampered with? Are we going to be using third-party software to carry out our network audit? That's some questions you have to ask yourself at this stage. Then we collect the network configuration data and that you want to audit and the accounts you want to audit. So this means firewall logs, firewall configurations, access list configurations, security group configurations, IAM policies configurations. You collect all this data and then you execute your audit plan using those tools that you've chosen to perform your audit, right? AWS has the AWS Audit Manager that you can use to audit your network, right? AWS Systems Manager is also useful in carrying out some audits. The AWS config is also useful in auditing because it shows you who has made configuration changes to your network. So these are some inbuilt tools by AWS to help you implement your audit strategy. You could also use third-party tools, right? So you could use AlgoSec, which kinds of audits your firewalls and tells you when access policies have been changed and gives you timestamps and stuff like that. It's a third-party software that you can use to achieve this aim. And then finally, you want to review the results of your audits and then take actions on the results. So now let's talk about common network problems that you would come across in the cloud, right? Or in AWS. Misconfigurations. That's the very first one, right? And it's not so much that sometimes network admins don't know what to do, but it's just having that overall picture of the network and how these components are supposed to interconnect. So for example, if you have a firewall in place, right, you're supposed to route all the traffic to the firewall, and then the firewall routes traffic to the internet gateway, right? So there could be a misconfiguration in place that allows an EC2 instance direct access to the internet gateway. So in that case, it bypasses the network firewall, right? So these are some common network problems that you find in the cloud. Misconfiguration is one of them. An EC2 instance can crash due to various reasons. One popular reason is installing untested patches on your EC2 instances, right? And this happens all the time. Microsoft will release a patch and then 3 weeks down the line, they say, oh no, there's a problem, uninstall that patch which was installed. So it could get problematic when you patch a system without testing it first. Of course, the CPU being maxed out can also cause a crash of the system. Another common network problem is when you don't have a route to a specific destination, right? So you have to always check your routing tables to see that your routing has been done correctly. Now, for VPN tunnels, what are some some common problems with VPN tunnels? A mismatch in maybe the encryption algorithm. So one side is using AES 256 and another side is using AES 128, or a mismatch between Diffie-Hellman groups or the hashing algorithm. These are some issues that can cause the IPsec tunnel to go down. And usually the IPsec, well, in some, I haven't seen it, but I assume that there's a provider somewhere that could upgrade their security device. So let's say you have a VPN with from AWS to a Cisco router or a Cisco firewall, and then they upgrade the firmware of the Cisco firewall, and then it no longer supports AES 256, right? So when that router comes up with the new firmware, the IPsec tunnel is going to go down because it's now going to default to another encryption standard. So these are some of the things. I've not seen it that often. I've seen a little variant of that in the sense that, so yeah, real life example. So when you build your VPN tunnels, right, you choose the subnets that you want to allow over the VPN tunnel, right? So if you have 10 subnets, for example, that you want to send over the VPN tunnel, you can create a supernet, right? Summarize it, right, and send it over the VPN tunnel. And then we try to build a VPN with another a partner, not with the cloud now, and it was working fine until we upgraded the firewall, right? I think it was a checkpoint firewall, and then the VPN tunnel went down. So after extended troubleshooting, we found that we had to specify those 10 subnets individually over the VPN tunnel for the connectivity to be restored. So you might run into some little problems like that where you have experienced people to help you solve the problems. Now, how about security problems? What are some common security problems you come across in AWS? Misconfiguration of your network access list. It's too restrictive, right? Same thing with the security groups. It's too restrictive, right? It could be it could be a software running on the server, right, that is identifying legitimate traffic as illegitimate and dropping that traffic, right? It could be incorrect identity and access management policies that has been configured in AWS. These are some common security problems that we'll find in the cloud. And then lastly, we want to talk about how we can eliminate risk and achieve efficiency in a cloud networking environment. So the first thing we have to understand is that all risks cannot be eliminated, right? But we can mitigate them. We can take steps to reduce the amount of risk that we have in our AWS cloud. So when it comes to risks, you could mitigate the risk, right? And like I've said, you can't eliminate risk, all of risk. You can reduce risk and then accept the remaining risks, or what we call the residual risk. So you reduce your risks to an acceptable level, something that you can live with, and then work with that in your AWS cloud. So you would usually want to use a risk management plan to help you to reduce risks. And Mike mentioned some of that when he mentioned Pasta and Stride when he was talking about threat models. So you typically want to use a risk management plan or framework to help you manage your risk. Now, there are some technical controls that we can implement as networking professionals to help us manage risk in our infrastructure. One of that is encrypting your data. It's very key that to enforce confidentiality of your data, you encrypt it, so that even if the data were compromised, the bad guy will have no use of it because he can't decrypt the data, right? You want to also use packet filtering, right? And this will be done at your firewall level. You want to filter out the packets coming into your network and going out so that illegitimate traffic does not get in or go out, right? You could also employ a data loss prevention system just to protect what kind of information is taken out from your infrastructure. Use firewalls. Web application firewalls, they help to keep your web applications safe from web application attacks. And there are quite a lot of them. Cross-site scripting attacks, injection attacks, SQL injection attacks, buffer overflow attacks, and the likes, right? Having a web application firewall helps you to reduce the risk of being affected by these kind of attacks. You also want to use access control leaks and security groups as well. You want to do what we call segmentation of your VPC. Mike talked about a demilitarized zone earlier, a DMZ. So you want to compartmentalize your services so that if one compartment is breached, right, the bad guys cannot move from that compartment to another compartment. More like microservices, right? It's segmented so that it just reduces the blast radius. You can only affect this compartment that you've gained access to. So segmentation is very important. Then have a backup plan. You have to have a backup plan, right? You have to take backup of your network devices, of your firewalls, your EC2 instances, because one day things are going to get broken, and then you have to rely on your backups. It could be that you suffer a ransomware attack, and then the bad guy gets access to your EC2 instance and then encrypts all the data and says, pay me $1 million to give you the encryption key. You just call his bluff because you have a backup, terminate that instance, delete it, spin up a new instance, and then load the backup there. And then, of course, find the hole which let the bad guy in and block it so that it doesn't encrypt your new EC2 instance. So have a backup plan. It's important for disaster recovery as well. Manage user access control, identity and access management. Who has access to your network? It could be a last form of defense, right? For your services. How about multi-factor authentication? It's important as well. Two-factor authentication. And when we're talking of multi-factor authentication, we're not talking of having a password and a PIN, right? These are two. We have different types of authentication. These are type 1 password, something you know, right? So you know your password and you know your PIN. Have a multi-factor authentication strategy that combines different authentication factors. So you want to combine a password and Google authentication app, right? Or Cisco Duo Mod authentication app, right? So you have your phone. The bad guy doesn't have your phone. So when you enter your password, it sends a push to your phone. You click and accept the push, and you get access to your network. So also, you want to train your employees. Well, in my opinion, I think one of the easiest ways to gain access into a network is by social engineering. People always fall for it. I mean, I fell for it in my last job. My manager then, on a Saturday morning, sent a mail to all of us, and I was in the bathroom with my phone, and the mail came into my phone, and I couldn't really see the email header because that's something I look out for. Look at the email, and then you see whether there's a max email ID after the email, then you know this is scam. So I couldn't see it, and I clicked on it, and it told me, well, you have failed the test, right? I got a mouthful on the next Monday, but it can happen to anybody, right? So train your employees, employee awareness, security training, user education. It just helps to raise the level of the security awareness and helps you to manage the risk of having this infrastructure in AWS. So we can take some questions now, after which Mike, I believe, will talk about some hybrid cloud architectures.
Yes, absolutely. Hybrid cloud stuff, which I love. So let's bring in some questions. Who has questions for us? I'll read the question. Can we integrate VPC traffic mirroring with SNS notifications? Maybe the incident response team. So I'm not 100% sure I understand what the actual question is. Either of you, and it's hard in the YouTube chat box. I get it. Do either of you understand it?
So let me try here. So when you're talking of an incident response team, I would assume that it's a team that is monitoring a sort of SIEM solution, right? So that when there's an event, they can respond, right? You could send the logs from that EC2 instance to your central log location where the incident response team would have access to it. So yes, there'll be some correlation there, and then there'll be visibility into the logs from
Now that I understand the point, you could do that. And you'd also want to segment that because your incident response team probably has some lawyers that are attached to it. It has some PR people that are attached to it. It's got some senior executives that are going to be attached to it, and they probably don't need to know this. But the security admins that can fix this and the security engineers that would be part of your incident response team, that would be good, yeah.
Name not found. Why do we need to do all this monitoring and investigations on a mirror instance? Can all this work not be done on the source EC2 to save time? Well, I wouldn't want to be doing analysis on a production server, right? That is accepting traffic and responding to requests. I would like to offload that data to a separate instance and then do my analysis there. That's why I'll do the traffic mirroring.
But it's more than that. If you try to do things you're really trying to find one way where you can look at the big picture. And by putting everything in one place and that one place can see everything, it's going to be able to make better correlations than if stuff's all over the place and you can't figure out how to access it. But it's really good thinking.
Sunday Okuns, can we use a third-party application like Zscaler to block unauthorized IP? It's like asking, can we use a third-party application like a Cisco firewall to block unauthorized IPs? there's that possibility to use vendor devices from different vendors. It could be Zscaler, Palo Alto, Sophos, and the likes. As long as you have it in the, and you could even spin up an EC2 instance and install the software there and use it to protect your network. Yeah, so you can. Shumak, if you automate the patching of EC2, are the instances when patching may block applications? Can you please throw more light on data keys with encryption of data at rest? So this is a two-patch question, right? So if you automate the patching of EC2 instances, can it? Well, the first thing is that I would not automate patching of my production servers. When the patches come from Microsoft every second Tuesday of the week, right, of every month, I'm going to test it in my lab.
Yes.
I'm going to go to Microsoft's site to see if there are complaints about this particular patch. And then when it's certified that all is well and good, I can now push out the patches to my EC2 instances.
Yeah.
Can you please throw more light on data keys with encryption of data at rest? I'm not sure I understand this question,
So
but
I think So I think what he's talking about is the key management system, and all the ways you can manage the keys. So it's a fairly big topic on key management and encryption at rest. But the good news is, next month, i.e., June, we're going to do a full AWS Solutions Architect Bootcamp, and we're going to get involved in a lot of storage. And when we get involved in storage, that's really talking about encryption at rest. Having that key management system and the various storage things in the networking course isn't going to fit when we've got about 30 minutes to finish it. But I will definitely cover that at length, and we're going to be doing this course completely free, and it's going to be a pretty big solutions architect course, the one we ran before, plus a tremendous amount of new content and other things that'll be there as well. So we will cover that there. Is there an AI tool that can analyze all the logs and send alerts? There's been SIEM systems that have been doing this for a while, and they have been using AI for a while. Having said that, I can tell you many organizations that have high security environments have been taking these logs and streaming these logs with something like an Apache Kafka, creating an object storage type data lake, and then running machine learning algorithms and visualization tools to see what's been going on in their systems. So they could create their own things in addition to the commercial SIEM systems that are out there. Absolutely.
So Joseph is asking, when you create a backup of your instances or web application servers, do you create these backups in the same regions, or do you get charged by AWS for these backups? So the first thing that I want to do as a security professional is not to save my backups in the same production system, right? So if I'm running a multi-cloud system, I'll probably be saving my AWS backups in Azure or saving the backups on-prem, right? So that if there's a problem there, right, my backups are safe and secure, and I'm going to have more than one backups. Now the backups are going to be stored. If you decide to store your backup in AWS, you want to store it in another region, right? In another availability zone. You don't want to store it in the same place where the device is. It's like storing an encryption key on the server that you have encrypted data on. Once the bad guy gets into the server, he can just get the encryption key and and decrypt the data. So it's the same thing. Once your infrastructure is compromised and the bad guy sees the folder called backup, he's so happy because he has got you by the jugular. So there are different types of backup strategies that you can implement, right?
And we'll briefly get into disaster recovery things soon, but think about it. If it really matters and you need some real critical backups, don't put it on the same cloud in case the cloud goes away.
Yeah. So Joseph is asking again, is the transit gateway created within a specific availability zone between various VPCs? And also, does the transit gateway act as a route reflector? I think Mo answered this the last time, that you can have more than one transit gateway in different regions and then you pair them, right? And then you can allow routing between different locations in the transit gateway. So I believe that answers the second part of the question. Does it act as a route reflector? I don't think routing is enabled by default, right? But you can go in there and allow.
Somebody has a loud motorcycle or car somewhere or something that needs a muffler.
But,
the key when we're using CloudHub or Transit Gateway is that it functions like a route reflector, enabling, if we want to enable it for routing, multiple VPCs to be able to have a hub and spoke environment by allowing transitive routing, just like a BGP route reflector.
Shumuk is asking, is there anything like gateway logs? What application is gateway? Do you mean the transit gateway logs? Because I covered that earlier, that you can get login from your transit gateway.
You could be referring to routers, which are also called gateways, and routers generate logs. Not sure.
Yeah, is it fair to say that almost every resource, we can pretty much take logs from every resource and use it inside CloudWatch?
Yes, I mean, there's that capability.
Okay, well, we've got still an ambitious amount of content to go through in a short period of time. So we're going to get back to the content. If you just joined us, please note that we've got 2 full days or almost 2 full days worth of great labs for you to do. So please make sure you sign up for them. And they're free. So go sign up for them. They're in the description in the chat box. And so we know you're awake, alert, and oriented. Please give me a hashtag AWS Advanced Networking. And if you're enjoying the lessons, please give it a like, subscribe, hit the bell, those sort of things. So we're going to talk briefly about a hybrid cloud architecture, which is an incredible way to go. And a hybrid cloud architecture is quite simply having your data center and connecting it to the cloud. So that's it. And by leveraging it, you're eliminating single points of failure. You're typically saving money because cloud compute costs, when all is said and done, David Lithicum's numbers are 250% of data center costs. It's about what I've seen. So things that run 24 hours a day, 7 days a week are typically much cheaper in your data center. Things that run sporadically or need to scale typically need to run better in the cloud. So a hybrid cloud enables you to leave some of your things in your data center, some of your things in the cloud. Your high performance things that you need control over, you can run in your data center. The ultra high security things you can run in your data center under extreme security. And you can use the cloud for what the cloud is good at, which is scalability, near unlimited capacity, and simplicity, and capacity on demand. So that's your hybrid cloud architecture. And there's a couple ways to do hybrid cloud architecture, but one of them that we're really talking about is offload, hybrid cloud offload. So let's say we've got an organization and they've got their data center and they're running a private cloud on it, say OpenStack or Nutanix software, and they've got a private cloud. We can have it set up where those systems can run in that private cloud. And when they reach a certain capacity, add capacity in AWS, Azure, or Google when you need it. Pay for it when you need it, scale back when you don't need it. So that's what we're talking about data center offload. And basically speaking, we've got similar servers in our data center, virtual machines in the cloud, and we can scale out as we actually need. We can do it with web-based applications where we use Route 53 or DNS in an environment where we say 80% of the traffic in the data center, 20% of the cloud. We could set over a failover routing, run the data center completely, switch over to the cloud. So that's where we're really talking about it from a hybrid cloud and where hybrid clouds really shine. So we're going to talk about leveraging the public cloud right now for disaster recovery. But here's the thing. Let's say we're in the AWS cloud and we want to do disaster recovery. We don't want to do disaster recovery in AWS. That's silly. That's like saying, hi, I've got a building and a business, and I'm going to back up all my stuff and I'm going to put it in my own business. No, that's silly. We put it somewhere else. Typically, our data goes far away. So if we're going to do really good disaster recovery, we can back up our data center in a cloud provider with great disaster recovery. And if we're on AWS, chances are we should, realistically speaking, put our disaster recovery on, say, Google or Azure, not just another region in AWS, because that's not real disaster recovery. Now, when we define a disaster recovery plan, here's what we need to think about. What is the business's maximum tolerable downtime? What is maximum tolerable downtime? The amount of downtime a business can have before their business has significant and permanent long-term losses. So we must know the maximum tolerable downtime. And that's an executive decision from that business. When we know the maximum tolerable downtime, we can come up with a recovery time objective, which is going to be less than the maximum allowable downtime, or the maximum tolerable downtime. And then we can also start looking at how quickly we need the data. At what point do we need to recover our data? Can we tolerate data that we lost for 5 minutes, for 5 days, for 5 weeks, or 5 months? And what's going to drive that is business needs. If we're dealing with a bank that processes 50 million trades an hour of stock, and we lose an hour's worth of trades, that's going to be serious. That bank cannot tolerate a recovery point of an hour. Maybe it can tolerate a minute. Maybe it can tolerate 10 seconds. Likewise, we've got another business that can tolerate a week's worth of downtime loss, and it's no big deal. So we have to think about that in the context of the business needs. So let's talk about our architectures for disaster recovery. And this gets a lot better with infrastructure as code, but the same principles apply. So the first disaster recovery architecture we're going to talk about is going to be the lowest cost. And basically, a situation is we have our systems in our data center, or we have our systems in a cloud. We back them up into another cloud. We back up in the forms of virtual machines, call them machine images, what have you. We have snapshots of our database, and again, an image of our database and stored database in another cloud. And if our data center goes down, we launch them on the cloud provider, or we launch them on another cloud. We launch all these virtual machines. It's going to take a little while to get all these virtual machines set up. It'll be a little quicker with infrastructure as code. It could take, a bit, a couple of hours to really get it up and running perfectly. And that's going to be our lowest cost disaster recovery. Copy our virtual machines someplace else, copy our data someplace else, and then poof, that's our lowest cost option for disaster recovery. What's our second lowest disaster recovery option that gives us a little better? Well, we take our data center, back it up into a cloud, we back up all those virtual machine images. Or we're in, say, AWS, and we back up all our virtual machines, and we keep a copy of all those virtual machines in Azure. Same thing. It really doesn't matter. And now we keep our databases synchronized. So if we've got a database, let's say an Oracle database in AWS, we synchronize that database in real time with the database in, say, Azure. So now, if we're using AWS and we're creating disaster recovery in Azure, we've got copies of every single virtual machine we have, and we've got a synchronized database. So now, if an outage occurs, we leverage an infrastructure as code script, we launch all our systems, and we've got fresh data from the database. So better than before, where we just backed it up and created backups of our data. Now we've got backup images, and a synchronized database. So it's going to come back faster with less data to be lost. Now, what we're going to get into next is where the cloud gets really beautiful for disaster recovery. Let's say all I have is a very simple 3-tier website in my data center. Or it could be the AWS cloud going to Azure. It doesn't matter. It's the same thing. But let's say I've got a very simple website. I've got 30 web servers, 30 app servers, and say 10 database servers by the time we're done with all our read replicas and everything else that we have. So 30 web servers in my data center. I now create an environment in AWS or any cloud I want. And instead of having 30 web servers up, I have 3 web servers up sitting behind a load balancer in an auto-scaling group. I have my app servers in here, but instead of having 30 of them, maybe I have 3 in an auto-scaling group. And I replicate my databases from my one data center or cloud to the other cloud provider. I create, say, a DNS policy for this architecture. Data center 1 fails, or cloud provider 1 fails, go over to cloud provider 2. And then what happens is all the traffic comes in to the second data center or the second cloud. The traffic will initially overwhelm all those servers because you only have 3 and you had 30 before. Auto scaling will occur. These servers will add capacity. And within 30 to 45 minutes, this system is up and it's running and it's functional. The data is carrying. This type of warm standby type environment is one of the benefits of cloud computing-based disaster recovery. Set up a very small environment, put everything in an auto-scaling environment, keep our data synchronized. One thing goes out, poof, within 30 to 45 minutes, you've got a completely up cloud and everything's up and running. So that's really where cloud scales, and that's going to work for really businesses that have, fairly significant needs, but they don't have to be up. And the last type of disaster recovery environment we're typically going to talk about is the hot environment. And here's what this means. If you've got a data center with 10,000 servers in it, you're going to have the cloud with the same 10,000 servers configured exactly the same way. And they both run up and up at all times. You're paying for twice the servers at all times. Should you have a problem in one data center, it will go down, traffic will shift directly to the other data center, and it's up and it's running and it is 100% capacity. So, cheapest option, backup of our information, backup of our virtual machines. Launch if there's a disaster. 2, backup of our information, backup of our virtual machines, synchronize our databases so it comes back quicker. Option 3, keep our systems in the data center and small versions of them on a cloud or backing up one cloud to another cloud, put them in auto scaling. Should anything happen in the primary cloud, everything will shift over to the backup disaster recovery cloud. Auto scaling will scale it out in 30 to 45 minutes and you're up and running. And the last option is identical copies. Same thing in one data center, same thing in the other data center, rapid come and rapid response time. So that's really what we're talking about. Now, at that point, you might wonder, why don't you just run 2 clouds full time and send your information to both clouds and not even need disaster recovery? But that's going to be a different high availability versus disaster recovery situation. So let's talk a little bit about storage gateways and what they are and why we use them in hybrid cloud architectures. All a storage gateway is it's going to be an appliance, basically a server, like a file server, that you stick in your data center. It's going to be a virtual machine, typically VMware. And what'll happen is you'll mount information on that server. If you pop it on the server, it'll copy it on the cloud. If you've got your information stored in the cloud, you'll be able to reach to that server and it's going to feel like, and that server will go reach out to the cloud to get to the data. So I'll give you some examples of what it's going to look like. Typically speaking, we have file gateways, we have volume gateways, and we have tape gateways. So realistically speaking, let's talk about a file gateway. All it really is, and let me show you this because I think these are really cool topics, the way these gateways work. I think if I draw it out for you, it'll be pretty helpful. Bear with me. Okay, so here's your situation. You've got your data center, or you've got your campus. Let's call it a data center. You've got one server here called the storage gateway. It can be any of the types of the storage gateway. You've got your data in the AWS cloud. And let's say your data is sitting in S3, which is object storage. Object storage is not normal storage. You're not going to mount it with your servers as a general rule. So how do you get your information back into AWS? Well, realistically speaking, if you've got a network connection between AWS and your data center, and you've got a storage gateway here, your users will connect to this storage gateway, and it's going to look like a server. And it can either run NFS, if you're connecting to Unix systems. They typically can run iSCSI, or they can also run server message block if you're connecting to Windows systems. So you connect to the storage gateway, and if you store some information on the storage gateway, it's going to get pushed to the cloud. What if you want to access information from the storage gateway? That's okay too. Your users will connect to the storage gateway. The information will then be pulled from the cloud, sent to the storage gateway, and sent to the user. And one of the other cool things to think about these storage gateways are they actually cache information. They store that information so that the next time someone requests the same piece of information, if it's stored on a cache, it won't be necessary, where they won't have to reach across the wide area network to get it. So another graphical way you can actually look at these storage gateways here is you can connect to the cloud provider over these storage gateways and set it up where your information is put on S3. And you can even create a lifecycle policy where your information will be stored wherever it's going to be most cheap based upon your use case patterns and what you're actually doing. So, just a touch on storage gateways just to prepare you for this in case it's touched. So let's talk about our connectivity to the cloud. In a normal world, we either need a VPN or a direct connection. But what if you need real security, heavy-duty security on your direct connection? You can run IPsec over the direct connection. And by doing so, we've got a direct connection, which theoretically is private because of the 802.1q tags that we're using, and a layer 2 VLAN's a layer 2 VLAN. But this way, if somebody were to break into the AWS Direct Connect facilities and they stuck a protocol analyzer or a sniffer on a span port, they could see your traffic as encrypted garbage, so they wouldn't know what it is. So that's one of the reasons we like to encrypt information on the direct connection. Plus, the other component of encryption is that endpoint verification. If I'm connecting to Benedict, I want to know that Benedict is a Benedict and not someone pretending to be Benedict. So we can set up VPNs over our direct connections. So let's talk about the concept of a transit VPC very quickly. What if you wanted to take your data center and connect it to multiple VPCs that you own? So, you've got the option of VPC peering, right? For your VPCs, but your VPC peering is not transitive. So if you wanted to have an environment where you're going to connect from your data center to all your different VPCs, it's going to get relatively ugly. But you can actually create something called a transit VPC, and it's not that different than traditional networking. Here's what you do. You create a transit VPC, and you put a VPC that you connect to, and you then connect that VPC to other VPCs. And by doing so, you can use your transit VPC to connect your data center to your multiple VPCs. And in your transit VPC, you'll put a virtual router, and you basically do it the same way we've done everything forever. There's a virtual router. We can set up BGP on it, and that's how we can use a transit VPC. So it's going to be a whole lot like this. We've got multiple VPCs. We create a transit VPC. These transit VPCs ultimately have a logical router on them or a virtual router on them. And in that particular environment, that transit VPC functions basically like any other networking router we've had for the last 30 years. And now, poof, we can use that transit VPC for networking. So let's talk a little bit about billing. So there's a lot of billing and expenses on the cloud. This is usually what typically shocks people. So normally speaking, when you build a network, you don't pay to use it. You pay for the hardware that you have, and then you pay for whatever your ongoing links are. But when you connect to AWS, there's going to be a lot more fees. So they typically deal, let's say for your connections to the cloud, Instead of just with a normal wide area connection, I get a network connection between me and Chris, and I pay a monthly fee for the connection. Here, we're going to have to pay for the connection. We're going to have to pay a hourly port fee to have the port that actually exists. And then typically speaking, we're going to have to pay to send the data. Now, when we're dealing with systems on the cloud, we're going to pay data processing fees. So we're going to pay for the data that's going to go out, our NAT gateways, for example, pay for the data that's using our load balancers. So understand that as we traverse the AWS network to go from point A to point B, they're also going to charge us for that too. So we're going to get billed for a lot of different things. Now, when you have a VPN, you're going to get billed for every hour that your VPN tunnels out, whether you use it or not. Same thing for your direct connect, you're going to be charged there. But depending upon the way your traffic actually runs will determine what you're going to pay. So kind of keep that in the back of your mind. If you are using AWS Private Link, you're going to be charged for every hour that you've got a VPC interface endpoint. And you're also going to be charged for every piece of data that traverses that VPC endpoint. Same thing for the NAT gateway. You're going to be charged as long as you have the gateway. Then you're going to be charged for the traffic that's processed by your gateway. And then you're going to be charged for the traffic that's sent by the gateway. So process, sent, and you're going to be charged for the NAT gateway. Now, there's also other service and port hour fees. There's going to be load balancer fees. You'll be charged for the number of hours the load balancer is in operation. You'll be charged for the load balancer capacity units, which are going to be a combination of traffic flows, bandwidth uses, and the number of rules on the load balancer. So the smarter you configure these load balancers, the more you're going to need to pay. Typically speaking, outbound traffic was always billed to the internet. There were some changes very recently, started with Google that's not charging, and I believe AWS just caught up. And you will also be you'll pay for region to region transfer. So if you've got something set up in the US and now you're dealing with a region in Europe, you'll be charged for those transfers. So sometimes if you had object storage in an object storage based website in the US and you had a lot of users in the UK, it may make sense to replicate that object storage to both sides of the pond in the UK and the US and have the UK people and European people served locally as opposed to being served from the US. And of course, there's also going to be a charge for any type of data in and out of the Cloud Front content delivery network at the edge locations. Now, if you're using public IP addresses in the same region, there's going to be a data transfer charge. So try to use private IP addresses when you can instead of public IP addresses, because that way there'll be less communication charges going back and forth. And of course, if you're going to put your data in 2 different availability zones and your systems between 2 different availability zones for high availability, there's going to be additional fees and charges for that. And of course, any data you go from VPC to VPC will also be charged. So if you want to use micro-segmentation of your network for better security, please understand that's something that you're going to have to contend with. So we'll briefly mention the concept budget just in case it pops up. Budgets are a way for an organization to help monitor their budgetary requirements, meaning set up a budget to be alerted when you're spending a certain amount of money. If you're doing a lab, you might set a budget for $50. Why? Because $50 will get you a whole lot of labs for a non-production environment. But you can set up a budget that goes off at 50%. So if for some reason today you're at $1 and all of a sudden you get an alert you're at $25, what did you do? What got left on? So you can fix it fairly quickly so you don't have a big expense before you get it. Basically, you'll set a budget, the budget you create in the management console or the billing console. And when you get to a percentage of exceeding that budget, you will be notified of it. And then briefly, we'll go into AWS Trusted Advisor. Now, in reality, a trusted advisor is a human person that's got areas of expertise. They have absolutely no bias in them. And you go to them for expert. Like if you go to your physician, they're typically a trusted advisor. Hopefully, they're not bought off by the drug company to go prescribe something for you. They shouldn't be. And you're going to go there and they're going to look at you and they're not going to say, I have a preference for this company's medications. They're going to be trusted. And AWS has a service and online tool to kind of help organizations control their spending. And basically, how it works is Trusted Advisor will scan your infrastructure. It will compare your infrastructure to AWS best practices, and it'll make recommendations. But remember, it's an automated tool. You may get some wacky recommendations. But when the recommendations are good, it can improve your performance, your security, your availability, and potentially even your costs. And there's going to be 2 versions of Trusted Advisor. For organizations that are on basic and developer support plans, they'll get 6 security checks and 50 service limits checks as part of their Trusted Advisor. And for organizations that have business or enterprise support, they'll receive 115 Trusted Advisor checks, of which 14 will be cost optimization, 17 will be security, 24 will be fault tolerance, 10 will be performance, and 50 will be service limits. Well, it's going to go back to Benedict to talk about AWS networking limits and quotas. And we are running a few minutes behind, but not too many. I tried to go through some of those more easy materials fairly quickly there. So we'll come back. Benedict, for time purposes, why don't you go straight into networking limits and quotas? But you're muted, Benedict.
Thanks, Mike. All right, so is the cloud infinite? No. There are limitations to cloud, right? So AWS has networking limits and quotas that can affect usage and performance. So you have to be aware of this, right? It's important to be aware of these limits so that you can plan your network resources accordingly and you don't exceed these limits and quotas. Although if you hit the limit, you could contact AWS support team and ask for a service increase. So they have a dashboard where you can go and track and manage the quotas for each of these services. So AWS place limits on the number of VPCs, subnets, security groups, direct connections, and virtual interfaces that you can create per region, right? So there are also limits on the number of NAT gateways and elastic IPs per subnet that can be allocated per VPC. So what does this look like really? I'm going to take you to the dashboard of the limits and quotas page on AWS. And share my screen now. Thank you. So this is what the dashboard looks like, right? The quotas and service quotas dashboard, right? So you have a dashboard and it shows you the different services. So I'm in the current region here and tells me that I have I can create 155 EC2 instances in this region, 24 CloudFormation instances in this region, and stuff like that. So what if I hit the limit and I want to go beyond that? I want to create more instances. What I would need to do is to search for that application or that AWS service that I want to increase the quota, right? So I'll click here on the left on AWS services. Then here I'll just type the name of the service that I want to request an increase for. So for example, here it's Amazon CloudWatch, right? And then it takes me to the service page. I'll select the quota name that I wish to apply for a quota, right? And then takes me to the next box and asks me how many instances do I want to increase it by. So if I need an extra 100 instances of the CloudWatch service, I'll just type in 100 and then click on request, right? So this request will go to the AWS support team backend, and they'll review the request and grant my request if they are able to. So just keep that at the back of your mind that there are networking limits and quotas when we are dealing with AWS services. So that's all from me, Mike.
Okay, thank you so much for that, Benedict. I am going to go briefly into high availability network design, or at least the things you can think about for the exam. I'll then talk a little bit about things you can do to pass the exam, and we'll finalize with questions. So let me know you're awake by typing a hashtag AWS Advanced Networking into the chat box. If you're having a good time, you're learning something, please give this video a like, and please subscribe to the channel and tell others about this video and our channel in general. So let's talk about high availability system design. And we have to define, what does that mean? And what is availability? Availability is your systems being there for you to use when you need it. So if I want to turn on my electric and I try to turn on a light switch in my house and I can't do it, the electric is not available. I'll put on some candles, I'll hang out with my cat, maybe drink a glass of wine. I might think it's fun. Somebody else might not be so happy about it, but availability is that. So when we talk about availability, we'll typically talk about three levels. We'll talk about it in number of nines. 99% versus 99.9% available versus 99.99% available versus 99.999%. Now, I'm going to tell you right now that I have designed many 5 nines available systems, but 5 nines available systems, meaning 99.999% of the time, is realistically speaking 5 minutes and 25 seconds of unplanned downtime per year. So it's really nothing. Most organizations would consider 99.99% high availability, most organizations. And what determines the amount of availability needed? The organization's business needs. What is the cost of downtime from a quantitative and a qualitative perspective? And you have to calculate that with that organization's executives. It's something we teach our cloud architect students, because it's very vital. Because if you don't know the business and you don't know what you're designing for, you can't plan those. So, wrong button. So let's talk about where you would need these. So most businesses, 99.99% available, gives them about 52 minutes of downtime. It's fine. But what if you're a bank and a minute of downtime could be millions of dollars? What if you're a hospital and when your systems go down, somebody dies? Or an emergency services system where you go to call 911 in the US or 999 in an emergency and it isn't there. That's where you need ultra high availability systems. So let's talk about principles for system design. No single points of failure. So realistically speaking, if you have a mission critical system, like an emergency call system, or an entire government's military, or a bank, you probably should not put it all in a single cloud, because no matter how many availability zones and regions you use, that cloud provider becomes a single point of failure. So you should spread that load. For more moderate availability systems, we're dealing with something else. So let's talk about things that you need to think about in high availability. I'll first start with the tech pieces. Redundant power. If you've got a router connecting to the cloud provider and that router dies because the power goes down, you got a problem. So you should probably be dealing with high availability routers which have multiple power supplies. Lose a power supply, you're fine. And each power supply should be put on a different power distribution unit on a different circuit breaker. Blow a circuit breaker, system goes down. Cooling. In your data center, if it's a private cloud, you better have redundant cooling systems, because if the air conditioners go down, your data center stops. The cloud provider should hopefully have redundant cooling. Redundant network connections. If you're going to connect to the cloud, you need more than one provider. It could be a private line or a direct connection and a VPN. It could be 2 private lines, but on different service providers, not on the same one. Because you've got 2 lines on AT&T has an outage. It doesn't matter how many lines you have, you're down, you are done, and that's no good. So let's talk about routers. Our routers may need to be high availability routers. That means, a router has a brain or a control module. If it really matters, we're going to need multiple control modules. On the links between our routers, maybe they're on different line cards because the routers have cards, and if a card fails, your system goes down. It means we need servers more than one. We need switches more than one. We need load balancers to eliminate single points of failure. We can leverage DNS to route between different websites or different clouds. Our storage, we need to have redundancy so that if one storage system goes down, then another thing, and potentially RAID. We might have two different storages where we're running active, and if one of the storage arrays goes bad, we can pick up the second one immediately with no loss of data. So our applications need to redundant. Our databases need to redundant. I hope you're getting the point. So think about this. And, for example, let's say I wanted to get a link aggregation group to the routers that's going to connect to the cloud. If all my links in the link aggregation group are on AT&T, I got a problem. So what if I need 40 gigs of throughput at all times? I might need 4 10-gig connections to AT&T to AWS, and maybe 4 10-gig connections off of Verizon. So let's think about that. Now, firmware-wise, don't experiment when you're dealing with high availability systems. This message I got over here, I thought was hilarious. It actually showed up on my firewall. And when I looked at this, I actually laughed. Could you imagine a high availability system telling you this? Your security appliance is running stable firmware to try some of our new features we've been developing. Click here for beta. Don't use beta software in a high availability environment. I mean, seriously, you would think it's a joke, but no, the firewall I have in my house, which is made by a major networking company and security company, actually says that when you log into it. It's ridiculous. So your systems need to be checked, etc. Now, when it comes down to it, you can do every piece of technology right, everything. And then you can have Sally, the computer tech, or Billy, the computer tech, that goes in at 2 o'clock in the morning and creates one access list on the network and breaks everything. So you're going to have a very good change management process in place, which means anytime a change is desired, you're going to have to present the change to an architectural review board. That architectural review board is going to have managers, stakeholders, department heads, and they can all evaluate your change request and determine if your change will have any impact on the global system. And if it does, but it's still needed, find a time where you can do it where it's least impactful for the business, or don't make that change if it's not the right change for the organization. Now, it's a little easier with the cloud provider to get high availability because for the most part, they're pretty good at what they do. They have redundant power, they have redundant cooling, they've got redundant connections to the internet, their switches and routers are redundant, so it's there. But there's also much more that can go wrong on the cloud provider because they can't run QoS the way we can. They can't run as invasive of security measures as we can on our own systems because they have to allow for everyone's traffic. So what I'm going to give you now is best practices according to the cloud providers for your exam. But what I tried to tell you before is exactly how you would do it in the real world. But it's a certification, not the real world. So if 99.9% is, so each availability zone in AWS is considered 99.9% available, which means if you need 99.99% available, you need to use 2 availability zones. So typically speaking, in a theoretically perfect world, 2 availability zones in a cloud provider, and you have 99.99% availability. Believe me, there's a lot more that goes into change management security, but for right now, for your exam, just understand that. Now, according to the cloud providers, if you went higher than that, instead of you put 2 availability zones in 2 regions, and then you've got 4 total availability zones, and that should give you 5 nines availability. That's great until the cloud provider has a security event, a network event, or has a problem with their control plane and the entire cloud goes down. And we've seen that too. So I wouldn't put all my eggs in that one basket. But anything that needs high availability should be in multiple availability zones at minimum. That means important virtual machines, important databases, load balancers, DNS, everything. So connections to the cloud. For most people and most organizations, it's going to be a direct connection and a VPN backup. But if we need link aggregation groups for bandwidth, we might need a redundant link aggregation group. So just think about that. And ideally, If you're going to connect to 2 different links, they probably should be on different routers at your data center, because if that router at your data center has all your links to AWS and that router dies, you lost the whole cloud. Now, when we're dealing with high availability, security has a major impact here. So when it comes to security, leverage security properly. That means leveraging the least principal of least privilege with regards to our identity and active management systems. It means disabling unnecessary services that we don't need to run on our systems, because each service that we run is a new attack vector. It means making sure that patches are tested and that systems are patched on a regular basis. It means limiting the blast radius of problems, either by segmenting your system into multiple VPCs or using AWS organizations, or a combination of both. It means keeping unwanted traffic out of your subnets with access control lists. It means protecting your hosts and your services with security groups. It means leveraging firewalls and next generation firewalls and DDoS protection and IDS IPS systems. It also takes physical security, because if anybody can just walk in and plug into your systems, now they can access your system. So think about that. It requires strong passwords when strong passwords are needed. It requires using tokens and other things when it's at all possible. It involves templating good system configurations and making sure your people can't deploy the wrong things and break the system. It means high availability means good backup strategies to protect against lost data that are based upon the business needs and how much tolerable downtime can they lose, for example, and how much data can they lose. It means storing your backups in an alternative location. When I was a kid, I backed up my papers that I wrote on a floppy disk. And then, but it was like, what happened if my house caught fire? So what I used to do is then email anything that was important to everybody that I knew. The point is, I got it off of my house and out of my location. And it's the same thing with data. Send your backups somewhere that you own or somewhere that's secure, but away from you. Take images of all your servers so you can come up with, and should anything happen, you can relaunch those servers immediately. Your routers and firewalls are typically going to have a text-based configuration. Copy those configurations somewhere so you could launch them quickly and easily if you needed. Now let's think about it. If we can decouple our architecture components, we can also tend to increase scalability. So if we have messages that are going into a database, but the database is down, but there's a queue before the database, we can store those messages in the queue. We should cut, and part of high availability is making sure the systems can scale with demand. Cloud's great here with regards to auto scaling, and we can leverage that. We can leverage caching, because I talked about earlier how, for example, if your web server was down temporarily, but the information was cached, your users could potentially still get access to the information. And we talked a lot about DNS and how we could use DNS to route in between environments for high availability. And we talked a lot about leveraging load balancers to improve performance and mitigating single points of failure. Part of being able to keep your systems highly available is to know what's going on. So make sure there's a good logging and auditing function. And in today's world, there should be some security event monitoring systems to correlate things that are going on. We want to be moderating for systems alerts. We want to be moderating for security breaches. We want to be moderating for usage. And we want to be monitoring for performance. And again, change management is going to be so critical that we need to be, before any changes, key stakeholders need to evaluate those changes, the impact of those changes, and agree on a time to make those changes, and agree on a testing system after those changes. It's about as much high availability as we could do here. In our main architect training programs, we get very heavy into high availability system training. But let's talk about passing the exam. Here's the thing. All AWS exams are challenging. It doesn't matter what they are, they can make something challenging. And the reason is the way AWS questions, they can pick little minutia from any parts on the curriculum. But what really makes this exam hard is not the content on the exam. That's not that complicated. But the way AWS asks the questions, they are very wordy. Something you could ask in, 10 words might be asked in 80 words. And there's going to be a lot of jargon and acronyms, and it's going to make it feel like you're doing it and reading something in another language. And then you're going to have to translate that into what it actually is. That's the biggest challenge of the exam. Plus, there may not be a clear winning answer. So I want you to think about this, because here's where people go wrong on these certification exams, if they know a lot. These certification exams are based upon the entry-level person that just took a certification course and passed. So if you're a network architect with 20 years experience, you probably know too much. So if that's the case, you're going to struggle when you take this exam. So if you've got a lot of networking background, I want you to think just like the training material and the way it's presented, because we presented it at more of an intro level, and you will be fine, because that's the thinking they need you to have when you take the test. Kind of like when someone graduates and they take their medical boards. Out of school, they know exactly the school answers, but 20 years later, they know exactly how to do it in real world. Same thing here. Consider yourselves fresh out of school. Look at the AWS curriculum and then master it exactly the way they want to hear it. And then in your real world, do it exactly the way it needs to be done. So you're going to look for the best answer for the bunch. So I've got some recommendations. Go through this program a second time. Personally, I actually like to read the Cybex books. And the reason I like to read the Cybex books is they are typically authorized by the providers themselves to create official curriculums. So I typically recommend the Sybase books. I typically also recommend reading the AWS white papers, because they'll pull a lot of exam questions from your white papers. And for me, I recommend getting a practice test. Why? Well, the point of the way Amazon asks questions can be very tricky with their wordiness. And if you get used to the way people ask questions, then it becomes normal for you. And by getting a practice test and taking the practice test, you'll be in a position to understand the way they ask questions. And truth be told, the practice test can identify gaps that you don't know, and then go research anything you don't know and research it well. If you got a question wrong in the practice test, research what was right, why you got it wrong, and the thing that you thought that was right, why it wasn't right. Make sure you learn that. And I generally recommend keep working on any practice test until you can score a 95 on every attempt, and then you'll pass every exam for the most part you've ever done. So there's that. Now, I want to mention this. The hardest part of the AWS exam is the wordiness. These things are written so hard to read, so that's the hardest part. So the night before the exam, don't stay up till 3 o'clock in the morning and drink 10 martinis because you thought it would be fun. Go to bed early, eat a healthy meal, get a good night's sleep, arrive to the exam early. If you're going to a physical center, get there 30 minutes early. If you're taking it virtually, arrive 20 minutes early, so when you log in and they're not there and your system freezes, you're going to be okay. Make sure you bring photo ID with you. You'd hate to study, prepare everything, and not have your photo ID with you. And if you're going to drive there, please give yourself time to park and give yourself time not to be stuck in traffic jams. So, that's my guidance on passing the exam. Chris, bring us back on screen. And we will be back to finalize anything. We can probably take questions, but we have to finish at 6:30, which is about 30 minutes late, because I promised somebody that I would make sure that I was available to them then. Is disaster recovery done at the data center level or per application level based upon criticality? It's based upon the business needs. We have to understand the business needs to determine what we need to put in disaster recovery. Great question. So is it correct to say backup pilot light to another cloud provider while warm and active in another region due to cost? So I'm going to try and get rid of any jargon whatsoever, because everybody has their different jargon. You've got the following options. You've got backup, which is basically you back up your data and you back up your virtual machines to another cloud. You have what I like to call backup plus, which is you back up your data, you back up your virtual machines, and you synchronize your data. You can have what I like to call active semi-active or warm standby, which is basically you have your primary environment and you have it replicated. And it can be replicated to another cloud. It can be replicated to another region. Now, I wouldn't replicate it to another region, because if the cloud goes down and you replicate it to another region, you're kind of out of luck. So that doesn't seem like the good disaster recovery for me. So warm standby, I'd replicate it somewhere else. But it would be the same if you're in the same cloud or a different cloud. The only difference is your IP connectivity. And then active is hot, full things running in one versus the other. And by doing so, you get the best performance. You need a router on AWS. Anytime you're going to route, you need a router. So in a transit VPC, you're basically using a software-based router, right, Benedict and Mo?
Yes.
Yeah, it's a virtual router.
So is transit VPC regional or global? Technically, it's regional because it's a architectural pattern, right? You're creating a transit VPC, you're setting up your VPN tunnels, and then you're using transit virtual routers, right? And then you're routing traffic through those routers. So it's technically it's regional. I can answer.
So it says, can you expand on what a transit VPC logical router is? Is it an EC2 instance with router software installed, or is it an AWS resource? So it's an AWS service, right? But what is happening in the background is that there's a virtual router that is doing this routing between all your VPCs. So technically, yeah, it's just that it happens behind the scenes and they present that service to you. So Manish, I tried to put in this the response to this. The screenshot I showed was actually CloudWatch and not CloudFormation. So the quota was on CloudWatch.
Samsung, honestly, I came with low expectations, not knowing how you run it, but you guys did an amazing job. Thank you. Superb Bootcamp. You all earned trust big time. Thank you so much. It's really essential for us at Go Cloud Careers. We really want to go out there and help people. And whether it's our paid career programs where we're working on every aspect of someone's career, or our free tech training, it matters to us. We want to really help those that are out there. We all come from a world where, we had to work ourselves to get anything, and we want to share as much expertise as we can. So thank you so much, Samsung, and thank you for coming. So much learning on this bootcamp, Cantor. This is great. Thank you. A million thanks to Mike and team. Yes, please thank the team as well. I got to say, Mo and Benedict are rock stars, let alone the team behind the scenes that made this possible, like Chris and Tyrone. I mean, there are people all over the world. Tyrone's in there at South Africa. It's like 11 o'clock at night, and he's still been around helping Chris, and Alonzo's helping him. There's a lot of people behind this. So thank you so much.
Can we minimize maybe cost per client VPN endpoint? So are you asking how to minimize the cost for client VPN?
Don't use it. They charge you for everything you use.
So, Joseph, when replicating between two different public cloud providers, how do those services understand one another in order to synchronize?
Okay, what a great question, Joseph. So we do this the same way we've dealt with things for the last 30 years. So I'm not going to have Amazon DynamoDB and Google Cloud Bigtable and try to synchronize these things. That would be like me trying to synchronize Greek with Mo's Arabic all at the same time. That's going to get ugly really fast. I translate every day of my life, but it gets ugly really fast because some things don't translate. But if I use Apache Cassandra in both clouds, it's nothing to get them synchronized. If I use the Palo Alto firewall systems in both clouds, I can push similar policies. So what I'm going to do is not use the cloud provider's proprietary services. I'm going to use more standard services that work in all clouds. And here's the reality. You're going to get a better firewall from people like Palo Alto that basically 90% of their business is firewalls than from AWS, who is a great company, but they make hundreds of different things, let alone being a retailer. So, it's not like, they can have the focus on a firewall the way a Palo Alto could. No, we don't provide any kind of practice exams. I wish we did. We work really hard to not try and charge for certification materials, but there are some good ones that are out there. T-Town Scott, really appreciate it. We're thrilled you're here. Martin, great boot camp above and beyond, and thanks so much. Thank you, Martin. And Valerie, thank you so much. I was thrilled that you're here. I look forward to seeing you soon, Valerie. Richard, always good to see you. Wonderful to see you. It's been an honor to work with you. Mo and Benedict, thanks so much. And Adrian, always good to see you as well.
Thank you.
Okay, so everyone, it's been wonderful. My team, if you haven't gotten a copy of the labs, will pop in some lab opportunities for you. I will pop in one day this week, possibly even tomorrow, to answer any tech career questions on our YouTube channel. So if you're not a subscriber, please subscribe and hit the bell. You'll be notified of it. On Thursday this week, we're going to run a How to Get Your First Cloud Architect Job webinar. And I may have a special guest who's been an architect with me for a couple decades as well, if it works out time-wise. So please join us. You can ask me or any of our architects any questions. And thank you for being here. And thank you for being here from all over the world. I know where some of you are coming from. I've seen your names. And I'm so flattered and honored that you joined us from everywhere. I can say everywhere from Egyptian, and I think I saw in Eritrea as well. So, we're there. I saw people in Asia. I saw people in India. I saw people all over Europe, the Middle East, and South America. So thank you so much. Have a good night, everybody. Make sure to sign up for the free things we have for you. Take care.
All right.